Have you ever wondered how ChatGPT understands you and gives you the desired output every time? Or how Netflix knows exactly what you'll binge next? Or how self driving cars make split second decisions? That's artificial intelligence. And it's no longer the future, it is the present. AI is quietly powering everything around you, from the morning alarm to the ads you scroll past. And right now, the world is looking for people who can build this intelligence. The question is, will you be one of them? Welcome to Intellipaat's Artificial Intelligence Full Course, your one-stop destination to understand AI from scratch and understand how the most powerful tech in the world really works. This isn't just a tutorial, it's a career launchpad. We'll walk you through the core concepts of AI, ML, and deep learning, hands-on projects using Python, TensorFlow, and more, and the exact roadmap to land a job in AI, even if you're starting from zero. No fluff, no filler, just real job ready AI skills. So, if you have ever felt curious, or if you ever wanted to not just use smart technology but build it, then you are on the right place. Let's begin your journey with artificial intelligence right now.
What is an explainable AI? Before I answer this question, let us go back and understand why exactly it exists first. Let's say I have gone ahead and built a model which helps recognize if the patient has a disease based on their X-ray records and MRIs. I have done this by using a deep learning model to recognize the pattern out of the images. Now I gave this particular model to the doctors. They went ahead and put out some patient samples through the model, and the model provided almost the right decisions. But this fact scared the heck out of doctors. They asked, how exactly is this model coming to these particular deductions? What things or computations are happening behind the scenes to reach these particular decisions? And how can I trust the results generated by a machine to treat my patients? Basically, doctors or you viewers don't know anything about my model. It's kind of a black box for you or everyone. I mean, you can just provide an input, some magic will happen within the black box and you'll receive the output. But you'll not be able to interpret what's exactly going inside this black box. Well, the irony is even me, the developer who has developed this particular model, will not be able to explain how it came to a particular decision. You see, it's not just about me. Any data scientist or machine learning engineer or an AI engineer will not be able to explain the computational details behind predicted output. They'll not be able to explain how a model reached a certain decision for a peculiar instance in a testing sample. And this is a problem, right? Well, if there is a problem, there is going to be a solution as well. And that solution in our case is explainable AI, briefly abbreviated as XAI. Well, it do help us humans worried about black box situations understand how an AI model comes up with results and how much we can trust those particular results. Let us explore the different components of explainable AI to better understand how exactly it works. In a basic sense, it comprises three different components. Number one is prediction accuracy, then there is interpretability and justifiability. The prediction accuracy and interpretability are two technical aspects, whereas justifiability is something that's going to solve our problem. That is, understanding how a model reached a certain decision. Let's start by understanding the prediction accuracy. Prediction accuracy is a highly important metric for any machine learning engineer or data science professional, right? Because the success of your machine learning model is going to be judged by comprehending how accurate results your model provides. Generally, when we compute the accuracy, we try to learn the pattern in data and then check how accurate results the learned model is making for the testing set, right? Well, in case of explainable AI, it is not going to change. It will remain the pretty much same, but it's just that you'll comprehend the performance by using models like LIME and running multiple simulations to match results and understand the performance. LIME is a technique that helps to explain the prediction of an AI model at the local level. Next one is interpretability. Interpretability, or in other words, what we call as traceability, is yet another important factor. Generally, when we try to work and build a model, we actually happen to have a problem and data set at our disposal, right? We try to visualize the attributes present in the data to figure out their correlation. We even dispose of certain columns that don't feel much relevant, right? By doing all these things, we are actually trying to interpret the question and how a solution can be framed. In a similar manner, in the case of machine learning or AI model, interpretability resembles how the learning of a model can be broken down into chunks. If it is a decision tree model, what are the rules the model is setting? What are the important features the learning process is revolving around, etc. Figuring out answers to these factors is basically what known as interpretability. To achieve this, we have a framework called as deep left, which explains predictions by analyzing input feature changes. Finally, we have something called as justifiability. Well, as we already mentioned, this component is all about solving the human mistrust in AI or ML model. If I were to explain justifiability with a simple decision tree that predicts whether a student can get into BTech program based on the marks he got, if he got more than 85% marks in computer science, he can easily get CSE, or even if he got 80% mark but carries excellent extracurricular skills, then too he can get into the BTech program. So we arrive at the conclusion that certain factors within my dataset would lead to alteration of results. Figuring out these exact rules, figuring out these exact attributes that have more say in the decision, etc. are the main components that we try to break down. Not only that, we try and understand if there is a slight change in the input provided, and if there is a change, what kind of output will turn out to be. Now let me put all these three components into a practical use case by taking the same example that I took in the beginning of the video. Say, if a person has cancer, our model should be able to take X-ray images and detect the cancer cells accurately. It should not interpret it with any other disease. This highlights how much the outcome of this model can be trusted, which is known as prediction accuracy. To understand the nature of disease, the AI model has to break it down into smaller chunks, which would narrow down the scope of the data. The amount of data we humans are able to understand from these smaller chunks of data is defined as interpretability of the AI model. Why the cells in the X-ray were termed as cancer cells and why not any other disease underlines the justifiability of an AI model. So you see, overall the explainable AI is not just about building trust or understanding how a decision was made, but it is about troubleshooting the misprediction and improving models' performance.
Hello everyone, Intellipaat offers executive postgraduate certification in data science and artificial intelligence in collaboration with iHub IIT Roorkee. Through this particular course, you'll get to learn multiple tools like Python, PySpark, SciPy, NumPy, Pandas, Matplotlib, TensorFlow, Git, etc. You are going to learn multiple skills like data science, natural language processing, deep learning, fundamentals of generative AI, prompt engineering, and application-based generative AI, as well as recent trends like agentic AI. This course is designed to get you ready for the AI world. So do check out link available in the description. Also, through this course, we have already helped thousands of learners take positive step in their career. You can check out their testimonials on our Achievers channel.
Need to be analyzed to determine the best course of action. This is the main function of the control algorithm and software, and this is where reinforcement learning comes into picture. This is the most complex part of the self-driving car since it has to make decision flawless. A flaw like in case of Uber's self-driving car can be fatal. Okay? In today's world, the most famous self-driving car are those from Tesla and Google. Tesla cars work by analyzing the environment using a software system known as Autopilot. Autopilot uses high-tech cameras to view and collect data from the world, same as what we do with our eyes. It's called as computer vision or sophisticated image recognition. It then interprets this information and makes the best decisions based on it. So this was one of the use case of reinforcement learning. Iris flower dataset. Well, the project which we are going to perform is generally known as the hello world of machine learning. So it's the best project to start with because it's so well understood. Okay, and why it's so well understood? Because so all the attributes in this dataset is numeric. So all you have to do is figure out how to load and handle the data. So it's a classification problem, thereby allowing you to practice with perhaps an easier type of supervised learning. Okay, it also supports a multi-class classification problem that may require some specialized handling. So this iris dataset consists of 4 different attributes: sepal length, sepal width, petal length and petal width, and it consists of 150 rows, meaning it is very small and it can easily fit into the memory. All the numeric attributes are in the same unit and the same scale. Okay, so this dataset doesn't require any special scaling or transformation to get started. Okay, so let's get started to your Hello World machine learning project in Python. So let's get started with your Hello World machine learning project in Python. Okay, so this is my Jupyter notebook. So the very first thing that I'll be doing up here is importing all the required libraries. So I'm importing pandas, and from pandas I'm importing scatter matrix. Next I'll be importing matplotlib as PLT. Then we are importing model selection from sklearn, classification report from sklearn.metrics, confusion matrix from sklearn.matrix, accuracy score again from sklearn. And these are various machine learning models. Okay, KNN classifier, linear discriminant analysis, Gaussian naive Bayes, and support vector machine. Okay, so we are importing all these models from our scikit-learn library. Okay, so let's execute it. Our next step is to load the dataset. So the very first parameter that I'm passing up here is the URL of my dataset. Okay, or the path of my dataset basically. So there's my dataset, just to show you. So this link consists of my dataset. Okay. Next, I'm defining an array as names. This consists of the name of the attribute, sepal length, sepal width, petal width, and class. Okay. And next, I'll be defining a variable as dataset. And next, I'm defining a variable dataset. So dataset equal pandas.readcsv URL comma names equal names. So what it is basically doing, it is fetching the data from here, from this link, URL from this URL, and it is giving the name of the attribute as all these: sepal length, sepal width, petal width, and class. Okay, so this will basically load your dataset. Fine, let's execute it. So our dataset is loaded. Now let's summarize the dataset. Now let's check how many rows and columns do our dataset have. So let's execute this and check the shape of our dataset. So our dataset consists of 5 different columns and 150 rows. Okay. Next, if you want to check the sample dataset, then you have a head function over here. So this will give you first 20 result of your dataset. Okay, 0 to 90. Fine. Next is the dataset.describe function. So this will give you the various description from your dataset, like count, mean, standard deviation, minimum, percentile, 25 percentile, 50 percentile, 75 percentile, and max. So count is basically the total count of sepal length, sepal width, petal length, and petal width. Okay. Similarly, mean of all, similarly standard deviation, and so on. Okay. Next, what if I want to check how many different classes are there, or how many values contains in each class? So we'll group by the class and we'll find the size of each class. Okay. Let's execute it. So we got the output up here as iris setosa 50, iris versicolor 50, iris virginica also 50. So this means that we have 3 different classes: iris setosa, versicolor, and virginica. All 3 of them consist of 50 values. Okay, fine. So next is data visualization. So now that we have some basic idea about our data, let's create some visualization out of it. So we are going to look at 2 different types of plot. The first would be a univariate plot, that is to understand about each attribute, and next would be the multivariate plot to understand the relationship between the attributes. Okay, so first let's plot a univariate plot, that is plot of each individual variable. Okay, so this is the univariate box and whiskers plot. So let's consider just sepal length. So the bottom part of here, this represents the minimum value, and this is the maximum value. Okay, and this green bar over here, it represents the mean value. So if you see the mean of sepal length, it's around 5.84. It's also representing the same. So it's 5.84. Okay. These circles above and below the minimum point are nothing but the outliers. Okay. Yeah, one more thing, the minimum and the maximum value, right? So minimum is 4.3 for sepal length and maximum is 7.9. Okay, so the minimum value you got up here is 4.3. Okay, so this is my 4.3 minimum value, and here we have the maximum value as 7.9. Okay, and these are the outliers, these circles. Similarly for sepal width, my minimum value was sepal width was 2.0 and maximum 4.4. So minimum from here is 2.0, this value, it's an outlier, and the maximum value is 4.4, this value 4.4, it's also an outlier. And the mean value of sepal width is 3.05. So we got mean somewhere around here. Okay. So in order to understand our data in a better way, we created a univariate box and whiskers plot. Okay. This gives us a much clearer idea about the distribution of the input attributes. Okay. Well, if you want, you can even create a histogram of each input variable to get an idea of the distribution. Okay, so let's execute it. So there's my histogram. So in sepal length and sepal width, I can find the Gaussian distribution up here. Okay, so this is a useful to note as we can use algorithms that can exploit this assumption. Okay, next we have is the multivariate plot. Well, multivariate plot is used to check the interaction between the variables. Okay, so let's just execute it and see what's the output. So here's a scatter plot of all pairs of attribute. So this can be helpful to spot structured relationship between input variables. Okay, so as you can see, we have diagonal grouping of some pair of attributes. So this suggests a high correlation and a predictable relationship. Okay, so from here you can say that sepal length is more dependent on sepal width as compared to petal length and petal width. Similarly, same thing over here, right? So petal length is more dependent on sepal width as compared to sepal length and petal width. Okay, and the petal width, it's more dependent on sepal length as compared to sepal width and petal length. Okay, so these are the things that we can conclude after visualizing our data. Okay, now it's time to create some model and estimate their accuracy on unseen data. Okay, so here we'll follow step-by-step procedure. Okay, first we'll separate out a validation dataset, that is divide our dataset into train and test part. Then we'll use a 10-fold cross-validation technique that will randomly distribute our data into 10 different data sets. Okay, so that we can perform training and testing on each part. Then we can finally combine the result of all of them to get a better accuracy. Okay, then we are gonna build 5 to 6 different models to predict species from flower measurement. Okay, and then finally we'll select our best model. So our first step is creating a validation dataset, that is dividing our dataset into train and test. So here what we are doing, dividing our dataset into train and test. Fine. Array equal dataset dot values. So it consists of all the values inside your dataset. Here you're defining x equal array starting. So here you're taking a portion of the array. Okay, and you're placing it in x. So what is that? So your row up here is nothing. So it will start from the very first row and the column 0 to 4. So it will take up to fourth column. So 4 column from the first row, that is x is storing all the name of the attribute. Fine. Similarly, we are defining a variable y. So y will consist of the fourth column. Next, I'm defining a variable y, array of starting from first row and fifth column. Okay, as 0, 1, 2, 3, 4. So here number 4 represents my fifth column. Okay, next I'm defining a validation size as 0.20. So here validation size means it will split my data as 80% in one part and 20% in other. Okay, so next we are defining a seed value. So this seed value is used to initialize the randomization. Saving or setting it to same number each time guarantees that every time you execute the algorithm, it will come up with the same result. Okay, next we are defining scoring as accuracy. And here we are defining x train, x validation, y train and y validation. So here we are defining x train, x validation, y train and y validation. So x train would be my training data from this part and x validation is the testing data from same. Okay, so according to my above code, my 80% of the data will lie in the training part and the rest 20% would be treated as a validation data or the test data. As I have already mentioned, the validation size is 0.20 or 20%. So this means that 20% of my data is test data. Fine. Similarly, we'll define y train and y validation. That is 80% of the training data from this array and rest 20% of the testing data from same array. Okay, so here we are basically splitting our data set. Okay, on the base of x, y, test size equal validation size that we have already specified as 0.20 and my random state equals c and my random state is c. So every time I execute it, the algorithm will come up with the same result. Fine. So now that we have created a split among our dataset and we have divided our dataset into train and test, so our next step would be to build our model. Okay, so this is how we are building our model. Okay, so from the scikit-learn library, we are calling logistic regression, we are calling linear discriminant analysis, KNN, decision tree, Gaussian naive and SVM or support vector machine. Okay, here what we are doing, we are creating 10 folds. Okay, so 10 folds, let me just go step by step. So here we are defining a variable as k-fold. So k-fold equal model underscore selection. K-fold, how many split we want to perform is 10 split and random state again c, that is 7. So every time it will perform the same random split. Okay, so this is how my data would be splitted into 10 different parts. Okay, now once the data is split into 10 parts, then we'll define a variable as CV underscore results. Okay, so CV underscore results equal model selection dot cross validation score. Inside that we are passing our model, what model we are choosing. We are passing the X train data, the Y train data, CV equal K fold, whatever the value of K fold is there, and then finally scoring, which we have initialized up here as accuracy. Okay, then what we are doing, we are appending our result. So our CV result would be appended to results, that is to this list. So next we have is result dot append CV underscore result. So this list would be updated with the CV underscore result value, and here we are appending the name, and finally we are printing our desired result. So one by one this will go in a loop. Okay, so every time this loop execute, you'll get the accuracy of one of the model. Okay, so here right now our model consists of all these values. Okay, as we are appending it, that is we are adding all these values one by one to our model. It consists of logistic regression, decision tree, Gaussian naive Bayes, and support vector machine. All of them are in our model. Okay, and finally it is printing the message. Let's check the output. So we got the output as this. So here the accuracy of a logistic regression is 0.96, that of linear discriminant analysis is 0.97, KNN 0.98, decision tree 0.96, naive Bayes 0.97, support vector machine as 0.99. So from this we can say that support vector machine is having the highest accuracy. Okay, so now our next step would be to compare the algorithm and select the best model. So just by looking at this output, we can say that support vector machine is having the highest accuracy. But let's compare all these algorithms and see which one fit the best. So for that, I'll be plotting a box and whiskers plot for the accuracy versus the name of the algorithm. Okay, so there's my algorithm comparison. Here I have the name of my algorithm and this is the accuracy for them. The green point which you can see up here is nothing but the mean values or this value. Okay, for linear regression I had 0.96, for linear discriminant analysis I had 0.97, and so on. So from this graph what I can say is KNN, naive Bayes, and support vector machine, these are having the highest accuracy. Okay, as there is no minimum and maximum value, only they are having a maximum value and few outliers, these outliers. Okay, so in case if you are removing these outliers like this one, these two, and this, so by removing them KNN will give you the 100% accuracy result. By removing these two outliers, naive Bayes would give you the highest accuracy result or 100% accurate result. So even in case of SVM, if you remove this outlier, you will get a model with 100% accuracy. Okay. Now next is making the prediction. Well, just accuracy shouldn't be your metric to decide that this is your best model. Okay. So for selecting a model, you have several other features which you should decide apart from accuracy. Okay, so your accuracy will not always be the metric to select the best model from. Okay, so let's move ahead and see how to make the prediction. So we have already calculated the accuracy, right? So now from this graph we know that support vector machine is giving the highest accurate result even with the outlier. If this outlier is removed, then it's the best one. Okay, now let's make some prediction on it. Okay, so let's execute this. So here we are printing the accuracy score, we are printing the confusion matrix and the classification report for Y validation and prediction, that is testing and predicted value. So here we are printing the accuracy score for the tested value and the predicted value. We are printing a confusion matrix for the tested value and the predicted value, and finally a classification report, same for the tested value and predicted value. So if you check the score for tested value and predicted value, like accuracy score while using SVM or support vector machine is 0.93. So there's my confusion matrix up here. And finally, we have a precision, recall, F1 measure, and support data for all these three classes: Iris setosa, Iris versicolor, and Iris virginica. So let me just explain you what is precision, what is recall, what is F1 score, and support. So this precision, it tells how accurate or precise is your model. That is, out of those predicted positive, how many of them are actual positive. So this is precision. Okay. Next is recall. It calculates how many of the actual positives our model has captured through labeling it as positive. Okay. Next is F1 score. It is used when you want to seek a balance between precision and recall because of a large number of actual negative values. Okay. And finally, we have support, which is the number of sample of the true response that lies in that particular class. Okay. So while predicting with SVM, we had 7 true responses in case of Iris setosa. 12 in case of Iris versicolor, and 11 in case of Iris virginica. Okay. Similarly, I made prediction using SVM model. If you make prediction using KNN, you'll get a different result up here. In this case, we got the accuracy as 0.9, and the precision score, recall score, FN score, and support score all are different. Okay. So here in case of KNN algorithm, you can see that we have the accuracy as 0.9 or 90%. The confusion matrix provides an indication of the 3 errors that we made. Finally, the classification report provides a breakdown of the class by precision, recall, FN score, and support. Okay. So we use Python to create few machine learning model and select the best model out of them. So our best fit model is SVM, as it is giving the highest accuracy and high values of precision and recall.
Here's a quiz question for you guys. What is machine learning? Your options are a type of computer hardware, a programming language used for data analysis, a branch of artificial intelligence that focuses on the development of algorithms that can learn and make predictions based on data, or a type of advanced robotics technology. Please mention your answers in the comment section.
So regression is a technique of finding the relationship between two or more variables. Okay. It is based on the fact that a change in dependent variable is associated with a change in one or more independent variable. Like you can see over here, a regression is a technique that displays the relationship between variable y based on the values of variable x. For example, as the temperature drops, people puts on more jacket to keep them warm. So the selling of jacket and the drop in temperature are both directly related, right? Here, temperature is an independent variable and the selling of jacket is directly dependent on temperature. Okay, so the jacket selling is a dependent variable and it depends on what? On the temperature. Fine. So let's move ahead. Next is regression use case. Let's see some of the use cases related to regression. First, we have temperature versus number of cones sold at ice cream store. So again, temperature is an independent variable and number of ice cream cones sold at ice cream store depends directly on temperature. It's like if it's a summertime or when the temperature is high, so number of ice cream cones sold will be more, right? Next is inches of rainfall is an independent variable and new cars sold directly depends on it. Fine. If there would be more rain, then the number of cars sold in the market would be more. Fine. Next is daily snowfall versus number of skier visits. Again, daily snowfall is an independent variable. It does not depend on anything. But the number of skier visiting directly depends on snowfall. If there would be no snowfall, then there would be no skier visit. Right? More snowfall means more skier visit. So these type of problem come under the regression category. So if you think there is a relationship between two things or two variables, then regression would help to confirm it. For example, temperature has one variable and number of cone other variable. If you think that there is a relation between temperature and number of cones sold, then you can use regression to confirm it. Okay, let's move ahead. Next we have is the type of regression. Well, there are various types of regression, but for now, we'll mainly focus on linear regression and logistic regression. So let's see what is linear regression and logistic regression. So linear regression generally deals with continuous variable. Okay, so what do I mean by continuous variable? For example, the amount of rainfall. Okay, so it's a continuous variable. It can range from 0 to 100 centimeter, anything. Or the price of the house. Again, it's a continuous thing, right? The price of the house can range from $100 to around $5,000, anything. Okay. On the other hand, logistic regression deals with categorical variable. These are the kind of variable in which you have to just predict either yes or no, like whether it will rain tomorrow or not. Okay. So these are categorical variable. Next, linear regression, it is used to solve the regression issues. We already discussed some of the regression issues previously. For example, selling of the car directly depends on amount of rainfall in a year. If it is raining more, then the amount of cars sold in the market would be more. So it's a regression issue and it deals with continuous variable. Okay. On the other hand, logistic regression. Logistic regression is used to solve classification issues like is this mail a spam or not? Okay, or will it rain tomorrow or not? So these kind of problem comes under classification. You have to classify either yes or no. Okay. Next is when you have to predict a new point, the point is predicted using a straight line in case of linear regression. But the prediction in case of logistic regression is done by drawing a S-curve. Okay, don't worry, we'll see in detail how these lines are plotted. Alright, for now, we'll mainly focus on linear regression and how the straight line is formed. So, what is linear regression? Well, linear regression is plotting a straight line of a form y equal mx plus c such that it predicts a new data point. In other words, you can understand that if your model is well trained using linear regression, then in that case, the predicted point would lie on the regression line. Okay, and your aim is to draw that regression line. A simple linear regression is useful for finding relationship between two continuous variables. One of them is independent variable and the other is dependent variable. Let's understand linear regression in depth. Let's suppose we have two axes over here, x-axis and y-axis. X has independent variable and y has dependent variable. And your aim is to draw a line of regression. Okay. Now let's suppose we have a data point on the x-axis. It's an independent variable. So if the independent variable is increasing, what should be the change in dependent variable? So if the dependent variable is also increasing, then in that case, we'll get a positive line, right? Both the independent variable and the dependent variable is increasing. So we get a positive line. Next, if the dependent variable is decreasing, and for the decrease in dependent variable, we have an increase in the independent variable. Okay, it's like dependent variable is decreasing and independent variable is increasing. So in that case, we'll get a negative line. Alright. So the line I'm talking about is the line of linear regression. Alright, let's move ahead. Let's suppose this is our observation. Let's add some observation. Okay. Now our aim is to draw a regression line that would help us to predict the point in future, and we'll be doing this using the least square method. Let's understand what exactly is least square method. So suppose this is our estimated or the predicted value and this was the actual value. The difference between actual value and estimated value is nothing but the error, and our main goal is to reduce this error. Okay, and remember, this red point which I am plotting over here is the predicted point and it lies on the linear regression line. Okay, so closer the regression line lies to the actual value, the more better it will be. Okay, so coming back, your main aim is to reduce this error or reduce the difference between the actual value and the estimated or the predicted value. Okay, you have to repeat this step for every single point. Okay, and your goal is to minimize the error. Fine. So this is what a least square method is. Don't worry, we'll understand about it in detail. Okay, for now, let's just continue. So let's suppose we have speed on the x-axis and distance on the y-axis. So if you plot a graph, you'll get a positive relation between both of them. It's like for a constant time, if the speed is increasing, the distance would also increase. Okay, we get an equation of line as y equal mx plus c. Here y is the distance traveled in a fixed duration of time. X is the speed of the vehicle. On the other hand, m is the slope or the positive slope of the line. And c is the y-intercept of the line, or the point where the line y equal mx plus c cuts the y-axis. Okay. Now let's consider another example. Suppose we have speed on the x-axis and time on the y-axis. Then for a fixed distance, if the time is increasing, the speed would decrease. Or if the speed is increasing, the time would decrease. Both are inversely related to each other. So we'll get a negative relation in that case. So here our equation of line would change to y equal minus of mx plus c, where y is the time taken to travel a fixed distance, m again. Here we'll get m as negative. So m is the negative slope of the line. X again speed, and c is a point where the line y equal minus of mx plus c cuts or intersect the y-axis. Okay, let's move ahead. So when you plot a graph between the dependent and independent variable and you get a regression line of y equal mx plus c, in that your y is dependent variable and x is independent variable. Okay, so let's understand linear regression in depth. For this, we'll be plotting few random points and check whether the two variables which lie on the x-axis and on the y-axis are actually even related to each other or not. Okay, we'll see the relationship between x and y variable. So on the x-axis, we have 1, 2, 3, 4 and 5. Let's plot them. X-axis 0, 1, 2, 3, 4, 5, 6. Okay. And on the y-axis, we have 4, 3, 4, 2, 5. So let's plot it again on the y-axis. 1, 2, 3, 4, and 5. Maximum is 5. Okay. Now let's plot our point. So we need to plot x1 and y4. So x equal 1 here and y equal 4. This point. So the coordinate of this point would be 1, 4. Okay. Similarly, the next coordinate that we have is x2 and y3. So x2, y3. Similarly, next coordinate is 3, 4, then 4, 2, then 5, 5. Okay. Now our goal is to create a regression line which passes through all these points with the least error. Okay. So for that, the very first step that we'll do is calculate the mean of both x and y. Remember, the line would pass through the mean of x and y always. So the very first step that we'll do, we'll calculate the mean of x and y. So mean of x is 1 plus 2 plus 3 plus 4 plus 5. That is 15. 15 by 5 is 3 again. So we'll draw a line x equal 3. So there's our line. Next, we'll calculate the mean of y. That is 4 plus 3 plus 4 plus 2 plus 5. That is 18 by 5. Okay. And we'll draw the line y equal 3.6. Okay. The equation of green line is y equal 3.6. So the intersection of both the lines would be the point from where a line of regression would cross. So the coordinate of this point is 3 and 3.6, and the equation of the line is y equal mx plus c. Okay. Now goal is to find the value of m and c. Let's see how we are going to find it. So for finding the value of m, we have a formula as summation of x minus x bar multiplied by y minus y bar upon summation of x minus x bar whole square. Okay. So let's calculate each point one by one. So first let's see for x minus x bar. So x minus x bar is nothing but the distance of all the point from the line x equal 3. Okay. So first point that we have is value of x is 1 and x bar is 3. So 1 minus 3, that is minus 2. For next point we have x is 2 and y is 3. So 2 minus 3, that is minus 1. 3 minus 3 is 0, 4 minus 3 1, and 5 minus 3 2. Okay, so we got the value of x minus x bar as minus 2, minus 1, 0, 1 and 2. Now we'll calculate the value of y minus y bar. And what is that? It is the distance of all the points from the line y equal 3.6. Okay, so y minus y bar, we have y as 4 and y bar as 3.6. So 4 minus 3.6, how much? 0.4. Next, 3 minus 3.6, that is minus of 0.6. Next is 4 minus 3.6, that is 0.4. Then 2 minus 3.6, that is minus of 1.6. Then 5 minus 3.6, that is 1.4. Okay. Now we'll calculate the value of x minus x bar whole square. Okay. So let's calculate the value of x minus x bar whole square. So there's the square of this green box. So minus 2 square is 4, 1 square 1, 0 square 0, 1 square 1, 2 square 4. Okay. Now we have to calculate the multiplied product of x minus x bar and y minus y bar. This is x minus x bar multiplied by y minus y bar. So minus 2 multiplied by 0.4, that is minus of 0.8. Similarly, minus 1 multiplied by minus of 0.6 is 0.6. Then 0, then 1 multiplied by minus of 1.6 is minus of 1.6, then 2 multiplied by 1.4, it's 2.8. So we got all the values. Now next our turn would be to summate them. So summation of x minus x bar multiplied by y minus y bar upon summation of x minus x bar whole square. So let's calculate the summation of each one of them. So summation of x minus x bar whole square is 4 plus 4, 8 plus 2, 10. Okay, and summation of minus of 0.8 plus 0.6 minus 1.8 plus 2.8 is 1. How? So it's like 2.8 plus 0.6, it's 3.4. 3.4 minus of 2.4 minus of 1.6 minus of 0.8, right? It's 2.4. So 3.4 minus 2.4 is 1.0. So we'll get the value as 1 by 10. So we got the value of slope as 0.1. Now let's talk about our equation of regression line. So for that we have to find an equation of a line such that we have a slope and it passes through a particular point. So our slope is 0.1 and it passes through the point 3 and 3.6, which we have already calculated, right? Where I said that the regression line would definitely pass through the mean of all these points. Okay, so we have y as 3.6, this line, m is 0.1, and we have x as 3, right, this line. So we have to calculate the value of c. We have the equation 3.6 equals 0.3 plus c. So c equal 3.6 minus of 0.3, that is 3.3. So we got the value of c as 3.3. So now we know that our regression line would intersect y-axis at the point 3.3 and it will cross through the point 3.6 and 3. So for the regression line for m equals 0.1 and c equal 3.3, we'll get the equation as y equals 0.1x plus 3.3. So this is our regression line. Okay, so now that we have drawn our regression line, we have to check whether the independent variable is even dependent on the dependent variable or not. Or in other words, we have to find out if our independent variable is even related to the dependent variable or not, right? So for that, what we'll do, for given m equals 0.1 and c equal 3.3, we have to predict the values for y when x equal 1, 2, 3, 4 and 5. So for x equal 1, m equals 0.1 and c equal 3.3, the predicted value of y would be 3.4. Okay. Similarly for x equal 2, y predicted is 3.5. X equal 3, y predicted as 3.6. Similarly for x equal 4, y predicted is 3.7. And for x equal 5, y predicted is 3.8. Alright, and the line passing through all the predicted values of coordinate x and y predicted is nothing but the line of regression. So next is finding the best fit line. So in order to find the best fit line, you have to do multiple iteration for different values of m and b. What you'll do, you'll calculate the error for different values of m and b, and the line having the minimum error would be your final line or the best line of regression. For now, just check if our independent variable is even related to dependent variable or not, right? This was our main goal. So for that, we have to calculate R square. R square is a parameter which tells us whether the independent variable is related to dependent variable or not. If yes, then by how much factor? If no, then by how much? Okay. So the formula for R square is predicted distance minus mean whole square divided by actual distance minus mean whole square and summation of both. So it's like summation of y predicted minus y bar whole square divided by summation of y minus y bar whole square. Okay, so let's calculate it. So what all we have? For now we have x and y predicted. For x equal 1, y equal 3.4, 2, 3.5, 3, 3.6, 4, 3.7, 5, 3.8. So for now, let's plot the value of y as we need it in the calculation. So we had y as 4, 3, 4, 2, 5. Okay. Now we'll calculate yp minus y bar, the numerator of r square. That is yp minus y bar. So yp minus y bar is 3.4 minus 3.6. Okay, it's minus of 0.2. Next is minus 0.1, then 3.6 minus 3.6 is 0, then 3.7 minus 3.6 is 0.1, and 3.8 minus 3.6 is 0.2. So next we'll calculate is y minus y bar, that is 4 minus 3.6. That is 0.4. Okay. Next 3 minus 3.6, that is minus of 0.6. 4 minus 3.6, that is 0.4. 2 minus 3.6, that is minus of 1.6. Then 5 minus 3.6, that is 1.4. Okay. So let's move ahead. Next, what we have to do, we have to square them. So first we'll calculate y predicted minus y bar whole square. So it's minus of 0.2 square, that is 0.04. Then minus of 0.1 square, that is 0.01, 0 square 0, 0.1 square again 0.01, 0.2 square, that is 0.04. Okay. Then we'll calculate the value of y minus y bar whole square, that is 0.4 whole square, that is 0.16. Then minus of 0.6 whole square, that is 0.36. again 0.4 square, that is 0.16, minus of 1.6 whole square, that is 2.56, then again 1.4 square, that is 1.96. So if you summate them, so for the formula of r square, we have to summate the value of yp minus y bar whole square and y minus y bar whole square. Okay, so we have to summate them. So summation of yp minus y bar whole square is 1.0 and summation of y minus y bar whole square is 5.2. So if we put these values in the formula, we'll get r square as 0.1 divided by 5.2, which is approximately equal to 0.019. That means the value of r square is almost equal to 0. So when you get r square value tends to 0, then in that case you can say that independent variable is not at all related to your dependent variable. Okay. So it's like more the value of r square, more you can say that your independent variable is dependent on the or related to your dependent variable. If you have the value of r square as 0.6, you'll find that error in this case, or the difference between the actual point and the predicted point, is less as compared to the line where r square is almost equal to 0. So if you keep on increasing the value of r square, the error would keep on reducing, or the distance between the actual point and the predicted point would keep on reducing. For the line r square tends to 1, that would be a line in which your predicted point and the actual point almost overlaps each other. Okay. Now let's just move forward and perform a hands-on in Python, and let me show you how you can calculate and plot the linear regression in Python. So there's where I'm going to write my linear regression code. Well, if you see, there are multiple datasets available out there on the internet, but for now we'll implement the simple linear regression on our own dataset. For this, we'll be considering two variables, x and y. X would be the house size, which ranges from 1000 square feet to 10,000 square feet, and y, which is an independent variable, that would be the cost of house, which ranges from 300,000 to 1200,000. Okay. Now, since we are using simple linear regression, so we have only one factor, that is size of the house, which is affecting the price of the house. Right. When you are dealing with multiple linear regression, we would have more than one factor affecting the house, like locality or the number of room, etc. Don't worry, we'll deal with them later. But for now, as we are dealing with simple linear regression, so we have one variable which is dependent on the other one. Okay, so now our goal is to find a regression line, a line which fits the best if we plot both our variables x and y, so both x and y, so that we can predict the response y, that is the cost of the house, for any new value of x, that is size of the house. Okay, so let's start coding. So first of all, let's import the required libraries. So we'll be needing NumPy and Matplotlib. So import NumPy as np, and I'll be importing matplotlib.pyplot as plot. Okay, as we have discussed already what is NumPy and what is Matplotlib, so just to give you a recap, so NumPy is a library for Python programming language which is generally used in machine learning because we have to deal with large data in machine learning, and this is faster than the normal array or the list. So a NumPy is a library for the Python programming language which is generally used in machine learning, as we have to deal with large data in machine learning, and this is faster than normal array or the list. Okay, and Matplotlib is a plotting library for Python which is generally used for plotting the graph. Okay, so here we are using NumPy as np and matplotlib.pyplot as plt. This is done to rename the huge name to something smaller. Okay, just to ease it. That's it. So instead of writing numpy.array, the short form is np.array. That's it. Or matplotlib.pyplot.plot x and y, the short form would be plt.plot x and y. That's it. That's just for ease of coding. Okay. So now that we have imported our libraries, our next task would be to create a function. So we have to create a function to estimate the coefficient of x and y values that are passed into this function. So we'll start as define name of the function, estimate the coefficient of x and y. In this, what we have to define first, the size of the dataset or the number of observation or point. So the number of observation or the point, let's say n, my n equal np dot size of x, size of y, anything. Okay, then we'll calculate the mean of x and y. Since we are using numpy, so just calling the mean of numpy is sufficient. Okay, there's a predefined function mean in that. So mean of x and mean of y equal np dot mean of x and np dot mean of y. Fine. Next we'll be calculating ss underscore xy and ss underscore xs, which is nothing but the sum of squared errors. So my ss underscore xy will be equal to np dot sum y cross x minus of n multiplied by total mean of y multiplied by mean of x. Fine. These two variables, mean x and mean y. N is what? So np dot size of x. So total size of your observation multiplied by mean of y multiplied by mean of x. Okay. Next, sum of square of x and x equal np dot sum x multiplied by x minus of n multiplied by mean of x multiplied by again mean of x. Fine. Now we'll be calculating the regression coefficient, that is the amount or the value by which the regression line need to be moved. So for that, let's say b1 equal ss underscore xy divided by ss underscore xx, and the value of my b0 will be equal to mean of y minus b1 times mean of x. Okay, and from this function I want to return the value of, and from this function I want the value of b0 and b1. So this is my coefficient estimation function. Okay, so this is my estimate coefficient function, which will be used to determine or estimate the coefficient when x and y values are passed into the function. So my next function would be to plot the graph based on the calculated values. So I'll create a function for plotting my graph. So plot my regression line. Inside that I'll pass three parameters, x, y and b. Okay, so now we'll be plotting our point as per our data set. So since there's a function, so let's define a function for that. So I need a scatter plot, plt.scatter. Inside that x coordinate, y coordinate, these are the location of the point on the graph. Then I'll specify the color. So I'll select the color as M. Color here is basically the color of the plotted point. You can change it to red or green, orange, or any color depending on your need. Then we'll define a marker. So marker is the shape of the point, like a circle or any other symbol. Okay, so I'll specify marker as circle and marker equal O. So these are basically optional. You can just write plt.scatter, that is also enough. Okay, next what we'll do, we need to predict. So next we have to create a predicted response vector. So predicted values of y, so y predicted equal b0 plus b1 times of x. Next we'll plot the regression lines. So plt.plot x and the predicted values of y underscore red, and let's say the color is green. Okay, so next we'll plot the label of both the coordinates. So plt.x label, it's what? Size, and plt.y label, it's what? Cost. Okay, and finally plot.show to show the plotted graph. Okay, fine. Now finally let's create our data set and call these function. Now let's add some point on our x-axis. So x equal np.array. All things I want to add: 1, 2, 3, 4, 5, 6, 7, 8, 9 and 10. These are house sizes ranging from 1000 square feet to 10,000 square feet. Okay. Here 1 represents 1000 and 10 represents 10,000. Okay. And y equal np dot array, the cost of the house 300k, comma 350k, comma 500k, comma 700, 800, 850, 900, again 900, then 1000, then finally 1200. So these are our array. Our next task would be to estimate the coefficient. So b equal estimate the coefficient of x and y. Both the values will be taken from here. Then print estimated coefficient estimated coefficient slash n b naught equal s slash n b1 equal s dot format p of 0 comma p of 1, and finally we'll call plot underscore regression line with the values of x, y and b. Here b is the estimated coefficient. Okay, let's execute it. Got the error built-in function. Okay, I think we have messed these brackets over here and here. Okay, so we got the value of b naught as minus of 7.5 and b1 as 137.72. We got an error named plot regression line is not defined. Let's just copy this as it is. Okay. Double T, where is that? Okay, sorry. Okay, so we got our regression line. The plot which we got is a line of linear regression. So the plot which we got is our linear regression line. The screen line is nothing but linear regression line.
So what basically happens in simple linear regression is there is just one independent variable. So there is one dependent variable and one independent variable, and you try to understand how does the dependent variable change with respect to that independent variable. So let's go ahead and start a demo. So our first task would be to load the Boston dataset, and we'll be loading the Boston dataset with the help of pd.readCSV function. So again, for that we'd have to import the pandas library first. So I'll just type in import pandas as pd, and then what I'll do is I will load the boston.csv data file, and I'll store this in this object and name it as data. Now after that I'll have a glance at the first few records of this dataset. Right, so this is our Boston data set, and it comprises of all of these columns. So there is CRIM, ZN, Indus, CHES, NOX, RM, and so on. Now out of these, the main column which we are interested in is MEDV. So this MEDV column basically indicates the median price value of the houses in Boston. And for our simple linear regression, what we're going to do is we're going to take this as our dependent variable, and we're going to take LSTAT as our independent variable. So here LSTAT signifies the percent of population which is below poverty line. Alright, now let's go ahead and have a glance at the shape of this data set. So we'll type in data.shape. So what we get is 506 and 14. Now this basically means that there are 506 rows in this data set and 14 columns in total. Now let me also go ahead and use the describe method on this data set. So I'll just type in data.describe. Right. Now this just gives me the different aggregate functions on top of all of these columns. So I've got the count, mean, standard deviation, the minimum value, the 25 percentile, 50 percentile, 75 percentile, and the maximum value, right? So let me actually take this crime rate over here. Now this count which you see, this basically tells you the number of records in each of these columns. And as we already know, since all of these columns belong to the same data set, and hence the number of records should be the same for all of these columns. And the mean crime rate, we see that it's around 3.6, the minimum crime rate is 0.006, the maximum is around 88. Right, so these are the different summary statistics which you can get from this data set. Now, let's just have a glance at our two main variables, which would be our independent variable and the dependent variable. So as I've already told you guys, our independent variable would be this LSTAT column and our dependent variable would be this MEDV column. Now, from this entire data set, I'd be only segregating these two columns and storing that in data underscore. And after that, I'll have a glance at the first 5 records. Alright. So this is my independent variable and this is my dependent variable. Now let me go ahead and make a plot with respect to these two, and I'll be plotting the LSTAT column onto the x-axis and MEDV column onto the y-axis. So for that purpose, I'd have to load the matplotlib package. So I'll just type in import matplotlib.pyplot as plt, and I'll type in data.plot. So LSTAT is mapped onto the x-axis and MEDV is mapped onto the y-axis, and I'll just go ahead and give the labels to them. So the label which I'm giving to x-axis is LSTAT and the label which I'm giving to y-axis is MEDV, and then I'll go ahead and just plot this. So y-axis we have MEDV, x-axis we have LSTAT. Now what we see is there is sort of an inverse relationship. So as LSTAT increases, MEDV decreases, right? So as the population percentage which is below the poverty line increases, the median value of the price of the house decreases, which is actually quite intuitive, isn't it? So if the population is below poverty line, obviously they can't really afford luxury houses, can they? So what we basically understand from this is there is sort of an inverse relationship between these two columns, right? Now it's finally time to go ahead and build our model. And before we do that, we'd have to prepare our data first. So what I'm going to do is I'm going to take this LSTAT column and store it in X. And similarly, I'll take this MEDV column and store it in Y. So this is done. Let me have a glance at the size of these two objects. So this tells me that there are 506 rows in X and Y. Well, that is again very simple to understand. Now I'll finally go ahead and divide this data set into training and testing sets. Now it's very important to divide our data set into training and testing sets, because if you go ahead and just build our model on top of the entire data set, then there are chances of overfitting and it'll fail miserably when new data comes in. And that is the main reason why we'd have to divide our data into training and testing sets. So I'll go ahead and import train test split from sklearn.model selection, and I'll use this function. So I'm passing in all of these parameters. So X is basically all of my features, Y is the labels or the dependent variable, and then I'll set the test size to be equal to 0.2. So this basically means that 20% of the records should be in the test set and the rest of the 80% records should be in the training set. Right, and I'll be storing all of these results in xtrain, xtest, ytrain and ytest. So xtrain over here basically denotes the training set for LSTAT column. Similarly, xtest over here denotes the test set for LSTAT column. And then we have ytrain, which denotes the training set for MEDV column. And then we have ytest, which is basically the test set for MEDV column. Right. Now again, let me go ahead and have a glance at the shapes of all of these 4 objects. So the shape of xtrain is 404, 1. So this means that there are 404 records in xtrain, and then we have xtest. So the shape of xtest is 102. This means there are 102 records in xtest, and it's the same for ytrain and ytest. Alright. Now I'll go ahead and import linear regression from sklearn.linear model and create an instance of it, and I'll store that in regressor. And then finally I'll go ahead and fit this model on top of the train set. So I'll type in regressor.fit and I'll pass in these two objects, which are basically xtrain and ytrain, which in turn is nothing but your training set. Right, so we've fit the model on top of the training set. Now, as you already know, linear regression is basically built on top of the linear line, or in other terms it is basically y equals mx plus c. So here y is your dependent variable and x is your independent variable, and you're trying to understand how does y vary with x. Now, apart from y and x, you have 2 other terms over here. So the 2 other terms are m and c. Now, m is your slope and c is your intercept. So let's go ahead and find out the values of m and c. Right. So I'll go ahead and print the value of C, which is basically the y-intercept. So I'll print regressor.intercept. So we see that the value of intercept is 34.33. And similarly, I'll go ahead and also print the value of coefficient, which is nothing but the slope. So the slope value is minus 0.92. Now, when you see that there's a negative value associated with the coefficient, and this basically means that as the independent variable increases, the dependent variable would decrease. Or in other terms, there is an inverse relationship between the independent variable and the dependent variable. So now that we've built the model, let's go ahead and predict the values on top of the test set. So I'll print in regressor.predict and I'll give xtest as the parameter inside this. Alright. So I have also predicted the values on top of xtest. So it's finally time to go ahead and find out the error in prediction. So for that, we'll be importing metrics from sklearn, and I'll be having a glance at different metrics such as mean absolute error, mean squared error, and root mean squared error. I'll click on run and we have these values. So mean absolute error comes out to be around 5.07, mean squared error comes out to be 46.99, and root mean squared error comes out to be 6.85. Now what you need to understand is the lower the value of root mean squared error, the better the model. And this basically helps you to compare multiple models. So let's say you have model 1 and model 2, and model 1's root mean squared error is around 10 and model 2's root mean squared error is around 5. So now when you see these two metrics, you can clearly say that model 2 is better than model 1 because its root mean squared error is less than model 1. Alright, so we have successfully built a simple linear regression model. Now let's go ahead and build a multiple linear regression model where we'll have multiple independent variables. Right. So we'll pretty much perform the same steps over here. I'll go ahead and load the pandas and numpy package, and I'll load up this Boston dataset and store this in this dataset object. Again, I'll have a glance at the dataset, which is basically the same dataset which we were dealing with. Now this is where the change comes. So I'll be taking all of the columns except the last column into this X object, and this X object basically denotes all of my independent variables, and in Y object I'm just taking the final column. So here the final column represents this MEDV column, right? So all of these columns over here, that is the first 13 columns, would be my independent variables, and the 14th column would be my dependent variable. Right, so I'm storing this in X and Y. Now I'll do the same thing. I'll go ahead and divide this data set into train and test sets. And over here I'm setting the test size to be equal to 0.3. So this means that 30% of the records would be in the test set and the rest 70% of the records would be in the training set. Right. Now I'll also go ahead and fit the model on top of the train set. So I'll just say regressor.fit and I'll pass in xtrain and ytrain as the parameters. I'll click on run. Right, so we've successfully fit the model, and we'll also go ahead and predict the values on top of the test set. So over here, I'll type in regressor.predict and I'll pass in xtest as the parameter. Right. So we have also predicted the values on top of the test set. Now I'll go ahead and find out all of the metrics. So we'll see the same metrics, which are basically mean absolute error, mean squared error, and root mean squared error. Right, and this is what we get this time. Let me compare these values with the first model. So for the first model, we saw that the root mean squared error came out to be 6.85, and for the second model, the root mean squared error comes out to be 5.54. So as I have already told you guys, if the root mean squared error is lower for a model, it basically means that this model is better than other model. So we can basically conclude that model 2 is better than model 1. And guys, this is how we can implement linear regression with the help of sklearn.
So this is Lauren. She's looking for a property to buy, but she's confused how to start. So she goes to one of her friend, Josh, and asks him if he could help her to find a property with bigger garden area for X bucks. Our guy, Josh on the right, agrees to help her to find a property, but he himself doesn't know how. So what he do, he goes to another friend of him, explains him the whole situation, and asks him if he can do anything about it. He immediately says yes and start doing some calculations. Then he says to Josh that spending X bucks can get her a property of area Y. Now Josh is confused and asks him, how did he find out? The friend goes like, simple linear regression. Now let's see how exactly he used simple linear regression to solve his issue. So here are our dependent variable and independent variable. Property size being the dependent variable and money being the independent variable. What this guy want to do? He want to find out a relation between the property size and money. So it's like if you want a house of bigger area or bigger property size, then you have to spend more money. So both of them are directly proportional, right? So in this case, we'll get a positive linear regression line, right? That is, spending more money will get her a bigger property. Okay. In other case, but again, our next scenario is she wants a bigger garden area, right? So imagine the scenario keeping the property area constant. The house area is inversely proportional to the garden area. It's like if you want to increase the garden area, so you have to reduce the house area. So take it like this. Suppose you have already fixed the property and you want to construct a house with a garden in it. But now your demand is you want to have a bigger garden area. So if the size of the property is fixed and if you increase the size of the garden, then obviously you have to reduce the size of your house, right? So in this case, if you try to plot a regression line, you'd get a negative regression line, right? Bigger garden area means smaller house, right? Now let's take an example to see how exactly did he predict the value of the house. So in order to find the regression line, what he did, he took the historical data of property area sold in the particular price, okay, and he plotted it on the graph. So this was the plotted point of property area sold in past for a particular price, okay. Now what he did, he drew a regression line. Now to find out what property area she can buy with X bucks, he plots X on the independent variable scale and project it to the regression line. And then against that point, there he has the area Y. This is the area Y. So this is how he predicted Lauren can buy Y area of property in X bucks. Alright. Now let's see what he can and what he cannot say from this. So he can say that if Lauren spends X amount of money, she can buy a property area of Y. But what he cannot say is, will the property would have a good neighborhood or not? Or will the location be noiseless suburb or a bustling city? Right, so these are the questions which even he cannot answer using this graph. So the questions like, will the property will have a good neighborhood? Or will it rain tomorrow or not? Or is this mail a spam or not? All these kind of problems fall under a particular category known as classification problems in machine learning. Now with linear regression algorithm, we could not answer these problems. So that is where logistic regression comes into picture. Now let us see where this logistic regression algorithm that we just talked about lies in the machine learning algorithm tree. So in machine learning, we use two traditional learning techniques to build a predictive model: supervised learning and unsupervised learning. Again, look at the supervised learning. There are two categories, regression and classification, right? In regression, we have linear regression, and in classification, we have logistic regression and SVM. So our today's topic of discussion is logistic regression, which comes under the category of classification. Okay. So now that we have got a little bit idea about logistic regression, let's go a little bit deeper and discuss about what exactly is logistic regression and why do we use it. So what is logistic regression? Well, logistic regression is a statistical classification model that deals with categorical dependent variable. Again, you must be wondering, what are these categorical dependent variable? Well, these are some of the discrete variable that have two or more categories without having any kind of natural order. For example, temperature, area, or gender. Okay. So you can say that logistic regression is generally used where the dependent variable is binary, or where the dependent variable is binary. That is, only two outcomes are possible, either yes, no, true, false, 1, 0, etc. Right. And also remember a fact that you can use both continuous and discrete input data with logistic regression. So before moving ahead, let's look at the graph. See, there are two variables. One is independent and other is dependent. Can you figure out which one is dependent and which one is independent? So before moving ahead, let's take a look at this graph. So So over here we have two different variables, hours studying and probability of passing exam. Can you figure out which one of them is dependent and which one of them is independent? So if you have guessed that hours of studying is your independent variable and probability of passing the exam is dependent variable, then I'd say that you are 100% correct. So now that you know what exactly is logistic regression, let's move ahead and see why do we use logistic regression. Well, logistic regression can be used as a tool for applied statistics and discrete data analysis. Why? Because it gets the output in the form of probabilities, which help us to easily classify the given data. Okay, so this is why we are using logistic regression. So now that we have successfully established the basic of logistic regression by understanding what and why of it, let's go ahead and see how logistic regression can be applied for classifying data with the help of an example. So here we are using an example of spam email classifier. We need to build a predictive model that would classify whether a mail is spam or not. So let's look at the approach that we are going to take while building this model. First, we'll try to understand the variable that on the basis of which we are classifying the mail. Next, we'll plot the label data. Once we are done with plotting the label data, we'll draw the regression curve. And finally, we'll try to find out the best fitted curve using maximum likelihood estimator. Alright? So let's get started. So step 1 is defining the variable. So let's start off by understanding what is independent variable in our case. So in our case, the independent variable is count of spam words. Well, here are some examples of commonly used spam words. Word like buy, get paid, guarantee, winner, unlimited, etc. Okay, so these are the kind of words which when found in the mail is treated as spam. If the number of these kinds of words are more in a mail, then that mail would definitely be a spam mail. Okay, just for a better representation, let me put them in a bag of spam words. Let's put the bag. So there's a bag of spam words. Let's put all the words in them one by one. Buy, get paid, guarantee, winner, and unlimited. Okay. Now, what about our dependent variable? Well, our dependent variable is going to be the probability of mail being a spam. If the probability is 1, that means the mail is spam. If it's 0, it means it's not a spam mail. Well, in general, the mail with less number of words from the list of spam words will be treated as a spam mail. With 5 or more spam words in a mail would be treated as a spam mail. But there can be cases where you might find mails with less spam words being spam. Also, you might find cases where mails with more number of spam words is not a spam mail. So here our aim is to build a predictive model to classify the mail with minimum error. Okay. Let's see what is our next step. So our next step is plotting the label data. Let's say this is a set of data that we'll be using to build the model. This is a very small data set, but just remember that whenever you are using logistic regression, make sure that you are using a large amount of data. Logistic regression works pretty well with large amount of data. It doesn't work that good with small amount of data. Okay. Here, just for the purpose of understanding, we are using small data set. Alright. So we have two variables, number of spam words and the probability of mail being spam against each mail. Okay. Next, as a step 3, we'll draw the regression line. So next what we'll do, we'll plot our data set on x-axis and y-axis with independent variable on the x-axis and dependent variable on the y-axis. So number of spam words in a mail is an independent variable, right? And the probability of that particular mail being a spam or not a spam is a dependent variable. It depends on the number of spam words in a mail, right? So let's plot these words one by one. So first we have is one word and the probability of this mail being a spam is 0. So it will be plotted up here. So next we have is 5 spam words in a mail and the probability of that mail being a spam is 1. So it will be plotted somewhere here. Next is 3 spam word is a spam mail. So it will be plotted again here. 2 words, it's not a spam mail. So I'll be plotting up here. 7 words, again a spam mail up here. 4 words, not a spam mail here. 9 words, it's a spam. 8 spam words, again, it's not a spam. So once we are done with the plotting, this is how our plotted data would look like. Now let's say that we have a new mail and now we want to figure out whether it's a spam or not. So before moving ahead, let me just tell you, in real world scenario to perform logistic regression, you need a large amount of dataset. And also you might find many cases where a spam mail might contain only 2 words, where a spam mail might contain only 2 spam words. Or also it might be possible that you get a mail where you are having more than 5 spam words, and even in that case, your mail is not a spam. Okay, so here we are building a predictive model with primary aim to reduce the error. Okay. Now let's say we have a new mail up here. Now we need to figure out whether this mail is spam or not. But how do we do that? Well, first of all, we need to plot a regression curve which would fit the best. And that curve would be our logistic regression curve. But now the question comes, how to find out which is the best regression curve? Okay. Well, this will contain 3 steps. Well, the first step is to convert the y-axis from the scale of probability confined between 0 and 1 to a scale of log odds. Then drawing a random regression line out of the data that we already have. Then with the help of sigmoid function, we'll convert the log odds to the probability of mail being spam. We'll plot each mail on the base of their new probability values. And this will form our regression curve. Then finally from this plot, we'll find out the log likelihood values of each mail. Now from this plot, we'll find out the log likelihood values of each mail. The individual likelihood. At last, we'll find the log of likelihood. That would be our log likelihood of the regression curve. Now the question comes, what are these terms such as log odds or log likelihood means? So before moving ahead, let's discuss that. So what does log of odds mean? Let us explore this with the help of an example. So before we proceed any further, let me just clarify you one thing. This probability and odd, these are not the same thing. Let me explain you this with an example. Suppose this guy, he goes to fishing 5 times a week. So out of 5 times, he catches a fish 2 times and he failed to catch 3 times. Okay. So now in this case, what is the probability and odd for getting a fish for dinner? So let's first calculate probability. So probability is chances for divided by total chances. So chances for catching a fish. So what is the probability of catching a fish? That is how many times he caught a fish. That is 2 divided by total chance he had to catch the fish. So that was 5, right? So here probability of getting a fish for the dinner is 2 by 5. Okay. Next comes the odd. Chances for divided by chances against. That is the ratio of how many times he caught the fish divided by how many times he failed to catch a fish. Okay, so he caught the fish for 2 times and he failed in catching the fish for 3 times. So the odd for getting a fish for dinner is 2 by 3. Okay, so now that we know odds, now let's see what log of odds and log odd ratio are. Are they same? Let's find out. For your information, log odds is also called as logit function. Okay. So in our previous example where the fisherman was catching a fish, let's add another factor to his fishing. Let's add a factor as weather. So then we can recreate the entire scenario as he was successful 2 times on a rainy day. But on a sunny day, he was successful for 3 times. Now the odds of catching fish on a sunny day is how much? It's 2 by 3, right? And the odds of catching on a rainy day is 3 by 2, right? As it's already mentioned that on a sunny day, he catches 3 times. So he is successful for 3 times and he failed for 2 times. So let's see he was successful 3 times on a rainy day and 2 times on a sunny day. So odds for catching a fish on a sunny day is 2 by 3. That is, he's successful 2 times on a sunny day and he failed for 3 times in a week. So odd for catching fish on a sunny day is 2 by 3. Similarly, odd for catching fish on a rainy day is 3 by 2. And now log of odds of catching a fish on a sunny day is just log value of 2 by 3. And similarly, log of odds of rainy day is log of 3 by 2. Now log of odds ratio is nothing but the log of odds on a rainy day divided by odds on a sunny day. Okay. Next is log of odds ratio. So log odds ratio is nothing but the ratio of log of the odds on a sunny day to log of the odds on a rainy day. That is log of 2 by 3 by 3 by 2, which is nothing but log of 0.44. So here we can say that odds and odd ratio are both different things. Now let us go back to this step. So now that we have understanding of log odds, so we are ready to perform this step. Okay. So let's see how we converted the 0, 1 axis to minus infinity to plus infinity axis. So here we'll be converting the probability scale to scale of log odds. Okay, so for the log odds, we have a formula as log of probability of spam divided by 1 minus probability of spam. So here the probability of a mail being a spam is 1. Okay, so we get the value of log odds as log of 1 divided by 1 minus 1, that is log of 1 by 0. It's positive infinity. How we got that? So log of 1 by 0 is nothing but log of 1 minus log of 0. And log of 0 up here is minus infinity. So minus of minus infinity is what? Plus infinity. How log of 0 up here is minus infinity? Let's see. So in general logarithm, so we have log 0 with base b equals c. So if you convert it into exponential form, we get 0 equal b to the power c. Right. So if the value of b is less than 1, so the value of c has to be extremely small or closer to minus infinity for this equation to be true. Okay. And we'll get a positive infinity in the case where b is greater than 1 or our base is greater than 1. Okay. So coming back up here. So here log of 1 by 0 is nothing but log of 1 minus log of 0. And we got the result as positive infinity. As log of 0 up here is minus of infinity, and minus of minus infinity is what? Plus infinity. How we got the value of plus infinity? Let's see. So log 0 with base b equals c. If we convert this into exponential form, we get something like this. 0 equal b to the power c, right? So for the equation 1 to be true, if the value of b or the base is less than 1, then in that case the value of c will be positive infinity. Okay. For example, 0.1 to the power 1000 would be smaller than 0.1 to the power 100, right? So more the value of c up here, more closer will the number get to 0, right? And in next case, if the value of b is greater than 1, so for this we have to make the value of c closest to minus infinity. Why? For example, we have 10 to the power minus 1, okay? Or 10 to the power minus 10, which is more smaller. 10 to the power minus 10, right? So which is much smaller or closer to 0? 10 to the power minus 10, right? So that's why we have to keep the value of c as less as we can. So here, if the value of b is greater than 1, the value of c would have to be close to minus infinity in order to make the equation true. So in this case, log of 1 by 0, by default we have base as 10. Okay, so that's why we took the value of c as minus infinity. So minus and minus of infinity is plus of infinity. So that's why we got the plus infinity up here. I hope this thing is clear to you. How we got the value of log odds as plus infinity. So I'll plot this up as plus infinity log odds. Now next, let's find the log odds of non-spam mail. So here we have the formula as log of probability of a mail not being a spam divided by 1 minus probability of mail not being a spam. So log of 0 divided by 1 minus 0. So we have log of 0 by 1, which is log 0 minus log 1, which tends to minus infinity. Okay, similar concept. Now we have our data up here. So first we'll assume one regression line. So now we have our data up here. So first we'll assume one regression line. Then we'll project our data onto the regression line. Okay. Now let's just go back to this step where with the help of sigmoid function, we'll convert the log odds to the probability of mail being spam. Okay. But what does this sigmoid function mean? So sigmoid function is the standard logistic function. The logistic function is defined as L multiplied by e to the power k times of k minus k dot upon 1 plus e to the power k times of x minus x naught. So here L is the curve's maximum value, k is the steepness of the curve, x naught minus x is the value of sigmoid point. Okay, so here the sigmoid function e to the power x divided by 1 plus e to the power x, here k equal 1 and x naught equals 0 and L equal 1. So this mathematical sigmoid function forms S-shaped curve which is confined between 0 and 1. Let's try to understand how logistic function works with the help of an example. So let's say we have a set of unspecified data and on these data we need to apply a sigmoid function. So let's see what a sigmoid function can do by visualizing this graph. So let's say we have a unspecified data and on these data we need to apply a sigmoid function. So plot this data and find out the respective y for these points. Okay, so what a sigmoid function is doing, it can be visualized from this graph, right? So you are giving some values on your x-axis, and using sigmoid function you can predict its probability on the y-axis, right? So this is the reason why sigmoid function is very useful while solving the classification problem. It takes any real valued number and maps onto a value between 0 and 1. Okay. Well, now that we have an idea of how sigmoid function works, let us move ahead with our spam email classifier. So we are ready to perform this step. That is converting the log odds graph into a sigmoid function graph. Now we have to find out the best MLE. Okay. Best maximum likelihood estimator. So we are going to replace the log odd value of each mail to get the probability of each mail being a spam. So we have the formula up here, probability equal e to the power log odds divided by 1 plus e to the power log odds. So 1 by 1 will place the log odds of each mail into this formula and calculate the probability for each mail. Okay. For example, I have this mail which after projecting into the regression line gives us log odd value of minus of 3.2. Okay. So what we'll do up here, we'll calculate the probability using the value of minus 3.2. We'll place the value minus 3.2 in our formula, e to the power log of minus of 3.2 divided by 1 plus e to the power log of minus of 3.2. So from here, we'll get the probability as 0.03. So plot it accordingly onto the new graph between probability of mail being spam versus spam word count. So on the basis of probability, our mail would lie somewhere near to 0. So according to the prediction, this mail is not a spam mail. Again, for another mail which is projecting on a regression line, this gives us a log odd value of 5.6. So when we put the value of 5.6 in the formula, we get the probability as 0.99. So the probability of this mail being a spam is 0.99. So again, we put this into this graph. Similarly, 1 by 1 will calculate for each one of them. For this mail, after projecting onto the regression line, we get the log odds value as minus of 4.5. So minus of 4.5 when put into the formula, we get the probability as 0.01. So the prediction of this mail is not a spam mail, which is same as actual, right? So again, we plot this mail onto a graph, alright? So similarly, you can repeat this step for the rest of the email as well. And finally, we got the S curve up here. So there's our regression curve. But you must be wondering, is this the best fitted curve? Or how do we find out whether it's best or not? Well, this is when the concept of maximum likelihood comes into picture. So now that we have regression curve, let's find out the likelihood of this curve. So first find out the individual likelihood of each mail. Again, you must be thinking, how do we get the likelihood value? Well, likelihood of each mail is nothing but the probability value of each mail being spam. So likelihood of first mail being spam is 0.01. Likelihood of second mail being spam, again 0.01. Similarly, third 0.03, fourth 0.05, and so on till 8th mail being 0.99. Okay. So once you get the individual likelihood of each mail, multiply them to find out the likelihood of the entire curve. Okay. Then calculate the log of likelihood. For calculating the log of likelihood, you can just take the log of the previous result. Okay. You can just take the log of previous multiplied result. Here we are adding all the logs because log of A multiplied by B equal log of A plus log of B. Okay. So we got the value of log likelihood of this curve as minus of 0.084. Now let us rotate this line to find out the best fitted regression line. So we got the log likelihood of this curve as minus of 0.084. Now let us rotate this line to find out the best fitted regression line. Again, we calculate the individual log likelihood of each mail. For this one, let's say we got log likelihood which is shown on your screen. So final value we got up as minus of 0.207. So we got the value as minus of 0.207. So now if we compare the log likelihood values for these two regression lines, we'll see that line A has bigger value of log likelihood than line B, right? As line A has log likelihood value of minus of 0.084. So the log likelihood value for line A is minus of 0.084, whereas for line B is minus of 0.207. So minus of 0.084 is bigger than 0.207, right? So therefore we can say that line A has better likelihood value than line B. Now again we'll rotate the line. We'll keep on rotating the line until we get the maximum value of log likelihood. And then finally we'll choose a line which is having the maximum log likelihood, and that line would be the best fitted regression line.
So let's quickly go to Jupyter Notebook and start with a demo, right? So this is Jupyter Notebook, guys, and our first task would be to load up the heart disease dataset, and for that purpose we would have to import the pandas package. So I'll just type in import pandas as pd, and I'll use this read_csv method from the pandas package. So I'll type in pd.readcsv and I'll pass in the name of the dataset, which is basically heart.csv, and I'll store this in this dataset object. Now let me have a glance at the first few records of this dataset. So this is our dataset which comprises of all of these columns, and we're going to build the logistic regression algorithm on top of this column over here, which is basically target. So target would be our dependent variable and the rest of the columns would be the independent variables, right? And this target basically means that, so you have 1 and 0 values over here. The 1 value means that the person or the patient has the heart disease, and 0 basically means that the patient does not have heart disease, right? Now let me also have a glance at the shape of this dataset. So I'll just type in print dataset.shape, and this gives me a value of 303 and 13. So 303 means that there are 303 records in this dataset and 13 columns. Now let me actually have a glance at the value counts of this target column. So this value counts basically tells me the frequency of these two values. So I have these two values in this column, which is basically 1 and 0. So there are 165 records where the value is 1, and there are 138 records where the value is 0. So this basically means that in this data set there are 165 patients who actually have the heart disease and 138 patients who do not have the heart disease. Now I'll go ahead and actually visualize this. So I'll load up the matplotlib package and seaborn packages, and I will pass in this target column onto the x-axis, and the data is our data set, which is basically this heart disease data set. And what I'm doing is basically building a histogram, and I'll plot this up over here, right? So this is the bar plot for the value of 0, and this is the bar plot for the value of 1. And this basically tells us the same thing. So 165 is the value of the number of patients who actually have the heart disease. So this basically is for all of those patients who do not have the heart disease. Alright, now let me go ahead and divide the data set into features and label sets. So I'm storing all of the features into this X object. So all of these 12 columns would be my features, and this target column would be my label or would be my dependent variable. Alright, and this is how I'm going to divide the data set. So I'm going to extract all of the columns except the last column and store it in this X object. And similarly, I'll only take the last column and store it in this Y object. Alright. Now let me have a glance at these individual independent variable and target variable. So x.head gives me all of the independent variables and y.head gives me the target, right? So now that we have our independent variables and the dependent variable, let me go ahead and divide this dataset into training and testing set. And for that purpose, I'd have to load up the train test split method from sklearn.model selection. And over here, I'm setting the test size to be equal to 0.2. So this means that 20% of the records are in the test set and the rest 80% records are in the training set. Alright, I'll click on run again. Now we have divided the data set into training and testing sets. Now finally it's time to build the model, and for that purpose I'll be importing logistic regression from sklearn.linear model. And I'm going to create an instance of this. So I'll just use this method logistic regression and I'll name that instance to be log model. And I'm going to fit this model on top of the train set. So I'm basically passing x train and y train as the parameters. Right, I'll click on run. Right, so we have successfully built the model on top of the train set. Now we're going to go ahead and predict the values on top of the test set. So I'll type in log model.predict and I'll pass in xtest as the parameter and I'll store the result in ypred. So we have also predicted the values. Now it's time to calculate the accuracy. So I will type log model.score and I'll pass in xtest and ytest. So I want to calculate the accuracy for the prediction on top of the test set, right? So the accuracy comes out to be 73%, which is actually not that bad. And let me actually also build the confusion matrix. So confusion matrix would give me a table of values, which actually comprises of the correctly predicted values and misclassified values. So I'd have to import confusion matrix from sklearn.metrics, and again I'll just pass in ytest and ypred as the parameters inside this function, and I'll print this out. Right. So this left diagonal which you see, this left diagonal actually represents all of those values which have been correctly classified, and this right diagonal represents all of those values which have been misclassified. And if you want to get the accuracy, all you have to do is add up 20 plus 25 and divide it with all of the values, and you'll get the same accuracy. So let me actually add up a new cell over here and calculate the accuracy from this confusion matrix. So I have to divide this left diagonal with all of the values. So that would be 20 plus 25 divided by 20 plus 25 plus 10 plus 6. And this gives me a value of 73.77, which is the same as I got over here. So the accuracy is 73%, right? So we have built the confusion matrix. Now I'll also go ahead and build the ROC curve. So the ROC curve, it sort of gives me the right trade-off between the true positive rate and the false positive rate. So let me go ahead and plot this, and this is what we get over here. So on the y-axis we have the true positive rate, and on the x-axis we have the false positive rate. And basically you can understand this plot this way. So the closer this curve is to this top right corner over here, the better the model. That is, this curve needs to cover greater area. And this, what you see, red line, so this basically represents a classifier which would give you around 50% accuracy, and your model would be as better as it is far away from this red line.
So classification is a process of grouping things according to similar features they share. The example given up here represents a set of different garbages which are segregated as per the category into different bins. For example, paper, metal, plastic, e-waste, glass, organic, everything are segregated properly and are separated in different bins. So here we are classifying what? So here we are classifying the waste and adding them into different bins. Okay. So let's move ahead. Next is classification versus regression. Well, there's a very important thing to understand. So what is the difference between a classification and a regression? I'm assuming you know that both are related to prediction, right? Regression is used to predict a value from a continuous set. That is, it deals with continuous variable. On the other hand, classification is used to predict the class or to which class that particular variable or that particular data belongs to. So basically, it deals with categorical variable. For example, the price of the house depends on its size, right? Size here is a numerical value which can be continuous. So this relates to regression. Similarly, prediction of price can be in words like very costly, costly, affordable, cheap, and very cheap. So this relates to classification. So this was about regression and classification. I hope now you know when to use regression and when to use classification. So let's move ahead. Next is the types of classification algorithm. So we have logistic regression, we have decision tree, random forest, k-nearest neighbor, and neighbors. Let's have a look at them one by one. So first is the logistic regression. So we have already learned about it in detail in our previous session. Let me just summarize things for you. So logistic regression is used when the dependent variable is categorical. For example, you have to predict whether the given mail is spam or not. Okay, so in that case, you will be using a logistic regression. So for detailed understanding on logistic regression, I'd suggest you to go through our previous session. Okay, for now, let's move ahead. Next is the decision tree. Well, decision tree is a graphical representation of all the possible solutions to a decision. Here, the decisions are mainly based on some conditions, and the decision and the output generated can be easily explained. From the image shown here, you can see that the main stem of the tree is nothing but the issue at hand. The branches of a tree or the subtree are the possible decisions, okay, and the leaf nodes or the leaf of the tree are possible scenarios. Let me just give you an example of a decision tree. For example, you have to predict whether the given person is fit or not. So the very first thing that you will be looking for is age less than 30. If the condition is true, then you will check if the person eats a lot of pizza or not. If the person eats a lot of pizza, then he is unfit. In case he doesn't eat a lot of pizza, then you can say he is fit. But what if the person's age is greater than 30? Then in that case, you'll check another condition, like you'll go for whether he exercises in the morning or not. If he does, then he is fit. If not, then he is unfit. Okay, so this was about decision tree. Next is the random forest. Well, random forest builds multiple decision tree and merges them together to get a more accurate and stable prediction. So you can say that decision tree is a basic building block of a random forest. Okay. Now the question arises, why it is called random? Well, it's called random because each decision tree in a forest considers a random subset of features when forming questions. Now the question arises, why it is called random? Well, it's called random because each decision tree in the forest considers a random subset of features when forming questions, and they only have the access to a random set of training dataset. So this increases the diversity in the forest, leading to a more robust overall prediction and the name random forest. Okay. So now when it comes to prediction, random forest takes an average of all the individual decision tree estimate. Well, you can say that there are two main fundamental ideas behind the random forest, and both of them are well known to us in our daily life. The first is constructing a flowchart of questions and answers leading to a decision. And the next is the wisdom of the random and diverse crowd. So the random forest is the combination of these ideas that has led to the power of random forest model. Well, if you talk about its training, the training is done using bagging method. Now, you'd ask what exactly is bagging? Well, we have already discussed it. Not the terminology, but I have explained you the concept. Bagging is building multiple decision tree by using random set of the training dataset and finally voting the trees for a consensus prediction. One last thing. So using random forest, you can correct the decision tree's habit of overfitting the training dataset. So this was about random forest. Let's move ahead. Next we have is k nearest neighbor. Well, KNN algorithms use the data and classify new data points based on a similarity measures. The K in KNN algorithm is the nearest neighbor we wish to take vote from. It is one of the simplest and most used learning algorithm. Well, KNN is a non-parametric, lazy algorithm whose purpose is to use a database in which the data points are separated into several classes to predict the classification of a new sample point. And when I say it's non-parametric, it means that it does not make any assumptions on the underlying data distribution. And when I say it's lazy learning algorithm, it doesn't mean that it's lazy like a polar bear or something. Okay, it means that it does not use the training data points to do any generalization. In other words, there is no explicit training phase, or it's very minimal. So this implies that training phase is pretty fast. And the lack of generalization means that KNN keeps all the training data. So all of them are needed during the testing phase. So in this example, you can see that we have a test sample up here in green. We need to classify, we have to predict whether it belongs to a red triangle or whether it belongs to a square. So the test sample should be classified either to the first class of the blue square or to the second class of a red triangle. If k equal 3, that is, it's outside the circle. So it is assigned to the second class because there are two triangles and only one square inside the circle. Now, if for example k equal 5, then it is assigned to the first class, which has 3 squares versus 2 triangles outside the outer circle. Okay, I hope the example is clear to you. So let's move ahead. And finally, in the end, we have naive-Bayes classifier. Naive-Bayes classifier is a probabilistic machine learning model that is used for classification. It is completely based on Bayes theorem. We can find the probability of happening of A given that B has already occurred. So here B is the evidence and A is the hypothesis. So the assumption made here is that the features are independent. That is, the presence of one particular feature does not affect the other. Hence, it is called naive. Okay. So this was the summary of all the different types of classification algorithm tree. So let's say this is our data set. So our data set consists of 3 different attributes: color, diameter, and label. Label consists of different types of fruit. So we have 3 different types of fruit up here: mango, lemon, and cherry. And if you talk about color, so in color we have 2 varieties of mango. One is of green and one is of yellow. Okay, now our task is to create a decision tree for this dataset. So now we'll split this dataset on the basis of some condition and create a decision tree. So for splitting the dataset, let's consider this attribute, diameter. So as you can see, we have 3 different fruits with common diameter of 3 and 2 diameters which are less than 3. So we have a condition of split over here. So we can check if the diameter of the fruit is greater than or equal to 3 or not. If the condition is true, then we'll have green mango, and yellow lemon as a part of our splitted dataset. And if the condition is false, then in that case, all we'll get is cherry. Okay, so here you can say that this is our leaf node. So in case if you reach till here, so you can predict your value and say that it's a 100% cherry. Okay, but if the diameter is greater than equal to 3, then what will you predict? Is it a green mango? Is it a yellow mango? Or it's a yellow lemon? You can't say, right? So again, you have to split this data set. So how can we split? Let's see if we have any common feature to split this data set. So as you can see, we have a common color over here. So we have a yellow mango and a yellow lemon. So again, we got the condition of split over here. So we'll check here if the color is yellow or not. So if the condition is true, we'll get all the yellow fruits in this dataset. And if the condition is false, we'll get all the non-yellow fruits in it. So we got green mango over here. So if you reach till this node, then you can say that the probability of finding green mango at this particular node is 1, or it's 100%. And at this leaf node, you can say that the probability of finding a yellow mango is 50% and the probability of finding a yellow lemon is also 50%. Okay, so now you can see that we have some terms over here like Gini impurity equals 0 or Gini impurity equals 0.44. So what does this mean in this visualization? So for any particular node, if Gini impurity equals 0, it means that that particular node is a pure node and it does not have any mixed values. So as you can see, we have all cherries in it. So if you focus to this node, you can see that the Gini impurity value is non-zero. So it means that it's a mixed data set or it's a mixed value. Okay, it's not a pure value, and there is a further chance to split the data set on some condition. Okay, so now if you focus on these conditions like is diameter greater than 3 or is color equals 0, so they have some value of information gain. So it's like you can gain maximum information at your root node, and as you reach towards the leaf node, the information gained is decreased. So as you can see, this is the parent node for this node, right? Or this is the child node for this node. So the value of information gain at the parent node would always be greater than the value of the information gain at child node. Okay, so this was about how you can visualize a decision tree. Now let's move ahead and understand about the decision tree terminologies. So the very first thing that we have is the root node. The root node represents the entire population or sample, and this population further gets divided into 2 or more homogeneous set. Okay, so when we pass the entire data set to one particular node, so that node is root node. Okay, next is leaf node. Well, leaf nodes are the node which cannot be further segregated into further nodes. Like in our previous example, the point where we got 100% lemon or 100% mango, so those nodes were leaf nodes. So it's like we cannot further segregate it down. It's the last point of that particular branch or that particular node. Next is splitting. Well, splitting is dividing the root node or the sub node into different parts on the basis of some condition. Like in our example, we divided the tree on the basis of 2 conditions. The first one was, is the diameter greater than or equal to 3? And the second one was, if the color equals yellow or not. So next is branch or subtree. Well, a branch or subtree is formed by splitting the tree or the node. Next is pruning. Well, pruning is just opposite of splitting. Pruning is basically removing unwanted branch from the tree. So it's like if you want to reach to a particular scenario, so you would remove all the unrequired decisions and the condition from between. Okay, so this is the concept of pruning. Next is parent node or child node. Well, root node is the parent node and all the other nodes branch from it is known as child node. Okay, so any doubt up till here? If you have, please reach out to us. Okay. So this was all about decision tree terminology. Now let's move ahead and see how we can create a decision tree. So there's a sample dataset. Our dataset consists of outlook, temperature, humidity, windy and play. So based on outlook, temperature, humidity and windy condition, we have to predict whether a person can play or not. Okay, so how will we do that? So in order to resolve this query, I'll be creating a decision tree for it. Now in order to create a decision tree, the very first thing that I would have to do is we have to pick one of the attribute. So now the question arises, which one among outlook, temperature, humidity and windy should you pick first? So the answer is determine the attribute that best classifies the training data. But how do we choose the best attribute? Or how does a tree decide where to split? So how do we split a tree? So in order to split the tree, we have various concepts. Let's have a look at them one by one. So on number one, we have entropy. Entropy defines the randomness in the data. It is a metric which measures the impurity. It is the very first step to solve the problem of a decision tree. Now once you find the entropy, your next task would be to calculate the information gain. So the information gain is the decrease in entropy after a dataset is split on the basis of an attribute. Constructing a decision tree is all about finding an attribute that returns the highest information gain. Okay? And the attribute with the highest information gain will be the attribute which would be selected as a root node or a node from where we'll split. Now, once you calculate the information gain, the next thing that you will calculate is the Gini index. So now that your data set is divided, now you have to check whether the splitted data is pure or not. So for checking the purity of the data, we have a measure as Gini index. It is the measure of impurity or purity used in building a decision tree. Okay. And finally, we have reduction in variance. Well, reduction in variance is an algorithm used for continuous target variable, that is regression problem. The split with lower variance is selected as a criteria to split the population. So as I said earlier, the very first thing in order to construct a decision tree is to calculate its entropy. So this is the formula for entropy. Entropy of S total space equals minus of probability of yes multiplied by log of probability of yes minus probability of no multiplied by log of probability of no with base 2. So if you take a look at the graph and the formula, so from here you can say that, so if number of yes equal number of no, that is probability of total sample space becomes 0.5, that is this point. Okay, so here entropy becomes 1. And if it contains all yes or all no, then in that case probability of total sample space is 1 or 0. If it consists of all yes, that is all 1 or all 0, then in that case the entropy is 0. Okay, now let me just show you what I just told you. So the formula for entropy was minus of probability of yes times of log of probability of yes minus probability of no multiplied by log of probability of no. So now when probability of yes equal probability of no, that is total sample space consists of equal number of yes and no. So in that case both would have the equal probability of 0.5. So if you put 0.5 in the formula above, you will get minus of 0.5 times of log 2 0.5 minus 0.5 times of log 2 0.5, okay, which will evaluate to 1. So here it proves that entropy for the case when probability of yes equal probability of no would be 1. Or you can say that there is maximum randomness in the dataset when probability of yes equals probability of no. Let's take another case where we have all yes. Okay, so probability of yes equal 1. Our total sample space consists only of yes. Okay, so for that we'll get the formula as E of s equal 1 of log base 2 times of 1, which is nothing but 0. This point, when the probability of yes is 1, then in that case the total entropy that you would get is 0. Now what if the probability of no is 1? That is, your entire data set only consists of no. There is no yes in the entire data set. So similarly you will get the value of entropy as 0. Okay, I hope I made my point clear. So let's move ahead. So now coming back to our data set. So our data set consists of 14 different instances. Out of them we have 9 yes and 5 no. So now if you add the value of yes and no to the formula, so it results to minus of 9 by 14 times of log of 9 by 14 minus 5 by 14 times of log of 5 by 14. So it drills down to 0.41 plus 0.43, which equals 0.94. So here the total entropy for my entire sample space is 0.94. Fine. So now that we have calculated the entropy for our dataset, our next task would be to calculate the information gain. So information gain equal entropy minus weighted average multiplied by entropy for each feature. So in order to find the root node, you have to calculate information gain for each attribute. And the attribute having the maximum value of information gain will be the attribute that will be selected as the root node. Okay, so let's do it one by one. So starting with Outlook. So if we choose Outlook, we have three different parameters: sunny, overcast and rainy. In sunny, we have 2 yes and 3 no's. In case of overcast, we have all yes. And in case of rainy, we have 3 yes and 2 no. So moving on ahead, we'll calculate the entropy when Outlook equals sunny, when Outlook equals overcast, and when it equals rainy. So we'll calculate all three individual entropies. So starting with when Outlook equals sunny. So in that case, we had 2 yes and 3 no's. So if we put those values in the formula for calculating the entropy, it would look something like this. And we'll get the result as 0.971. So in case of overcast, we'll get the value as 0. As the probability of yes in case of overcast is 1. We have all yes over there, right? And the probability of no is 0, as it is not available there in the dataset, right? So from here you can see that we calculated the entropy for Outlook equal overcast is as 0. Now entropy for Outlook equal rainy. In case of rainy, we had 3 yes and 2 no. So if you put all those value in the formula, so you'll get the result as 0.971. Okay. So now we have calculated entropy for each feature of the Outlook. So next we'll be calculating is the information from Outlook. So for calculating the information, we had the formula weighted average multiplied by entropy of each feature. So total information from the Outlook equals, so summation of all the information from different features. Starting with sunny. So in case of sunny, the weighted average is 5 by 14. So how did we get this 5 by 14 value? Like in case of sunny, we had 2 yes and 3 no's. So 2 plus 3 is 5 divided by total number of data points, that is 14. So 5 by 14 is the weighted average for sunny multiplied by the entropy value of sunny, that is 0.971 plus 4 by 14. How we got 4? So we had 4 yes in case of overcast, right? So here we got the weighted average as 4 by 14 multiplied by the entropy, which was 0, plus again 5 by 14, 3 plus 2 multiplied by 0.971. So if you calculate all these values, this result to 0.693. So the total information from the Outlook is 0.693. Now we'll calculate the information gained from Outlook. So total information gained from Outlook is total entropy minus information from Outlook, which equals to 0.94 minus of 0.693, which results to 0.247. Okay. Now similarly, we'll calculate entropy for each feature. We calculated the entropy for Outlook, temperature, humidity. So as you can see, in case of Outlook, we got an information gain of 0.247. In case of temperature, the information gain was 0.029. And in case of humidity, the information gain was 0.152. So here we can see that our Outlook is having the maximum information gain. So here we can conclude two things. First, our Outlook would be our root node, as it is having the maximum value of information gain. Okay. And secondly, we won't use temperature to create a decision tree, or we can avoid using temperature in our decision tree, as the information gained from the temperature is very less. Okay. So here we got our root node as Outlook. So here we got our root node as Outlook. We can split it into sunny, overcast and rainy. But now sunny and rainy both have some numbers of yes and no, right? Overcast is the only feature which consists of only yes. So our overcast would be treated as a leaf node. But again, we have to decide which node would be used when Outlook is sunny and which node would be used when Outlook is rainy. So again, we have to decide which node would come when Outlook is sunny or Outlook is rainy. Okay, so let's see how we'll do that. So again, we'll select it one by one. Next, we'll calculate the entropy for windy. Okay, so in case of windy, you can see we have two different features, false and true. In case of false, we have 6 yes and 2 no. In case of true, we have 3 yes and 3 no's. So next, we'll calculate the entropy of windy equal true, which we got as 1. Why? Because it has equal number of yes and no. Okay, so in this case, the probability of yes equal probability of no. So remember the first case where I told you if you would be having an equal number of yes and no. So for that case, the total entropy that you'll calculate, you'll get it as 1. Okay, and for windy equal false, you'll get it as 0.811 using the same formula again. Okay, so if you calculate the information from windy, you'll get it as 8 by 14 multiplied by 0.811, this is for windy equal false, plus 6 by 14 multiplied by 1 for windy equal true. And if you summate it, you'll get the value as 0.892. Now information gained from windy is total entropy minus information from windy, which is 0.94 minus 0.892, that is 0.048. Okay. So similarly, you will calculate for other features as humidity and temperature, and finally you will get this decision tree as the final output. So there's the final decision tree that you'd get. Okay. So let's see how does it answer our query and see the scenario where we can play. So first, outlook. So if outlook is sunny and the humidity is normal, then we can play. Or if outlook is overcast, then we can definitely play. No further condition attached to it. Or if the outlook is rainy and it's windy and the wind is not strong enough, it's a weak wind, then in that case also we can play. Okay. So this was about how you calculate entropy and information gain to create a decision tree using CART method, that is classification and regression.
Here's a quiz question for you guys. What is supervised learning? Your options are a machine learning technique where the model learns from labeled data to make predictions or decisions without human intervention. A machine learning technique where the model learns from unlabeled data to make predictions or decisions with high accuracy. A machine learning technique that doesn't involve data labeling, making it highly efficient. Or a machine learning technique used exclusively for image recognition. Please mention your answers in the comment section.
Decision tree regressor. That is, we'll be using decision tree as a regression algorithm, and we'll be implementing this decision tree algorithm on top of the Boston dataset. So before we go ahead and load up the dataset, let me actually import the requisite packages. So we would require the NumPy, Pandas and Matplotlib package, and with the help of this read_csv function, which comes from the Pandas library, I'll load up the Boston.csv dataset. Alright. So now that we have loaded up the dataset, let me have a glance at the first few records of this dataset. So I'll just type in Boston.head, and these are all of the columns present in this dataset. Alright. Now, for our first model, we'll be taking MEDV as our dependent variable and RM to be our independent variable. So, RM basically stands for the average number of rooms per dwelling, and MEDV denotes the median price value of the house. So, we basically want to understand how does the median price value of the house change with respect to number of rooms per dwelling. And I'll go ahead and make a scatter plot between these two columns. So, I'll map RM onto the x-axis, and I will map MEDV onto the y-axis. Right. So let me click on run, and this is what we get. So what we see is, as the average number of rooms increase, the median value of the price of the house also increases. And this again is quite intuitive, isn't it? So if the number of rooms increase, the size of the house would also increase, and this would in turn increase the price of the house. Alright. So now that we've done a bit of visualization, let me actually go ahead and extract the features and the target from the original data frame. So I'll extract this RM column and store it in the X object. Similarly, I'll extract the MEDV column and store it in the Y object. So X basically denotes my feature column and Y basically denotes my target column. Alright. Now I'll go ahead and divide this dataset into training and testing sets. So for that purpose, I'll be importing train test split method from sklearn.model selection, and I'll be passing in all of these parameters. So X and Y, I'll just pass in features and target, and I'll set the test size to be equal to 0.20. And this means that 20% of the records would be in the test set, and the rest of the 80% records would be in the train set. Alright, so we have our testing and training sets ready. Now it's time to finally build the model. So I'll be importing decision tree regressor from sklearn.tree. So again, I'm restating it, guys. So even though we're using the decision tree algorithm, we are able to perform regression with this, right? So now I'll create an instance of this. So I'll just call in this method decision tree regressor, and I'll name that instance to be regressor, and I'll fit this model on top of the train set. So the parameters which I'm passing inside this are xtrain and ytrain. So now that I've built the model, let me go ahead and predict the values on top of the test set. So I'll type regressor.predict, and the parameter which I'm passing inside this is xtest. Alright, so now we have also predicted the values. Now it's time to find out the RMSE value or the root mean square error value. and we'll be importing mean squared error from sklearn.metrics, and I'll be using this method, and I'll just pass in ypred and ytest. So ypred contains all of the predicted values, ytest contains all of the actual values, and I want to find out the error in prediction. Now since I've imported mean squared error, I'd actually have to find out the square root of it. So I'll type in np.square root and I'll pass in the value of MSE into this, and this will give me the root mean squared value. So the root mean square value for the model which we've built is 7.102. Now again, the model which we've built, that just has one independent variable. So this is a simple model. Now we'll go ahead and add multiple independent variables. So this time our features are RM, LSTAT and age columns. So in the first model we just had one independent variable, and in the second model which we are building we'll be having three independent variables which are RM, LSTAT and age, and again our dependent variable is the MEDV column, and I'll store them in X and Y again. Now I'll go ahead and divide this dataset into train and test split. And another difference which I'm making over here is I'm setting the test size to be equal to 0.30. So this means that 30% of the records would be in the test set and the rest 70% of the records would be in the training set. Right, I'll click on run, and then again I'll import the decision tree regressor, and I will fit the model on top of xtrain and ytrain, and I'll predict the values on top of xtest. Now again I'll find out the RMSE value. Alright, so this time the RMSE value comes to be around 5.509. So now let me compare it with the RMSE value of the first model. So the RMSE value of the first model is 7.10 and the RMSE value of the second model is 5.50. So this basically means that the second model produces less error, or in other words, second model is better than the first model. Right, so that was an example where we use decision tree as a regression algorithm. Now we'll go ahead and use decision tree as a classifier, and we'll be building this decision tree classifier on top of the iris dataset. So over here I'll type in pd.read_csv and I'm loading up the iris.csv file, and now I'll have a glance at the head of this. And these are all of the columns. So I've got sepal length, sepal width, petal width, and the species column. So now what I basically want to understand is what is the species of this flower based on these four columns over here. So these four columns would be my independent variables and species would be my dependent variable. So that is what I'm doing over here. From this entire iris data frame, I'll extract these four columns and store them in the X object, and I'll just extract the species column and I'll store it in the Y object. Alright, now I'll go ahead and divide this dataset into training and testing set. So again I'd have to import the train test split, and I'm setting the test size to be equal to 0.30. Now since we are building a classifier, we'd have to import decision tree classifier from sklearn.tree, and I will create an instance of this. So I'll just use this method decision tree classifier and I'll store the result in this new object. I'll name that object to be classifier, and I will fit this model on top of xtrain and ytrain. Right, so we have successfully built the model on top of the train set. Now we have to go ahead and predict the values on top of the test set. So I'll type in classifier.predict, and the parameter which I'm passing in this is xtest. So this is also done. Now let me go ahead and find out how the prediction has been done. So I'll start off by creating a confusion matrix. So I'll import confusion matrix from sklearn.metrics, and this takes in ytest and ypred. So ytest comprise of all of the actual values and ypred comprise of all of the predicted values. So I'll click on run over here. Now this left diagonal which you see, this left diagonal tells you all of the values which have been correctly predicted, and the rest of the values have been misclassified. So what we see is there is just one value or one record which has been misclassified. The rest of the records have been correctly classified. Right. Now I'll go ahead and calculate the accuracy score, and the accuracy score comes out to be 97.77%. Right, so this is how we can use a decision tree algorithm.
So the confusion matrix shows the ways in which your classification model is confused when it makes predictions. It is basically a summary of prediction result on a classification problem. The main key to a confusion matrix is summarize the count value of correct and incorrect prediction. So the image shown on your screen represents a confusion matrix. Let's see what exactly does it mean. But before that, let me just tell you how to create a confusion matrix. This would make things more clear for you. So let's see how. So for creating a confusion matrix, you would be needing a test dataset or a validation dataset with expected outcome values. Then make a prediction for each row in your test dataset. Then from the expected outcome and prediction, count the number of correct prediction for each class and the number of incorrect prediction for each class, organized by that class that was predicted. Okay, let's see what exactly does it mean. So here's an example. We have some expected output and a predicted output for that. So from here you can see that all the red color results are the incorrect predicted values and the green ones are the correct ones. So in total we have 7 correct prediction out of 10. Okay, so from here you can say that the accuracy of your model is 70%. Now here men classified as men are 3, 1, 2 and 3, and women classified as women are 4, 1, 2, 3 and 4. And now men classified as women, men as women 1 and men as women 2. Okay, so 2, and women classified as men 1. Now if you create a confusion matrix out of it, you'll get something like this. Men classified as men 3, men classified as women 1, women classified as men 2, and women classified as women is 4. So from here you can say that total actual men 3 plus 2 is 5. Total actual women 1 plus 4, again 5. And total correct values, men classified as men and women classified as women, that is 3 plus 4, it's 7. So from here you can say that there are more errors while predicting men as women rather than predicting women as men. Okay, so this was about how you can calculate a confusion matrix. Now let's come back and see how to interpret a given confusion matrix. This is the sample of a confusion matrix. So here we have created a confusion matrix for a fire alarm. So this represents an actual alarm, this represents no actual alarm. Here predicted fire positive and here predicted fire as negative. So if the alarm goes on in case of fire, so it's a true positive event. The alarm goes on and there is no fire, so it's a false negative event. There is no alarm in case of fire, so it's a false negative event. And there is no alarm and there is no fire, then that means it's a true negative event. Okay, so let me just explain you this example. This should make things more clear to you. So actual alarm and predicted fire. So total true positive events we have 40 and total false negative event we have 10. So from here you can say that total number of times the alarm rang was 40 plus 10, that is 50. Okay, here we have false positive event as 5 and true negative event as 95. So the total number of times the alarm did not rang was 5 plus 95, that is 100. And this one is the predicted fire or not. So true positive plus false positive, that is 40 plus 5. How many times the machine positively predicted the fire? So that is 40 plus 5, 45. And how many times the machine was not able to predict the fire? That is 10 plus 95, that is 105. And total number of events, that is 50 plus 100 or 45 plus 105 is 150. So we have mentioned n equal 150 up here. That is total number of events. Okay, so this is how you interpret a confusion matrix. So let's move ahead. So now let me just show you in my Jupyter notebook how you can create a confusion matrix. Let me just open my Jupyter notebook. So this is my Jupyter notebook, and what we are gonna do is create a confusion matrix in Python. So the very first thing that I'll be doing up here is importing the required libraries. So from sklearn.metrics, so I'll be importing confusion matrix. Next, let's create some expected value. Let's say expected equal. So let's add some values in it like 1, 1, 0, 1, 0, 0, 1, 0, 0 and 0. Now this is my expected value. Now let's create some predicted values for that. So predicted equals, first it's predicting correct. Next let's say 0, 0, 1, 0, 0, 1, 0, 1. So this is a predicted value. Now let's calculate the confusion matrix. So let's say results equal confusion underscore matrix. Inside this we'll pass our expected and predicted value. Expected comma predicted and print the result. That's it. let's execute it. So here you got the result as 4, 2 and 1, 3. So what does it mean? So first we have is 4. So 0 predicted as 0 is 4 times. 1, 2, 3 and 4. So 0 predicted as 1 is 2 times. 0 predicted as 1, 1. 0 predicted as 1, 2. Okay. Next is 1 predicted as 0. So 1 predicted as 0 is just once here. Okay. And next is 1 predicted as 1, that is 3 times. 1 predicted as 1, 1, 2 and 3. So this is a confusion matrix. And what we can say from here, so total number of correct prediction made by machine is 4 plus 3, that is 0 classified as 0 and 1 classified as 1. Okay. And total number of incorrect prediction is 2 plus 1, that is 3. So we have 7 correct prediction and 3 incorrect prediction. Okay. And the total number of times the machine predicted the value to be 0 is 4 plus 2, that is 6 times. And total number of times the machine predicted the value to be as 1 was 4 times. Okay. So from here we can say that our machine predicts the result 7 times correct and 3 times wrong. So the accuracy of our machine is 70%. So this was all about how you can create a confusion matrix in. Well, naive-Bayes classifier is a commonly used algorithm in machine learning. It is a classification algorithm which is mainly based on Bayes' theorem. According to naive-Bayes algorithm, the presence of a particular feature in a class is completely unrelated or is independent to the presence of any other feature. For example, a fruit may be considered to be an apple if it is red, round, and about 3 inches in diameter. A naive-Bayes classifier considers each of these features to contribute independently to the probability that the fruit is an apple, regardless of any correlation between the features. But these features are not always independent, and this is one of the disadvantages of the naive-Bayes algorithm. And this is the reason why it is called naive, because it makes assumptions that may or may not be correct. So in a nutshell, you can understand that this algorithm allows us to predict a class from a given set of features using the probability. So in some other fruit example, you can predict the class like whether the fruit is an apple, orange or banana based on its feature, like its color, shape, etc. Okay, so let's move ahead. Now before we move ahead and see how a naive-Bayes classifier works, we need to understand the basic of it. Okay, so the very base of the naive-Bayes classifier is conditional probability. Okay, so what exactly is this conditional probability? Well, it is used to calculate the probability of happening of the second event given that the first event has already happened. For example, drawing a second ace from a deck given that we already got the first ace, or finding the probability of a disease given that you were already tested positive, or finding the probability of liking Game of Thrones given that the person likes fiction. Okay, let's see what exactly it is. So basically you're defining two events over here. Event A is the probability of the event that we are trying to calculate, and event B is the condition that we know or the event that has already happened. So conditional probability is represented as probability of A bar B, which means the probability of the occurrence of event A given that B has already happened. So probability of A by B equal probability of A intersection B divided by probability of B, that is probability of the occurrence of both A and B divided by probability of B. Okay, let's understand this with the help of an example. So suppose you have a jar containing 6 marbles, out of which you have 3 black and 3 red. So what is the probability of getting a black given that the first one was black too? So let's see how we'll calculate it. So we have P of A as the probability of getting a black marble in the first turn. P of B is the probability of getting a black marble in the second turn. So probability of A, that is probability of getting the black marble in the first turn, is 3 by 6. Okay. And probability of B, so how many marble remained after we have taken one out? So we are left with 2 black marble and in total of 5 marbles. So the probability of again getting a black marble would be 2 by 5. Okay. And next is probability of A and B, or probability of A intersection B equal probability of A multiplied by probability of B. Okay, so that is 3 by 6 multiplied by 2 by 5. 3 by 6 is nothing but half. So half multiplied by 2 by 5, that is 1 by 5. Okay, so probability of B given A equal probability of A intersection B upon probability of A, which equals to 0.2 divided by 0.5, that equals to 0.4. Clear? Fine. Let's take another example. Let's say John's favorite breakfast is cereal and his favorite lunch is pizza. So the probability of John having cereal for breakfast is 0.6. The probability of him having pizza for lunch is 0.5. And the probability of him having a cereal for breakfast, given that he eats pizza for lunch, is 0.7. Okay? Now, what if I want to know the probability of having a pizza, given you had a bowl of cereal for breakfast? So you have to calculate probability of B by A. So that is, you have to calculate the reverse probability. So here in this example, you already know the probability of him having cereal for breakfast. But after having a cereal for breakfast, you have to calculate what is the probability of him having a pizza for the lunch. Okay? So now, this is where Bayes' theorem comes into picture. Bayes' theorem describes the probability of an event based on the prior knowledge of the conditions that might be related to the event. In simple words, Bayes' theorem shows the relation between a conditional probability and its reverse form. If conditional probability is probability of A by B, then you can use Bayes' rule to find the reverse probability, that is probability of B given A. Okay? Let's see how. Here's a proof of Bayes' theorem. So according to conditional probability formula, so if you compute over here, probability of A given B equal probability of A intersection B upon probability of B, and probability of B given A equal probability of A intersection B upon probability of A. Correct? So from this equation, we have probability of A intersection B common in both. So we can equate them, right? So probability of A intersection B equal probability of A given B multiplied by probability of B, which in turn equals probability of B given A multiplied by probability of A. So here, if you reverse the conditional probability, you will get the formula as probability of B given A equal probability of A given B multiplied by probability of B divided by probability of A. And this is nothing but Bayes' theorem. So in this formula, the probability of A given B is the probability of A being true given that B is already true. Probability of B given A is the probability of B given true given that A is already true. And probability of A is the probability of A being true, and probability of B is probability of B being true. Okay? So coming back to where we left. So now what if I want to know what is the probability of having a pizza given that you had a bowl of cereal for the breakfast? So you have to calculate probability of P by A. That is, you have to calculate the probability of him having pizza for the lunch given that he already had cereal in his breakfast. So that equals probability of cereal given that he's having pizza for the lunch multiplied by probability of having pizza upon probability of having cereal. Okay, which in turn equates to 0.7 multiplied by probability of pizza, that is 0.5, upon probability of cereal, that is 0.6. Okay, so let's move ahead. So here's a Bayes' theorem use case. Like, find out a patient's probability of having liver disease if they are an alcoholic. So here we are defining an event and the test. So an event is patient has liver disease. So from the past data, you can tell that 10% of the patients entering your clinic have liver disease. So here probability of A equal 0.10. Okay. So next is the test that a patient is an alcoholic. So 5% of the clinic's patient are alcoholic. So from here you can say that probability of B equal 0.05. Okay. Now you might also know that among those patients diagnosed with liver disease, from that 7% are alcoholics. So this is your B given A, correct? It is the probability that a patient is alcoholic given that they have liver disease is 7%. Okay. So now according to Bayes' theorem, probability of A given B equal 0.07 multiplied by 0.1 divided by 0.05, which in turn equals to 0.14. So in other words, if the patient is an alcoholic, their chances of having a liver disease is 0.14, that is 14%. There's a large increase from 10% suggested by past data, but it's still unlikely that any particular patient has liver disease. Okay. So coming back to our Bayes' theorem formula, so probability of A given B is posterior. Probability of B given A is the prior, that is what you believe before you saw the evidence. Probability of A, this is likelihood of seeing that evidence if your hypothesis is correct. And probability of B, this is likelihood of that evidence under any circumstances. Okay, so this was all about conditional probability and Bayes theorem. And whatever information or whatever knowledge you gain till now, will be using them to learn naive Bayes in a step-by-step way. So next is step-by-step to naive Bayes classifier. So here's my dataset consisting of 14 different rows with 5 different attributes. From this, I have to predict whether I'll play today or not. Okay. So from here, outlook, temperature, humidity and windy are the main attribute which will help us to predict the class play, whether we are going to play or not. Okay. So total sample here is 14, total yes is 9, total no is 5. So probability of getting yes is 9 by 14 and probability of getting no is 5 by 14. Okay. Now the very first thing that we'll do is calculate frequency table for each attribute. So for outlook we have sunny, overcast and rainy. So how many yes and how many no's are over there? So we'll calculate the frequency for that. So we have 2 yes for sunny, 4 yes for overcast and 3 yes for rainy. So total number of yes again 9. And we have 3 no for sunny, 0 no for overcast and 2 no for rainy. That is in total 5. Okay. Next is temperature. So we have 2 yes for hot, 4 yes for mild and 3 yes for cool. And similarly 2 no for hot, 2 no for mild and 1 no for cool. Again back to humidity. We have 3 yes when the humidity is high. We have 6 yes when the humidity is normal. And next we have 4 no when the humidity is high and we have just 1 no when the humidity is normal. Similarly for windy. For windy, so if the weather is not windy, we have 6 yes. But if the weather is windy, we have 3 yes. And next, if the weather is not windy, we have 2 no. And if the weather is windy, we have 3 no. So now that we have calculated the frequency table for each attribute, next thing that we are going to do is probability for each attribute. That is, we are going to calculate probability of A. Okay. So from here you can see that total times we'll get sunny is 5 out of 14. Total times we'll get overcast, that is 4 by 14. Total times we'll get rainy, 3 plus 2, that is 5 by 14. Okay. Similarly, you will calculate it for temperature, humidity and windy. Okay. So here we got the probability for each attribute, that is probability of A. Next is the probability for each attribute, that is probability of B. Probability of B is nothing but probability of playing the game or not, right? That is probability of yes and probability of no. That is 9 by 14 and 5 by 14. Next, we'll calculate the likelihood for each attribute. That is, we are going to calculate probability of A given B. So let's have a look on this example. So when outlook is sunny, so the probability of getting yes in that case is 2 divided by 9. And how many no are there? 3 out of 5, right? So we got 3 by 5. Similarly, for overcast, we got 4 by 9 and 0 by 5. For rainy, 3 by 9 and 2 by 5. Okay. Similar calculation you'll do for temperature, humidity and windy. Okay. So now we have to calculate probability of B given A. So we have the formula probability of A given B equal probability of A intersection B upon probability of B, that equals to probability of A multiplied by probability of B given A upon probability of B. Correct? From here I want to find this value. I have this value and this value. Okay. So let's see. So if I want to play, what would be my ideal condition for playing? The outlook should be sunny. So the probability for outlook to be sunny is 5 by 14. Correct? The temperature should be cool. So the probability of the temperature to be cool is 4 by 14. Next is humidity should be normal. So the probability of humidity to be normal is 7 by 14. And the weather should not be windy. So the probability of the weather not being windy is 8 by 14. Okay. So now if you calculate total probability of the ideal condition, that is P of X equal 5 by 14 multiplied by 4 by 14 multiplied by 7 by 14 multiplied by 8 by 14, which in turns come out to be 0.029. Okay. So this was the ideal condition. Now ideal condition to play the game. So probability of outlook equals sunny when play equal yes, that is 2 by 9. Probability of temperature being cool when play equal yes, that is 3 by 9. Next is probability of humidity being normal when play equal yes, that is 6 by 9, and probability of windy equal false when play equal yes, that is 6 by 9. Okay, so the probability of playing game in ideal condition is, so probability of x given yes equal multiplication of all these values, that is 2 by 9 multiplied by 3 by 9 multiplied by 6 by 9 multiplied by again 6 by 9. So you'll get the value as 0.033. Okay, so the probability of playing the game in ideal condition. So we have to calculate probability of yes given x. So probability of yes given x equal probability of x given yes into probability of yes upon probability of x. So probability of yes given x equal 0.033 multiplied by probability of yes, that is 9 by 14, upon probability of x that we just calculated 0.029, which in turn result to 0.73. So from here you can say that the probability of playing the game in ideal condition according to Naive-Bayes classifier is 0.73.
What exactly is support vector machine? Well, it is a supervised machine learning algorithm which classifies data based on its features. So let's say we have this input data comprising of apples and tomatoes. Now we'll feed this data to a support vector machine. Now SVM will basically learn all the features associated with the input data and separate apples and tomatoes into different classes. So now that we know what exactly is SVM, let's understand the working mechanism behind SVM. So support vector machine separates or classifies data based on hyperplanes. So over here, this is our hyperplane which separates apples and tomatoes into different classes. But the problem is there could be infinite possibilities to draw this hyperplane. So there could be a hyperplane like this, and this is also another possibility. And it could be any one out of all these different hyperplanes. So how do we determine which is the best one? So this is where we'd have to take the help of support vectors. So support vectors are basically the two nearest data points to our hyperplane. And we have to choose a hyperplane in such a way that the distance between two support vectors is maximum. And the distance between these two support vectors is known as margin. So the aim of the model is to maximize this margin between the support vectors. Now let's say we add a new data point to our sample and then implement the SVM model. So we'd have to draw a hyperplane in such a way that it best separates these two classes. So we'll start off by drawing a random hyperplane, and then we'll find the support vectors, and then we'll go ahead and find the margin between the support vectors. Now similarly, we'll draw another hyperplane like this, and again find the support vectors and also calculate the margin between the support vectors. So now when we compare these two hyperplanes over here, we see that the margin for the first hyperplane is greater than the margin for the second hyperplane, and that is why the first hyperplane would be the optimal one for the scenario. So till now the data which we saw was linearly separable, but what in this case? So can we actually draw a line over here to separate the circles and the triangles? Well, let's check it out. So I've drawn three hyperplanes, and we see that in all these three cases it is not able to separate the data into different classes. So this is where SVM uses something known as a kernel function. So this kernel function helps in transforming the 2D nonlinear data into higher dimensions so that we can separate the data using a hyperplane. So obviously when we look at this image on the right side, we see that we can separate the circles and the triangles by drawing a hyperplane along the z-axis. And these are some of the kernel functions which we can use along with our SVM model. So we have polynomial kernel, Gaussian radial basis kernel, and Laplace RBF kernel. Now it's time to head on to the demo. So we'll be using this cancer dataset to implement SVM. So this dataset is computed from a digitized image of a fine needle aspirate of a breast mass. And the columns basically describe characteristics of the cell nuclei present in the image. So there are different features such as mean radius, mean texture, concavity error, and so on. And the target column comprises of two labels, which are malignant and benign. So you're basically trying to classify whether the tumor of the patient is malignant or benign on the basis of all the features. So our first task would be to import the package and the dataset required for this demo. So from this sklearn library, we are importing all the datasets, and then the dataset which we need is breast cancer. So I'll just use this function load breast cancer, and I will store this in this new object called as cancer. I'll click on run. So we have successfully loaded this data set. Now let me have a glance at the features and the target values. So all I have to do is use this print function, and with the help of cancer.feature names, I'll get all the names of the features. And over here with cancer.target names, I'll get the target names. I'll click on run. So these are all of the different features which are present in the data set. So we have mean radius, mean texture, concavity error, symmetry error, worst concavity, and so on. And then in the target, we have two labels. First is malignant and then second is benign. And then again, as I already told you guys, we are trying to determine whether the patient's tumor is malignant or benign. So now that we've had a glance at the features and the labels, let's have a glance at the shape of this data set. So for that, we'll just type in cancer.data.shape. I'll click on run. So we have this value 569 and 30. So this means that there are 569 rows in this data set and 30 columns. Now let me have a glance at the first 5 records of all of the features. So cancer.data, and then I want to have a glance at the first 5 records. So this will go from 0 to 5. Right, so these are the first 5 records, or the values for the first 5 records. Now similarly, I'll have a glance at the target values. So cancer.target, I'll just print it out. See that we have the values which are 0 and 1. So wherever we have the value 0, it represents that the patient's tumor is malignant, and wherever we have 1, it represents that the patient's tumor is benign. Now it's time to go ahead and build the model. So before we go ahead and build the model, we are actually supposed to divide our data set into training and test set. So for that, we'll be importing this train test split method from sklearn.model_selection. And after that, using this train test split function, I will go ahead and divide this into training and testing sets. So this over here takes in these parameters. First parameter is the list of all of the features, which will come from cancer.data. Next parameter is basically the target values, which is this result over here. And then we'll set the test size. So here I am setting the test size to be 0.3. So this will mean that 30% of the records from the data set will be in the test set, and the rest of the 70% of the records from the data set would go into the training set. And then again, I'll just set a seed value so that I can build the same model again. Now over here on the left hand side, we see that we are storing this result into X train, X test, Y train, and Y test. So these X labels basically represent all of the features, and these Y labels basically represent all of the target values. So this X train is the training set for all the features. X test is the test set for all the features. Similarly, this Y train is the training set for all the target values, and this Y test is the test set for all the target values. Right. So now we have successfully split this data set into training and testing set. Now it's time to go ahead and build the model on top of the training set. So now what I'll do is I'll go ahead and import svm method from sklearn library, and after that I'll go ahead and build the model. So for that, I would have to set the kernel. So as we saw in the slides, we can have different kernels. So for this demo, I'm just setting the kernel to be linear. That is, we are building a linear model over here. So I'll use svm.svc and kernel is equal to linear, and I'll store this in CLF. Now after that, I will fit the model. So CLF.fit, and it takes in 2 parameters. First is X train, next is Y train. That is, I'm basically building this model on top of the training set for both the features and the target values. And after I build the model, I'll go ahead and predict the values on top of the test set. So it'll be x_test. I'll click on run. So we've built the model, we've predicted the values. Now let's go ahead and find out the metrics of the model which we've built. So I'll import metrics from sklearn, and then first we'll go ahead and build a confusion matrix. So again, metrics.confusion matrix, this over here takes in 2 parameters, which is Y test and Y pred. So this Y test comprises of the actual values, and this Y pred comprises of the predicted values from the model which we've built. Now I'll click on run, and this gives me this confusion matrix. So the 61 which you see, it represents all of those values where the actual label was malignant and it has been correctly classified as malignant. So 61 are such cases. And then we have this 104, which basically represents all of those values where the actual value was benign and it has been correctly predicted as benign. And this what you see? So over here, the actual was malignant, but it has been predicted as benign. And this 4 what you see? So this represents all of those cases where the actual was benign, but it has been predicted as malignant. So this left diagonal represents all of those values which have been correctly classified. And this right diagonal represents all of those values which have been misclassified. So this is the information which we can get from the confusion matrix. Now I'll go ahead and also calculate the accuracy. So this again matrix.accuracy score takes in two parameters. First is y-test and then we have y-pred. So see that the accuracy is 96%. So you can actually get this accuracy value from this confusion matrix. So as I have already told you guys, this left diagonal represents all of those values which have been correctly classified. So we'd have to divide this left diagonal with all of the values. So let me go ahead and do that. There'll be 61 plus 104 divided by 61 plus 104 plus 2 plus 4. Now I'll click on run. So you see that we get the same accuracy, which is 96.49. So we have successfully built the SVM model and we've got an accuracy of 96%. So you can consider ensemble modeling to be a collection of multiple models. So we basically combine several base models in order to produce one optimal predictive model. So let's take this example to understand ensemble modeling better. So let's see there's this data set on which you want to do some prediction. Now, instead of building one model on this entire data set, we can take samples of this data set and build a model on each of the sample data set. So let's say we take k samples and then we'll build k models in total. Now, each of this model will give us a result. So we'll take the aggregate of all the results and that would be a final answer. Now, one such ensemble method involving decision trees is bagging. So let's understand bagging with this example. So let's say we have this data set A and there are n records in it. Now what we'll do is draw samples from this data set. So this actually will be sampling with replacement. Now I'll take one record from data set A, take note of it, enter the same sample in data set A1 and then put the record back to where it came from. And I'll repeat this process n times so that there are n records in dataset A1 as well. So what you need to keep in mind is, out of these n records in A1, some of them might have come twice, thrice or even several times over, while some records from A might not have made it at all to A1. So this is how I've created A1. And then I'll go ahead and create multiple datasets the same way. So I have A1, A2 and it will go on till AX. And each of these have the same number of records as A. And the X over here, it could be anything. Let's say 100, 500 or even 1000. So from just one data set A, we're able to create multiple data sets for our advantage. So again, just for our sake, let's say data set A has 1000 rows and the value of X is also 1000. So this would be 1000 cross 1000, which would give us 1 million rows. That is from just 1000 rows of data, you're able to get 1 million rows. Now what we'll do is, for each of these X datasets, we'll fit one decision tree each. So we have X decision trees coming from X datasets. So now we have a group of trees, or in other words, what we have over here is ensemble of trees. Now let's say a new record Ri comes our way, then we are going to pass this record to each of these X trees and we're going to get each tree's prediction on what class this new record is going to represent. And since we have X trees, we'll have X predictions in total. That is, let's say if X was 500, we would get 500 predictions. Similarly, if X was 1000, we would get 1000 predictions. Now, to get the final prediction, all we have to do is select that class which would have the majority of the votes across all the predictions from individual trees. So what we are really doing is aggregating the predictions across all of these trees. So guys, this is the concept of bagging. Now we'll head on to random forest. So random forest is just an extension of bagging. So till here the process would be the same. We'll be creating X bootstrap samples from the original dataset. And this is where the difference comes. So now what we'll do is, for each of these X datasets, we'll fit one decision tree, but the process of building the decision tree changes over here. So let's say this A1 dataset has 10 independent variables. Now, when it came to bagging, we considered all of these 10 independent variables to be a choice for the split candidate. But what happens in random forest is, each time a node is being split in a decision tree, not all 10 variables will be provided to the algorithm. This is important, so I'm reiterating this, guys. Each time a node is being split in a decision tree, not all the columns will be provided to the algorithm. So now the question arises, what will be made available to the algorithm? So only a random subset of these 10 columns would be available to the algorithm. So let's say I want to split this root node. Now instead of providing it all the 10 columns, only a subset of columns will be provided. So let's say 3 columns. Now it could be any 3 out of the 10. And with those 3, the algorithm goes on to split the node. And similarly for the left node over here, it is again going to be provided with a random set of variables. And it is not necessary that the left node should get the same 3 variables. It can be a different set of 3 columns altogether. So whenever we are splitting a node, it is given a random set of m predictors from the entire predictor space. And the reason this is done is to make each of these X trees very different. So let's compare bagging and random forest. So in bagging, all trees had the entire predictor space available to them. So the eventual trees which you would end up building would be very similar to each other. And in the case of random forest, we bring in randomness with respect to the columns provided. That is, only a random set of columns are provided to the entire predictor space. And that is why the set of decision trees which we get would be pretty different from each other. So now we'll head on to the demo. So we'll be implementing random forest on top of this iris dataset, right? So we'll go ahead and load this iris dataset. So first we'll import the datasets module from sklearn library, and then we'll load the iris dataset, and I'll store this in the iris object. I'll click on run. Now I'll go ahead and have a glance at the target names and feature names. So all I have to do is use iris.targetNames, which would give me the target names. And then I have iris.featureNames, which would give me the feature names. I'll click on run. So these are the target names. So this is the target variable, which comprises of these labels. So the iris species, it could either be setosa, versicolor, and virginica. And these are the features. So we have sepal length, sepal width, petal length, and petal width. Now I'll have a glance at the top 5 records of this iris dataset. So iris.data, and it'll go from 0 to 5. So these are the first 5 records of this iris dataset, and this will give us only the feature values. Now if I want to have a glance at the target values, I'd have to print iris.target. So these are the target values. So if the value is 0, it represents that the iris species is setosa. If the value is 1, it represents that the iris species is versicolor, and if the value is 2, it represents that the iris species would be virginica. Now let me go ahead and have a glance at the type of this iris data and iris target. So we see that both of them are NumPy arrays. And for a model building process, first we'd have to convert these two NumPy arrays into data frames. So I'll take the first column from the iris data and I'll name it as sepal length. Similarly, I'll take the second column from iris data, I'll name it as sepal width. The third column, I'll name it as petal length. And the fourth column, I'll name it as petal width. And finally, I'll take these values from iris.target and I'll name them to be species. So we are creating this data frame which would comprise of 5 columns, and those 5 columns would be sepal length, sepal width, petal width, and species. And I'm storing this in this data object. I'll click on run, and we also have the head of this new data frame which we've just created, right? So these are all of the columns which are present in this data frame. So now, before we go ahead and build the model, we are again supposed to separate the features and the target column. So I will store all of the features in this X object, and I will store the target in this Y object. I'll click on run. So all of these features are sepal length, sepal width, petal length, and petal width, and our target would be species. Or in other words, we're trying to determine what is the species of the iris flower on the basis of these feature values. Now, I'll have to divide this data set into training and testing set. And for that purpose, I'll be importing this train test split function from sklearn.modelSelection. And after that, inside this function, I'll give in these parameters. So the first parameter is the object which comprises of all of the features. The second parameter is the object which comprises of all of the target labels. And then I'll give in the test size, which is 0.3. So this basically states that test data would have 30% of the entire data and the training data would comprise of 70% of the entire data. So this is the train test split. And we are storing this in these four objects. So we have xtrain, xtest, ytrain, and ytest. So this xtrain is basically the training set for the features. This xtest is the test set for the features. And then we have ytrain, which is the training set for the target. And then we have ytest, which is the test set for the target. So we went ahead and we've also divided the data set into training and testing sets. Now it's time to build the model on top of the training set and predict the values on top of the test set. So I'd have to import the random forest classifier from sklearn.ensemble and I'll create a model from it. And I'll set the number of decision trees to be 100. So over here, this parameter which you see, n estimators equals 100. So this basically means that the random forest algorithm which we'll be creating, it will have 100 decision trees. So we'll get the aggregate result of these 100 trees. Now I'm storing this in this CLF object. Now I'll go ahead and fit or build this model on top of the train set. So we have xtrain and ytrain. Now after I build the model, I would have to predict the values. So I'll predict the values on top of the xtest. So now that we've predicted the values, it's time to build the confusion matrix and find out how good is a model. So I'll import this matrix from sklearn and then I'll go ahead and build the confusion matrix, which takes in the ytest object, which basically has all of the actual values. And then the next parameter is the ypred object, which has all of the predicted values. Now I'll go ahead and build this confusion matrix. So this first row represents the Setosa species, second row represents the versicolor species, and the third row represents the Virginica species. And this left diagonal which you see, this diagonal represents all of those values which have been correctly classified. So if we take this row here, then this means that so in total there was 14 species which were actually Setosa and all of them have been correctly classified as Setosa. And over here we see that in total there were 16 species of versicolor. Out of them, 15 have been correctly classified as versicolor. And this row if we take, so we see that there were 15 values of Virginica. Out of them, 14 have been correctly classified. Now, if you want to get the accuracy of this model which you've just built, we'll use this accuracy score and we'll pass in the same objects, ytest and ypred. I'll click on run. So see that the accuracy for the model which you built is 95.55%. Now I'll go ahead and predict values for a single item. So let's say if I give individual values for each of the columns. So these are the values for sepal length, sepal width, petal length and petal width. So let's say if sepal length was 3, sepal width was 5, petal length was 4 and petal width was 2, then what is the species of this iris flower? I'll click on run. So see that if these are the values for the columns, then it belongs to array 2. Or in other words, it basically belongs to the Virginica species. Similarly, and if these are the values for sepal length, sepal width, petal length and petal width, then let me predict this. So again we see that this time also the species would be Virginica. Now I'll go ahead and have a glance at the importance of the different features. So inside this pd.series, I'll get the importance of each of the individual features. So clf.feature importances, and I'll also have the feature names along with the feature importances. And I'm basically creating a pd.series object out of it, and I am sorting it in descending order. So this parameter ascending is equal to false. This would basically give us these feature importances in descending order, and I've stored that result in feature IMP. I'll click on run. And these are the different feature importances. So we see that the most important features or the most important independent variables are petal width and petal length. So now I'm going to go ahead and make a plot of the feature importance. So I'll import the Seaborn and Matplotlib packages, and then I'll make a bar plot for the feature importance. So on the x-axis, I would have the feature importance, and on the y-axis, I would have the labels for each of these features. I'll click on run. So see that the X label is feature importance score, Y label is features, and the title is visualizing important features. And again, we get the same result. So petal width and petal length are the two most important features when we build this model. Now, since we've understood that the two most important features are petal width and petal length, we're going to go ahead and build a model with only these two features. So this time in the X object, I will take only petal length and petal width as the features, and again the target would be the species column. Now I'll again go ahead and divide this data set into train and test sets, and again I'll set the test size to be 0.3. So in other words, test set would comprise of 30% of all of the data values and training set would comprise of 70% of all of the data values. I'll click on run. So we've divided the data set into training and test set. Now again it's time to build the model and predict the values. So we'll use this random forest classifier, we'll build the model and then we'll fit the values and then we'll predict the values on top of X test. Now it's time to build the confusion matrix. I'll click on run and this is the confusion matrix which we get. So we see that all of the Setosa species have been classified correctly. When it comes to versicolor, out of the 16, 15 have been classified correctly, and when it comes to virginica, out of the 14, 13 have been classified correctly. Now again we'll calculate the accuracy. So we see that the accuracy is 95.55%. So in the first model which we built, the accuracy was 95.55%, and also in the second model which we built, the accuracy is also 95.55%. So we've understood that we don't have to include the other two independent variables. So without including sepal length and sepal width, we've got the optimal accuracy value for this data set. So my first task would be to import the pandas library. So I'll type in import pandas as PD. Now it's time to load the data set. So I will use the read CSV function. And inside this, I will give in the name of the dataset. So the name of the dataset is iris.csv and I will load this in a new object and I will name that object to be iris. So I have loaded the file. Now I'll go ahead and have a glance at the top 5 records of this dataset. So I would have to use the head function for that. So iris.head, and this would give me the top 5 records which are present in this dataset. So we've got all of these columns which are present in the iris dataset. So we've got sepal length, sepal width, petal width, and the species column. Now, our task for this session would be to implement the XGBoost classifier on top of this dataset to find out what species does this iris flower belong to on the basis of the rest of the columns. So on the basis of sepal length, sepal width, petal length, and petal width, I'd want to know what is the species of this particular flower. So we've got 3 different species of iris flower. We've got Setosa, versicolor, and virginica. Right. So before we go ahead and implement the algorithm, we'd have to divide the dataset into training and testing set. Now again, before that, we'd have to divide all of the predictors and the response variable. So all of these would be the predictors and this would be the response variable. So let me extract that. So inside the X object, I will go ahead and I will store the rest of the columns except the species column. So it would be sepal length. Let me type in sepal length over here. So after sepal length, I would also require the sepal width. And before this, I'd have to give in the name of the data frame over here, right? So from iris data frame, I would require sepal length. I would also require the sepal width. So let me type in sepal width over here. And after sepal width, I would require the petal length column. So I'll type in petal width, and after petal width, I would require the petal length column. So I'll type in petal.length. So these are all of the columns, the first 4 columns which I'm storing into the X object. And then I'd also need the dependent variable, which would be the species column. So inside this, I'll just give in species. So I've got all of the independent variables stored in the X object, and I've got my dependent variables stored in the Y object. So now that I have my dependent and independent variables with me, I will go ahead and divide this data set into train and test set. So for that purpose, I'd need to import the train test split from model selection. So I'll type from sklearn.model selection. I'd be importing train test split. Now I have the train test split method. Let me use it, and inside this I will pass in X and Y. So X consists of all of the predictors, Y consists of the dependent variable, And after this, I will give in the test size. So the test size is equal to 0.3. So this would mean that 30% of the records would go into the test set and the rest of the 70% records would go into the train set. Now this would return 4 objects, and those 4 objects I'd be storing in xtrain, xtest, ytrain, and there would be ytest after this. Right, so I've divided all of this into 4 parts. I've got xtrain, xtest, ytrain, and ytest. So xtrain basically consists of the independent variables of the train set, xtest consists of independent variables of test set, ytrain would have the dependent variable of the train set, and ytest would have the dependent variable of the test set. So now that is done, it's time to go ahead and import the XGBoost classifier model. So I will type import XGBoost as XGB. Now I will go ahead and create an instance of this. So I'll type xgboost.xgb classifier, and let's say I'd want 10 decision trees inside this. So I will set the value for n estimators. So with the help of the n estimators attribute, I can decide the number of trees which would be present in this XGBoost classifier. And I'd want 10 trees to be present in this. And also I can set the tree depth. So I'll set the maximum tree depth for all of these decision trees to be equal to 5. And I will store this in a new instance and name this to be XGBC. So XGBNC, right? So I have created an instance of this XGBoost classifier. Now it's time to fit the model. So XGBC.fit. And inside this, I will pass in the xtrain and ytrain objects. So I'm basically fitting this model on top of the train set. So I have successfully built this XGBoost classifier on top of the train set. Now it's time to predict the values. So to predict the values, I'll just type xgbc.predict and I will pass in the xtest inside this. Right, so because xtest is basically all of the independent variables which are present in the test set. Now for all of these values, I am going ahead and predicting a result. And I will store this in, let's say, ypred. So I have also predicted the values on top of the test set. Now it's time to build the confusion matrix and see how much classification is correct. So from sklearn.metrics, I'd be importing the confusion matrix. Now once I import the confusion matrix, inside the confusion matrix, I'll pass in the actual values which are present in the test set and the predicted values which are present in ypred. So this is our confusion matrix. So this, what you see are the actual values and these are the predicted values, and this left diagonal would tell you how many of the values have been correctly predicted. So this is for Setosa, versicolor and virginica. So we see that all of the Setosa species have been correctly classified. When it comes to versicolor, 12 of them have been correctly classified, 2 of them have been incorrectly classified. Similarly for virginica, 12 of them have been correctly classified and 2 of them have been incorrectly classified. To find out the accuracy, I'll just divide the left diagonal with the rest of the values. So it'll be 17 plus 12 plus 12 divided by 17 plus 12 plus 12 plus 2 plus 2. So this gives us an accuracy of 91.11%. And this is how we can build the XGBoost classifier. Click on run. Right. So we have successfully created this list of lists. Now let me have a glance at the first list. So you see that the first list, or in other words, the first row. This is our first row and this contains these items: burgers, meatballs and eggs. So this is the first transaction which contains these items. So now that we've converted the pandas data frame into a list of lists, we can finally go ahead and build the a priori model on top of this list of lists. So for that purpose, we'll be using this a priori function, which takes in all of these predefined parameters. So first we'd have to give in the object on which we are supposed to build the a priori model. So the object is obviously records, and then we'll set the values for minimum support, minimum confidence and minimum lift. So in this model, we are setting the minimum support to be 0.0045, or in other words, the minimum support threshold is 0.45%. Now This basically means that out of all of the transactions, this model should include at least 0.45 of the transactions. Next, we have minimum confidence set to be 20%. So this minimum confidence level of 20% states that out of all the antecedents, at least 20% of them should also have the consequence with them. And then finally, we have the minimum lift threshold. So we see that the minimum lift threshold which we've set is 3. And then we have the minimum length which is equal to 2. So this minimum length of 2 states that there needs to be at least 2 elements in the rule. Now I will store this result in association rules, and then I'll go ahead and convert this object into a list, and I'll store this in association results. I'll click on run. Now let me go ahead and have a glance at the number of rules this algorithm has given me. So I'll just use the len function, which will basically give me the length of this list. So we see that this algorithm has generated 48 rules in total. Now I'll go ahead and have a glance at the first rule. So I will just type in association results, and since I want to have a look at the first rule, I'll set in the index value to be equal to 0. Over here we see that this is our rule, light cream, chicken, and over here we have item base, which is light cream, and items add, which is chicken. So over here light cream would be our antecedent and chicken would be our consequent, and we are trying to determine the association between light cream and chicken. Or in other words, we are trying to determine if someone buys light cream, what is the association or what is the correlation of him buying chicken along with light cream. So for this, the support value is 0.004, the confidence value is 0.29, and the lift value is 4. So the support is 0.4%, confidence is 29%, and lift is 4. So this confidence value of 0.29 states that out of all the antecedents, at least 29% of them have the consequent, which is chicken, present in them. Now again, similarly, let me have a glance at the second rule. I'll click on run. So this is our second rule, where the antecedent is mushroom cream sauce and the consequent is escalope. So we're trying to determine if someone buys mushroom cream sauce, what is the probability of him also buying escalope with the mushroom cream sauce. So for this, the support value is 0.005, the confidence value is 30%, and the lift is 3.79. So this was our first model. Now similarly, we'll go ahead and build another model where we'll give different threshold values. So this time over here, I am setting the minimum support to be equal to 1%, minimum confidence to be equal to 50%, and minimum lift to be equal to 2. I'll click on run. Now again, let me have a glance at the number of rules given by this algorithm. I'll click on run. So you see that there are just 4 rules with these minimum support, minimum confidence, and minimum lift values. So now again, I will go ahead and have a glance at the first rule. So in this first rule, we see that the antecedent comprises of eggs and ground beef, and the consequent comprises of mineral water. So we are trying to determine if someone buys eggs and ground beef together, what is the correlation of him also buying mineral water after he or she buys eggs and ground beef. And for this rule, the support is 1%, the confidence is 50%, and the lift is 2.12. Now similarly, let me also have a glance at the second rule. So this is the second rule where the antecedent is milk and ground beef, and the consequent is mineral water. So this time we're trying to determine if someone buys milk and ground beef, what's the probability of him also buying mineral water along with these two. And this time the support is 0.11, the confidence is 0.50, and the lift is 2.11. So guys, this is how we can find out association rules in Python. Now what is a recommendation engine? So a recommendation engine is basically a filtering system that seeks to predict and show the items that a user would like to purchase. Now it may not be entirely accurate, but if it shows you what you like, then it is doing its job right. So recommender systems have become increasingly popular in recent years and are utilized in a variety of areas, including music, news, books, social tags, and any other products in general. So mostly used in the digital domain, majority of today's e-commerce sites like eBay, Amazon, and Alibaba make use of this proprietary recommendation algorithms in order to better serve the customers with the products that they're bound to like. And if it is set up and configured properly, It can significantly boost revenues, conversions, and other important metrics. So, moreover, they can have positive effects on the user experience as well, which translates into metrics that are harder to measure but are nonetheless of much importance to online businesses, such as customer satisfaction and retention. And all of this is possible only with the recommendation engine. So, recommendation engines basically are data filtering tools that make use of algorithms and data to recommend the most relevant items to a particular user. Or, in simple terms, they're nothing but an automated form of a shop counter guy. So, you ask him for a product. Now, not only he shows you that product, but also the related ones which you could buy. So, they are well trained in cross selling and upselling. And with a growing amount of information on the internet and with a significant rise in the number of users, it is becoming important for companies to search, map, and provide them with a relevant chunk of information according to their preferences and tastes. So let's consider an example to better understand the concept of a recommendation engine. So if I'm not wrong, almost all of you must have used Amazon for shopping, right? And just so you know, 35% of Amazon.com's revenue is generated by its recommendation engine. So let's understand the strategy. Now, Amazon uses recommendations as a targeted marketing tool in both email campaigns and on most of its website pages. So, Amazon will recommend many products from different categories based on what you're browsing and pull those products in front of you which are likely to buy. So, like the frequently bought together option that comes at the bottom of the product page to lure you into buying the combo. And this recommendation engine has one main goal: increase the average order value. That is, to upsell and cross sell customers by providing product suggestions based on the items in their shopping cart. So, Amazon uses browsing history of a user to always keep those products in the eye of the customer. And it uses the ratings and reviews of the customers to display the products with a greater average in the recommended and best selling option. Now, Amazon wants to make you buy a package rather than just one product. Say you bought a phone, it'll then recommend you to buy a case or a screen protector. It'll further send these recommendations to your email and keep you engaged with the current trend of the product or the category. So now that we have defined recommender systems, their objective and usefulness, next we'll go through the different types of popular recommender systems in use. So mainly there are three types of recommendation engines. So collaborative filtering methods are based on collecting and analyzing a large amount of information on users' behaviors, activities, or preferences and predicting what users will like based on their similarity to other users. While content-based filtering methods are based on a description of the item and a profile of the user's preference. So in a content-based recommendation system, keywords are used to describe the items, and a user profile is built to indicate the type of item this user likes. So recent research has demonstrated that a hybrid approach combining collaborative filtering and content-based filtering could be more effective in some cases. So hybrid approaches can be implemented in several ways by making content-based and collaborative-based predictions separately and then combining them, or by adding content-based capabilities to a collaborative-based approach and vice versa. Or we can even unify the approaches into just one model. So Netflix is a good example of a hybrid system. They make recommendations by comparing the watching and searching habits of some similar users. That is, collaborative filtering, as well as by offering movies that share characteristics with films that a user has rated highly. That is, content-based filtering. So now we'll discuss collaborative filtering recommender systems in detail. So in this type of recommendation engine, filtering items from a large set of alternatives is done collaboratively by users' preferences. So the basic assumption in a collaborative filtering recommender system is that if two users share the same interests as each other in the past, they will also have similar tastes in the future. So if, for example, user A and user B have similar movie preferences, and user A recently watched Titanic, which user B has not seen yet, then this movie, Titanic, is recommended to user B. So the movie recommendations on Netflix are a good example of this type of recommender system. So there are two types of collaborative filtering recommender systems. So first is user-based collaborative filtering. So in user-based collaborative filtering, recommendations are generated by considering the preferences in the user's neighborhood. So this user-based collaborative filtering is done in two steps. By identifying similar users based on similar user preferences and recommending new items to an active user based on the rating given by similar users on the items not rated by the active user. So another type of collaborative filtering is item based. Now in item based collaborative filtering, the recommendations are generated using the neighborhood of items. So unlike user based collaborative filtering, we first find similarities between items and then recommend non-rated items which are similar to the items that active user has rated in the past. So item-based recommender systems are constructed in two steps. So we calculate the item similarity based on the item preferences and find the top similar items to the non-rated items by active user and recommend them. So now let's discuss each of them in depth. So first, let's try to understand how does user-based collaborative filtering work. As previously mentioned, the basic intuition behind user-based collaborative filtering systems is that people with similar tastes in the past will like similar items in the future as well. For example, if user A and user B have very similar purchase histories, and if user A buys a new book which user B has not yet seen, then we can suggest this book to user B as they have similar tastes. So from here we know that we need to compute the similarity between users in user-based collaborative filtering. So how do we measure the similarity? So there are basically two options, Pearson correlation and the cosine similarity. So let U of ik denote the similarity between user I and user k, and V of ij denote the rating that user I gives to the item j. So now both the measures, Pearson correlation and cosine similarity, are commonly used. So the difference is that Pearson correlation is invariant to adding a constant to all the elements. So now we can predict the user's opinion on the unrated items with this equation over here. So now let us illustrate it with a concrete example. So in the following matrix, each row represents a user while the columns correspond to different movies, except the last one which records the similarity between that particular user and the target user. So each cell represents the rating that the user gives to that movie. So assume user E is the target over here. Since user A and user F do not share any movie ratings in common with user E, their similarities with user E are not defined in Pearson correlation. Therefore, we only need to consider user B, C, and D. So based on Pearson correlation, we can compute the following similarity. And this is the resultant table that we see over here. So in this table, you can see that user D is very different from user E as the Pearson correlation between them is negative. So he rated me before you higher than his average rating, while user E did the exact opposite. So now we can start to fill in the blanks for the movies that user E has not rated based on other users. Now although computing user-based collaborative filtering is very simple, it suffers from several problems. So one main issue is that users' preference can change over time. So it indicates that pre-computing the metrics based on their neighboring users may lead to bad performance. And to tackle this problem, we can apply item-based collaborative filtering. So now we'll look at how does item-based collaborative filtering work. So now instead of measuring the similarity between two users, the item-based collaborative filtering recommends items based on their similarity with the items that the target user rated. So likewise, the similarity can be computed with Pearson correlation or cosine similarity. And the major difference is that with item-based collaborative filtering, we fill in the blanks vertically as opposed to the horizontal manner that user-based collaborative filtering does. So the following table shows how to do so for the movie Me Before You. It successfully avoids the problem posed by dynamic user preference as item-based collaborative filtering is more static. However, several problems remain for this method as well. The first main issue is scalability. The computation grows with both the customer as well as the product. And the worst case complexity is order of mn with m users and n items. In addition, sparsity is also another concern. So take a look at the above table again. Now, although there is just one user who rated both Matrix and Titanic, the similarity between them is 1. So in extreme cases, we can have millions of users and similarity between two fairly different movies could be very high, simply because they have similar rank for the only user who ranked them both. Or in other words, the genre of Matrix and Titanic is completely different, and even though the similarity over here is given to be 1. So while building collaborative filtering recommender systems, we need to know how to calculate the similarity between users, how to calculate the similarity between items, how recommendations are generated, and how to deal with new items and new users whose data is not known. So the advantage of collaborative filtering system is that they are simple to implement and very accurate. However, they have their own set of limitations, such as the cold start problem, which means collaborative filtering systems fail to recommend to the first time users whose information is not available in the system. So let's understand what is dimensionality reduction. So dimension reduction refers to the process of converting a set of data having vast dimensions into data with lesser dimensions, in turn ensuring that it conveys similar information concisely. In general, it is used to reduce the complexity of data while keeping the relevant structure intact. So this method is typically used to solve machine learning problems to obtain better features. Now let's have a look at the types of dimensionality reduction. Broadly, dimensionality reduction has two classes: feature elimination and feature extraction. So feature elimination is the process of removing some variables completely if they are redundant or if they're not providing any new information about the dataset. And this helps us to keep our dataset small. However, one major drawback is we might lose some information. On the other hand, feature extraction is nothing but extracting the information of new variables from old variables. For example, say you have 10 variables in your dataset, then feature extraction will create 10 new variables which will also include all the 10 old variables. Well, PCA is one such technique that works on feature extraction. So why do we need dimensionality reduction? The main motto behind this technique is to decrease the unwanted dimensions in machine learning. For example, consider a motorbike rider in racing competitions. So the rider position and movements are measured by various factors, such as GPS sensors on bike, gyrometers, multiple video feeds, and smart devices. Now the data analyst has to analyze the racing strategy of a biker, where he'll have a lot of variables or dimensions which are similar and of little incremental values. Hence, such data has to be treated to reduce the number of dimensions or remove unwanted dimensions. Now let's have a look at some applications of dimensionality reduction. The best example which we can give is image processing. So I'm sure you might have come across this Facebook application. Which celebrity do you look like? Concept behind this is a dimension reduction technique. To identify the matched celebrity image, the algorithm uses pixel data, and each pixel is equivalent to one dimension. So in every image there is a high number of pixels, that is, a high number of dimensions, and every dimension is important here. Now you can't just omit dimensions randomly to make better sense of your overall dataset. So in such cases, dimension reduction techniques help you to find the significant dimensions using various methods. Now let us move on to principal component analysis. So what is principal component analysis? The process of reducing the number of random variables of the dataset under consideration by obtaining a set of principal variables is nothing but PCA. So the main idea behind PCA is to find the low dimension set of axes that precisely fit the data. For better understanding, consider a data set of vehicle properties which includes different variables such as number of wheels, the color of the car, the number of seats, and so on. Well, many of these features are measure related and will be redundant. Hence, this redundant data has to be eliminated to describe the car with fewer features. So this is where the PCA comes into the picture. For instance, think about the number of wheels. Almost all cars and buses will have 4 wheels, and only in very rare cases some buses will have 6 wheels. And hence we can say that this feature has less variance. So this feature will make the bus and car look the same, but in fact they're actually not. Now let's consider the height variable. Now it's very obvious that cars and buses will have completely different values when it comes to height. Well, this property can be taken into account to separate them, as PCA does not take information of classes into account. It will just consider the variance of each feature. Now let us move on to the working mechanism of PCA. So consider that some data is placed in an oval shape on the coordinate axis. In order to find the direction with more variance, we'd have to find the line where data is more spread out when projected onto it. Here the data is not spread out widely. Therefore, it will not have large variance, and probably it is not the principal component we are looking for. Now let us try using the horizontal line. So on this line, we can see that the data is more spread out and has large variance, and hence it can be considered as the direction for our principal component. Now you might be thinking, how can we find out this principal component? Well, we have eigenvectors and eigenvalues to find the principal component rather than drawing lines and unevenly shaped triangles. So what are these eigenvectors and eigenvalues? So these two exist in pairs. Every eigenvector has a corresponding eigenvalue. The line or the vector which we drew in our previous example is nothing but the eigenvector, and the variance is the eigenvalue. So in the example above, the eigenvalue is a number telling us how spread out the data is on the line, and the eigenvector with the highest eigenvalue is therefore the principal component. For better understanding, let us consider that you have two measures, age and hours on the internet. So there are two variables, and hence it will be a two-dimensional data set, and therefore it will have two eigenvalues and two eigenvectors. The reason for this is that eigenvectors put the data into a new set of dimensions, and these new dimensions have to be equal to the original number of dimensions. So this sounds complicated, but again an example should make it clear. So we can see that the oval is on x and y axis, where x refers to age and y refers to hours on the internet. Now let us split the data by drawing a line. So the eigenvectors should be able to span the whole xy area, and therefore they need to be orthogonal to each other. Hence the second eigenvector would look like this. Now we'll just reframe the data in these new dimensions, and the resultant is as shown below. So you can also make sure that nothing changes by moving the data to the origin. So these eigenvectors basically give us a new set of axes, and these axes are much more intuitive to the shape of the data now, as these are the directions where most of the variation occurs. Now let us see how PCA is used to reduce the dimensions of a given data set. So it reduces the data down into basic components by taking out the unnecessary parts. So consider that you're measuring three variables: age, hours on internet, and hours on mobile. Now imagine that the data forms an oval shape on a plane as shown in the figure. Since we have considered three measures, it will have three eigenvectors and three eigenvalues for the data set. And out of these, two eigenvectors will have large eigenvalues and one eigenvector will be 0. Here EV1 is the first eigenvector, EV2 is the second eigenvector, and EV3 is the third one. And since it has an eigenvalue of 0, we'll not consider that. So we can now rearrange the axis to the origin, and we'll also represent the data in two dimensions as EV3 is 0. So what we've done here is nothing but dimension reduction, and hence the three-dimensional problem is now reduced to two-dimensional problem. So reducing dimensions helps to simplify the data and make it easier to visualize. So this is how PCA algorithm works.
So here we have a multi-dimensional movie rating dataset where every dimension or column is a movie and different users are rows. So we'll call this matrix as A, and if you have learned about the PCA, which is the principal component analysis, so if you use PCA on this particular dataset, so it can boil down this dataset to a much smaller number of dimensions, and those dimensions will best describe the variance in the data, and often those dimensions that PCA will find that will correspond to the features that we have learned as humans in the real world. So for example, if you run PCA on this particular dataset, so it will find those latent features and extract them from the data. So PCA actually would not know what those features mean, but still it will find those features. So we'll ask PCA to find three dimensions in this data, and if you run PCA on this data to find three dimensions, so it will boil down our data or ratings down to three latent features that it identified. So PCA would not know what those features are and what to call them, but let's say that they end up being measures of each person's interest in action, sci-fi or comedy movies. So for example, we might think of user 1 as being defined as interested in 30% action, 50% interested in sci-fi movies, and 20% interested in comedy movies. So now let's take a look at the columns in this new matrix. So each column here is a description of users that make up that particular feature. So we can say that the action can be described as the 30% of user 1 and the 10% of user 2 and the 30% of user 3. So let's call this matrix as V. So just like we can run PCA on our user rating dataset to find profiles of different kinds of users, so we can now flip things around and try to run PC on profiles of different kinds of movies. So if we rearrange our input data so that now the rows are the movies and the columns are the users, so it will look like this. So we'll call this as the transpose of the original ratings matrix, or A of T for short. So now if we run PCA on this particular dataset, so it will identify some latent features again, and it will describe each individual movie as some combination of them. So now each column is now a description of some typical movie that exhibits some latent feature. So again, these columns have no inherent meaning, but in practice they might fall along the movie genre lines. But in reality, it is more complex to name these features. So now let's call this particular resulting matrix that describes typical movies as U. So how do these matrices actually help us to describe typical users and typical movies to help us predict ratings? So it turns out that the typical movie matrix, which is U here, and the typical user matrix transpose, which is V of T, and they are both the factors of the original matrix A that we started with. So here A is a m by n matrix with m rows and n columns, and U here is m by m matrix, so it has m rows and m columns, and S is m by n matrix, and V of T is your n by n matrix. So if we have both U and if we have V, so we can reconstruct the whole matrix A. And even if there are missing values or missing ratings, and if we have both U and V, so we can fill in all those missing values using these two matrices in A. So that is why we call this as matrix factorization. So we'll describe our training data A in terms of smaller matrices, and that are the factors of the ratings that we want to predict. So there is also a matrix S which is in the middle, so it is just a simple diagonal matrix, which means that the non-zero elements will be on the diagonal of this matrix and rest of the elements will be zero. So the only purpose of this matrix is to scale the values so that we end up into the proper scale of the values that we calculate using U and V. So here U and V are both orthogonal matrices, which means that if you multiply these matrices with their transpose, so you'll get the identity matrix. And S is the diagonal matrix, which means that the non-zero elements will be on the main diagonal and rest of the elements will be zero. So that is why we call this as matrix factorization. So you can just multiply the scaling matrix into V or U, and you will still think of R as just, or A as just the product of the two matrices. So you can just multiply the scaling matrix into V or U and still think of A as just the product of the two matrices, that is V and U. So you can reconstruct whole A at once by multiplying these factors together and get the ratings for every combination of the users and the items or the movies in this particular case. So once you have these factors, so you can also just predict a rating for a specific user. So here is a screenshot for a real data set that we'll code in our coding environment, and then you can, if you want to calculate the rating, or if you want to predict the rating for the customer 7 for the movie 3, so the columns represent the movie IDs and the rows represent the customer IDs or the user IDs. So if you want to know or predict the rating for the customer 7 or user 7 for the movie 3, so we can do that by taking the dot product of the respective row in U and for the user and the respective column in V of T for that particular movie, so which will give us the predicted rating for the user ID 7 for the movie 3. So finally, we are going to tie this all together. So later on in this course, we'll use a built-in recommender called the SVD. So SVD is known to produce very accurate results, and SVD stands for singular value decomposition. So it is just a way of computing the matrix U, S and V all together all at once very efficiently. So all SVD does is to run PCA on both the users and the movies, and it gives us back the matrices that we need, which are the factors of the original rating matrix that we had. So SVD is just a way to get all of these factors in one go. So mathematically, we can represent the expected rating or the predicted rating as the dot product of U and V of T, where P of U is here is your U and Q is your V. So what SVD does is it tries to minimize the values of P and Q such that we minimize this particular loss function. So now the problem arises when we have missing data in our rating dataset, so which is most of the times we will have. So this is an actual screenshot of the Netflix price data where you can see most of the values are missing. So when our original matrix, that is A, has some missing values, so we cannot actually run PCA on this matrix because it has missing values, so it must be a complete matrix to run PCA. So one way to solve is to just fill these missing values using the mean values, but there is a better way to do that. So if we remember from the previous slides that every rating can be described as a dot product of some row in the matrix U and some column in the matrix V of T. So if you want to find the rating for user 1, so we'll take a dot product of the corresponding row in the matrix U and the corresponding column in the matrix V of T. So let's assume that if we have at least some known ratings for any given row and column in both matrices U and V, so we can treat this as a minimization problem where we actually try to find the values of those complete rows and columns that best minimize the errors in the known ratings for the matrix A. So there are a lot of machine learning techniques that we can use to solve this problem. So one technique is called the stochastic gradient descent, which is SGD for short. So basically what it does is it just keeps iterating at some given learning rate until it arrives at a minimum error value. So again, SGD is just one way of doing it. So there is another method called the ALS, which is alternating least squares, that we can use to solve this problem. And when we say that we are using SVD for recommendations, it is not really just SVD, because you cannot actually apply SVD to missing data. So it is just an SVD inspired algorithm, not a pure SVD. So a specific variant of SVD is called the SVD++. So, and there is another technique called the restricted Boltzmann machines, which are used to solve these problems. So the important points that you have to take away is that you can think of all the rating metrics as a set of users and items as a matrix A, and the matrix A can be factored into smaller matrices that describe the general categories of the users and the items that can be multiplied together. So a quick way to get those matrices is by using a technique called SVD, which is called the singular value decomposition. So once we have those factored matrices, so you can predict the rating of any given item. So the rating is predicted by taking a dot product from each matrix. So techniques such as SGD and ALS, which is alternating least squares, can be used to learn the best values of those factored matrices when you have missing data. So now let's implement the SVD algorithm in Python on the movie lens dataset. So I'll start by importing the required libraries, that is NumPy as NP and Pandas as PD. So once you have imported these libraries, now let's import our data sets. So we have two data sets called ratings and movies. So first of all, I'll import the ratings.csv, which I have already uploaded to the Jupyter notebook. So we have 4 columns in this dataset, that is user ID, movie ID, rating and timestamp. So we'll use these columns and we'll store the dataset in ratings data frame. And after that, if you want to see the head of this data frame, that is the first 5 rows, so you'll run the ratings.head and it will print the first 5 rows of this dataset. So we have user ID for a particular user, and the movie ID that this particular user has rated, and then the rating that this particular user has given to these movie IDs, and then the timestamps. So now let's see the second dataset, that is our movies.csv. So we'll use the read_csv function to read this dataset, and we have 3 columns, that is movie ID, title and genres. So we'll store this in movies data frame. So once we have imported these 2 datasets, now let's look at the heads of both of these datasets. So our movies.head, it prints these 3 columns. So we have movie ID as the first column, which corresponds to the movie IDs in our ratings dataset, and then we have the title of these movies, the year of the release, and then we have the genres of these movies. So if you want to look at the head of the ratings dataset, we have user IDs, movie IDs, ratings and timestamps. So this is our movie lens dataset, and we are going to make an SVD recommender system using SVD algorithm. So before that, we'll calculate how many unique users are there and how many unique movies are there in our dataset. So in our ratings dataset, our user ID columns contains the user ID for different users. So each user might have given ratings to more than one movie. So here you can see this particular user with the user ID of 1 has given movie number 2 a rating of 3.5, movie number 29 a rating of 3.5. So there are different movies and movie IDs and the different ratings. So if you want to know how many unique users are there, so we'll use the unique method of the column, that is user ID, and then we only want to get the first element. So if you omit the dot shape method from here, if you run this, so you'll get an array, and if you just write the shape, so you'll get a tuple where the first element of the tuple is the number of users or unique users in our dataset. So if you want to access the first element, you will just write the indexing. So in the indexing or the slashing, will write the 0 or the first index, that is our users. So we have around 7120 users in our whole dataset. And then if you want to know how many movies or unique movies are there in our dataset, so we'll use the same unique method on the movie ID column, and then we'll get the first element. So once we print this, so we have printed it using the f string. So an f string is just a string that is used to print Python expressions. So if you have a Python expression that you want to print including a string, so we have written number of users, and you have to keep the Python expression in these braces, and these Python expressions are the variables that we have just calculated above, that is number of users and number of movies. So once you print this, you'll get number of users as 7120 and number of movies as 14,026. So we have 7,100 unique users. We have given different ratings to 14,026 movies. So now before moving ahead, as I've already told you that our algorithm, SVD algorithm, it takes a matrix which is a real rating matrix. So that matrix should be in such a way that the columns are movie ratings or the movie IDs and the user IDs are represented by rows. So we'll do that by using the pivot method of the data frames. So our data frame is ratings, so we'll use the pivot method. So it will create an array that corresponds to the movie IDs on the column side and the row IDs or the user IDs on the row side. So the index of this particular matrix will be user ID and the columns will be represented by movie IDs and the values in the columns and the rows will be represented by our ratings. So these are the different ratings given by different users to different movies in this ratings dataset. And if you want to fill all the missing values with 0, so we'll write fill NA 0. And if you delete this particular method from here and you print it, so you will get all the missing values represented by NaN values. And if you want to replace these NaN values by 0, so we'll replace it with fill NA 0, so it will replace all the NA values with 0. So now to implement the SVD algorithm in Python, we're going to use the library called scikit surprise. So if you want to install this library, you have to run this particular command in your anaconda prompt. So if you go to your anaconda folder and in the anaconda prompt, you have to type this particular command. And once you run it, so you will be asked to press Y or no. So you press 1 and then this particular package, which is scikit surprise, it will be installed in your anaconda system. So since I've already installed this package, so I will not install it again. So now I will import all the required libraries and classes that we need to implement the SVD algorithm. So from the surprise package, we'll import the reader class, the dataset class, and the SVD algorithm. So there are different versions of SVD algorithm that are present in our surprise package. So we are going to use the SVD, and there is also one algorithm called the SVD++. So we are going to firstly use the SVD algorithm, and also we want to evaluate the performance of our model. So for that, we'll import the cross validate function from the model selection package or the model selection module of the surprise package. So once you've imported these two, now you can instantiate an object of the reader class. So we'll use this object to read datasets and we'll convert those datasets to your dataset object that is used by your SVD algorithm. So once you run this particular code, your dataset will be loaded. So to load the dataset, we have the dataset class and we'll use the load from df method of this class, and inside the method we have to mention our data frame and a different column. So there is a format that this particular class requires. So the format is that your first column is your user ID, the second column is your movie ID, and the third column should be your ratings. And we'll use the reader class to read this particular data frame, and it will convert this particular data frame to a dataset object that will be used by your SVD algorithm. And after that, we'll instantiate an SVD class object that is called SVD that we'll use later on to fit the model. And then first of all, we'll evaluate the performance of the model using the cross validation. So we're not going to implement training and test sets. We'll implement the cross validation, and using the cross validation, we'll get to know the performance of our model. So we have used the cross validate function that we've just imported from the model selection package. And this function takes two arguments, that is SVD, your model, and the data that you're going to run on, and the data that you want to run SVD on. The measures will be your two measures or more than two measures that you want to evaluate the performance for. So we'll calculate the RMSE values, which is the root mean square errors and the mean absolute errors. And then CV equals 3 means that we want this algorithm to run cross validation 3 times. And then we have verbose equals 2, so it will also print whenever it runs cross validation, so it will print the results along with the process. So after running this, it might take some time because the cross validation process takes some time. So once it's over, so we'll move ahead with the rest of the code. So here are the results for our threefold cross validation. And if you want to know more about these functions, so you can press shift and tab here, so it will open the documentation. So in the documentation, you can see that if you want to use a custom data set that is stored in a pandas data frame. So it takes two arguments, that is your data frame and the reader object of the reader class. And if you want to know more about this, so you can read this particular documentation. And after that, if you want to know more about the cross validate function, so you can click here. So it takes your algorithm as the first argument. So our algorithm is SVD, and then the data is data, and different measures as RMSE and MAE. And cross validation is the number of times it will perform the cross validation. So it will be a threefold cross validation. So these are different results for our cross validation. So for the fold 1, we have an RMSE of 0.84, and for fold 3 we have an RMSE of 0.8473, and this is the mean and the standard deviations. So now if you look at the head of your ratings dataset, so you will see we have different user IDs, movie IDs and rating. So now if you want to predict the ratings for the user one for different movies which this user has not rated yet, so that we can recommend those movies, and we'll recommend all those movies where the prediction is 5 or the highest rated movies by this particular user. So first of all, let's create a matrix, or let's create a data frame. So now before moving on, let's see how many movies this particular user has rated as 5 stars. So we'll take all the movies which are rated by user 1, and we'll take all the movies which are rated by user 1 as 4. So if you write 5 here, so it will display all the movies which have been rated by user 1 as 5 stars. Then we have set the index of this particular data frame as movie ID. So this movie IDs will be treated as an index, and now after that we'll join movie IDs and our ratings. So we'll join our ratings and the movies data frame using the title column. So once you run this, you'll get this particular data frame that will contain all the movie IDs along with the movie names that have been rated as 4 stars by this particular user. So you can see these are the movies that have been rated as 4 stars by this particular user, and if you write 5 here, so it will display all the movies that have been rated as 5 stars by this particular user. So based on these results and based on the movies that have been rated 5 stars by other users, we will recommend different movies that this particular user has not seen that other users have seen. So now first of all, let's copy our movies which dataset which contains the title of the movies. So once you use the .copy method, so it will create a copy of this particular dataset and it will store in user 1. So if you now make any changes to the user 1, so our original data, that is our movies data, will not be affected. So that is why we use the copy method. So once we have used the copy method, so now we'll reset the index. So reset the index is when you start the index from 0 again. So if the index was movie IDs before, so now it will be reset to 0s and 1s. So this is how our movie ID or user 1 dataset looks like. So we have indexed from 0 to 1 again, and this is the movie IDs, these are the titles, and these are the genres. So now we'll train our SVD algorithm using this particular dataset. So we'll use again the dataset class, and we'll use the load from df method from this class, and we'll pass our data. So our data is ratings data, so it contains 3 columns, that is user ID, movie ID and our rating. And then we'll use the reader class to read this particular dataset, and it will convert into a dataset object that will be used by our SVD algorithm. So after creating the dataset, we'll build the training set. So if you want to build the training set, we have a method called build full train set. So it will take all the set or all the dataset, and it will build a training set from that particular dataset. So we'll store that dataset in train set, and then we'll pass our train set to our SVD algorithm. So we have already instantiated an object of the SVD class, that is SVD. So we'll use the fit method of this particular object, and we'll pass our training set to this particular method. So once we pass our training set to this particular method, so our SVD algorithm will be fitted to this particular training set. So after fitting our algorithm to our training set, we'll now estimate the scores or the ratings by this particular user for different movies. So we'll store that in a new variable in our data frame, that is user 1. The variable name is estimated score. So we'll write user 1 then movie ID. So we'll take all the movie IDs and we'll apply this lambda function on all the movie IDs. So this lambda function will take all the movie IDs as an input, and we'll use the .predict method. So lambda function is a function which is an unnamed function. So it will use this particular method, which is the predict method of our SVD object, and it will pass x, which is our movie IDs here, and it will find the estimated ratings for different movies that is not yet given by this particular user. And based on those estimated ranks or estimated ratings, we'll only recommend those movies which are estimated to be the highest rated movies by this particular user. So after we pass this, we will have all the estimated or predicted ratings for this particular user for different movies. So this that object or that data frame will also contain these columns as well. So movie IDs will be there, genres will be there, indexes will be there. So we don't want these 3 columns, we just want the title of the movies and the movie IDs which will be already stored as the index. So we'll drop all these 3 columns and we write x is equals 1 if we want to drop anything from the column side, and we'll store all the results, or we'll store the results in the data frame called user1, and now we'll sort the values of the user1. So our user1 now will contain the estimated values or the predicted ratings for this particular user whose ID is 1. So we'll start the values of the estimated scores by descending order. So we'll have to write ascending equals false, so it will be sorted in descending order. So then we'll print the first 10 ratings, which is the highest 10 ratings for our user 1. So it will also contain the movie titles. So once you run this particular code, so we'll have all the highest rated movies, or the movies that are highest rated, and those are predicted by our particular SVT algorithm. So after this code finishes executing, you'll get all the first 10 titles or the movie titles which are expected or which are predicted to be the highest rated by this particular user. So the highest rating this particular user will give is 4.7 to these movies. So we'll recommend these movies to this user, which this user has never seen these movies based on the rankings that have been given by other users. So this is how we use the SVT algorithm to build a recommendation system that will recommend different movies to a user based on the UCBF, which is the user-based collaborative filtering.
Now, there are many ways of knitting the nodes of a neural network together, and each way results in a more or less complex behavior. Possibly the simplest of all topologies is the feed-forward network. So when feed-forward neural network, signals flow in one direction without any loop in the signal paths. And typically, artificial neural networks have a layered structure. The input layer picks up the input signals and passes them on to the next layer, known as the hidden layer. And there can be more than one hidden layer in a neural network. And at last comes the output layer that delivers the result. Now, the first question to pop into your head would be, what is the inspiration behind these artificial neural networks? Well, the answer to that is the biological neural network of our brain. So let us first understand the architecture of a biological neuron. So as you can see in the slide, our biological neuron has these 3 main components. So we have the dendrite, the cell body, and the axon. These dendrites receive the signals, and the cell body processes these signals, and the axon finally sends out these signals to other neurons. So just like the biological neuron, the artificial neuron has a number of input channels, a processing stage, and one output that can fan out to multiple other artificial neurons. So now let's understand these artificial neurons in detail. These artificial neurons are the most fundamental units of deep neural network. It takes an input, processes it, passes it through an activation function, and returns the output if the condition is met. Or else it will process it again until you get the correct output. And such type of artificial neurons is called as a perceptron. So they are basically like a linear model which is used for binary classification. So as the figure shows, we have x1, x2, x3 and going on till xn as inputs in the input layer. Now, to which we add the weights and the bias that are randomly selected. So here we have w1, w2, w3 going on till wn as weights. So we multiply these weights with the corresponding inputs and add all the values together, and finally we add bias to that sum. So this final sum is passed through an activation function which finally gives us the output. So let us see this in detail. So here we have 3 arrows which correspond to the 3 inputs coming into the network. Now for these 3 inputs, we have corresponding weights associated with them. So input 1 is associated with a weight of 0.7, input 2 is associated with a weight of 0.6, and input 3 is associated with a weight of 1.4. Now, these inputs are multiplied with their respective weights and their sum is taken. So if the 3 inputs are x1, x2 and x3, the sum would be x1 into 0.7 plus x2 into 0.6 plus x3 into 1.4. And to the sum, we add an offset which is called as bias. So this bias is just a constant which is used for scaling purpose. Now let us understand the concept behind these weights. So these weights basically determine the relative importance of the inputs. So let's say we have two inputs, humidity and wearing a blue shirt. So here we can see that wearing a blue shirt has almost no correlation with the possibility of rainfall. So that is why the weight assigned to input x2 would be low in order to bring down its importance. Now let us see why do we need activation functions. So consider this scenario where you have two different classes. One class is represented with triangles and the other class is represented with circles. Now let's say I ask you guys to draw a linear decision boundary which can separate these two classes. So is that really possible? Can we draw a linear line which can segregate these two classes? Well, the answer is obviously no, isn't it? So let me tell you guys how can we do this. So we'll have to add a third dimension to create a linearly separable model which is easy to deal with. So the logic is when you're going from 2D to 3D, you're making your equation non-linear. So with the third dimension, I have introduced non-linearity in our data, which helps in creating a linearly separable model. And in real-world situations, you don't always get linear problems. So you should know how to deal with non-linear problems as well. And this is where activation functions help us to convert the linear equation to non-linear form. So these activation functions bring in non-linear functional mappings between the input and the response variable. Their main purpose is to convert an input signal of a node in an artificial neural network to an output signal. And if we do not apply an activation function, then the output signal would just be a simple linear function. Now there are many types of activation functions, and today we'll be discussing some of the widely used ones. So let's start with the identity function. So the identity function gives out the same output as the input. So no matter how many layers we have, if all the activations are identity functions, then the final output of the last layer would be the same as the input given to the first layer. And the range of the identity function goes from -infinity to +infinity. So after that, we have the binary step function. So this binary step function is usually denoted by h or theta, and it is a discontinuous function. So if the input is less than 0, then the output would be 0. And if the input is equal to or greater than 0, then the output would be 1. And this is why binary step function is used to solve a binary classification problem. So after that, we have the sigmoid function. So the formula for the sigmoid function is denoted by 1 upon 1 plus e power minus x. The sigmoid function basically scales the values between 0 and 1. So if the input is a large negative number, it is scaled towards 0. And similarly, if the input is a large positive number, it is scaled towards 1. Then we have the tan h function. It is a hyperbolic trigonometric function which scales the values between -1 and 1. So one advantage of tan h function over sigmoid is that it can deal more easily with negative numbers. And after that, we have the ReLU function, which stands for rectified linear unit. So this function will give out 0 if input is less than 0. And on the other hand, if input is equal to or greater than 0, then it will act as an identity function and give out the same value as the input. And this ReLU function is the most widely used activation function and is primarily implemented on the hidden layers of the neural network. Then we have the leaky ReLU, which is just a modified version of ReLU. So the leaky ReLU, instead of just completely removing the negative part, it just lowers the magnitude. And finally, we have the softmax function, which is ideally used in the output layer for classification problems. So the softmax function basically gives a set of probability values for each class of the output. And that particular class, which would have the maximum probability, will be our output class. So that was all about activation functions. Now let us learn more about perceptrons. So like we were taught how to behave in certain conditions, perceptrons also require training. So they have a learning algorithm through which they produce the output. By training a perceptron, we try to find a line, plane, or some hyperplane which can accurately separate these two classes by adjusting the weights and biases. So consider this image where we give the dogs and horses as input. So here after the first iteration, error value is 2 since the horse has been classified as dog and there is one dog which is placed in the horses class. And in the second iteration, the error value is reduced to 1 as it is just the dog which is classified as a horse. And finally, in the third iteration, we get the correct output as the perceptron has been trained well with no error. So all the dogs have been placed in one class and all the horses have been placed in one class. Now let's understand the perceptron training algorithm. So this perceptron over here receives multiple inputs and each input is initialized with a random weight. So after these, we multiply these weights with their corresponding inputs and then we get the sum. Now this input is passed through the activation function which would give us a non-linear output. So this process until here is known as feed forwarding. Now if the output which we get is not optimum, we calculate the error in prediction and then go back and then update the weights and bias. So this process where we go from output to the input layer is known as backpropagation. And we keep on backpropagating until we get the desired output. So that was the perceptron training algorithm. Now let's have a look at the benefits of using artificial neural networks. So the artificial neural networks can learn organically. This means an artificial neural network's outputs aren't limited entirely by inputs and results given to them initially by an expert system. So artificial neural networks have the ability to generalize their inputs. This ability is valuable for robotics and pattern recognition systems. Artificial neural networks also help in nonlinear data processing. So nonlinear systems have the capability of finding shortcuts to reach computationally expensive solutions. These systems can also infer connections between data points rather than waiting for records in a data source to be explicitly linked. This nonlinear shortcut mechanism is fed into artificial neural networking, which makes it valuable in commercial big data analysis. Artificial neural networks also have high potential for fault tolerance. When these networks are scaled across multiple machines and multiple servers, they are able to route around missing data or servers and nodes that can't communicate. And these artificial neural networks can also self-repair themselves. So if they're asked to find out specific data that is no longer communicating, these artificial neural networks can regenerate large amounts of data by inference and help in determining the node that is not working. This trait is useful for networks that require informing their users about the current state of the network and effectively results in a self-debugging and diagnosing network.
Here's a quiz question for you guys. What do you mean by artificial intelligence? Your options are the ability of a machine to think and learn like a human, the use of computers to solve complex mathematical problems, a computer program that performs repetitive tasks automatically, or the study of natural intelligence in animals and humans. Please mention your answers in the comment section.
Hello everyone, Intellipaat offers executive postgraduate certification in data science and artificial intelligence in collaboration with iHub IIT Roorkee. Through this particular course, you'll get to learn multiple tools like Python, PySpark, SciPy, NumPy, Pandas, Matplotlib, TensorFlow, Git, etc. You are going to learn multiple skills like data science, natural language processing, deep learning, fundamentals of generative AI, prompt engineering, and application-based generative AI, as well as recent trends like agentic AI. This course is designed to get you ready for the AI world. So do check out link available in the description. Also through this course, we have already helped thousands of learners take positive step in their career. You can check out their testimonials on our Achievers channel.
So why AI? Well, AI is actually everywhere. It's omnipresent like God. And AI's applications are present in every single industry, from banking and finance to medical science and also in aerospace. Now, it is actually a known fact that many banks have numerous activities on a day-to-day basis which need to be done accurately. And most of these activities take up a lot of time and efforts from the employees, and at times there is also a chance of a human error in these activities, so to speak. So, some of the works that banks and financial institutions handle are investing money in stocks, financial operations, managing various properties, and so on. And with the use of AI system in this process, the institutions are able to achieve efficient results in a quick turnaround time. So the strategic implementation of artificial intelligence in the bank helps them to focus on every customer and provide them quick resolution. And similarly in medical science field as well, it has wide applications. So AI has completely changed the way medical science was perceived just a few years ago. So there are numerous areas in medical science where AI is used to achieve incredible value. So with the help of AI, the medical science was able to create a virtual personal healthcare assistant. So these are used for research and analysis purpose. There are also many efficient healthcare bots introduced in the medical field to provide constant health support to patients. And it is also used in the aerospace industry. So in aerospace, there are a lot of features from booking the tickets to the takeoff and operation of the flights that AI takes care of. AI applications make air transport efficient, fast, safe, and also provides a comfortable journey to the passengers. And it has also changed the face of gaming. So these days we're able to play TV and computer games on the whole new level, all thanks to artificial intelligence application. So these are just some of the applications where artificial intelligence is used. And all in all, it is used to reinvent the world. So scientists are riding on the back of AI when machine intelligence will surpass the human intelligence. Scientists believe that once the AI system starts working in its full capacity, it will reinvent the world that we know today. So think of the world where all the menial tasks such as garbage disposal, construction, digging, and so on will be taken care of by AI applications. So it'll all be a time when the hierarchical order dictates the limits of a human. It'll be the world where no one will be looked down upon and every human will be considered equal. So this way, humans can then focus their strengths on higher levels of work to accomplish a lot more and always taking technology to new heights. So now that we've understood the importance of artificial intelligence, let's learn more about AI. So AI is basically a field of computer science which emphasizes on the creation of intelligent machines which can work and react like humans. So I'm reiterating it. So AI is that field of computer science where we create machines which can work and react like humans. So let's keep this definition at the back of our head. Using this definition, let's actually look at some applications of AI which are currently existing in today's world. So we have simple chatbots like OK Google and Siri which help us in assisting whatever we want. So let's say I want to know the current time. All I need to do is ask Siri, Siri, tell me what is the current time. Similarly, if I want to know the distance between India and Malaysia, I'll ask Siri, tell me what is the distance between India and Malaysia. Again, let's say I'm just sad and I want to listen to a simple joke. I'll ask Siri, tell me a simple joke. Right? So these are some of the applications of artificial intelligence. And then we have Sophia. So Sophia is the first humanoid robot. So she is the first humanoid robot who can actually speak to us like natural humans. So Sophia can show some wide range of emotions exhibited by humans, but she is actually a robot. Another application of artificial intelligence is the self-driving car. So you have self-driving cars by Google and Tesla, which actually drive by themselves. So they do not need any external driver to drive, right? So these cars work by themselves. So similar to self-driving cars, we also have self-flying drones, which do not need any human intervention and they can navigate by themselves. So now let's actually get a bit deeper and understand what is intelligence. So intelligence can be defined as one's capacity for understanding, one's capacity for self-awareness, one's capacity for learning, and one's capacity for problem solving. That is, how well is something or someone able to understand? How well is someone able to learn new things? And how well is someone able to solve problems by themselves? So, now that we know what is intelligence, let's understand what is artificial intelligence. So, when you apply the same intelligence to machines, this is known as artificial intelligence. Now, just imagine there's a machine which can understand things which are normally understood by human. There is a machine which is self-aware, and there is a machine which can solve problems by itself. Now that's just amazing, isn't it? Right. So this is the artificial intelligence which I'm talking about. So now that we also know what is intelligence, I'll ask another question. So tell me, what is it that makes humans intelligent? Well, we as humans can reason, we as humans can learn, we can perceive, we can solve problems, and we also have linguistic intelligence. That is, we can figure out what is someone else saying, and we can also understand the grammatical intricacies of different languages. So, again, my question would be, what if a machine could exhibit all of these factors normally shown by a human? Again, that's just amazing, isn't it? So this is what is known as artificial intelligence. So a machine which can show traits normally shown by a human, that is known as artificial intelligence. Alright, so now that we're clear with artificial intelligence, let's segregate AI, ML, and DL. So normally most people get confused between artificial intelligence, machine learning, and deep learning. So this is where I'm going to help you out in understanding the difference between these three. So we have AI at the top, and you can consider machine learning and deep learning to be subsets of AI. So again, machine learning and deep learning are just ways to achieve artificial intelligence. So I'll restate it again. Machine learning and deep learning are just ways to achieve artificial intelligence. Now, machine learning is that part of artificial intelligence which aims to teach the computers the ability to do tasks with data without any explicit programming, right? So we don't need to do any explicit programming, and the algorithms do tasks by themselves. And in ML, we mostly use numerical and statistical approaches to achieve artificial intelligence. And then we have deep learning, which is actually a subset of machine learning. So first we have AI, and then we have ML, and then we have DL. So deep learning comes in where machine learning fails. And we apply deep learning through something known as artificial neural networks, about which we'll obviously learn later. Right. So now let's understand artificial intelligence in a bigger set. So as I've already told you, artificial intelligence is the superset under which comes machine learning, under which comes deep learning. And then machine learning and deep learning are basically ways to achieve artificial intelligence. Now these are the different areas of research of artificial intelligence. So you have ML, again a part of ML is deep learning. Then we have natural language processing. So over here we basically understand what is spoken or written by a human. And then we have speech, where we either translate the speech to text or we translate the text to speech. The next subfield is robotics, and then we have autonomous vehicles under robotics. So Google's self-driving car is an example of this over here. So now that we've also understood the difference between artificial intelligence, machine learning, and deep learning, let's see different examples of machine learning around us. So most of you would have shopped on Amazon. Now, when you go into Amazon, you see that there are some products recommended to you. Now, how do you think that would happen? So this is something known as recommendation engine. And recommendation engine is nothing but a component of machine learning. So let's say you and your friend buy similar products. So your friend buys 5 products and you buy 3 products. Now, out of those, whatever 3 products you buy are same as what your friend buys. So let's say the common products are an iPhone, a back cover for the iPhone, and a Bluetooth headset. Now, let's say the other 2 products bought by a friend would be a MacBook and a mouse. Now, since there are 3 products which are same between you two, this is why the products which your friend has also bought, those are the products which will be recommended to you. So, on the basis of the commonality between you and your friend, you will be recommended a MacBook and a mouse as well. So this is nothing but a concept of machine learning. And then we have Amazon Alexa. Amazon Alexa is a really good example of speech recognition. You know, when you say Alexa, turn on the lights, it'll turn on the lights. When you say Alexa, book a ride for me, it'll do exactly that. When you say Alexa, order a cheese pizza, and that is exactly what Amazon Alexa will do. Now, Alexa is just a machine, right? But when you say do something, order a pizza, book a cab for me, turn on the lights, how is the machine able to understand all of this? So, the idea behind this is speech recognition, and that is again a component of machine learning. And then we have Netflix's movie recommendation. So, let's say you watch 2 TV series. First TV series is Friends, and the next TV series is Big Bang Theory. And since you watch these 2 TV series which belong to the genre comedy, that is why maybe you will be recommended How I Met Your Mother, or you can be recommended Silicon Valley, or some other TV series belonging to the comedy genre. So this again is machine learning. And then we also have Google traffic prediction. Let's just say you're traveling in your car and there is huge traffic there. You desperately want to get out of the traffic. So you turn on Google Maps, and Google Maps tells you the best direction from where the traffic would be the least. Now, how does Google Maps do this? This again is machine learning. So now that we've looked at different real world applications of machine learning, let's actually understand what exactly is machine learning. So, as I've already told you, machine learning is a subset of artificial intelligence which gives the machine ability to learn without being explicitly programmed. So over here, data is the key, or in other words, you basically teach a machine how to learn without any explicit programming, and the machine learns with the help of data, right? So now that we know what exactly is machine learning, let's also understand how does machine learning work. So as I've already told you, machine learning depends totally on data. So first, we take in a data set and divide it into 2 parts. So the first part would be the training set, and the second part would be the testing set. And we will train the model on top of the training set. So now, once we train the model, we will give it new data and check for its accuracy on top of that new data. And if the accuracy of that new data comes out to be good enough, then we will go ahead and use that machine learning model. On the other hand, the model which you built, if the accuracy of that model is not good enough, then we'll go ahead and fine tune that model till we get the desired accuracy. This is the basic premise behind machine learning. Now let's look at the subcategories of machine learning. So we have supervised learning, unsupervised learning, and reinforcement learning. So in supervised learning, you can consider that the learning is guided by a teacher. So we have a data set which actually acts as a teacher, and its role is to train the model or the machine. So once the model gets trained, it can start making a prediction or decision when new data is given to it. So let's take this example. So over here, we are training this machine by giving it samples of data. So over here, the data is nothing but different images of apple. And along with each image of apple, we are also giving it the label of the image, right? So this image goes with its label, which is apple. Again, this image goes with its label, which is apple. Again, the same with these two, right? So we are teaching this machine that whenever it sees an image something like this, it is nothing but an apple. And after time, when we give it a new data from whatever learning it has done, it will predict whether it's an apple or not. So on the basis of its learning, this machine predicts that there is a good possibility. There is actually 97% possibility that the image which has been fed to the machine is nothing but an apple. So a use case of supervised learning could be spam classifier. So spam classifier basically means that whether the email which we get it's a spam or not. And that is done on the basis of different textual parameters. So let's say a genuine email wouldn't contain too many exclamation marks. It wouldn't contain a catchy headline and so on. But on the other hand, if it's a spam email, maybe it'll contain a lot of exclamation marks with maybe a lot of numbers, and it'll have statements like, hey, congrats, you've won a lottery, or hey, could you help me out? So this spam classification is basically an example of supervised learning. Then we have unsupervised learning. So in unsupervised learning, the model learns through observation and finds structures in the data. So once the model is given a data set, it automatically finds patterns and relationships in the data set by creating clusters in it. So what it cannot do is add labels to the cluster. Like it cannot say this is a group of apples or mangoes, but it will separate all the apples from mangoes. So over here, we have this set of images. Now, this unsupervised learning model which is applied on this, it will segregate these fruits on the basis of similar characteristics. So over here, we have segregated these four into one cluster, these three into second cluster, and these three into the third cluster. Now, even though the unsupervised learning does not have any labels, it has still segregated these three into three clusters, right? So the machine over here does not know that these are apples or these are oranges or these are bananas. Yet it has segregated these three on the basis of similarity of characteristics. So it found out that these four objects are similar to each other, and there is quite a bit of variability when it comes to these four objects and these three objects. Similarly, this machine was able to figure out that these three objects, they are quite similar to each other. But when compared with these three objects, they are very dissimilar. So this is the underlying concept of unsupervised learning. And a good example of unsupervised learning would be again Netflix movie recommendation. So over here, the movies are segregated on the basis of different genres. So over here, TV series like Friends, How I Met Your Mother, and Silicon Valley are clustered into one group because those come into the same category. Similarly, movies such as Secret Superstar and Dangal could come under the same category because they have the same lead actors. So over here, we are segregating the movies on the basis of similar characteristics, even though there are no labels in it. And it's finally time for the third machine learning type, which is reinforcement learning. So over here, there is an agent and there is an environment. And the agent interacts with the environment and finds out what is the best outcome for it. So it basically follows the concept of hit and trial method. The agent is rewarded or penalized with a point for a correct or a wrong answer. And on the basis of positive reward points gained, the model trains itself. So let's take this example. So over here, this self-driving car would be our agent and the road is the environment. And this car is interacting with this environment. So it will observe the environment and it has two choices over here. So either to go straight or turn right. Now, let's say this agent or the self-driving car decides to go straight. Then what happens is it goes and bangs straight into this barricade. So then it realizes that the action taken by it was not in its best interest and that is why it is penalized. So since it is penalized, it realizes that the action taken by it was wrong and that is why from the next time onwards it'll do the opposite action. So instead of going straight, it'll take the right turn. And when it takes the right turn, it realizes that the road is correct and the agent is rewarded. So this is how reinforcement learning basically works. So the agent interacts with the environment, it takes an action, and if the action turns out to be incorrect, it is penalized. And if the action turns out to be correct, it is rewarded. So this cycle goes on and on till it completely learns its environment properly. And the best use case of reinforcement learning is again self-driving car. So companies such as Tesla and Google are working on these self-driving cars. So just to sum it off, these are the three different types of machine learning algorithms. So we have supervised, unsupervised, and reinforcement machine learning. So under supervised, we have regression and classification, and in unsupervised, we have clustering techniques, association analysis, and hidden macro model. And then the third is obviously reinforcement learning, which works on trial and error method. And if you want to do some really cool machine learning projects, you can check the sites out. Now let's look at some limitations of machine learning. So when it comes to machine learning algorithms, they would require massive stores of training data. So again, as I've told you, machine learning is totally based on the data which it has. So if you have more amount of data, only then it will be able to give correct accuracy. So let's say you take in very small amount of data and there's a good possibility that the results which you're getting are very biased or very incorrect. And also, error diagnosis is quite difficult when it comes to machine learning because again, the amount of data is very huge and wherever there's a mistake, you'd have to go through the entire algorithm which you've written and then find out that particular mistake by yourself, which is very difficult. And also when it comes to machine learning algorithms, they're not really that creative. So these ML algorithms are built only for one specific purpose. So let's say I'll build a machine learning model which will predict whether it will rain or not today. Now, if I want to use the same model to predict the stock prices, that'll not work, right? So basically one model is built only for one particular task. So this is the lack of creativity that I'm talking about when it comes to machine learning. And also there are a lot of time constraints as the model has to learn through a lot of historical data. So that was everything about machine learning. Now let's start off with deep learning. So deep learning is a subset of machine learning where it learns through data representations as opposed to task-specific algorithms. So we saw that the drawback in machine learning models was that the models are specific to only one particular task. But this is not the case with deep learning models, as these deep learning models are based on the data representations. And these deep learning models are mostly built with something known as deep neural networks. So this is how a deep neural network looks like. So these deep neural networks completely learn the data which is fed to it. So this is the data. So let's say if this image of woman is fed as the data to the deep learning model, then it will completely extract all the features of this data by itself. Again, the difference between ML and deep learning over here is that the feature extraction in machine learning is manual. But when it comes to deep learning, the feature extraction is automatic. So the deep learning model automatically extracts all of the features associated with that image. And when new images are fed to it, it automatically is able to tell whether the image is same to this or not. So this over here we have a graph which tells us how does performance vary with respect to the amount of data. So what happens in machine learning is that as we keep on increasing the data, the performance increases only up to a particular threshold. After that, if we increase any more data, there is no increase in performance. So this is another problem when it comes to machine learning. But on the other hand, when it comes to deep learning, the more amount of data you give it, the better will be its performance. And that again is because deep learning is based on learning data interpretation. So the more data you give it, it'll automatically learn all those features of the data by itself, and it'll be keep on increasing its performance gradually. Now let's look at some applications of deep learning. So speech recognition is one application of deep learning. Now you need to understand that you cannot build speech recognition applications with machine learning. So this is where machine learning fails and deep learning comes in and helps you to build speech recognition applications. Also, another application of deep learning is self-driving cars. So we see over here that the person is just sitting. He is not even touching the steering wheel and the car is driving by itself. So just an amazing application of deep learning. And then we have language translation over here. So this again is a part of deep learning. So over here we are typing something in Spanish and it is being automatically converted into English. So we also have visual translation over here. So over here this text or this board is in some random language, and this app over here which uses deep learning automatically converts this visual into English. So those were some applications of deep learning. Now let's actually understand how does deep learning work. So most deep learning methods use neural network architectures, and that is why deep learning models are often referred to as deep neural networks. So a deep neural network basically has these three models: an input layer, the hidden layers, and the output layer. And the term deep usually refers to the number of hidden layers in the neural network. So traditionally, neural networks only contain 2 to 3 hidden layers, while deep networks can have as many as 150 hidden layers. Now that's a very huge amount, isn't it? So deep learning models are trained by using large sets of labeled data and neural network architectures that learn features directly from the data without the need for manual feature extraction. So all of the input data is given to this input layer, and this input layer automatically extracts the features by itself. Now that data is sent to this hidden layer which performs all sorts of processing tasks, and then the final result is given out through the output layer. So now let's also understand what exactly is a neural network. So a neural network is a computing model whose layered structure resembles the network structure of neurons in the brain with layers of connected nodes. So it can learn from data which can be trained to recognize patterns, classify data, and forecast future events. So the neural network is based on the biological neural network of our brain. So that is why it is given the name neural network. So the layers are interconnected via nodes or neurons, with each layer using the output of the previous layer as its input. So its main function is to receive a set of inputs, perform calculations, and then use the output to solve the problem. Now, as I've already said, these artificial neural networks are based on something known as a biological neural network. So, our biological neural network has dendrites, cell body, and axon. So, dendrites are where the input is taken, cell body is where the processing is done, and axon is where the message is transferred to other neurons. And the same thing happens in artificial neural network as well. So first, we give in the data, that data is processed, and then the final processed result is given out as the output. So over here, let's say we train the data with images of cat and the labels would be either cat or not cat. After that, we give in a new image of a cat, and then we basically try to predict whether the model correctly classifies this as cat or not cat. And since the model has learned the data properly, it correctly classifies this image as cat. Now, to implement these artificial neural networks, we would need the help of a deep learning framework. So the first question to pop into your head would be, what are the different deep learning frameworks available? So TensorFlow is arguably one of the best deep learning frameworks that we have today. It is an open source software library developed by the researchers and engineers from the Google Brain team for high performance numerical computation. One well-known use case of TensorFlow is Google Translate. So Google Translate is coupled with capabilities such as natural language processing, text classification, forecasting, and tagging. So TensorFlow basically comes with two tools, TensorBoard and TensorFlow Serving. So building massive deep neural networks could be complex and confusing. This is where we can use TensorBoard to visualize our TensorFlow graph and plot quantitative metrics. And then we have TensorFlow Serving, which is a flexible, high-performance serving system and can be used for rapid deployment of new algorithms while retaining the same server architecture and APIs. So now let's look at the next deep learning framework, which is Keras. So Keras is actually a high-level API which can run on top of other deep learning libraries such as TensorFlow, Theano, or CNTK. And with the help of Keras, we can implement both convolutional neural networks as well as recurrent neural networks. And the best thing about Keras is, model building is extremely easy. It's like stacking layers on top of each other. So next, we have PyTorch, which is a scientific computing framework developed by Facebook. So we can get from the name itself that PyTorch is Pythonic in nature. That is, it can leverage all the services and functionalities offered by the Python environment and also smoothly integrates with the Python data science stack. Another great feature of PyTorch is that it offers dynamic computational graphs which can be changed during runtime. This is highly useful when we have no idea how much memory will be required for creating a neural network model. And the next deep learning framework is DL4J. So unlike deep learning frameworks which we saw till now, which were all based on Python, Deep Learning 4J is a deep learning programming library which is written for Java and the Java virtual machine. And the biggest advantage of DL4J is it includes inbuilt integration with Apache Hadoop and Spark. So it helps in getting state-of-the-art results on image recognition tasks. So it shows matchless potential for image recognition, fraud detection, text mining, parts of speech tagging, and also natural language processing. And finally, we have MXNet. So MXNet is a deep learning framework developed by Apache Software Foundation specifically for the purpose of high efficiency, productivity, and flexibility. And the beauty of MXNet is that it gives users the ability to code in a variety of programming languages such as Python, R, Julia, and Scala. This means that you can train your deep learning models with whichever language you're comfortable in without having to learn something new from scratch. And this deep learning framework is known for its capabilities in imaging, speech recognition, forecasting, and NLP. So when you hear the term TensorFlow, the first question to pop into your head would be, what exactly is a tensor? So in TensorFlow, data is represented in the form of tensors. Simply put, a tensor is a multi-dimensional array in which data is stored. So you can consider these tensors to be the building blocks in TensorFlow. Now, these very tensors are given as the input to the neural network. So as I've said, a tensor is nothing but an n-dimensional array. So the number of dimensions used to represent the data is known as its rank. So if a tensor has just one element, in other words, if it has just magnitude and no direction, then its rank will be 0. If a tensor has magnitude and direction in one plane, then its rank will be 1. Similarly, if a tensor has magnitude and direction in two planes, then its rank will be 2. And this goes on higher up the order. Now, TensorFlow, as the name states, is a combination of two words, tensor and flow. Here, the data is stored in tensors, but the execution is done in the form of a graph. So this is not like your traditional programming where you just write a bunch of lines and everything gets executed in sequence. So first, you'd have to prepare this computational graph, and then this computational graph is executed inside something known as a session. Now, in this computational graph, all the mathematical operations are depicted inside the nodes, and all the tensors are represented on the edges. So the entire computation process is done in two stages. In the first step, the code is depicted onto the computational graph, and in the second step, a new session environment is started and the graph is executed inside this session. So that was all about the computational graph. Now let's look at the program elements in TensorFlow. So we have three program elements: constant, placeholder, and variable. So let's start with constants. So constants are program elements whose value does not change, or in other words, the value is fixed. So let's head on to Jupyter Notebook and work with these constants. Right, so my first task would be to import the TensorFlow framework. So I'll type import TensorFlow as TF. I'll click run. So let me just wait till the import is done. Right, so we have successfully imported the TensorFlow framework. Now, as I've said, let's go ahead and start working with the constants. So let me just type in constants over here. So I'll create the first constant and name this constant as con1. Now, this is how we can create constants in TensorFlow. So I will use this TF and then put in a dot and then type in constant. Now inside this, I will give the value of the constant. So let's say the value is 10. So this is an integer type constant. Now similarly, I'll also create a floating type constant and I'll store this in con2. So I'll type tf dot constant and the floating value would be 3.14. Now after this, I'll create a string type constant. So again, this would be tf dot constant and the string which I'd be giving would be this is Sparta. And finally, we have a Boolean type constant and I'll store this in con4. So this will be tf dot constant and let's say the value is false. Now I'll run. Now let me print all of these values. So I'll use the print function and then I'll go ahead and print all of these values, con3, con4. Right. So we see that this first constant is a tensor of type integer. The second constant is a tensor of type float. This third constant is a tensor of type string, and this fourth constant is a tensor of type boolean. Now we see that we only have the data types of all of these tensors, but we don't have their values. This is because, as I've already told you guys, we have to create a computational graph and then execute that computational graph inside a session. But till now, we have not started our session. So let's go ahead and start a session first. So I'll type ses equals tf dot session and I'll hit run. Now I will run all of these inside this session. So I will type ses dot run and let me go ahead and run all of these: con1, con2, con3 and con4. So this time we have the values of all of these tensors. So the value of constant 1 is 10, the value of constant 2 is 3.14, the value of constant 3 is this is Sparta, and finally the value of constant 4 is false, right? So first we'd have to create all of the constants, then we'd have to create a session, and inside this session we'd have to run all of these constants. Now let me go ahead and perform some simple operations on all of these constants. So let me just type in operations over here. So I'll do a simple addition operation. So I'll type addition over here. And let's say the value of the first constant is 20. I'll put a plus symbol. and then I'll take in the next constant, and the value of the second constant would be 30. So I am basically adding two TensorFlow constants. The value of the first constant is 20, the value of the second constant is 30, and I'm storing that result in addition. Similarly, I will multiply these two constants now. So multiplication tf dot constant. So I'll give the value of 20. Now I'll put the asterisk symbol, and then this would be tf dot constant of 30. So this time I'm multiplying these two values, right? So I'll hit on run. So now again, if I'd have to see the resultant addition and multiplication values, I'd have to run these two inside a session. So I'll type sys dot run and then put in these two values over here, addition and multiplication, right? So we see that 20 plus 30 gives us an addition value of 50. And similarly, when we multiply 20 with 30, we get a result of 600. Right. Now, so this was basic operation with scalars. And we already know that tensors can have higher dimensions. So let's go ahead and perform addition and multiplication with these higher dimension tensors. Right. So again, I'll just put in addition over here. And I will take in the first constant, and inside this, I will give in a list of values. So let's say I will take in 1, 2, 3, 4, and 5. And I will add this list with the next constant. And this time, the second constant has the values of 5, 4, 3, 2, and 1. Similarly, I'll also multiply. So multiplication equals tf dot constant. And this will have values, let's say the same values, 1, 2, 3, 4, and 5. Let me put a comma over here. Right. Now I'll put the asterisk symbol. Again, I'll type tf dot constant, and I will give in the list of the values 5, 4, 3, 2, and 1. Now I'll hit run. Again, I need to run these two inside a session. So sys dot run. Let me put in addition over here. After that, I would also need the multiplication value. Right, so this is a result. So when we add 1 plus 5, we get 6. When we add 2 plus 4, we get 6. Similarly, when we add each of the corresponding elements with these elements inside the list, we get all of the 6s over here. Now let's take this multiplication result. So over here, when we multiply 1 with 5, we get 5. When we multiply 2 with 4, we get 8. 3 cross 3 gives us 9. 4 cross 2 gives us 8. And again, 5 cross 1 gives us a 5. So this was addition and multiplication with respect to lists. Now let me also do a simple operation on strings. So let me take in the first string and name it as str1. So this is a constant. So tf dot constant. And let's say I type over here, I love, and then I give a space. Now I will take in the second string, which would be str2. And inside this, and again, this would be a constant. So tf dot constant, and the value of this constant would be TensorFlow. Right. Now I will run this, and let me execute this inside a session. So sys dot run of str1 plus str2. So the result which you get is I love TensorFlow, right? So the first string is I love, and then there's a space, and the second string is TensorFlow. So when I add these two strings, the resultant is I love TensorFlow, right? So that was all about constants. And then we have placeholders. So when it comes to placeholders, we don't have to provide an initial value and can specify it during the runtime. So this allows us to build our computational graph without needing the data. And this is how we can create placeholders. So tf.placeholder is the syntax. And inside that, we just give the data type of the variable, which we will substitute later on during execution. So let's head back to Jupyter and work with these placeholders. So let me just type in placeholder over here. So let me create my first placeholder. So I'll name that as A. and tf dot placeholder, and this would be of integer type, so tf dot int 32. Now I will create another variable which would be b, and the value of b would be actually a cross 2. So let me run this. Now I will run these two inside a session. So sys dot run, and I want to see the result of b. So I'll put in b over here. Now, since we know that a placeholder takes in a value during runtime, so this is when I'll feed the value to this placeholder a over here. Now to do that, I would have to create something known as a feed dictionary. So feed dict equals, let me create a dictionary over here. So it would be a, and the value which I'll be giving to a would be, let's say, 5. Now let me run this and let's see what do we get. Right. So during the execution time, I have assigned a value of 5 to a. And when we multiply this 5 with 2 over here, we get the value of b, which is 10. Right. So all of this is happening during runtime because with the help of a placeholder, we can assign it a value during execution. Now similarly, let me go ahead and give a list of values over here. So instead of 5, let me give the list of values 1, 2, 3, 4 and 5. Now I'll run this. So over here, 1 cross 2 gives us 2, 2 cross 2 gives us 4, 3 cross 2 is 6, 4 cross 2 is 8 and 5 cross 2 is 10. So you get an array of values during runtime. Now similarly, let me also create a placeholder for strings. So I'll type string placeholder over here. So now let me create this variable and name this as string name, and this would be your placeholder. So tf dot placeholder, and I am taking in a string. So tf dot string. Right. Now let me create another string over here. So the name of this string would be my name. And let's say the value of the string is I am. Alright. Now let me run this and I'll execute this inside a session. Sys dot run, and I want the result of my name when I add it with respect to string name. Now let me also create a placeholder for strings. So I'll just type string placeholder, and let me create the first placeholder. So I'll name that as str1 name, and since this is a placeholder, tf dot placeholder, and I will be giving in a string during execution time. Now I'll also create another string value over here and name that to be my name, and the value of this string is I am, and then I'll give a space. Right, so now I'll hit run and let me execute this inside a session. Now let me also create a placeholder for strings. So this will be string placeholder. Right, so let me create this placeholder. I'll name this as str name, and since this is a placeholder, I need to use tf.placeholder, and I will be assigning a string to this during execution time. Now I will also create another string which would be my name, and this would be equal to I am, and there's a space, and I will be adding this with str name. So let me hit run. Right, now I'll execute this inside a session. So for that, I'll type sys dot run, and I want the result of my name. So I'll just put in my name over here, and then I'll provide the feed dictionary. Feed dict equal to, let me put in the dictionary over here, and I will assign the values of str name over here. Right. So the values of str name would be Sam, Bob, and Charlie. Now let me hit run and let's see what do we get. Right. So what we are basically doing is we are adding this with the placeholder value over here, and we are giving the values during the execution time. So I am Sam, I am Bob, and I am Charlie. Now these three values are coming from this feed dictionary during the runtime. Right. So this is all about placeholders. And finally, we have variables. So a variable is just a program element which allows us to add new trainable parameters to the graph. And this is the syntax to create a variable. tf.variable, and then we give the value, or we initialize the value, and then we specify the data type of that variable. Right, so let's head back to Jupyter now. I'll just type in variables over here. Right, so let me create my first variable, and the name of that variable would be var1. And we can create a variable like this, tf.variable. So guys, you need to keep in mind that this v over here is actually capital. Right. So now after this, I would have to assign a value to it. So let's say I assign this variable a value of 20. And this is of integer type. So tf.int32. I'll run this. Now another thing to be kept in mind is whenever we are declaring values in TensorFlow, they have to be initialized. So this is how we can initialize all of the variables. So we have something known as global variable initializer. And when we invoke this function, all of the variables which we have declared would be initialized. I'll hit run. So now let me execute this inside a session. So says dot run of init, and I have initialized this variable over here. Now let me also go ahead and run that variable. Says dot run var1. Right. So we have the result of var1, which is 20. Now since this is a variable, the value of a variable can be actually updated. So let me go ahead and update the value of this. So I will name this as updated var1, and the function would be tf.assign. And inside this, the first parameter would be the variable which I'd want to update. And after that, I need to give the value to which I'd want to update this. So I want to make this value of 20 to 25. Right. Now I will run this. So now this is actually a variable. We can actually update the values. So let me go ahead and do that. So the name of the updated variable would be, let's say, updated var1. And the function for that would be tf.assign. And this takes in two parameters. The first parameter would be the variable which we are supposed to update. And the second parameter would be the value to which we are updating it. So I want to make this 20 to 25. I'll hit run. Right now, let me run this inside a session. Says dot run, and I need to pass in the variable which would be updated var1. Let me make it small v over here. I'll run this. Right. So initially the value of var1 was 20, but we have updated it and made its value to be 25. Now let's also go ahead and create a small linear model. So let me just type in linear model over here, and this is how our linear model would look like. wx plus b, where w and b would be variables and x would be a placeholder. Right. Right, so let me start off by creating w. So w is a variable, so w would be equal to tf dot variable, and I am initializing it with a value of, let's say, 10, and this is of integer type. So this would be tf.int32. Now, similarly, I will also assign the value for b. So b is also a variable and its initial value would be 5, and this is also of integer type. And finally, we have x, which is a placeholder. So x is equal to tf.placeholder. And since placeholder does not actually take an initial value, it just takes a data type. So the data type is again tf.int32. So I'll run this, and now what I'll do is I will multiply w with x and add b to it. So the equation would be w cross x plus b, and I will store it in a variable and name that variable to be linear model. Right, so this is w cross x plus b. I'll run this. Now again, if I have to execute this, I have to run this inside a session. And since also I have created two new variables, I'd have to initialize them first. So init1 equals df dot global variables initializer. I'll hit run. So now I will create a session. So sys dot run, and I will execute init1 first. So I have successfully initialized these two variables w and x. Now I can go ahead and run this linear model. Sys dot run. Now I would want the result of linear model. So linear model, and then I will use the feed dictionary. Now inside this feed dictionary, I would have to assign a value to this placeholder x. So x equal to, let's say I give a list of values over here, and the list of values would be 1, 2, 3, 4, and 5. Now I'll run this and let's see what do we get. Right. So if the value of x is 1, we get 15. So this basically means that 10 into 1 plus 5, which is 15. Now after that, if the value of x is 2, so this would mean 10 into 2 plus 5, which is 25. Similarly, if x is 3, that would mean 10 into 3, which is 30, plus 5 is 35, right? And same is the case for 4 and 5.
So these two commands will update your TensorFlow version for the CPU and the GPU both in your Jupyter notebook. And once you have updated your TensorFlow, now you will import the TensorFlow package or the library as TF. And if you run this command, your TensorFlow package will be imported into the Jupyter notebook. And once you have imported the TensorFlow into Jupyter notebook, now we'll verify whether the version of the TensorFlow that we're using is 2.0 or not. So we'll use the print. So we'll print tf dot underscore version underscore underscore. So once you print this line, you will see that we have the latest version, which is 2.0.0. And once you are sure that you are using the version 2.0, so now we'll move ahead and build some tensors. So a tensor is just a fancy name for an n-dimensional array, and you can also think of it as a general representation of a vector in higher dimensions. So we'll start by making a constant tensor, which means that its value cannot be changed later on. So we'll use the tf.constant method. So if you run this particular line here, and if you press shift and tab here, so it will open this documentation where you can check different attributes of this particular method. So the first is your value. The first attribute is the value, or the parameter is the value, where you put the value of your tensor. So here we have passed a string hello, and you can also mention the data type of the value that you're passing, and also the shape that you're passing if it is a multi-dimensional tensor, and it will create a constant tensor for you. So we have passed hello, so it will automatically create a string tensor for us. So once you run this, and we have stored the tensor in hello, and if you check now the type of the tensor, so you will see that it is not a string, it is a tensor object. And before, in TensorFlow 1, if you wanted to print the value of this particular string, you would have to create a session. But in TensorFlow 2.0, our sessions are not valid now. So if you want to just print the value of a tensor, we can directly print it using the tf.print function. So this function will print the value of any string or the tensor that we have built. So if I use tf.print and I pass my tensor to it, so it will print the value that is actually contained in that particular tensor. So now let's create another tensor using tf.constant, which is a constant tensor, and we'll pass the string world to it, and we'll store the tensor in world. And now let's print the world tensor using the tf.print. So now we have two tensors, hello and world. And before, if you wanted to perform any operations on tensors, you would have to create a session, and inside the session you have to add or perform different operations. So now we can directly perform operations on tensors. So we'll perform the addition, we'll concatenate these two strings which are contained in hello and world tensor, and we'll store the result in result, and then we'll print the result. So you can see that our result is hello world. So it means we do not have to create a session in order to perform different operations on these tensors. So now let's move ahead and create a tensor which contains a numeric variable. So we'll pass numeric value as 10, and we'll store the tensor in A, and then we'll create another tensor, constant tensor with value 20. And now we'll perform the addition operation on these tensors without using a session. So once you perform the addition operation, it will display you this particular tensor object. So it will not actually display you the actual value of this particular operation. And here you can see, if you run this operation multiple times, so every time the ID here will be different. different. So the TensorFlow implicitly stores different functions or operations as IDs. So now if you want to print the value of this particular operation on these tensors, so you can use tf.print again. So once you use tf.print and you will pass the operation that you want to perform, so it will directly print you the value of that particular operation performed on these two tensors. So now let's build another tensor using the fill method. So if you run this command first and then you press shift and tab, so this will open this documentation, and this fill command or the fill method will create a tensor which is filled with a scalar value. So you have to pass a value and it will create a tensor with the following dimensions. So here we have passed the dimensions as 5 by 5, so it will create a tensor with 5 rows and 5 columns, which are the dim's argument, and then we have to pass the value. So we want a 5 by 5 tensor which will contain the value 5. And if you want to print this particular tensor, so you can use the tf.print method, so it will print the value of this particular tensor, and you can also print this value as the numpy array. You just have to write the value, the name of your tensor, and then you can use the numpy method. So once you run this, it will represent your tensor, or it will display your tensor as a numpy array. So now let's build another tensor using the constant method. So we'll build a two-dimensional tensor. So it will be a tensor with 2 rows and 2 columns. And once we run this, we'll build a tensor. And now if you want to know how many rows and columns are there in your tensor, and that is the shape of your tensor, so you can use the get shape method. So if you use the get shape method, it will display you the number of rows and the columns present in your tensor. Clearly we can see that we have 2 rows and 2 columns in our tensor. And similarly, if you create this particular tensor which has 2 rows and 1 column, and to get the shape of this tensor, so it will be displayed as 2 rows and 1 column. So now we can also create random numbers using tensors. So we'll create a tensor which contains normal distribution or random numbers from the normal distribution. So we'll use the random.normal method. So in this method we'll pass the dimensions, and then we'll pass our mean and the standard deviation. So if you press shift and tab here, so it will, first of all, the first argument will be your shape, and then your mean of this particular normal distribution and your standard deviation of the normal distribution. We want a 4 by 4 tensor which will contain 4 rows and 4 columns, and then we want the mean to be 0 and the standard deviation should be 1, so it will be a standard normal distribution. So once you run this and you store the tensor in my tensor, and now if you print the value of tensor, you will see that we have 4 rows and 4 columns in this particular tensor, and the numbers are from the standard normal distribution. So now let's discuss what do we mean by eager execution that is implemented in TensorFlow 2.0. So if you talk about TensorFlow 1.0 or 1.x, so it requires you to manually build a syntax tree which is also called the graph using different API calls. And then when you build a graph, then you have to manually compile the graph, and you have to pass the set of input and output tensors in the sessions.run function. But in TensorFlow 2.0, we execute eagerly, which means it executes like a normal Python programming language, that is line by line. So you don't have to create sessions, and your code will be executed line by line. So if you want to know more about the effective changes that have been made to TensorFlow 1 in TensorFlow 2, so you can go to the following link, and if you go to the following link, you will find a whole documentation that discusses different changes that have been made to TensorFlow 1 to migrate to TensorFlow 2. So now let's move ahead, and after performing this, we'll first of all check whether we are running eager execution or not. So in TensorFlow 2, this is the default execution, eager execution, and if you want to enable eager execution in other versions of TensorFlow, so you can use these commands. So first of all, we'll check whether the eager execution is enabled or not. So we'll use the if function here. So we'll pass our tf.executing eagerly, and if this is true, it means we are running eagerly. So if it is true, it will print eager execution is enabled, and then if it is not true, then it will print that you are not running eager execution, and we'll also print how to run and how to enable and disable eager execution. So right now eager execution is enabled, and if you print this code here, and if your eager execution is off, so it means if you want to disable your eager execution, so you can run the following command. So you have to import this particular module from this particular package, and then you can use the disable eager execution function or the method to disable your eager execution. And if your eager execution is already turned off, and if you want to turn it on, so you can use this particular command here. So using this command, you can enable your eager execution, and if your TensorFlow is not updated, so you can use these 2 lines to update your TensorFlow to the latest version, that is 2.0. So now let's move ahead and perform simple operations using TensorFlow 2. So there are some of the common operations that we'll use while using TensorFlow 2. We'll make tensors using constant, tf.constant and tf variable, and then we'll concatenate 2 tensors, and we'll make tensors using zeros and ones, and then we'll also learn how to reshape tensors, and we'll also learn how to cast tensors from one data type to another data type. So we'll start by making a constant tensor. So a constant tensor is a tensor that does not change. So we'll use the tf.constant again, and it is a tensor that has 3 rows and 2 columns. So the shape of this tensor will be 3 and 2, and once you run this command, your tensor will be stored in A. And if you want to print this tensor, there are two methods. So if you want to print the values of this tensor, so you can use the tf.print method and you can pass your tensor value to it. And if you want it as a numpy array, so you can use the .numpy method to print the value of this tensor as a numpy array. This mostly represents the values of the weights of the inputs in our neural network. So we'll use the tf.variable method to create a tensor which is a variable tensor. So we'll create a tensor which has 2 rows and 2 columns, and we'll store the tensor in VA, which is a variable tensor, and then we'll create another constant tensor which has 3 rows and 2 columns. So the shape of the tensor is 3 2, and we'll store the result in B. And then if you want to print B, so you can use tf.print, so it will print your B directly without running any session. So now let's move ahead and perform the concatenation of tensors using the tf.concat. So we'll create a concatenated tensor AB concatenated, and we'll concatenate values from the tensors A and B. So if you write x is equals 1, so the tensors will be concatenated according to the columns. So the new tensor will contain the columns from the two tensors that we have concatenated, that is A and B. And after we concatenate these two values, and if you press shift and tab here, so it will open the documentation, and in the documentation you can see that we have to firstly pass the values of the tensors, and then axis here represents the row or the column fashion. So if the axis value is 1, so our new tensor will have concatenated columns, and if the axis value is 0, so our concatenation will happen according to the rows. And after this we'll print the value of the concatenated tensors. So we'll write this f string. So in Python, this f string, which is started by writing f and then writing your string, so it will contain your Python expressions. So inside the f string, if you want to pass any variable, so you have to write your string, and then using these braces or using these brackets, inside the brackets you have to write the name of your variable. And once you run this command, so your tensors will be printed. So now you can see we have concatenated two tensors, that is A and B, and both tensors were, the A tensor was this particular tensor with 3 rows and 3 columns, and the B tensor was this tensor which is also having 3 rows and 3 columns. And we have concatenated these two tensors column wise. So the first two columns are of tensor A and the second two columns are of tensor B. And now we'll see how to concatenate tensors according to rows. So inside the tf.concat function, you have to just write x is equals 0, and the values are of the tensors A and B. And once you run this code and you print the value of the tensor using the f string, so once you run this code, your tensors will be concatenated according to the rows. So the first 3 rows represent the tensor A, and the second last 3 rows represents the tensor B. So now let's move ahead and make tensors using tf0s and tf1s. So we use tf0s to make tensors that contain zeros of a particular shape, and tf1s to create tensors of containing ones of a particular shape. So we'll use tf0s to contain or to make a tensor which is filled with zeros. And inside the tensor, if you run this particular code and then press shift and tab here, and inside this function you can see we have our shape argument, where you can mention the shape of your tensor. So the first argument will be your row and the second argument will be your column. And you can also mention the data type of your tensor. So here we are creating a zero tensor, a tensor filled with zeros with 2 rows and 4 columns, and the data type of those zeros will be integer 32. So our 32-bit integers will be 2 rows and 4 columns. And once you make this tensor and store the value in tensor, and then you print the value of this particular tensor using the f string here, and since we have printed it as a numpy array using the dot numpy or the numpy method, so our tensor will look like this, which has 2 rows and 4 columns containing zeros. So now let's move ahead and make tensors using tf.ones. So tf.ones are used to make tensors with a particular shape containing ones. So we'll use tf.ones method and we'll pass the shape of our tensor, which is 4 rows and 5 columns here. And then we have also passed the data type of our tensor, which is float 32. So once you print this tensor using the f string, you will see that we have a tensor which contains 4 rows and 5 columns containing the float 32 type of number. So now let's move ahead and use tf.reshape to reshape our tensors. So later on in this course you will see that a lot of times we will have to reshape different tensors so that we can pass those to our neural networks as features. So we'll first of all create a tensor for reshaping. So this tensor is a constant tensor and it contains four rows and 3 columns. And first of all we'll build this tensor, and after making this tensor we'll reshape it. So we can reshape it in the following way. So we'll use the tf.reshape method, and then we have to pass the value of our tensor that we want to reshape. And if you press shift and tab here, so it will open this documentation where you can see the first value is your tensor and then the shape that you want to reshape it into. So firstly our tensor is your this tensor particular, and then the shape that we want to reshape it into is 1 row and 12 columns. Since we have total of 12 elements in our particular tensor, so according to that we would have 1 row and 12 columns. So once you run this code, your tensor will be reshaped, and then now we'll print both the tensors, that is before reshaping and after reshaping, using the f strings. So now here you can see that we have our tensor which was before reshaping, and now this is our tensor which contains 1 row and 12 columns after using the tf.reshape function. So now let's move ahead and use tf.cast method to cast one type of tensor into another type of tensor. So first of all we'll create a tensor which will contain values of 32-bit float type, and then we'll convert into 32-bit integer values. So first of all let's create a tensor using tf.constant, which is a constant tensor. So this tensor contains 4 rows and 3 columns, and all of these numbers are floating point numbers which are 32-bit numbers. Then we'll first use the tf.cast method, and if you press shift and tab here, and the first argument is your tensor that you want to cast, and then your data type of the tensor that you want to cast it into. So we'll cast our tensor, which is tensor here, and then we'll cast it into a variable or a tensor which will contain values of 32-bit integers, and we'll store the result as tensors as int tensor. And once we have this tensor, we can use the f string to print both the tensors, that is before converting and after converting or casting. So we have just removed the decimal numbers, we have not rounded the number. So here you can see the 8.8 is converted to 8 because we have just removed these floating points without actually rounding these numbers. So now let's move forward and perform some linear algebra operations on tensors. So we'll start by first of all transposing a tensor. So we'll first of all create a tensor using tf.constant. So this tensor contains 2 rows and 3 columns with different values. So when we transpose a tensor, we'll convert our rows to columns and columns to rows. So our first row will be converted to first column, and our second row will be converted to second column. So we'll use the tf.transpose method, and we'll pass our tensor value, that is a. So once we print this value using the f string, so we'll get our transposed tensor, that is a, with the first row of the original matrix as, or the first row of the original tensor as the first column, and the second row of the original tensor as the second column. So now let's move ahead and implement matrix multiplication, which we'll use throughout the course, and most of the optimization algorithms also use matrix multiplication. So first of all we'll create 2 tensors, or first level we'll create a matrix and a vector v. So these both are 2 tensors. So our first tensor is a constant tensor that has 2 rows and 2 columns, and our second tensor is a vector which has only 2 rows and only 1 column. So we'll multiply these 2 matrices or these 2 tensors using matrix multiplication, and if you know the rules of the matrix multiplication, so you'll get this particular result. And we'll use tf.matmul function. So we'll pass our 2 tensors, and this order is also very important. So our first tensor is a 2 by 2 and our second tensor is also 2 by 1. So our resulting tensor will be 2 by 1 according to matrix multiplication. So once we print the result, which we have stored in AV using the f string, and we have passed our expression AV inside the f string, so we'll get this particular tensor which has 2 rows and 1 column. That is the result of the matrix multiplication between A and V. And now we'll perform element wise multiplication, and we'll see how they are different. So we'll compare both matrix multiplication and element wise multiplication, and we can see both are different because the rules of matrix multiplication are different from element wise multiplication. So we use the same 2 matrices or the tensors, that is A and V, and we'll use the tf.multiply, and the tf.multiply used to multiply 2 tensors element wise. So we'll store the result in AV, and then we'll print the result using the f string, and our AV is our expression that we have passed inside the f string. So once we print this, we'll get this result which is totally different from what we got for matrix multiplication. This is our element wise multiplication of A and V, and here also the order of these tensors matters the way we pass it into our multiply function or the matmul function. So now let's move ahead and see how to calculate or how to compute the identity matrix of a particular tensor. So identity matrix of a matrix is a matrix which that when multiply with a particular matrix, it will result in the same matrix that we have multiplied it with. So if we have a matrix A and if you multiply through the matrix multiplication an identity matrix of that particular matrix, then we'll get the result as the same matrix A. So here our matrix A, which is a tensor, we have created using the tf.constant, and it has 2 rows and 2 columns. And now we'll calculate the number of rows and the number of columns that we have in our tensor using the shape attribute. So we'll use the a.shape attribute of our tensor, and we'll assign the 2 values, that is 2 which is the number of rows and 2 which is the number of columns, and we'll print it using the f string. And now we know the number of rows and number of columns in our matrix, so now we'll create an identity matrix using the tf.eye method. So in this method we can pass different arguments. So firstly we'll pass the number of rows argument as rows here, which is 2, and then number of columns argument as columns, which is 2, and then we'll pass the data type of our values that will be containing in our identity matrix, that is 32-bit integer, and then we'll store the result in a identity, and then we'll print the value of a identity using the numpy array. So it will be represented as a numpy array, and here you can see we have an identity matrix 1001. So an identity matrix contains 1 on the main diagonal and all other elements are 0. So now let's confirm whether or this is an identity matrix or not. So we'll first of all multiply both the matrices, that is A and the identity matrix of A, and if the resulting matrix is A, then we can say that we have successfully computed the identity matrix for a particular tensor, that is A here. So we'll use the same matmul method. So we'll pass our both tensors, that is A and A identity, and then we'll store the result in AAT, and then we'll print AAT using the f string. So we can see we get the same result, which is the same matrix A or the tensor A that we created above. So now let's move ahead and see how to create a variable in TensorFlow 2.0. So in TensorFlow 1.x, you know that the variables are firstly instantiated, and then if you want to use those variables, you have to instantiate or initialize those variables using the global initializers. So in TensorFlow 2.0, we don't need to initialize variables. So to use the value of a variable in TensorFlow 2.0 graph, we'll simply treat it like a simple tensor without actually initializing using the global initializers. So we'll firstly see how to create variables. So we'll create variables using the tf.variable, and here we have created a variable with tf.0. So a variable is a tensor whose values can be changed, and these mostly represents the weight of the inputs in our neural networks. So we'll first of all create a tensor variable. So if you press shift and tab here, you will get different arguments, and you can check the different arguments that you can use here. So we'll pass the values as a tf.zeros tensor, and here we want to make a 0 tensor which will have 2 elements, with each element having 3 rows and 4 columns, and we'll store the result in my variable. And if you print my variable using the tf.print method, so we'll see we have 2 tensors or 2 0 tensors, with each tensor having 3 rows and 4 columns. So this particular code here represents that we have 2 tensors with each tensor having 3 rows and 4 columns. And now we have different methods that we can use on a variable. So we'll first of all create a variable which will contain a floating point number 0, and then if you want to add anything to our variable, so our variable here is v, and if you want to add 1, so here w is a tensor which is computed based on the value of v. So here w is our new tensor which will be computed based on the value of v. So anytime a variable is used in an expression, it gets automatically converted to a tensor representing its value. So here we have passed 1, so it will be automatically converted to a tensor, and then the value of 1 will be added to the value of v, and then we'll get the result. So our result here should be 1 because our w is v plus 1. So this is unlike TensorFlow 1.x, where you would have to initialize those variables before you actually use them. So here we don't have to initialize, we can just use them as normal tensors. So now let's print both v and w. So we'll write tf.print, and then we'll pass our v and then w. So you can see our v was 0 which we had declared, and then we added 1 to it, so we got 1. Now let's see another command which is assign. So we can assign using the assign method to different tensors or different variables. So well, first of all we'll create a variable tensor which has a value of 0.0 floating point, and then we'll assign it a value of 2 using the assign method. So we'll write v.assign and we'll assign it a value of 2. So now it will be having a value of 2. So now it is a TensorFlow object. So if you want to print it as a numpy array, so you can just write numpy here. So it will be a numpy array of the value will be represented, and you can also use tf.print, so directly the value of this particular tensor will be printed. So now let's see how to use the assign add method to perform the add operation on a tensor variable. So we have created a variable v with the floating point number 0 as its value, and now we'll use the assign add method to add 1 to the variable v. And if you run this, you'll get a variable object which is a TensorFlow variable object, and if you want to print the value of v after the assignment, you can use the tf.print method to print the actual value. So after printing the value, you can see that the value is 1 since we added 1 to our variable v using the assign add method. So now let's see how to use operations in TensorFlow 2.0. So in TensorFlow 1.x we used to define sessions, and inside of the sessions we used to declare our operations using placeholders. But in TensorFlow 2.0 we can just directly declare functions instead of declaring a session and a placeholder. So here we will first of all define an operation which is our add operation. So first of all I'll create a function which is add op with two inputs, that is a and b, and it will return the addition of those two inputs a and b. So now we'll print the sum of 10 and 20 using the add operation. So we'll call the add operation and it will sum the two numbers 10 and 20 and it will return the answer as 30. Now let's build a linear model using the TensorFlow 2.0. So first of all we'll create a variable w and a variable b, which are the parameters of an equation of a line, which is wx plus b. So before we used to create x as a placeholder, now we'll just pass the value of x directly to our function, that is our linear model function. So first of all we'll create two variables. The first variable is w, so the value of this variable is 10 and it is of integer 32-bit type, and the next variable is 5, which is also an integer 32 type, and the value of this variable is assigned to b. So now let's define a function which is a linear model function which will take one argument, that is x. So which once we plug x, we'll get the equation of a line, and the w and the b values are global variables, so we don't have to initialize it now in TensorFlow 2.0. So we'll directly call w and b, we'll directly use it inside this function, and once we define this function which will return us an equation of a line for different values of x. So now we'll call this function using different values of x. So we have passed a list which contains 5, 10, 15 and 20 as 4 numbers as different values of x, and once you run this particular line, so you'll get this particular object. So right now this is just a tensor object, so if you want to get the values as an array, so you can use the numpy method to get the values as a numpy array. So now we have got 4 values here. So if you plug x as 5 in this particular equation, so your y value will be 55, and if you plug x equals 10 in this particular equation with the respective values of w and b as 10 and 5, so your value will be 105. And if you plug 15 as x and w as 10 and b as 5, so you'll get 155. And similarly for 20, you'll get 205 for this particular equation using w and b as 10 and 5.
So let's understand the limitations of a single layer perceptron. So a single layer perceptron can only learn linearly separable problems. So if a non-linearly separable problem is given to a single layer perceptron, then it would not be able to come up with a solution. So we have the AND OR problems and the XOR problem over here. So as it is stated over here, AND OR problems are linearly separable, while an XOR problem is non-linearly separable. So over here, if we look at this AND OR problem, we are actually supposed to divide these two balls into two separate groups. So there are green colored balls and there is a blue colored ball. And we are supposed to divide these into two separate groups using a single layer perceptron. And that is quite easy for a single layer perceptron. So all we have to do is draw a linear line, and it places all of the green balls on the left side of the linear line, and it places the blue colored ball on the right side of the linear line. So this is a case where the single layer perceptron works properly. But then again, let's take the case of an XOR problem. So what happens in an XOR problem is it is non-linearly separable. So we have a blue colored ball over here, and then we have two green colored balls, and then again there is a blue colored ball over here. So If you're asked to separate these 4 balls into 2 groups, then it wouldn't be possible with a single linear line, right? So we can't create 2 separate groups with just a single linear line. So this is where a single layer perceptron fails. And it is very clear over here. So it is just not possible to draw a single line which would be able to separate the green colored balls and the blue colored balls into 2 separate groups. So this is where we'd have to use the help of multi-layer perceptrons. So now again, there are a lot of complex problems out there which cannot be solved with a single layer perceptron, such as image classification. Now what happens in image classification is there are a lot of dimensions and there is a lot of complexity associated with it. And there are a lot of factors which come into the equation. So taking care of all of these parameters, all of these dimensions, that is just not possible with the help of a single layer perceptron. And to find a solution for all of these non-linearly separable problems, we'd have to take the help of a multi-layer perceptron. So before we go ahead and find the solution for this, let's actually go through a use case. So consider that you own an e-commerce firm and you want to increase the traffic on your site. So you decide to give special discounts and you basically start an end season sale. And for this end season sale to work properly, you need to have a very good marketing strategy. And you have different options available with you. So to market this end season sale, you have different platforms such as the Google ads, personal emails, YouTube ads, LinkedIn, and so on. Now, you can either use a single platform to do all of your marketing, or you can use a combination of all of these platforms for your marketing. So as an owner, your priority should be to make as less investment as possible and come up with the maximum profits. And for a human to do all of this analysis, that could be a bit too complex. And if the owner decides to solve it with the help of a single layer perceptron, even that wouldn't be possible. So let's see what can be done over here. So these are all of the different marketing platforms which are available. And each of the marketing platform has its own advantages and disadvantages. Now, all of these factors have to be considered properly before we come up with the optimal solution. And that is just not possible with the help of a single layer perceptron. So again, we have the same thing over here. We have all of these different marketing platforms, and finding out the right permutation combination of all of these marketing platforms to come up with the perfect solution wouldn't be possible with this single layer. What I'm doing is I'm creating 3 numpy arrays, x1, x2 and x3. So x1 would basically be a numpy array which consists of 10 values in the range of 3 to 12. And then we have x2, which is again a numpy array which would again have 10 random values in the range of 9 and 18. And then we have x3, which is another numpy array which again consists of 10 random values in the range of 12 to 20. So we have x1, x2 and x3. And similarly, we'll also create y, which is our actual output, which would be x1 cross 7 plus 5 cross x2 plus 4 cross x3. So we have our input values and we also have the actual output with us. I'll click on run. Right. Now let me just print out the values of x1, x2 and x3. So this is x1, x2 and x3. So x1 is the numpy array which consists of 10 values between 3 and 12. x2 is the numpy array which consists of 10 values between 9 and 18. And x3 is the numpy array which consists of 10 values between 12 and 20. Now let me go ahead and find out the shape of this numpy array. Right. So the shape of this numpy array x1 comes out to be 10. Now let me also have a glance at the output, which is y. So this is my actual output, which is 176, 156, 146 and so on. So I have my actual values with me and I also have the actual output which I want. Now what I'll do is I'm going to reshape this. So I'll use this function y.reshape and I will pass in the shape over here. So here in the original value of y, so this is actually a numpy array where all of the values are present in one single row. But instead of having all of them in one single rows, I want to have them in 10 separate rows. So I'll use the y.reshape function and pass in the parameters, which is shape over here. So shape basically consists of the number of rows and then I just want one column. So shape, comma 1. So this tells me that y comprises of 10 values and all of those values are present in different rows. So I have my inputs and the output value with me. So now these inputs are actually individual values which are x1, x2 and x3. So I'll combine all three of them into a single NumPy array. So I'll use the function np.array and pass in x1, x2 and x3, and I'll store that in capital X and I'll print it out, right? So this becomes my new input. Now again I'll transpose this. So x.t would help me in transposing this NumPy array and I'll store it back to capital X. I'll click on run again. So this NumPy array, which initially had 3 rows and 10 columns, when we transpose it, it becomes a NumPy array with 10 rows and 3 columns, right? So now that we have our inputs and the actual output value, this is where we go ahead and set the learning rate and also initialize the random weight values. So over here, I am setting the learning rate to be 0.0001, and after learning rate, I'd have to initialize the weight values. So I am basically creating a NumPy array with 3 values in it, and those 3 values would be generated randomly. And to generate random values, I'll just use this np.random.randn and I'll pass in 1. So 1 basically means that it'll generate 1 random value. I'll click on run. So this is our weight matrix, which is a basically 3 cross 1 matrix, and it comprises of these values. So now we have the input values, the actual output, the learning rate, and the initial weight values. Now I'll go ahead and start the feed forward propagation. So again, this time the number of epochs is 50. And to get the predicted values, I'd have to use the mat_mul function. So what I'm doing is basically multiplying the input matrix with the weight matrix. So the input matrix is present in capital X and the weight matrix is present in W. And I can multiply these two with the help of np.mat_mul. And I'll store the result in ypred. So again, as I've already stated, the initial predicted values wouldn't be equal to the actual values. And if you have to find out the error in prediction, we'll just subtract ypred from actual y values. So error would be equal to y minus ypred. And since we want the squared error, I'll take the whole square of it. So we've done the forward propagation and we've found out the error in prediction. So now that we have the error in prediction, we'd have to find out the change in error with respect to weights. So now that the forward propagation is done and we've also calculated the error in prediction, this is when we go back. That is, this is where we back propagate and find out the change in error with respect to each of the weights. So we'd have to calculate the change in error with respect to weight 1, change in error with respect to weight 2, and change in error with respect to weight 3. So where we are finding out the change in error with respect to weight 1. So when we take the partial differentiation of this with respect to weight 1, this is what we get. So 2 times of np.mat_mul, and this is what we have over here, y minus ypred, and then we take a transpose of it. And we'd have to multiply this with minus x of 0 or the first input. So we are basically multiplying the change in this with respect to the first input. Similarly, when it comes to the change in error with respect to W2, we'll multiply this with respect to the second input. And when it comes to change in error with respect to W3, we'll multiply it with the third input over here. Now, since we have calculated the gradients with respect to W1, W2 and W3, we can go ahead and update these 3 weights. So the first weight, which is present in W00, so we are basically updating the weight matrix over here. So in the weight matrix, we are supposed to update the first weight value, and to update the weight value, we just have to use the simple gradient descent algorithm. So we'll subtract the old weight value minus the learning rate into the gradient of the error with respect to weight 1. Similarly, when we want to update the second weight, this will be the old weight minus the learning rate into gradient of error with respect to W2. Similarly, for the third weight, it will be the old third weight minus the learning rate into change in error with respect to W3. So now the back propagation is done and also the updation of the weights is done. So what I'll do is I'll keep on adding all of the errors calculated through each of the back propagation iterations, and I'll also print the value of W1, the value of W2, the value of W3 and error at each back propagation or error at each epoch. Now let me print this out and let's see what do we get. So this is value of W1, value of W2, value of W3, and this over here what we have is the error matrix, right? So initially the values predicted had an error of 39,176, 30,733, 26,158 and so on for those 10 values. So this was the case of the first iteration. So in the second iteration, the error, it became 2.62 plus of 0.2. So this you can consider it to be into 10 power 2. So 2.62 into 10 power 2 would be 262. So from 39,176, the error came down to 262. Similarly, over here, the error was 30,733. So from 30,733, the error, it came down to 200, right? So this is how the error, which started at 39,176, it kept on decreasing and it finally reached till 2, right? So in 50 iterations over here, or in 50 epochs, the error has reduced by a very great margin. Now, if we also want to have a look at this in a graphical way, I can just plot the error list which we had obtained through backpropagation. So I'll just plot it out. So we see that as the number of iterations increase, the error decreases significantly. So this would be maybe the third iteration or the fourth iteration. So here, as we saw, the mean error, it was somewhere around 40,000. So from 40,000, it came crashing down to around 10 in the second or the third iteration. So to get the global minimum error and to get the optimal weights value, we'd have to increase the number of epochs a bit more, and that'll give us the best result. Now again, let's understand backpropagation in a better way. Now let's say we have an image of a man over here and we give it as an input to this neural network. So this neural network will process it and then give us an output. But what happens with this neural network in the feed forward propagation mode is, it'll take the input, it'll do a bit of processing and it'll give us an output. But the output tells us that this is a gorilla instead of a smiling man, and that is actually an incorrect output. So to get the right result, we'd have to backpropagate and update all of these weights over here. So we give the input, we feed forward it, and then we get an output, and the output given is actually a gorilla. So what we do is we backpropagate, update all of these weights with all of these links over here, and when we get the optimal set of all of these weights, we'll get the final correct result, which tells us that the input is actually of a smiling human who's wearing glasses. Now let's again take another example. So over here we have the input, which is 0, 1 and 2, and our desired output would be 0, 2 and 4. So let's say initially we give out the weight value to be 3 over here. So when we give out the weight value to be 3, the output which we get is 0 for the first input, 3 for the second input, and 6 for the third input. But then again, these are not our desired outputs. So let's actually find out the error in prediction. So for the first input, the error is actually 0 because the desired output is 0 and the actual output is also 0. For the second input, the desired output is 2 and the output given by the model is 3. So this time the absolute error is 1. And again, for the third input, the desired output is 4 and the output given by the model is 6. So this time the error in prediction is 2. Now, instead of getting the absolute error, we'll actually have to work with the square error. So we'll square this up. So 0 is 0, square of 1 is again 1, and square of 2 becomes 4. Now, what we'll do is, instead of keeping the weight as 3, we'll update the weight and change it to 4. Now, when we update the weight value to 4, we'll get these outputs. So for input 0, the output is 0. For input 1, the output is 4. And for the input 2, the output is 8. So this time the squared errors are very large. This time the squared errors are 0, 4 and 16. So we see that as we increase the weights, the error also increases. So initially when the weight was equal to 3, the squared error was 0, 1 and 4. And then when we updated the weight and increased it to 4, the squared error became 0, 4 and 16. So now what we'll do is, instead of increasing the weight, we'll actually decrease the value of weight. So from 4, we'll bring it down to 2. And when we bring down the weight to 2, these are the final outputs which we get. For input 0, the output is 0. For input 1, the output is 3. And for input 2, the output is 4. So this time we see that the squared errors are 0, 1 and 0. And the squared error has actually decreased. So for this case, what we've seen is, as we increase the weight, the error also increased. And as we decrease the weight, the error also decreased. So this is how the backpropagation algorithm works. Now let's go through this graph to understand backpropagation in a better way. So we have this graph over here and our aim is to minimize the error. And to minimize the error, we can either increase the weight or decrease the weight. So let's take this side of the graph. So if you take this side of the graph, then the tangent which is passing over here, that would make a positive slope with this axis. And since it makes a positive slope with this axis over here, so if we decrease the weight, then the error would decrease. And if we increase the weight, the error would also increase. So similarly, if we take this side over here, then the tangent with this graph over here, that would make a negative slope. And since the tangent would give us a negative slope, that would mean it is inversely proportional. So if we start from this side, then if we increase the weight, then the weight would decrease. But if we decrease the weight, then the weight would increase. So basically the task of the backpropagation algorithm is to reach this global loss minimum. And to reach the global loss minimum, the backpropagation algorithm could either decrease the weight or increase the weight. And if it's on the right side over here, then it has to decrease the weight because it is directly proportional. And if it is on the left side over here, then it has to increase the weight because it is inversely proportional. So this is how the backpropagation algorithm works. So now that we've understood the theory behind backpropagation, let's understand the math behind it. So again, we have this neural network over here and these are the inputs. So for the given inputs 0.05 and 0.10, we'd have to get the outputs 0.01 and 0.99. And to get this result, we'd have to go through two steps. First would be the forward pass, where we'll go from the input layer to the output layer. And the second would be the backward pass, where we'll go from the output layer to the input layer and update all of these initially random weights. So let's just jump into all of the math. Now, in the forward pass, what we have to do is go from the first layer to the second layer. So over here, we just have to multiply all of the weights with the inputs. So W1 is multiplied with I1, W2 is multiplied with I2, and the bias is multiplied with 1. And you then add them up. So after multiplying all of the weights with the corresponding inputs, that is W1 into I1 plus W2 into I2, and then we have bias. So multiplying this bias with 1, we get this. So we have a result of 0.3775. Now this is just a linear value. Now we'd have to pass this linear value inside an activation function. This activation function which you see, this is the sigmoid function. So 1 upon 1 plus e power minus net of h1. So this is the net of h1 which we've calculated. So h1 is the first node in the hidden layer and we've calculated this value and we've passed this inside this sigmoid function. Now this activation function will give us a value of 0.59. So similarly, we'll do the same procedure for h2. We'll calculate the linear value first and then we'll pass that through the sigmoid activation function and then we'll get the value for h1 and h2. So we've done the calculation and then we've got the values for h1 and h2. So net h1 comes out to be 0.3775 and net h2 comes out to be 0.59. So once this is done, we'd have to find out the value for O1 and O2. So this time what we'll do is again multiply the corresponding weights with the corresponding outputs of h1 and h2. So similarly what we'll do is multiply W5 with O1 and W6 with O1 and also multiply the bias with 1. So this is how we can get the output for O1 and we'll do the same procedure for O2 as well. So W5 into output of h1 plus W6 into output of h2 plus B2 into 1. This gives us a value. And again, this value is passed through an activation function, which is basically the sigmoid function. And this gives us a value between 0 and 1, which is 0.75. So we've got the final output for O1. After this, we'd also have to find out the final value for O2. So we'll do the same thing. Multiply the corresponding weights with the corresponding inputs. And we'll pass down that linear equation through the activation function. And we'll get an output value of 0.77. So we've got the value for output of O1 and output of O2. Now we'd have to find out the error in prediction. And this is the formula to calculate the error in prediction. So we'll just subtract the target minus output. So we'll just subtract the output from the target and then square it up. So this was our initial value which was 0.01 and this is the predicted value which is 0.75. So we'll subtract the 0.75 from the 0.01 and then we'll square it up and we'll get a result of 0.27. So this is the error in prediction for the O1 layer. So the error in prediction for O1 node is 0.21. Similarly, we do the same process and get the error in prediction for O2. So the error in prediction for O2 comes out to be 0.0235. Now, to calculate the total error, we'd have to add up the error for O1 and the error for O2. And when we add up these two, we get a total error of 0.29. So now we're done with feed forwarding the input, and then we've predicted the result, and we've also calculated the error in prediction. So this is where the step 2 starts. So step 2 is basically backward propagation, where we start from the output layer and we keep heading back and keep on updating the values. So now we'll see how can we update the weight 5. So as I've already stated, to update the weights, we'd have to find out the change in error with respect to the change in weight. So we'd have to take the partial differentiation of total error with respect to W5. So this can be written as partial differentiation of E total with respect to output O1 into partial differentiation of output O1 with respect to net O1 into partial differentiation of net O1 with respect to W5. That is this entire process. So partial differentiation of E total with respect to output O1, partial differentiation of output O1 with respect to net O1, and partial differentiation of net O1 with respect to W5. And when we do this, we'll get the final result. So we'll start with this formula over here. So we have to find out the partial differentiation of E total with respect to output O1. So E total is basically this value over here, which is basically half into target O1 minus of output O1 whole square plus half into target O2 minus output O2 whole square. So over here, since we are differentiating it with respect to O1, this entire thing would be a constant and this would turn to 0. And when we differentiate this, this would become minus of target O1 minus of output O1. And we'll substitute the values for target O1 and output O1 and we'll get the value of 0.74. So the result for this would be 0.74. And then we'll come to the second term over here, which is partial differentiation of output O1 with respect to net O1. So we know that output O1 is 1 upon 1 plus e power minus net O1. And this is nothing but the sigmoid function. And when you differentiate the sigmoid function, you basically get the same value multiplied by 1 minus same value. So over here, this output O1 after differentiating would become output O1 into 1 minus output O1. So this is 0.75 into 1 minus 0.75 and this gives us a value of 0.18. So we got the value for the first term, which is 0.74. We also got the value for the second term, which is 0.18. And then we'll head on to the third term, which is differentiation of net O1 with respect to W5. And we have net O1 over here. Net O1 is W5 into output H1 plus W6 into output H2 plus B2 into 1. So over here, since we are differentiating this with respect to W5, all of these would be constant and would turn to 0. And when we differentiate this, this would become 1 into output of H1 into 1. So this basically is output of H1 and output of H1 we already know the value, which is basically 0.59. So we get the values for the final 3 terms. And all we have to do is multiply these 3 terms, then we'll get the partial differentiation of E total with respect to W5. So when we multiply these 3 terms, we get a value of 0.08. Now we've got the gradient. After getting the gradient, we have to pass this through the stochastic gradient. After we get the gradient, we'd have to pass this through the gradient descent formula. So this what you see is the gradient descent formula. So this is the new weight, this is the old weight, this n which you see is nothing but the learning rate, and this is the gradient which you've just calculated. So new weight is equal to old weight minus the learning rate into the gradient descent. Since we've already got the gradient descent, which is 0.08, what we'll do is we'll just multiply this gradient with the learning rate, which is 0.5. Now again, this learning rate is an arbitrary value, so you'd have to do the trial and error to get the best optimal value for this. So 0.5 into this, and you will subtract this from the initial weight value of W5. So the initial weight of W5 is 0.4. So when you subtract this value from 0.4, you'll get a value of 0.35. So initially W5 was 0.4 and after back propagating, its weight came down to 0.35. So we'll do the same procedure for the rest of the weights. Now when we apply the same procedure, W6, the new W6 value comes to 0. The new W6 value comes down. The new W6 value comes to 0.40, new W7 value comes to 0.51 and new W8 value comes to 0.56. So we are done through the first pass of backward propagation. After this, we have to go through the second pass and calculate W1, W2, W3 and W4. That is in the first pass of gradient descent, we calculated these 4 values. Now, we'll again have to go through another pass and then we'd have to update these 4 values over here, which are W1, W2, W3 and W4. So this time, if we have to update W1, then we'd have to find out the change in total error with respect to the change in W1. That is, we'd have to get the partial derivative of E total with respect to W1. And this can be represented as partial differentiation of E total with respect to output H1 into partial derivative of out H1 with respect to net H1 into partial derivative of net H1 with respect to W1. So this is how it can be understood. So let's start with the first term over here. So if we take this first term over here, then H1 over here, it contributes to both the output of O1 and O2. And that is why it can be split into 2 parts. So partial derivative of E total with respect to output of H1 becomes partial derivative of EO1 with respect to H1 plus partial derivative of EO2 with respect to out H1, right? So this is what we are doing over here. So if we want to find out the partial derivative of E total with respect to W1, we can get it by doing the partial derivative of E total with respect to out H1, and then we'd have to get the partial derivative of out H1 with respect to net H1, and then we'd have to get the partial derivative of net H1 with respect to W1. Now, when it comes to the first term, E total can be represented as E01 plus E02, and this term over here can be broken down as partial derivative of E01 with respect to out H1 plus partial derivative of E02 with respect to out H1. Right. Now let's understand the math over here. So this is the first term which we have over here. Partial derivative of E total with respect to out H1, and as you already saw, this can be represented as partial derivative of EO1 with respect to H1 plus partial derivative of EO2 with respect to H1. Now with respect to this equation, we'll take the first term. So this first term over here can be represented like this. So partial derivative of EO1 with respect to H1 can be represented as partial derivative of EO1 with respect to net O1 into partial derivative of net O1 with respect to out H1. So these two would be cancelled out and we'll get what is there on the LHS. Now again, we'll take the first term over here, and this first term can again be represented like this. So partial derivative of EO1 with respect to net O1 can be represented as partial derivative of EO1 with respect to out H1 into partial derivative of out H1 with respect to net O1. So these two would be cancelled out and we'll be getting what is there on the LHS. So we have already calculated these two values in the first backward pass. So the value for this would be 0.74 and the value for this would be 0.18. And when we multiply these two, we'll get a value of 0.13. So we've got the value for the first term, which is 0.13. Now we'd have to get the value for the second term. So the second term is partial differentiation of net O1 with respect to out H1. And we already know what net O1 is. So net O1 is W5 into out H1 plus W6 into out H2 plus B2 into 1. And since we want this partial derivative with respect to H1, these two would be constants. And when we differentiate this, we'll just be left with W5. And the value of W5 is 0.40. So the value for this term comes out to be 0.40. So we've calculated both the values for this. So that the value for the first term is 0.13 and the value for the second term is 0.4. And when we multiply these two values, we'll get the partial differentiation of EO1 with respect to out H1, which comes out to 0.055. And if we repeat the same process for EO2 as well, we'll get the partial differentiation of EO2 with respect to out H1, and this comes out to minus 0.019. So we've got partial differentiation of EO1 with respect to out H1 and partial differentiation of EO2 with respect to out H1. And when we add these two up, we'll get a final value of 0.03, and this is nothing but the partial differentiation of E total with respect to out H1. So again, this is not the final result. What we want is partial differentiation of E total with respect to W1. So we've just got the result for the first term. There are two more terms over here. So the second term is partial differentiation of out H1 with respect to net H1 and partial differentiation of net H1 with respect to W1. So let's start with the second term. The second term over here is partial differentiation of out H1 with respect to net H1. And we already know what out H1 is. It is this over here, which is basically the sigmoid function 1 upon 1 plus e power minus net H1. And we know that when we differentiate a sigmoid function, we get the same value into 1 minus the same value. So over here, this becomes output of H1 into 1 minus output of H1. So H1 is 0.59 and into 1 minus 0.59. So this gives us the value for the second term, which is 0.24. And then finally, we have the third term. So third term is partial differentiation of net H1 with respect to W1. And we already know what net H1 is. So net H1 is W1 into I1 plus W3 into I2 plus B1 into 1. And since we are differentiating this with respect to W1, these two terms become 0 and all we are left with is I1 and I1's value is 0.05. So we've got the values for all of the three terms. So the value for the first term or the value for partial differentiation of E total with respect to out H1 is 0.036 and the value for the partial differentiation of out H1 with respect to net H1 is 0.24 and the value for partial differentiation of net H1 with respect to W1 is 0.05. And then finally all we have to do is multiply these three values to get the result for partial differentiation of E total with respect to W1. And that comes to 0.0004. So we've got the gradient with respect to W1. And since we want the new weight for W1, we have to pass this down to the gradient descent formula, which is new weight is equal to old weight minus the learning rate value into the gradient with respect to W1. So over here, the gradient is 0.0004, the learning rate is 0.5, and the initial value of W1 is 0.15. So when we feed in this value over here, W1 becomes 0.1497. And in the same way, we'll update the values for W2, W3 and W4 as well. So this is the entire backpropagation algorithm with which we were able to update all of the weights starting from W1 to W8. So initially when the inputs were 0.05 and 0.1 respectively, and we forward propagated these inputs, we had an error of 0.29. But after applying the backpropagation once, the error came down to 0.29102. So even though we see that the difference is not much, but then again, when we implement this backpropagation algorithm around 10,000 times, the error plummets to around 0.000351. So at this time, when we feed forward 0.05 and 0.1, the output neurons generate 0.015 for the first output and 0.98 for the second output, which are very, very close to the actual outputs. So we see that we keep on back propagating until we find the lowest error and also find out the optimal weights and the optimal bias. So backpropagation is basically used to optimize our neural network. And we have many such optimization algorithms with us. And through all of these examples, the optimization algorithm which we used was the gradient descent algorithm. So let's understand this gradient descent algorithm in a better way. So the gradient descent algorithm basically measures how much the output of a function changes if you change the input a little bit. So for all of the examples which you saw, you can consider the weight to be the input and the error to be the output. So you want to know how much does the error change with respect to a small change in the input. So the higher the gradient, the steeper the slope and faster the model learns. Or in other words, if the change in error is very high when there is just a small change in weight, then this means that the model is learning very quickly. So this is the concept behind gradient descent. So now let's understand how does gradient descent actually work. So this is the formula for gradient descent. B is the new weight, A is the current weight, this what you see is the learning rate, and this is the gradient. So new weight or the next value is equal to current value minus the learning rate multiplied by the gradient. So let's say we have this graph over here, and these are our initial values of weight and bias. So the task of the gradient descent function would be to find the optimal values of W and B and to minimize the error. So let's say we start from somewhere over here and we have a random values of W and B. So let's say there's a ball and that ball keeps on rolling to the bottom of the curve. So the gradient descent algorithm has to make sure that it reaches to this bottom of the curve or the bottom of the hill in the fastest manner and the right direction possible. So restating it, we have random values of W and B, and the task of the gradient descent algorithm would be to find out the optimal values by reducing the error. And the reduction in error is done by going in the right direction of the slope. So let's say if there's a ball which starts from over here, it keeps on rolling down and it has to reach over here, and this value would be nothing but the global minimum. So when it reaches over here, it'll get the global minimum, which is nothing but the lowest error, and this is where we'll find out the optimal values for W and B. Right, now let's understand the importance of learning rate. So when the ball is rolling down the hill, the speed of that ball is determined by the learning rate. So let's say if the learning rate is very high or if it's very large, then what happens is it might overshoot the global minima. So let's say if it starts over here, then from here it will not come over here but it will shoot over here. From here it will come to the left side and from here it will reach over here. So what is happening is since the learning rate is very high, it will never reach the global minimum and it will keep on oscillating between the two walls of this curve. So this is what happens when the learning rate is very high. Now let's understand what happens when the learning rate is small. So when the learning rate is small, let's say if the ball starts from over here, then the speed of the ball to come from over here to the bottom of the hill would be very slow. So it'll start over here, then it'll come over here, then over here, over here, over here, and over here. So from here to here, it'll take eternity. And it'll consume up a lot of resources and a lot of time for this neural network to find the optimal values for the weight. So this is why we have to make sure that the learning rate is neither too big nor too small. So we also have to find out the optimal learning rate to get the optimal values of weight and bias. Now there are other interesting terms when it comes to gradient descent. So you have something known as an epoch. So one epoch is basically when we pass the entire data set forward and backward through the neural network once. So I'm again reiterating it. So when we pass the data set forward and backward through the neural network once, that is known as one epoch. Now when it comes to the neural network, it is very important that the data set is passed through more than one epoch. Because when we pass the data set through the neural network through only one epoch, then it leads to underfitting. Or in other words, it fails to learn all of the features associated with the data. Now, when we keep on feeding this data to the neural network, there'll come a stage where the curve would be the optimum for the data provided. But then again, if we keep on increasing the number of epochs and never stop, what happens is it'll lead to overfitting. So when it leads to overfitting, this would be good for that particular problem, but it is very bad at general problems. So when it is given some other data set, that will fail miserably. So this is why epoch is also important. So we'd also have to find out the right number of epochs for our model to be accurate enough. So after epoch, we have something known as batch size and iterations. So batch size is basically the number of training examples present in a single batch. Now we'll head on to iterations. So iterations is the number of batches needed to complete one epoch. Now let's understand these three terms through an example. So let's say there are 2000 entries in the data. And if we divide these 2000 entries into batches of 500, we'll have 4 batches in total. And it'll take 4 iterations to complete one epoch. So I'm reiterating it. let's say there's a data set which contains 2000 entries or 2000 records in total, and if we divide this data set of 2000 examples into batches of 500, we'd have 4 batches in total. So we'd have to iterate through all of these 4 batches to complete one epoch. Right. So now, as I had already stated during the agenda, the gradient descent comes with a lot of variants. So we have the vanilla gradient descent, which is nothing but the batch gradient descent. And then we have the stochastic gradient descent, and another variation is the mini batch gradient descent. So let's start with the batch gradient descent. So we'll understand all of these variants through this example. So let's say we have a data set which comprises of these 6 images of cars. So let's start with batch gradient descent. So the batch gradient descent algorithm takes all of these images at one go. So it takes all of these 6 images of a car at one go, and it calculates the loss for all of these 6 images at a single time. So it'll take all of these 6 images, it'll backpropagate, and it'll calculate the loss or the error in prediction. Now, once it calculates the loss for each of these 6 cars, then it'll go ahead and update the gradient descent. So it'll actually calculate the average gradient descent with respect to the loss of all of these 6 cars. Now, keeping this in mind, we'll head on to the next variant, which is stochastic gradient descent. So in stochastic gradient descent, what happens is it takes one record at a time, or for this particular example, it takes one image at a time. So the first image is sent to the neural network, it reads the image, it backpropagates, calculates the error, and after calculating the error, it there itself updates the gradient. Now, once it updates the gradient, it reads the second record. Now, after reading the second record, it backpropagates and calculates the error with the updated gradient. And again, it'll update the gradient for this record as well. And then it'll head on to the third record, calculate the loss, update the gradient. Similarly, it'll do that for each of the individual records. So this is what is done in stochastic gradient descent. And then finally, we have the mini batch gradient descent, where the data is read in batches or mini batches. So over here, let's say with respect to this example, the mini batch size is 2. So in the first mini batch, 2 images are sent to this neural network over here. So it backpropagates, calculates the loss, and calculates the average gradient descent for these 2 records. And with the previously found gradient descent, it'll again backpropagate and find out the updated gradient descent. And then it'll head on to the next batch and then update the gradient descent again. So this is what happens with respect to vanilla gradient descent, stochastic gradient descent, and mini batch gradient descent. So now that we've understood the gradient descent algorithm properly, let's understand how can we work better with this gradient descent algorithm. So to find out that optimal value of weight and bias, we can plot the cost versus time graph. So time is plotted on the x-axis and cost is plotted on the y-axis. And the aim of the gradient descent algorithm should be to reduce the cost as the time progresses. So we'll most probably get a curve which will start at the far end of the y-axis and it will come down to the bottom of the y-axis and then it will stay constant. So basically as time progresses, the cost has to decrease, or in other words, the error has to decrease. The next step when working with gradient descent algorithms would be to modify the learning rates. So again, we are never sure what learning rate would work with what data. So that is why we'd have to start with small learning rates. So we'll start with these small learning rates which are specified over here, and then we can go ahead and randomly play with these learning rates so that we get the optimal value. And we should also make sure that we rescale the inputs. So sometimes it happens that the data which we feed into the neural network is distorted or it is skewed. Now, when this happens, this neural network will not work properly. So that is why we'd have to scale this data in either the range of 0 to 1 or minus to 1 so that we get the optimal weight values and we can reduce the error as soon as possible. Right, so that was gradient descent. Now, apart from the gradient descent algorithm, we also have something known as the Adam optimization algorithm. So the Adam optimization algorithm basically stands for adaptive movement estimation, and it is a combination of gradient descent with momentum and RMS prop algorithms. Now the problem with gradient descent algorithm is, let's say if we take the example of that curve and we roll the ball down through the hill. Now what happens is if there are a lot of crests and troughs in that hill, then there'll be oscillation along the vertical axis as well as the horizontal axis. Now, when there is oscillation along the vertical axis, this will reduce the speed of the ball and this will also increase the time of reaching the global minimum. So that is why when we add momentum along with the gradient descent algorithm, the speed of reaching the global minimum would become faster. And also another change when it comes to the Adam optimization algorithm is the learning rate is variable. So the learning rate is not constant. So as and when the momentum changes, the learning rate also changes to adapt with that momentum. So a feed-forward neural network just contains multiple nodes which are arranged in multiple layers. And simply put, we have an input layer, a hidden layer, and the output layer over here. And a feed-forward neural network can contain two kinds of nodes. So there could be a mono layer which does not contain any hidden layers. And then we have our multi-layer perceptrons where there is one input layer and there exists at least one hidden layer and there is one output layer. So all of the inputs are taken through the input layer. The processing is done in the hidden layer and the final output is received through the output layer. Alright, so now let's actually discuss the solution to our e-commerce firm problem with the help of multi-layer perceptron. So we have this input layer, all of the inputs are sent over here and the processing is done over here in these hidden layers. Now each of these hidden layers does a part of the processing work. So let's say stage 1 of the processing is done in the first hidden layer. Stage 2 of the processing is done in the second hidden layer. Stage 3 of the processing is done in the third hidden layer and so on. And then we'll have a final linear equation. Now, this final linear equation is sent through an activation function and that activation function converts this linear equation into a non-linear solution and sends that out to the output layer. Right. So, over here in this multi-layer perceptron over here, we have these inputs, we have this hidden layer and we have the output layer over here. So let's start off with the input layer. So in the input layer, we have two external inputs, x1 and x2. And along with these external inputs, we also have a bias. Now the bias is generally 1. Now these inputs are sent to the hidden layer. And these links between the input layer and the hidden layer, these links are basically associated with weights. Now, once these inputs are sent to the hidden layer, all of the processing is done over here. So, what happens in the hidden layer is the inputs are multiplied with these weights associated. So, x1 is multiplied with w1, x2 is multiplied with w2, and 1 over here or the bias over here is multiplied with the weight w0. So, in the hidden layer, we get this equation w0 into 1 plus w1 into x1 plus w2 into x2. And this is our linear equation which we want. But then again, we'd have to convert this linear equation into a non-linear solution. And to do that, we'd require an activation function. So we'll basically pass this linear equation through an activation function and then we'll get a result. And that result is finally sent out through the output layer over here. Now, keeping these points in mind of how an input layer works, of how the hidden layer works, and how the output layer works, let's solve our use case. Alright. So again, we have the input layer, the hidden layer, and the output layer. So over here, all of the different marketing platforms which we have, they are sent as the individual inputs. So marketing via emails, that would be our first input. Marketing via referral programs would be a second input. Paid ads is a third input. And then we have direct marketing, social media marketing, and then we also have the organic search. So all of these platforms together combined become our inputs. And these inputs are sent to the hidden layer. And all of these links which you see over here, all of these links have certain weights associated with them. And those weights are multiplied with the corresponding weights over here and we get a linear equation. And that linear equation is passed through an activation function and that provides us a solution which is finally sent out through the output layer. And that is how we'll get the result where we'll know what combination of all of these marketing platforms would be the best idea for us. Right. Now let's actually go through another use case to understand multi-layer perceptrons better. So we have this data set over here which comprises of these columns. So this column tells us the number of hours studied by the student. This column tells us the midterm marks scored by the student. And this column tells us whether the student would pass in the exam or not. So one over here tells us that the student has passed in the exam. And 0 over here tells us that the student has failed in the exam. So these two would be our inputs and this would be our final result. Now, suppose we want to predict whether a student studying 25 hours and having 70 marks in the exam will pass the final term or not. So, the input for number of hours studied is 25 and the input for number of marks obtained is 70. And we'd have to find out, or we'd have to predict the final result. So, these are the three parameters which we have over here. And this is basically a binary classification problem. So, it's either 1 or 0. And we'll solve this binary classification problem through a multi-layer perceptron. Right. Now we've understood what feed-forward propagation is. So in feed-forward propagation, we start from the input layer and these inputs are sent to the hidden layer where all of the processing is done. And that processed output is finally sent out through the output layer. But then again, that wouldn't be our final solution. Now to get the final solution, the multi-layer perceptron uses something known as the backpropagation algorithm. And using this backpropagation algorithm, it will come out with the optimal solution. So we'll understand about backpropagation in the coming slides. Right. So coming to a use case, we have the input layer, the hidden layer and the output layer, and these are our inputs. So number of hours studied by the student are 35 and the marks scored by the student are 67. And these are given as the inputs to the input layer, and there is also a bias over here. So these are the initial random weights which are W1, W2 and W3. Now what happens in the forward propagation is we have predicted, and the prediction for this node over here, it comes out to be 0.4, and the prediction for this node over here, it comes out to be 0.6. But the actual results are different. So the actual result for this output is 1 and the actual result for this output is 0. So there's a difference of 0.6 and there's a difference of 0.4 over here. So there is an error in prediction. And normally for the final output layer, we'll be using the softmax function as the activation function. So the softmax function basically gives us probabilities, and when you add up all of those probabilities, the sum ends up to be 1. So as over here, we see that this probability is 0.4 and this probability is 0.6. And when you add these two up, you get a total probability of 1. And to get this probability in this way, we'll have to use the softmax activation function. And we have the same thing over here. So these are the inputs, number of hours studied and the midterm marks. So the number of hours studied are 35 and the midterm marks are 67. Now, these inputs are sent to the hidden layer where the processing is done. So W2 is multiplied with 35 and W3 is multiplied with 67, and then W1 is also multiplied with the bias, which is 1. So in total, the linear equation becomes 1 into W1 plus 35 into W2 plus 67 into W3. And this linear equation is passed through an activation function. Now, once this processing is done and it is sent to the activation function, we'll get an output, and that output is sent through the output layer. So again, as we see over here, the probability of passing is given out as 0.4 and the probability of failing is given as 0.6. But in actuality, this is wrong. So the probability of passing is 1 and the probability of failing is 0. So there's an error of 0.6 for the first output node and there's an error of 0.4 for the second output node. Now, this has happened because the weights and the bias were initially randomly assigned. So when you give in random weights, you'll also get a random result. So to correct this, we'd have to go back and optimize these weights and bias. So this is where backpropagation comes in. So what we'll do is, once we get the errors over here, we will go back and using an optimization algorithm, we'll update these weights. So we'd have to update W1, W2 and W3. And when we get the optimal weights for W1, W2 and W3, we'll get the optimal result, which would be 1 for the first node and 0 for the second node. And this is how the backpropagation algorithm works. So what we'll do is, we'll find out the change in error with respect to the change in weight. So we'd have to find out the change in Y with respect to the change in W4, W5 and W6. And when we get that, we will go back, that is, we'll backpropagate and then we'll update the weights for W4, W5 and W6. That is how we'll get the optimal weights. So once the backpropagation is done and we've updated these weights W4, W5 and W6, we see that the result has also changed. So we see that after using the backpropagation algorithm, the probability of pass, that is the probability for the first node, has changed to 0.8. And the probability of failing, or the probability for the second node, has changed to 0.2. And this time, the error in prediction for the first node is 0.2. And similarly, the error in prediction for the second node is also 0.2. So after backpropagating and updating the weights, we find out that the error has reduced. So this is how backpropagation works to optimize the weights. So I'll start off by loading the required packages. We would need NumPy, Matplotlib and Pandas. So I'll import NumPy as NP, I'll import the Matplotlib package as PLT, and I'll import Pandas as PD. I'll click on run. So let's say there is a hypothetical neural network, and to that hypothetical neural network I'm giving two inputs. The value of the first input, which is x1, is 2, and the value of the second input, which is x2, is 5. And for these two inputs, I would want the output value, which is y, to be equal to 31. So I'm basically initializing the values over here. I'll click on run again, and this is where I'll do all of the backpropagation and gradient descent work. So starting off, I'll give in the value for learning rate. So I'll set the learning rate to be equal to 0.01. So after learning rate, I'd have to assign some random weight values. So I'll have W1 and I'll assign it a random weight value of 3. And then I have W2 and I'll again assign it a random value of 7. So now through backpropagation, my aim would be to find those optimal values of W1 and W2 which would give me the correct value of y, which is 31. So what I've done is, in this for loop, I've basically taken 50 epochs. That is, I will pass in these inputs through the neural network 50 times. And this is the forward pass over here, where I'll go ahead and calculate the error in prediction. So that is basically W1 into X1 plus W2 into X2. So I've passed these inputs into the input layer. Now in the input layer, what is happening is the weights are multiplied with the inputs. So W1 into X1 plus W2 into X2. And I'm storing that into Y predicted. Now we obviously know that the predicted values would not be equal to the actual values in the first step itself. Then I'll go ahead and calculate the error in prediction. So error in prediction would be y, which is this value over here, minus y pred, which is basically over here. So y minus y pred, and I'll square this. So I need the squared error. So once I calculate the error, this is when I'll backpropagate and find out the change in error with respect to individual weights. So initially I want the change in error with respect to weight 1. So when I differentiate this, this becomes 2 times of y minus y pred, and partial differentiation, since this is with respect to W1, this would be a constant, this would become 0, and then this will become minus x1. Similarly, when I partially differentiate this with respect to W2, I get 2 times of y minus y pred into x2 over here. So I've backpropagated and I've got the partial differentiation of error with respect to W1 and W2. Now after this is done, I'd have to use the gradient descent formula and update the weight values. So the new value of W1 would be W1 minus learning rate into the gradient with respect to W1. Similarly, new value of W2 would be old value of W2 minus learning rate into differentiation of error with respect to W2. Now finally, I'll print out W1, W2 and the error. So I'll run this. So let's see what is happening over here. So initial value of W1 is 2.6, initial value of W2 is 6.2, and the error in prediction is 100. So in second iteration, the error comes down to 17. In the third iteration, the error comes down to 3. So we see that we are going in the right direction and the error falls down very, very quickly. So after around 50 iterations, the error is 0. Now, since the error is 0, let me find out the weight values now. So initially the weight values were 2.6 and 6.2. Now finally we have the weight values to be 2.3 and 5.27. And when we pass in these weight values into this formula, we get a value of 31.0, which is same as this actual output value. So the actual output value and the predicted output value, both of them are same. So initially we started with an error of 100. Now we kept on backpropagating 50 times and we reduced this 100 to 0 and we got the final correct value. So there are a lot of deep learning frameworks available today. So now my question to you guys would be, why should we use Keras out of all of these deep learning libraries? Well, let's understand. So the number one reason to use Keras would be it prioritizes developer experience. So Keras is a framework which is developed for humans and not machines. That is, it is very easy to code with Keras. You just have to keep on adding layers which you can invoke with functions, and you can keep on building neural networks. So it is that easy to work with Keras. And then Keras is also broadly adopted in the industry and also among the research community. So all of the PhD scientists over there and all of the data scientists, their most widely preferred deep learning framework is Keras. And the next reason would be it is very easy to turn all of these Keras models into end-to-end products. So let's say if you develop a simple prototype with Keras, and if you want to launch it on some platform, then you can easily do it. So you build a model and then you can easily launch it on, let's say, Android, iOS, or any other operating system as an end-to-end product. And Keras also supports multiple backend engines and does not lock you into one ecosystem. Now, what do I exactly mean when I say that Keras supports multiple backend engines? Well, Keras is basically a high-level API, and this high-level API can run on a lot of low-level APIs such as TensorFlow, CNTK, and Theano. So now Keras is what works at the front end, and at the back end you have either TensorFlow, Theano, or CNTK running. Right. Now Keras also has a strong multi-GPU support. So when I say Keras has a strong multi-GPU support, what I mean is you can basically divide the data, or you can basically train the data on multiple GPUs. So let's say you have an input data which comprises of 100 records and you divide into 5 mini batches. Now you can train these each individual mini batches on separate GPUs. So let's say you have a model and you have the input data. Now you'll be making copies of this input data, and each individual copy would run on each single GPU. And each of that GPU would give you an individual result which is aggregated, and you'll get the final result. So this basically speeds up the model building process. And Keras development is also backed by all of the major companies out there such as Google, Amazon, and Nvidia. Right. So now that we've understood why should we use Keras, let's actually understand what is Keras. So as I've already told you guys, Keras is basically a high-level API and it is written in Python. And this high-level API can run on top of Theano, TensorFlow, or CNTK. And it is very easy to work with Keras. So you have individual modules and you can invoke each of these individual modules to keep adding layers on the neural network. So now that we understand what is Keras, now let's have a look at the different models in Keras. So there are basically two types of models available in Keras, which are sequential model and functional model. So let's start with the sequential model. So simply put, sequential model is just a linear stack of layers. So you have one layer, on top of that one layer you add another layer, on top of the second layer you add the third layer, on top of the third layer you add the fourth layer. So it is basically a sequence of layers. So as we see over here, this input layer would be our first layer, and on top of this input layer we'll add the first hidden layer, and on top of this first hidden layer we'll add the second hidden layer, and finally on top of the second hidden layer we'll add the output layer. So simply put, a sequential model is just a linear stack of layers which processes the data and gives out the final output through the output layer. Right, and this is how we can invoke a sequential model through Keras. So first we'd have to import sequential from keras.models, and then we'd have to import whatever layers that we require. So the first step in creating a sequential model would be to create an instance of this. So we have to use the sequential method and we'll create an instance of it. So now that we've created a model, so with this model we can keep on adding layers. So what we are basically doing is, for this instance, I am adding the first layer. So this first layer is basically a dense layer and it comprises of 32 nodes, and the dimension of the input which this first layer takes is 784. And we are also adding an activation function to this first layer. So it is as simple as that. First, you create a model, and then whatever layers you want to add, you can just add it with the help of the add method. So this is how we can create sequential models in Keras. Now we'll head on to the second type of models, which are functional models. So functional models help us to create complex models. Now, the problem with sequential models is you can give inputs only at the beginning stage over here. So let's say if I want to add new inputs for the second layer, that wouldn't be possible. So once, if you give the inputs, you cannot add anything else in between. So this is where functional models differ. So in functional models, it is not necessary to follow the same sequence. So when it comes to functional model, any layer can be connected to any other layer. And these three steps which you see, these are the three steps which have to be followed to create a functional model. So we start off by defining the input. And once we define the input, we start off by building a set of layers. And these layers can be connected anyway. So I can connect the first layer with the fourth layer or the second layer with the 10th layer. So I start off by defining the inputs and then I'll create the layers and then I'll connect those layers. Now, finally, I will build the model. So these are the three steps involved. First, define the input. Second, build the layers and connect the layers. And then finally, build the model. Right. So let's understand each of these steps properly. So when it comes to a sequential model, we actually have to create and define a standalone input layer that specifies the shape of the input data. So as you see over here, we are importing input method. So from keras.layers, we are importing input and we are defining the shape of the input data. And this is extremely important when it comes to functional models. So first, we have to start off by creating the input layer. And once we create the input layer, we can keep on adding other layers. So as we see over here, first we import input method and after that we are importing the next layer, which is basically a dense layer. So as we see over here, first we create the input layer using the input method and the shape of the input is 2 and I'm storing it in visible. After that, I'll add another layer. So this is basically a dense layer. Now, this dense layer has two nodes in it and it is connected with the visible layer over here, right? So we give out the name of the previous layer after we create the first layer over here. Or in other words, layers in functional model are basically connected pairwise. So this is the dense layer and this dense layer is connected with the first input layer which is visible. Right, so we are done with the first two steps. So first we created the input layer and then we connected the rest of the layers. Now after that we have to create the model. So defining the model is extremely simple. So first we'd have to import the model method from keras.models and using this model method all we have to do is pass in the input and the outputs. So as we have already seen this before, input is the visible layer and output is the hidden layer. So we are passing these two layers in this method and we are storing this in the model instance. So this is how we can create a functional model. And Keras already has a number of predefined layers. So these are some of the predefined layers listed over here. So Keras can have core layers, convolutional layers, pooling layers, recurrent layers, noise layers, embedding layers, and so on. Right. So now that we've understood the different models available in Keras, now let's understand some problems when we are building the model on top of input data. So the aim of model building should be to gain the maximum accuracy. But then again, it is not that easy to build that perfect model. Many a times what happens is our model is not able to learn the right amount of data. So let's take this case over here. So let's say we build a neural network model on top of this data. And our aim is to classify this data into two classes. So the first class would be this cross and the second class is the circles over here. Now the problem with this model is it has not learned all of the features of the data properly. And since it has not learned all of the features of the data properly, the misclassification over here is quite high. So these three circles, which should actually be circles, have been classified as cross. And these crosses which you see, they have been misclassified as circles. And this misclassification is due to the underfitting of the model. So I again restate it. So underfitting of the model basically means that it is not able to learn all of the features of the data properly. And when it doesn't learn all of the features of the data properly, it is not able to predict or it is not able to classify the problem in a correct way. Or it doesn't give us the perfect accuracy. So let's say if this model is built on the train set, then the train set accuracy would be somewhere around 65% and the test set accuracy would be somewhere around 63%, which is not really that good, right? So this is basically the problem with underfitting. Now, instead of drawing a straight line, what if I make the model a bit more complicated? So what I'll do is I'll build a polynomial curve over here. So this is a complicated model. So this complicated model is better than this model over here. So this model gives just about the right fit. So over here, all of the circles have been classified correctly as circles, and just these two crosses have been misclassified as circles. So let's say this gives an accuracy of around 95% on the trained data and an accuracy of around 93% on the test data, which is actually good enough. Now, what if I get over enthusiastic and build a very complex model with lot of polynomial variables in it? So this would give me a curve something like this. So over here, all of the crosses have been classified into one pool and all of the circles have been classified into another pool. So this basically gives us 100% accuracy on top of the train set. But the problem is it fails miserably on the test set. So the problem actually is that it fails to generalize. So when it is given the train set, it learns all of the features of this train set perfectly. And when it comes to the test set, it has not seen the test set at all. And that is why it fails to perform properly on the test set. So when it comes to the train set, it gives out 100% accuracy. And when it comes to the test set, it might give only around 75% or around 80% accuracy. So that is why underfitting and overfitting should be avoided. And we need to find that appropriate fitting or just the right fitting to get that ideal accuracy on top of the test set. Right, so this graph over here explains this in a better way. So we have error on the y-axis and model complexity on the x-axis. As we see over here, as we keep on increasing the model complexity, the error, it decreases for the training set. But what happens with the test set is, as we increase the complexity, the error first decreases, but then again, the error increases as we keep on increasing the model complexity. Right? So to get that perfect accuracy on top of the test set, we need to find out that optimal model complexity. Only when we find out that optimal model complexity, that is when we'll get the maximum accuracy. Right. So now that we've understood why overfitting is harmful for a model, let's understand the solution to it. So the solution to overfitting is basically regularization. So there are some regularization techniques which help to reduce overfitting. So let's actually take this example over here. So here we see that we've built a very complex model and it learns all of the training data perfectly. But then again, since it learns all of the training data perfectly, this leads to overfitting. Now, the solution to this would be regularization. So when we apply a regularization technique on top of this data, what happens is it penalizes the weight matrices. So when it penalizes the weight matrices, so the values of those weight matrices and bias matrices would change a bit, and this would lead to a less complicated curve. Now also we need to make sure that we give the appropriate value for the regularization coefficient. So if we keep the regularization coefficient to be very high, then what might happen is some of the weight matrices would become 0. And when some of the weight matrices become 0, it would basically lead to a model which is underfitting the data. Right? So again, when we are applying this regularization technique or when we are tuning this regularization coefficient, we have to make sure that we don't alter the weights too much. And if we alter the weights too much, then we might end up actually underfitting the model. And that is something we have to avoid. So that is why we have to find out that right value of regularization coefficient which would give us this appropriate fitting. So we don't want a model which is too complex or too simple. We just want that right fitted model which is able to give us the perfect accuracy on top of the train set as well as the test set. Right, now let's actually see some regularization techniques. So one regularization technique could be to add dropouts in our neural network model. So now the question in your head would be, what exactly does a dropout do? The dropout basically means that we randomly remove or cancel some nodes during each iteration. So as we see over here, in the first layer, these two have been dropped out or these two have been removed. Similarly, in the second layer, these three have been removed, and in the third layer, these two have been removed. So this again is an arbitrary choice and we can give any random value to each of these layers. So now that we know what exactly dropouts are, let's understand how they are helpful. So when we cancel out these nodes during every iteration, they do not memorize the data. And when they don't memorize the data, this actually in turn helps in not to overfit the data. So let's actually understand this through an example. So let's say we have this training data and we are building this model on top of the training data, and this training data goes through 3 epochs or 3 iterations. So in the first iteration, in this layer, these 2 are cancelled out. In this layer, these 3 are cancelled out, and in the third layer, these 2 are cancelled out. Now, this is only with respect to the first iteration. Now, in the second iteration, again, a random set of 2 nodes would be cancelled out. And it's not necessary that these would be those 2 nodes. So those 2 nodes could be either this one and this one, or this one and this one. So it could be any random combination of 2 nodes which are cancelled out from this first layer. Similarly, again, from this second layer, a random combination of 3 nodes is cancelled out. Again, in this third layer, a random combination of 2 nodes is cancelled out. Again, we'll come to the third iteration. Again, the same thing happens in the third iteration. So basically, adding a dropout layer works as an ensemble model. So every iteration gives slightly different model. So in the first iteration, we have different set of nodes which are giving the output. In the second iteration, we have another set of nodes which are giving the output. Similarly, in the third iteration, we have totally different set of nodes which are giving the output, right? So a dropout layer basically works as ensemble models through each iteration. So we can basically set a probability of number of nodes to be dropped out. So over here p is equal to 0.5. So this means that the dropout percentage would be 50%. That is, we'll be keeping 2 nodes and we'll be removing 2 nodes. And it's extremely easy to add dropouts with Keras. So first we'd have to import the dropout method from keras.layers.code. So once we do that, we'll build a model, and in this model we are adding a layer over here. Now for this layer, for this dense layer over here, we are adding a dropout, and the probability of the dropout we are setting it to be 0.25. So it's as simple as that. So all we have to do is use this dropout method and set in the probability of dropout. So adding a dropout layer was one regularization technique. Now we also have another regularization technique, which is data augmentation. So the simplest way to reduce overfitting is to increase the size of the training data. Now, how can we increase the size of the training data? Well, we can basically modify the data to increase the size of it. So let's say we are dealing with images or images of these numbers over here. Now in this case, what we can do is we can augment the data. So let's say I have the input data, which is basically image of the number 2. Now if I want to create a duplicate of this image, what I can do is I can add some sort of transformation on top of it. Let's say the initial image which had the number 2 was over here at the center. So instead of keeping it at the center, what I'll do is I'll move it up. Similarly, let's say if I had the number 3 over here in the center, I'll move it down. Similarly, over here, the number 3, I'm pushing it to the right. And not just moving them to the top, bottom, left. We can also flip the image. We can also scale the image. So let's say this is my input image 7. So instead of keeping it like this, what I'll do is I'll flip it inverted like this. So I'll flip it and it'll be inverted. And also I can scale it up, or in other words, I can also increase or decrease its size. So these are different transformations which I can apply on top of the input data so that I can create more records, or records which are similar to the original records. So let's say if my input data consists of images of the first 100 natural numbers. Now if I want 1000 records instead of 100 records, all I have to do is add some sort of transformations on those original records and have records which are pretty much similar to the original records. So this is how we can augment the data. Now, what is the importance of data augmentation? Well, when we have more data, obviously it'll be difficult for the model to learn all of the features of it. So when we have less training data, then it is very easy for the model to overfit it. And when we have a lot of data, the model will obviously take a lot of time to learn all the features, and it is difficult for the model to overfit it. So this is how data augmentation works. And when it comes to Keras, we can perform all of these data augmentation strategies using the image data generator method. So we'll have to import this image data generator from keras.preprocessing.image, and it has a big list of arguments, such as over here we are setting the horizontal flip to be equal to true. So MNIST dataset comprises of handwritten images of numbers from 0 to 9. So this is basically a classification problem. So we take in the input data and we'd have to classify them belonging to this particular number. So let's say if I take in the image of number 1, then I have to classify to which of the numbers starting from 0 to 9 does it belong to. So this is basically the data set which we are going to working with. So we'll start off by importing all of the packages that we need. So from Keras, we'll import models, and we'd require the dropout layer as well as the dense layer. And we have to convert some of the values in the data set to categorical. So we'll be doing one hot encoding, and to do one hot encoding, we'll be importing the two categorical method from keras.utils. And as we are working on top of the MNIST dataset, we'd have to import this from keras.datasets. And we'll also be visualizing how the model works. So to visualize that, we'll be importing model 2 dot from keras.utils.wisutils. And we'll also be importing svg from ipython.display. So let me run this. Now I'll also import numpy. After that, I'll import the live loss plot. So live loss plot helps us to have a glance at the live training of the model. So we can actually visualize how the error is decreasing and how the accuracy is increasing for each of the epoch. So for that purpose, we'll be importing the live loss plot. And there are some initial variables which we are creating. So we'll set the number of rows to be 28, number of columns to be 28, the number of classes to be 10, the batch size to be 128, and the number of epochs to be 10. And then we'll go ahead and create a simple method which we can call again and again. So this method takes in 4 parameters: xtrain, ytrain, xtest, and ytest. So xtrain basically contains the train images, ytrain contains the train labels, xtest contains the test images, and ytest contains the test labels. And in this function, we are basically printing all of these things. So xtrain.shape, that is, we are basically printing out the shape of the training set images. After that, we'll print out the shape of the labels from the train set. And then we'll print out the shape of the images of the test set. And then we'll print out the shape of the labels of the test set. And finally, we'll just print out the train labels and the test labels. So I'll click on run. Right. So we've created the method. Now I will load up the data from MNIST dataset, and I'll store all of that data inside xtrain, ytrain, xtest, and ytest, right? And then I will pass in these 4 values into this method which I've just created. So I'm reiterating it. From the MNIST dataset, I'm loading all of the data, and I'm storing that data in xtrain, ytrain, xtest, and ytest, and I'll pass in these 4 values into this method which I've just created. So I'll click on run. Right. So this method basically gives me these things. So we see that the training images shape is 60,000, 28 cross 28, and the labels is 60,000. That is, this basically means that there are 60,000 entries in the training set, and this is basically the size of each image, which is 28 cross 28. And then again, this is the test images. So the shape is 10,000, 28, 28. This means that there are 10,000 images in the test set, and the shape of these images is 28 cross 28. And these are the train labels and the test labels. So these are basically labelings of all of the images. So the first image in the training set is of the number 5. The second image in the training set is of the number 0. Similarly, the third image in the training set is of the number 4. So you basically have to build a model on top of the train set so that it learns all of the features properly, and then we'll check for its accuracy on top of the test set. So before we go ahead and build the model, we actually have to reshape it. Now the train image shape, it cannot be 28, 28. So it has to be of a single dimension. So what we'll do is, we'll multiply this. So we have already stored the value of num rows and num calls over here. So num rows is 28 and num calls is 28. So this basically means that number of rows are 28 and number of columns are 28. And we'll multiply this, and we'll convert this 2-dimensional data into a single dimensional data. So we are basically reshaping this training data. Similarly, we'll take in this test data, which is of the shape 28, 28. And again, we'll convert this 2-dimensional data into a single dimensional data by multiplying those two. So over here, I am passing this xtest.shape, and I am reshaping this with just 1 dimension. So it'll be num rows into num calls, which is basically 28 cross 28. Right, so I've reshaped the image data. Now similarly, I'd have to reshape the labels as well, or in other words, I'd have to perform one hot encoding on top of this. So I just cannot have these values 5, 0, 4 individually. So what I'll do is, if there is 5, I will do one hot encoding and represent it as a numpy array of 10 values. So I am taking this y train and I am encoding it into categorical values. So I am passing the original y train value and the number of classes over here I've set it to be 10. So I'll just pass in the parameter which is num classes over here. Similarly, I'll take in y test and I will pass this inside this to categorical method and I'll set the num classes again. So this basically gives in 10 classes. I'll click run now. Now again I will pass in all of these modified data. So xtrain, ytrain, xtest, ytest, all of these have been modified. I'll pass these inside data summary method and let's see how these have been changed. Right, so initially train images shape was 60,028 and that has been changed to 60,784. Similarly, the train label shape was 60,000 and I've changed that to 60,010 and these have been changed like this. And also for the labels we have performed one hot encoding. So over here, if we have a glance at these test labels, so this is 7, 2 and 1, right? So over here 7 has been represented like this. 2 has been represented like this and 1 has been represented like this. So this 1 represents the place of that value. So if you have 1 at the 7th position, right? So now we have our data ready. And since we have our data ready, we can go ahead and build a sequential model. So using this instance which I've created models, I will call in the sequential method. So models.sequential. So I'll start off by creating an instance of a sequential model. So I'll call models.sequential and I'll store that in this model object. So now that I've created my model, I can finally go ahead and add all of the layers. So what I'll do is I'll add the first layer. So in this first layer, this is nothing but a dense layer. So this is a densely connected layer and this layer has 512 nodes and the activation function which I'm using is relu. And since this is the first layer, it needs to have the input shape. So input shape is nothing but number of rows into number of columns. So this basically comes to around 784. So this is the first layer and after the first layer, we are adding a dropout with a probability of 0.5. After that, we'll add the second layer and the second dense layer has 256 nodes in it and again the activation function is relu. And this time the dropout probability is 0.25. And then we finally have the output layer and the output layer comprises of 10 nodes. And we have 10 nodes because we have 10 classes in total, or these 10 classes represent the numbers from 0 to 9. So we basically have to classify whether this is an image corresponding to number 0, number 1, number 2 and so on. And the activation function which we've used for the final output layer is softmax. So softmax function basically gives us probabilities for each of these nodes in the output layer. And when you add up all of these probabilities, it comes up to 1. Right, so I'll run this now. So we have built the model. So now that we've built the model, we have to tune it a bit. And to tune the model, we have to use model.compile. So this is where we'll be using 3 parameters. So first parameter is the optimizer which we'll be using. Second parameter is the loss function which we'd have to reduce. And the third parameter is the metric which we'd have to calculate. So over here, the optimizer or the optimization algorithm which I'm using is RMS prop. And the loss which we'd have to reduce is categorical cross entropy. And the metric which we are getting is accuracy of the model. Right. So this is basically the tuning part. And after that, we have to fit the model on top of the training set. And to do that, we'll be using model.fit. And this takes in all of these parameters. So we'll pass in xtrain, ytrain. Or in other words, we are basically fitting this model on top of the train set. And we are validating this on top of the test set. So we have xtest and ytest over here. And we also set the batch size and number of epochs over here. So the number of epochs are 10 and the batch size is 128. So I'll run this now. Now this is our first epoch. So our first epoch has just started. So we see that the loss, it is reducing. So this is our graph over here. So we have 2 graphs over here. So the first graph, this tells us how the error reduces with each epoch. And the second graph tells us how the accuracy increases with each epoch. So over here, this orange line, it is for the validation data. And this blue line, it is for the training data. Similarly, this is what we have over here. So we see that the error it reduces considerably for the training data as well as the validation data as the number of epochs increases. And similarly over here, as the number of epochs increases, the accuracy also increases. So the accuracy for the validation data, it increases till over here, till the 6th epoch. Now after the 6th epoch, for the 7th epoch, the accuracy actually comes down and then it goes back up over here. Right? So we were able to visualize this because of the live loss plot which we had imported earlier. And we are done with all of the 10 epochs, and after the 10 epochs, we have the log loss and the accuracy over here. So we see that after completing the 10 epochs, the error, it comes down to 0.072 for the validation data, and the accuracy for the validation data is 0.983. Right, so we have successfully built the model. Now let's also have a glance at the summary of the model. So I'll use model.summary and I'll click on run. So this gives us a brief summary. So this is the first dense layer, this is the second dense layer, and this is the third dense layer over here. And this tells us the number of nodes with respect to each dense layer. So the first dense layer has 512 nodes, and then we have a dropout layer corresponding to the first dense layer. After that, we have the second dense layer, and the second dense layer comprises of 256 nodes. And then again, we have a dropout layer for the second dense layer. And then we finally have the output layer, which is again a dense layer. And this dense layer comprises of 10 nodes over here. So in total, the number of parameters are 535,818, and all of these are trainable parameters over here. So now that we've seen the summary, let's just actually visualize how our model has progressed. So for that, I will use the SVG method, and inside that I will pass in my model inside model2 dot, and I'll create a dot plot. So I'll click on run. So this is what we have over here. So I have taken the input and I have passed that input through the first dense layer, which is nothing but our hidden layer, which comprised of 512 nodes. And after that, I passed the result through the first dropout layer. And this result was then sent to the second hidden layer. And then this again was sent through a dropout layer. And then finally, the result from this dropout layer was sent to the output layer. So this was the entire process which we performed in this Keras sequential model. So now we'll work with the second type of model, which is the functional model. And again, we'll be applying the functional model on top of the MNIST dataset. So again, we'll start off by loading all of the required packages. So we have to import Keras, and then we have to import model from Keras, and I'll import all of the optimizers from Keras. I'll click on run. After this, I'll load in the training set and the testing set of the MNIST. So pd.readcsv helps me to load both of these CSV files. So training set has the train set of the MNIST data, and test.csv has the test set of the MNIST data. Again, I'll click on run. Right, so we've stored the train set in df_train, and we've stored the test set in df_test. Now let me have a glance at the training set first. I'll click on run. So df_train.head. So this gives me the first 5 rows of the training set. So this is our training set, which comprises of 785 columns. So this what you see, pixel 0, pixel 1, pixel 2. So we have 784 pixels in total, and these are the corresponding labels for each of these images. So the first image, it is basically the image of number 1. The second image, it is the image of number 0. The third image, it is the image of number 1, right? So we have the labels over here, and then we have the 784 pixels which combine to make up this image. Now similarly, let me have a glance at the test set. So df_test.head, I'll click on run. Now this is a dataset which comprises of 784 columns. Actually had a glance at the original training and testing set. What I'll do is I'll divide the training set into features and labels. So from the entire dataset, I'll select the column starting from column number 2 to the final column. That is starting from pixel 0 till pixel 783. And I will store it in df_features. So this basically represent all of my independent variables, or these basically represent all of my features. And similarly, from the training set, I'll just select this first column and I will store it in df_label. So I have my features and labels ready with me. And similarly, I'll also create the test set. So from the test set, I'll extract all of the rows and all of the columns and I'll store that in x_test. Now let me print out the shape of x_test. I'll click on run. So we see that there are 28,000 entries in the test set, or in other words, there are 28,000 images in the test set. So now we have our features and labels ready with us. We have to divide these features and labels into validation data and training data. And for this purpose, we'll be importing train test split from sklearn.model selection, and I'll be passing both the features and labels inside this. And the test size, I'll be setting it to 0.2. That is, 20% of the data points would be present in the validation data set and 80% of the data points would be present in the training set. And I'm setting a random seed of 1212 so that I can use the same result again whenever I want. Now, I will store the result in xtrain, xcv, ytrain and ycv. So this xtrain comprises of the training data of the features. This xcv comprises the validation data of the features. And we have ytrain, which comprises of all of the features of the training set. And then we have ycv, which comprises of all of the labels for the validation data. Now, after this, again, we have to reshape this. So we are going to reshape the xtrain and xcv. So we are going to reshape this xtrain and xcv into a matrix, and we are going to set the number of rows to be 33,600 and the number of columns to be 784 for xtrain. And for validation, I'm going to have 8,400 rows and 784 columns. And finally, we have the xtest. So I'll use xtest.as matrix. I'm converting this into a matrix and then I'm reshaping it to the same thing, which is 28,784. Right, now I'll run this. Right, now let's have a glance at the minimum and maximum values of the pixels present in the training set. So I'll click on run. So you see that the minimum pixel value is 0 and the maximum pixel value is 255. So these are basically grayscale images, and the values of these pixels of the grayscale images, they range from 0 to 255. So now that I've reshaped the data, I also have to normalize this data. And to normalize this data, I'll be dividing xtrain, xcv and xtest with 255. So first I will convert them to float, and after I convert them to float, I'll just divide them with 255. So I'll say xtrain by 255 and I'll store it back to xtrain. Similarly, I'll say xcv divided by 255 and I'll store it back to xcv. And then again, I'll divide xtest with 255 and I'll store it back to xtest. So we have also normalized our training data. Now, after this, we have to perform one-hot encoding of the labels. And to do this, we'll be using keras.utils.toCategorical. And this takes in two parameters. First is the object on which we'd have to perform one-hot encoding, and next is the value, which represents the number of classes this object has to be divided into. So over here we have given the value of 10 to num digits. So basically we want to represent this ytrain in the form of a numpy array where there are 10 values, and each of these individual numpy array would actually represent the value of the image, right? So we'll do the same thing for y_train and y_cv. That is for the training set as well as the validation set. I'll click on run. So we have normalized the data and also we have performed one-hot encoding on top of the labels. So now let me actually have a glance at the labels after performing one-hot encoding. Right. So we see that the first image in the training set, its label was actually 2. So now this 2 has been represented like this. So 0, 0, 1 and then we have zeros following it. So this basically means that wherever we have 1 over here, this represents that index position. So this is the 0th index, first index, second index. And since we have 1 at the second index, this basically denotes that the label of this image is 1. And then we have the third image from the training set. So over here, the label is actually 7 and it has been represented like this. So we have 0, 0, 0, 0, 0, 0 and 0, 1 and then we have 2 zeros following it. So we have 1 present at the 7th index position, and since it is present at the 7th index position, this basically means that the label of this corresponding data is 7. Right, so now before we go ahead and build our functional models, we'll set in all of our parameters first. So first I will set the number of features, that is the number of features are 784, and I'll store it in an input object. And then I'll add the number of nodes to be present in each hidden layer. So the first hidden layer has 300 nodes, the second hidden layer has 100 nodes, the third hidden layer again has 100 nodes, and the fourth hidden layer has 200 nodes. And after this, I will have num digits, which is basically 10. So this basically tells me that the number of digits are 10, right? So now I have set all of my parameters. I'll click on run. And this is finally time to build my model. So we'll be building a bunch of models. So we are going to build at least 3 to 4 models, and we are going to change the hyperparameters a bit, and we'll compare the accuracy of all of these models, and we'll see which model gives us the best accuracy. So we'll go ahead and build our first model. So our first model over here, as we already saw during the theory part, first we have to create the input layer. So I'll be using the input method and I'll pass in the shape of it. So the shape is 784. So this basically means that there are 784 inputs. And after that, I will create my first hidden layer. So over here, I will use the dense method and I will pass in n hidden 1. This basically means that there are 300 nodes in the first hidden layer. And the activation function which I'm using for the first hidden layer is relu. And I'll name this as hidden layer 1. Now I will give in INP inside braces over here. So this basically means that this hidden layer 1 is connected with the input layer, or input layer is my first layer. After that, it is followed with the hidden layer 1. And then I'll go ahead and create my second hidden layer. Again, I'll use the dense method. I'll pass in n hidden 2, which is basically the number of nodes. So in the second hidden layer, the number of nodes are 100 and the activation function used by me is relu. Now, after this, I'll name this as hidden layer 2 and I'll connect it with x again. So I am connecting this second hidden layer with the first hidden layer. Again, I'll create the third hidden layer. I'll do the same things. I'll use the activation function as relu. I'll name it and then I'll connect this with the previous layer over here. And then finally, I'll create the fourth hidden layer and I'll pass in the number of nodes. After that, I'll set the activation function and then I'll name it. And then again, I will connect this fourth hidden layer with the third hidden layer. And finally, I'll set the output layer. So over here, output layer, num digits, this is basically 10. So this basically means that there are 10 nodes in the output layer and the activation function used by me is softmax. So again, I am using softmax because it will give me a bunch of probabilities for each of these nodes. And when I add up all of these probabilities, this will amount to 1. And I am naming this as output layer. Again, I am connecting this output layer to the fourth hidden layer. So what I've basically done is, first I've created the input layer. After that, I have created 4 hidden layers and I've connected them with each other. And finally, I've created an output layer and connected that output layer with the fourth hidden layer over here. So now that the connection of all of the hidden layers is done, we have to pass the input and the output layer inside the model method. So we'll do that and I will store that in model. And let me have a glance at the summary of the model which I've just created. Right. So this is what I have. I have the input layer and then I have 4 hidden layers. And then I finally have the output layer. So this is the shape of the first input layer. So there are 784 nodes or 784 inputs for the first input layer. And then we have 4 hidden layers. Number of nodes in first hidden layer is 300. Number of nodes in second hidden layer is 100. Number of nodes in third hidden layer is 100. Number of nodes in fourth hidden layer is 200. And then the output layer comprises of 10 nodes. Right, I'll click on run. So this is where I'll set all of the hyperparameters. So I'll start off with the learning rate and I'll set the learning rate to be 0.1 and I'll keep the number of epochs to be 20 and the batch size to be 100. And the optimizer which I'll be using is SGD, or in other words, I'm using the stochastic gradient descent as my optimization algorithm, and inside this I'll pass the learning rate over here. Alright. Now I'll go ahead and compile my model. This is where I'm basically tuning my model. So this takes in 3 parameters. First is the loss which I have to reduce. Next is the optimizer. Next is the metric which I have to calculate. So the loss which I have to reduce is categorical cross entropy. And the optimizer used by me is SGD as we saw over here. And then the metrics which I want to calculate is accuracy. So I'm building a model and I want to find out the accuracy of the model which I built. Right, I'll click on run. Now I built the model. I've also tuned the model. So this is when I can go ahead and fit the model on top of the train set. So this takes in all of these parameters. So I'm basically fitting this model on top of X train and Y train. I'll give the batch size and number of epochs over here, and I want to validate this on top of XCV and YCV, which is basically my validation data. I'll click on run. So my first epoch has started. So in my first epoch, I see that the validation accuracy is 76%. Similarly, in the second epoch, I see that the validation accuracy is 87%, and this goes on. So the number of epochs are increasing. So we see that the accuracy is increasing. At the 12th epoch, the accuracy is 94%. At the 14th epoch, the accuracy is 94.69. So at the end of 20th epoch, we see that the validation accuracy is 95.82%. So we've built our first model, and our first model gave us an accuracy of 95.82%. Now, I'll go ahead and build another model. But this time what I'll do is, I'll not use the stochastic gradient descent optimization. So instead of stochastic gradient descent, I'll be using Adams, and let's see what difference it gives me in the accuracy. So we'll keep this in mind. So stochastic gradient descent gave us an accuracy of 95.82%. So again, for the second model, I'll give the input layer, I'll give all of these dense layers, and then I'll set the output layer. So all of these are same. So the input shape, that's same, 784. The number of nodes for these hidden layers is same. The activation function is also same. So the only thing which I'm changing in the second model is the optimization algorithm. So over here, I'll be using keras.optimizers.adam, and I'll be passing the learning rate, and I'll store this in Adam. And I'll go ahead and tune this. So while tuning, I'll set the loss to be categorical cross entropy, and the one change which I'm making, that is the optimizer used by me, that is Adam. Now I'll click on run. Right. And I'll go ahead and fit this model on top of the train set, and I want to validate it on top of XCV and YCV. I'll click on run. Right, so the first epoch has started. Right, so we're done with the 20th epoch. And at the end of the 20th epoch, we get a validation accuracy of 97.92%. So this is a considerable increase. So when we use the stochastic gradient descent as the optimization algorithm, we got an accuracy of 95.82. And instead of SGD, when we used Adams, the accuracy increased from 95 to 97. So now we've understood that it is better to use Adams instead of SGD. Now we'll go ahead and build some other models where we'll change something else. So this time what we're going to do is, we're going to keep the same optimization algorithm, which is Adams, but we'll change the learning rate. So initially the learning rate was 0.1. Now instead of keeping it 0.1, I'm changing it to 0.01. Rest everything will be the same. So I'll click on run over here. And then I'll go ahead and fit this model on top of train and test, and I'll validate it on top of XCV and YCV. So the training has started, as we can see over here. Right, so we're done with the 20th epoch, and we get an accuracy of 97.60. So let's compare it with the previous model. So in the previous model, when the learning rate was 0.1, the accuracy is 97.92, and this time it's 97.60. There's not much of a difference, but we see that when the learning rate is 0.1, we get a better accuracy than when the learning rate is 0.01. Now similarly again, let's try it out with a different learning rate. So this time I'm setting the learning rate to be 0.5. Again, rest everything would be the same. So we have the input, we have the same hidden layers which comprise of the same number of nodes, and then we have the output layer over here, and also the optimization algorithm is also the same. I'll click on run. Right, now I'll fit the model on top of X train and Y train and validate it on top of XCV and YCV. So we're done with the 20th epoch, and we get an accuracy of 97.7. So when we compare these three models, we see that we get the highest accuracy when the learning rate is 0.1. Right. Now what we'll do is we'll add another layer. So till now we just had 4 hidden layers. So I'll add another hidden layer which comprises of 200 nodes. So again, the input layer, it comprises of 784 inputs. We have the first hidden layer comprising of 300 nodes, second hidden layer comprising of 100 nodes, third hidden layer comprising of 100 nodes again, fourth again 100 nodes, fifth would contain 200 nodes, and then we finally have the output layer which comprises of 10 nodes. Right, I'll click on run, and again for all of these 5 hidden layers, the activation function is relu, and each of these is connected with each other. So input is connected to first hidden layer. This is connected to second. Second is connected to third. Third is connected to fourth. Fourth is connected to fifth. And this fifth hidden layer is connected to the output layer over here. And the activation function used for the output layer is softmax. Right, I'll click on run. So we have created the input data and we have also connected the layers. Now it's time to build the model. And to build the model, all we have to do is pass in the input layer and the output layer, and then I'll have a glance at the summary of the model which I've built. So I'll click on run. Right. So I have the input layer, and then I have 5 hidden layers, and then I have the output layer, and these are the number of nodes corresponding to each of these hidden layers. So now again it's time to fine tune a model. So I'll be using the same Adams algorithm, and I'll set the learning rate to be 0.01, and inside this compile method I'll set in these 3 factors. So the loss which I have to reduce is for categorical cross entropy, optimizer as Adams, and the metric which I have to calculate is accuracy. Alright, and then I'll fit this model on top of training set and validate this on the validation set. Right, so we're done with all of the 20 epochs, and this time we get a validation accuracy of 97.31. So we see that actually this is the lowest accuracy of all of the models which we've built. So this means that adding another hidden layer did not really make much of an impact to our model. So now we'll do something different. So what we'll do is we'll add dropouts after each hidden layer. So again, we have the input layer over here and we have 4 hidden layers. These are the number of nodes corresponding to each of these hidden layers. And then this is the number of nodes for the output layer. I'll click on run. Right, so over here I'll start off by creating the input layer. I'll set the shape, and the shape is 784, and then I'll create the first hidden layer. So the first hidden layer, the number of nodes are 300, the activation function is relu, and after this I will set a dropout layer. So the probability of this dropout layer is 0.3, and then I'll create the second hidden layer and I'll add a dropout to the second hidden layer, and then I'll create the third hidden layer. Again, I'll add a dropout to the third hidden layer, and then I'll create the final hidden layer, and after the final hidden layer, I'll create the output layer, and again this output layer would comprise of 10 nodes, and the activation function used is softmax, and this output layer is connected to the final 4th hidden layer over here. Right, so now that we've established the input layer and all of these hidden layers, let's go ahead and create a model. So all I have to do is pass in the input and output layers inside the model method, and I'll store this in model 4 instance, and I'll have a glance at the summary. Right. So we have the input layer, hidden layer, and a dropout layer after each of the hidden layers. So now that we've built the model, let's again fine tune it. So the loss which we have to reduce is categorical cross entropy, optimizer is Adam, and the metric which we've used is accuracy. And let me fit the model on top of training set and validate it on top of XCV and YCV. I'll again click on run. Right, so we're done with all of the 20 epochs, and this time we get a validation accuracy of 97.63. Right, so what we've done is we've basically built multiple models, and we were just trying to understand how does changing some of these parameters change the accuracy that we get. So now what we'll do is we'll use this final model, but that is the model 4 which you built, and we are going to predict the values on top of the test set with this model 4 which we've created. So I'm going to use the predict method from this model 4 instance. So I'll just type in model 4.predict, and over here this takes in 2 parameters. So the first parameter is the data on which we want to predict the results, which is X test, and then we'll set the batch size which is 200. So we'll basically predict the values on top of the test set, and I'm storing it in test pred. Alright, so now let's actually have a glance at the predicted results. So I'll have a glance at the head of this. So this is the image ID, and this is the label which we've predicted. So the first image we predicted that this image represents number 2. Similarly, the second image we predicted that this image represents number 0. The third image represents number 9, fourth image represents number 9 again, and fifth image represents number 3. Right. So now what I'll do is I'll take these predicted results and I'll create a CSV file out of this. So test.pred.toCSV, this helps me to create a CSV file, and I'll name that file to be mnist submission.csv. So now we'll start by understanding how our computer actually reads the images that we provide to it. So let's say we have this image of 3 really cute dogs. So we as humans, when we see this image, we understand that there are 3 really cute dogs in this image and there is grass beneath these dogs, right? But then again, if I feed this image to a computer, what will it exactly see? Well, so there'll be three channels, which is actually known as the RGB channel. So there is this red channel, green channel, and the blue channel. And each of these three channels would have their own corresponding pixel values. Now, when I say that the image resolution is 32 cross 32 cross 3, I basically mean that there are 32 rows, 32 columns, and 3 channels. That is, the red channel would have its own 32 cross 32 matrix, the green channel would have its own 32 cross 32 matrix, and the blue channel itself would have its own 32 cross 32 matrix. And this is what a computer basically sees. So there are basically a list of pixel values. So these are basically numbers which are fed into the computer, and this is what the computer reads. Now, we'll go ahead and understand what exactly is the problem with a fully connected network. So let's say I have this image whose dimensions are 28 cross 28 cross 3. Now, when I feed in this image to a fully connected network, so the first hidden layer would basically have 28 cross 28 cross 3 weights. That would amount to 2352 weights. Now that is a whole lot of weights, isn't it? So dealing with all of these weights would be sort of a difficult task for this network. And to be honest, this resolution is actually low. So 28 cross 28 is actually a small resolution image. Now what I'll do is, instead of this 28 cross 28 image, I'll feed in an image whose dimensions are 200 cross 200 cross 3. And when I multiply 200 into 200 into 3, I'll get 120,000 weights. And those are a whole lot of weights, aren't they? And dealing with all of these weights would be a really Herculean task for this fully connected network. And this is exactly where the fully connected network fails. And we'll have several such layers of neurons leading to several parameters. So thus this connectivity would be a waste, as the huge number of parameters would actually lead to overfitting, and we do not want any sort of overfitting for our model. So now that we understand what exactly is the problem with a fully connected network, let's see how can a convolutional neural network solve this. Alright, so CNNs are basically like your normal neural networks and are made up of neurons with weights and biases, and they take inputs, and those inputs are passed through a weighted sum, and then they are passed through an activation function, and then we finally get an output. But then again, the difference between a CNN and a normal fully connected network is this. So in a CNN, let's say if we take a neuron in one particular layer, then this neuron will not be connected with all of the inputs of the previous layer. So let me actually go back over here, and let's assume that this is a convolutional neural network. Then this neuron would only be associated with, let's say, the first and the second neuron. Similarly, if I take this second neuron over here, then let's say this would be associated with this fourth and the fifth neuron. Similarly, if I take this neuron over here, then this could be associated with the first and the third neurons from the first layer. Right? So this is what basically happens in a convolutional neural network. So a neuron in one layer is not connected to all of the neurons in the previous layer. Right. And rest of the things are actually pretty much same when it comes to the convolutional neural networks. So another difference when it comes to a convolutional neural network is, so a convolutional net actually perceives these images as volumes. That is, three-dimensional objects rather than as flat canvases to be measured only by width and height. Right. So now that we understand what exactly is a convolutional neural network, let's see what convolution means. So in simple terms, convolution basically means to roll together or to combine together. And when it comes to mathematical perspective, so let's say we have two functions f and g. Now, when we pass these two functions with each other, convolution basically means how much one function overlaps with the other function. So let's take this image over here. So this is our first function, which is f, and this is our second function, which is g. Now when I pass g with respect to f, so this is where the overlapping happens, and this is what we exactly mean by convolution. So a convolution is the integral. So convolution is the integral measuring of how much two functions overlap as one passes over the other. And again, in mathematical terms, you can consider convolution to be mixing two functions by multiplying them. So we have f and g, and we are mixing them by multiplying f with g. So this is what convolution basically means. So now we'll actually have a brief understanding about CNNs and then go through a use case. So what actually happens in a convolutional neural network is, there are many filters, and each such filter is passed over the entire image. So let's say we have this image of a car and we want to identify or classify this as a car among many such classes. So these are the different classes available to us. So there is horse, ship, airplane, truck and car. And we want to label this properly as a car. Now, when we feed in this image of a car to this convolutional neural network, what basically happens is there are different filters which are passed through this image. So let's say there is one filter which identifies or maps all of the horizontal lines. And then there is a second filter which identifies all of the vertical lines. And then similarly there is a third filter which identifies all of the left diagonals. And there is another filter which identifies all of the right diagonals. Now what happens is a convolutional neural network takes all of these filters and a slice of the image's feature space and map them one by one. That is, they basically create a map of each place wherever feature occurs. So we take this filter, map it on top of the image's feature space and basically understand if there is a match between the filter and the image's feature space or not. And a convolutional neural network basically comprises of these four layers. So there is a convolution layer, there is a ReLU layer, there is a pooling layer, and the final layer is the fully connected layer. Alright. Now we'll actually go through a use case to understand CNNs. So let's say our task is to identify, so let's say we have this image of X and image of O and we want to identify what exactly is this. So when we pass this image of X through this CNN, we want to identify or label this as X. And similarly, when we pass this image of O through the CNN, we want to identify or label this as O. Now this might actually seem simple. So if there is just one X or one O, it would be quite simple. You would just have to pass in this image of X through the CNN and it will easily identify that this is X. And it would be the same case with letter O as well. But then again, let's say we are dealing with sort of a tricky situation. Now, let's say we have all of these images of X. So this is our original image of X. So here what we are doing is we are thickening it up. And over here we are actually shifting up to the top left corner. And over here we are distorting this a bit. But then again, all of these are nothing but images of X. And when we feed all of these images to a neural network, we want that neural network to properly identify these as X, right? And similarly the case with O as well. And similar is the case with O as well. So all of these are distorted images of O. So when I pass these images of O to a neural network, I want that neural network to properly identify these images as the letter O. So now to do this, let's actually understand how a computer reads an image. So as we've already seen, a computer basically reads an image like a two-dimensional array of pixels with a number in each position. So this is what a computer basically sees, right? So let's say when we feed in this image of letter X to the computer, this is what it basically sees, right? So these are all of the numbers which are present in these pixels. So we have minus ones all over here in the blue spaces and one over here in the white spaces, right? So let's say this is our original image of X and this is our distorted image of X and it's pretty much the same, right? So wherever we have the white labels there the value in the pixel is +1 and wherever we have blue colors, there we have the value of -1. Now let's say if we use the normal comparison and compare each of these pixel values, right? So let's say we compare this pixel value with this pixel value. Similarly, this pixel value with this pixel value and this pixel value here with this pixel value. Now what happens with that sort of comparison is you would get a lot of missing pixels, which actually means that this is not the optimal way of image classification since it requires exactly the same images to classify. Right? So this is the original image. This is a distorted image and these orange pixels which you see. So these are basically all of the values which are not there in the original image. And this is not really the right way to classify our image. So this is where we can use a convolutional neural network. So let's understand how does a CNN solve this problem. So what actually happens in a CNN is we compare these images patches by patches, or in other words, we compare them with respect to these pieces or features. So earlier I had talked of something known as a filter. So these boxes which you see, these are those filters over here. So what I'll do is I will start off by creating a random filter, right? Now this random filter is nothing but an image of a left diagonal. Now what I'll do is I will map this filter on top of this original image and find out if there is any match between this filter and this new image. Similarly, this is my second filter. Now this second filter is basically a cross. Now what I'll do is I will take this filter and map this on top of this input image, and again I'll see if there is any sort of match or not. Again I'll do the same thing. I'll take this third filter, which is basically the image of a right diagonal, and I will map this on top of this input image, and I'll again see if there is any sort of match or not. So this is what is known as feature matching, and what I'm actually doing is creating some random filters and mapping those random filters on top of this new image to see if there is any match with respect to that new image or not. And each of these features is sort of like a mini image. You can consider this to be a small two-dimensional array of values. And as I had already said, we'll be using these three filters. So this is our first filter, which basically represents a left diagonal. So all of these white values, they have been represented with +1, and all of these black values, they have been represented with -1. And then we have the second filter, which basically represents a cross. So we have this left diagonal and right diagonal, which are basically the white spaces, and those white spaces have been represented with +1, and the rest of the black spaces have been represented with -1. And then finally we have this third filter over here, which actually represents the right diagonal. So over here, the values in the right diagonal or the white spaces have been represented with +1, and the rest of the values have been represented with -1. So again, what we'll do is pass these filters on top of this new image and see if there's a match or not. So now we'll start off by understanding each of these layers one by one, and we'll start with the convolutional layer. So as I had already said, when presented with a new image, the CNN doesn't really know where exactly these features will match. So what it does is, it tries them everywhere in every possible position. So in calculating the match of a feature across the whole image, they act as filters. And the math which is used to perform this is called as convolution, which you've already seen, right? So basically you can consider this to be a multiplication of two functions. So let's say you have a function f and you have a function g, and when you multiply these two functions, you'll have the overlapping part, and this overlapping part is what is known as the convolution. So there are 4 steps involved in this convolutional layer. So in the first step, what we do is we line up the feature or the filter on top of the image, and then we multiply each image pixel by the corresponding feature pixel. Now once we do that, we'll add all of the values and find the sum, and finally we'll divide the sum by the total number of pixels in the feature. So let's understand these 4 steps with the same example over here. So we've got this filter over here, and this is the filter of the left diagonal. Now what I'll do is I will place or map this filter on top of this image over here. Now once the mapping is done, what I have to do is multiply these corresponding pixel values. Now let's say if I take this pixel value at the bottom right hand corner. So what I have to do is just multiply these two pixel values and I'll get a +1. Now this is just for this pixel value. So I'll do this for all of the pixel values. So this is what basically happens. I have my filter over here or my feature over here, and I am placing this on top of this image space. So obviously I can't place this small filter on top of the entire image. I can place this only on one region of this image. So I'm taking this filter and I'm placing this over this region. Now this is the first step. In the second step, what we do is we multiply the corresponding values. So when we do that, what we get is 1 cross 1, which is 1, and then we'll do minus cross minus 1, which is again +1. Again it's minus cross minus 1, which is +1 again, and then we'll do minus cross minus 1, which is +1 again. So we are basically multiplying all of these corresponding values, and we'll get 1s over here. And after this, what we'll do is we'll divide this with the number of pixels in this cell, and that is 9. So when we add this up, this is 9, and then we divide it by 9 again. So we'll get a final result of 1. So going ahead, what we'll do is we'll take this 1 and place this at the center of this frame. Now similarly, I'll take the same filter and place this over this region of the image. So this is the first step, and again in the second step, what we'll do is multiply the corresponding values. So 1 cross 1 is 1 again, minus 1 cross minus 1 is +1. Now over here, when you multiply -1 with +1, what you'll get is a -1 over here, right? And similarly, when you take this value over here, it is -1 and it is +1 over here. So when you multiply 1 with -1, you'll again get -1 over here. So in the summation process, you basically have 2 -1s and 7 positive ones. So when you divide this value with this value, what you get is a final value of 0.55. So again, you'll take this value of 0.55 and place this over here at the center of the frame. And you'll repeat that process for all of the regions over here, right? So you'll take this filter, place it over here, multiply the corresponding pixel values, sum it up and divide it by the number of pixels and place the final value at the center. Similarly, you'll take this filter, place it over the second region, take this filter again, place it over some other region, take this filter again and place it in yet another region, right? And finally, you'll have this set of values after passing this filter through the entire image over here, right? But then again, that was just the first filter. When you notice, we actually had 3 filters. So there was a filter which basically denoted the left diagonal. There was a second filter which basically denoted across. And there was a third filter which basically denoted the right diagonal. Now, we were just done with the first filter. That is, we passed the first filter over the entire image and we got this 2-dimensional array. Now similarly, we'll pass the second filter on top of this entire image and we'll get this modified 2-dimensional array again. Similarly, we'll pass this third filter on top of this image and again we'll get this modified 2-dimensional array. So this is where the convolutional layer ends. So again, I'm repeating whatever happens in convolutional layer. So we'll start off by finding some random filters. So let's say there are 3 random filters. Now we will pass all of those 3 random filters on top of this entire image and multiply those corresponding pixels. After multiplying those corresponding pixels, we'll add them up, find the sum and divide it with the number of pixels present in the entire feature space. Right, so this is the end of the convolutional layer. Now let's understand what happens in the ReLU layer, which is basically the second layer over here. So in ReLU layer, what we actually do is pass in an activation function over the result which we obtained in the first layer. So this function basically activates a node only if the input is above a certain quantity. So when the input is below 0 over here, then the output is given as 0. But when the input rises above a certain threshold, then it will have a linear relationship with the dependent variable. And let's actually understand that with this table over here. So let's say when the input value is -2, then the output would be 0. Because whenever the input is negative, the output would be 0. Similarly, we have this input value of -6. Again, this -6 is fed through the activation function and we get a value of 0. Now, when we have this value of +2, this ReLU function actually acts like the identity function and would give the same value, which is 2 again. And again, similarly, if we pass in +6 or +6, then again the ReLU activation function would act as the identity function and again give the same value, which is 6 again. And this is the symbol for ReLU, which basically denotes that if we have any negative values, all of those would be represented as 0, and if we have any positive values, then this function acts like the identity function. Right, now we have the same 2-dimensional array which we got after passing in our first filter over the image. Alright, so now what we'll do is pass in this ReLU layer over this 2-dimensional array. And when we pass in this ReLU layer, what it basically does is converts this negative value into 0, right? And that is what we basically saw in the previous slide. So whenever there is a negative input, that negative input is turned to 0. And since the value over here is basically -0.11, it will be turned to 0. And similarly, wherever there are negative values, all of those negative values would be turned to 0 with the help of this ReLU layer. And that again was just the 2-dimensional array that we got from our first filter. And again, we'd have to do the same process for all of the 3 filters. So these are the 3 2-dimensional arrays which we got after passing through those 3 filters. And now what we'll do is we will take in these 3 modified 2-dimensional arrays and pass this through the ReLU layer. And what we'll get is again modified 2-dimensional arrays. So this time these 2-dimensional arrays have no negative values, right? So we have this 2-dimensional arrays over here and these 2-dimensional arrays have no negative values in them. Now after we pass these 2-dimensional arrays through the ReLU layer, what we have to do is we have to pass them through something known as the pooling layer. So let's understand what exactly is a pooling layer. So pooling is basically a way where we take large images and shrink them down while preserving the most important information in them. So I'm repeating it again. So what we do in the pooling layer is we take in really large images, pass them through the pooling layer and shrink them so that we can keep only the important information and discard the insignificant information. Now this pooling layer comprises of something known as a window, and we'll take only the maximum value which is part of the window. So normally the window size is either 2 cross 2 or 3 cross 3. And this what you see is the symbol for pooling. So this is our two-dimensional array after passing it through the ReLU layer. Now it's time to again pass this image through the pooling layer. So as we already know, what happens in the pooling layer is we pass this image through a window and we'll take the maximum value through that window. So over here the window size which I'm taking is 2 cross 2, right? So I will pass this window over these values, and what I see is the maximum pixel value is 1, and that is what I'll take over here. Similarly, I'll take a step size of 2 and again pass this window through this region over here, and this region would give me a maximum value of 0.33. Similarly, I'll pass this window to these 4 values, and from here I'll get a maximum value of 0.55. So now if you actually note this properly, we actually started with a 7 cross 7 matrix and we ended up with a 4 cross 4 matrix. So this is how pooling layer actually helps us in reducing the dimensions of the image, right? So this was the image after the second stage. We passed this through the pooling layer and we got a 4 cross 4 matrix. And again, this was just the result from the first filter. We'd have to do the same thing for the rest of the 2 filters as well, right? So we'll pass in all of these 3 two-dimensional arrays to this pooling layer and we'll get a modified array again, and these modified arrays are of 4 cross 4 dimensions. Right, now we'll go ahead and combine whatever we did through the convolutional neural network. So we had this initial image of X. We passed this in through the convolutional layer where we had basically mapped the filters on top of the original image and then multiplied the corresponding pixel values, added them up, and then divided it by the number of pixels present in the frame. Now after that, we had passed the modified two-dimensional array to the ReLU layer, which removed out all of the negative values. Now again, that modified two-dimensional array was passed through the pooling layer where we got a subset of the original array. And this is what we get after passing the original image through these 3 layers. Now what we'll do is, instead of having just one set of these 3 layers, we'll pass them through a multiple of convolutional, ReLU and pooling layers. So I have this image. I'll start off by passing this through a convolutional layer and a ReLU layer. Now again, I'll pass this through a convolutional layer, a ReLU layer and a pooling layer. And again, I'll do the same thing. I'll pass this through the convolutional layer, the ReLU layer and the pooling layer. So now after this process, the 4 cross 4 matrix has reduced to 2 cross 2 matrix. And this is the result after the final pooling layer. So we have something known as the fully connected layer where the actual classification happens. So these were our two-dimensional matrices. Now what happens in the fully connected layer is, we'll not actually treat these inputs as a two-dimensional array. So they are actually treated as a single list and each of these values are treated identical. So we start off with these two-dimensional arrays and we convert them into this list. So I'll take this one, place it over here. I'll take this 0.55, place it over here. Similarly, I'll take this 0.55, place it over here. I'll take this one, place it over here. And I'll do the same thing for these two-dimensional arrays as well. So I'm restating it. I had this two-dimensional array to start with, but then again I am converting this into a list, right? And these are the set of values which I'll get for the image X. And similarly, when I pass in the image O through the convolutional neural network, I'll again have a different set of values associated with it, right? So now let's actually take a look at this vector closely. What you see is a set of values which basically comprise of 1 and 0.5, and we'll be only focusing on the 1 values, that is only the values which are higher, that is the first value, 4th, 5th, 10th and 11th value over here. So wherever we have 1s, we'll take only those. Now how the classification basically happens is, let's say we have a new image. So from that new image, what we'll do is we'll compare the value which is present at the first position, 4th position, 5th position, and similarly these 2 positions. So if in the new image those corresponding values are 1, then there is a greater probability for that new input image to be X. right? And that is what happens with O as well. So over here for this list, we'll only focus on the high values. So over here, the second, ninth, and the 12th values are high. So whenever a new image comes in, we'll only compare these values over here. So wherever values are high, we'll compare only those values. And if those corresponding values are high in the new input image as well, then we can go ahead and say that there is a good probability for that new image to be equal to O. Right, so let's say we have this new image over here and it comprises of all of these values. Now I will go ahead and sum up all of those high values in the vector for x in the input image. So in the vector for x, this is 1, 1, 1, 1 and 1. So I basically have 5 ones which basically corresponds to 5. Now I will add up the same corresponding values in the input image as well. So I have 1 over here, I'll take 0.9. Similarly, I have 1, I'll take the 0.7. I have 1, I'll take 0.96. I have 1 over here, I'll take 0.9. Again, I have 1, I'll take 0.94. So what I'll do is, I will add up these values. So that is basically 0.9 plus 0.87 plus 0.96 plus 0.89 plus 0.94. And that gives me a final value of 4.56. So when I sum up the values from input image, I get a value of 4.56. And from this vector for x, I get a value of 5. And when I divide these two values, I get a probability of 0.91. So there is basically 91% probability that this new image denotes the alphabet x. Similarly, let's say if I want to compare this input image with the vector for O. So again, I'll do the same thing. I will take all of the high values. So I have 1, 1, 1 and 1, which basically when I combine it adds up to 4. Now I'll take the same corresponding values. So over here it is 0.65, 0.45, 0.44 and 0.53. Now when I add up these values, it comes up to 2.07. And when I divide 2.07 with 4, I get a final probability value of 0.51. This is actually very less. Now let's actually look at the summary of this. So we had this input image X. Now we took this input image and passed this to this convolutional neural network. And this convolutional neural network again had 4 layers. So the first layer was the convolutional layer where we mapped the filters on top of the input space and we got a modified 2-dimensional array. Now we took that modified 2-dimensional array, passed it through the ReLU layer and removed out all of the negative values. Now again we took this modified 2-dimensional array and passed it through the pooling layer where we got a subset of the original image. And then we finally passed it through the fully connected network, which basically gave us the classification probability. So over here we see that the probability for this image to be x is 0.92 and the probability for this image to be equal to O is 0.51. So this obviously means that the image basically denotes the alphabet X. And this is the entire theory behind convolutional neural networks.
So let's understand the issues with feed-forward network. So let's say this is our feed-forward network over here and we are trying to solve a simple classification problem. So let's say I given an image of a food item and it needs to label it properly. So what I'll do is first I will give this feed-forward network an image of chicken. So when I give in an image of a chicken to this feed-forward network, it correctly labels it as chicken. So let's say I gave this input at timestamp t. Now again after some time, let's say at timestamp t1, I'll give it an image of pizza. So it takes in this image of pizza and then it again labels it correctly as pizza. So till here all of this is fine. So first I give this an image of chicken and it is able to correctly label it as chicken. After a while at timestamp t+1, I'll give it the image of pizza and it is able to correctly label it as pizza. Now the problem is there is no relation between these two outputs. So first we get the output which basically states that the label associated with this image is chicken. And second we get that the label associated with this food item is pizza. Now the problem is there is no sequence or there is no relation between these two entities. So this is where feed-forward networks fail. So they can't really memorize previous inputs. Now there are a lot of cases where we actually want the network to remember all of the previous inputs. And this is not really possible with the feed-forward network. So let's actually take another example. So let's say I have this sentence over here which states recurrent neural. So this is the input and I want my feed-forward network to predict the next word in this sentence. Now, my question to you guys would be, would this feed-forward network be able to predict the next word?
Well, that really is not possible because as we already saw, a feed-forward network is not really able to memorize the previous inputs. So the answer for us humans is pretty obvious. We know that recurrent neural should be followed with network because we have already learned the previous words. So we know that after recurrent, the next word would be neural, and after neural, the next word would be network. And we are able to predict the next word because we are able to memorize the previous words, and that is how our brain functions. But then again, this is not really possible with the feed forward network. So this is basically where the feed forward network fails. So now let's understand how can we solve this with the recurrent neural network. So over here, let's take another example. So let's say there's this chef who only cooks 3 items and 1 item on each day. So let's say he cooks chicken on day 1, pizza on day 2 and noodles on day 3. And again he'll continue the same thing. That is, on day 4 he'll again cook chicken, on day 5 he'll cook pizza, and on day 6 he'll again cook noodles. So it's as simple as that. So basically he has a set pattern and he'll not break that pattern. So let's consider that this is output at timestamp t1. Now, since we know that the output at timestamp t1 is chicken and there is already a sequence which has to be followed, we can say that output at t plus 1 will be pizza. And similarly, since we know what the output is at t plus 1, we can also predict what the output is at t plus 2. So the output at t plus 2 would be noodles. So guys, keep this in mind, and this is how basically a recurrent neural network works. So a recurrent neural network is basically able to memorize this sequence between all of the outputs. Right. So now let's understand how a recurrent neural network works. So let's say on day 1 or on timestamp t1, I'll give this some input. And with respect to that input, this recurrent neural network would predict that the food to be prepared on day 1 is chicken. Now, this output at timestamp t1 is not just discarded. So this output over here is sent to the next neuron at timestamp t2. Now, for timestamp t2, we have an input, and along with that input, we also have the previous timestamp's output. So it'll take these two into consideration. And since it already knows what was prepared at timestamp t1, it is easily able to gauge that the output should be pizza at timestamp t2. Now again, this output is remembered as well. So this output which we've received at timestamp t2 is again sent to the third neuron over here. Now this third neuron has some input, and along with this input, it also takes in the output from the previous timestamp. So along with this output and the input, it is able to predict that the output should be noodles. So this is how a recurrent neural network works. So basically the outputs at all of these timestamps are dependent with each other, and this recurrent neural network is able to handle sequential data. So these, what you see, these neurons are really able to memorize the previous inputs. So I'm reiterating again, this is timestamp 1, and at timestamp 1, this RNN predicts that the output should be chicken. Now, this output at timestamp 1 is sent to the neuron at timestamp 2. Now, with the help of this output from the previous timestamp, it is easily able to predict that the output at timestamp 2 should be pizza. Now again, this output at timestamp 2 is sent to this neuron at timestamp 3. And with the help of this output, it is able to predict that the food item which has to be cooked is noodles. Right. So now that we've understood this example properly, let's understand RNNs in a better way. So as we saw in the example, RNNs basically have something known as a memory which captures information from the previous timestamps. And RNNs are called recurrent because they basically perform the same task for every element of a sequence. So let's say this is our input at t minus 1. Now this is sent to the neuron over here, and this will give us an output at t minus 1. Now whatever information that we get from timestamp t minus 1, that is sent to the neuron at timestamp t. Now, along with the input at timestamp t and along with the information from timestamp t minus 1, it is able to give an output over here. Now, similarly, this information from timestamp t is sent to this neuron over here, and along with this information, there is also an input at t plus 1. So, combining these two, this will give us an output at t plus 1. So, this is how the RNNs work. And if you roll this entire sequence, what we get is basically a loop. So we are performing the same thing at multiple timestamps, and that is why RNNs are called as recurrent. So we provide the input, the operation is done, and we get the output at, let's say, timestamp t minus 1. Now again, the same operation is done at timestamp t. Again, the same operation is done at timestamp t plus 1, and this goes on till we get our final optimal result. Right, so now that we've understood the theoretical part of RNNs, let's also understand the math behind it. So again, we have this RNN.
Here is a quiz question for you guys. The question is, what is a neural network? Your options are a type of computer processor used for high performance computing, a machine learning model inspired by the human brain, a type of encryption algorithm used for secure communication, or a software application for organizing and visualizing data. Please mention your answers in the comment section.
And we've unfolded this RNN, and when we unfold it, we have something like this. So we have different timestamps. So we have 3 timestamps basically, t minus 1, t and t plus 1. So let's actually consider this. So xt over here is basically the input at timestamp t. Now I'll send this input to this neuron over here, and the way we calculate the value of this node is pretty simple. So it's what we've always been doing. Is basically input into the weight associated with this link over here. So input is xt along with the weight over here, which is u. So this becomes xt into u. Now this is just the input. So this is timestamp t, and we've already seen that the current timestamp takes input from the previous timestamp. So over here we have information from the previous timestamp, and that information is basically w into st minus 1. So this st, what you see, this is basically what is known as the memory of the network. So for this node over here at timestamp t, we'll get this input and this information from the previous timestamp. So in total it becomes xt into u plus st minus 1 into w. But this is just a linear equation. Now we have to pass this linear equation through an activation function. So that activation function could either be tan h, relu, or any other activation functions that we've seen till now. And that is how we get the value of st. So again, I'm reiterating it. So to get the value of st, it is basically this input and the information from the previous output. So that is xt into u plus w into st minus 1. And we'll pass it through an activation function, let's say relu. And that is when we'll get the output, which is st. Now again, we have to pass this st through another final activation function, which is mostly softmax, because softmax would give us a range of probabilities, and when you add up all of these range of probabilities, it would sum up to be 1, right? So we'll pass this st through the softmax function, and we'll get the output at timestamp t. Similarly, let's consider this node at timestamp t plus 1. So over here, to calculate st plus 1, we'd have to take this input and this information from the previous output. So it'll be xt plus 1 into u plus w into st. And again, we have to pass this through an activation function, and we'll get the value of st plus 1. Now, if we want the final output at timestamp t plus 1, we have to again pass this through the softmax function, and the softmax function would give us a range of probabilities between 0 and 1. So this is how we get the outputs at different timestamps. This was the part where we did the forward propagation, and in that forward propagation we had outputs for different timestamps. Now again, after forward propagation, we would also have to train the network. And while training the network, what we see is the actual values and the predicted values are not really similar. And there would be quite a bit of error between the actual values and the predicted values. So what we'll do is, once we're done with the forward propagation, we will calculate the error for each timestamp. So here, let's consider this case. So let's say there are 4 timestamps. So we'll start with T4 or timestamp 4 over here. So over here, let's say the actual value is O4 and the predicted value is P4. Now, if we want to know the error in prediction, we have to subtract P4 from O4, and that'll give us an error over here. So this is the error for timestamp T4. Similarly, we'd also have to calculate the error in prediction for timestamp T3. So this time the error in prediction would be O3 minus P3. And then over here we have to calculate the error in prediction for timestamp t2. So this will be O2 minus P2, and for timestamp t1 it'll be O1 minus P1, and for timestamp t0 it'll be O0 minus P0. So now we have errors for each of the timestamps. So E0 is the error at timestamp t0, E1 is the error at timestamp t1, and so on. So now we have the individual errors for individual timestamps. We'd have to calculate the total error. And to calculate the total error, all we have to do is just sum up all of these errors. And when we sum up all of these errors, we'll get E total. So this is the total error which we've got while forward propagating. So now that we know the error in prediction, what we have to do is back propagate and fine tune our weights and bias so that we get the optimal value. And we've already seen how can this be done through back propagation and stochastic gradient descent. So in back propagation, what we saw is we have to calculate the change in error with respect to the weight. But that was simple back propagation. But now we are dealing with RNNs. So in RNNs, we have modules or nodes for each timestamp. So this time we have to calculate the change in error with respect to all of the timestamps. So now let me again go back and see how can we back propagate over here. So now while back propagating, we have to update three parameters over here. So those three parameters are U, V, and W. So what we have to do is we have to find out the change in total error with respect to U, V, and W. Now again, the gradient of total error with respect to these three parameters is nothing but gradient of E0 with respect to those three parameters, gradient of E1 with respect to UVW, gradient of E2 with respect to UVW, and so on. So what we'll do is we'll find out the change of these individual errors at each of these timestamps with respect to each of the parameter. So for this link, the weight associated was V. For this link, the weight associated was U. And for this link, the weight associated was W. So let's go ahead and back propagate and find out the optimal value for V. And if we have to do that, then we have to do it for each of the timestamps. And what we have to do is we'd have to find out the gradient of E4 with V. After that, we'll go back a timestamp and then we'd have to find out the change of E3 with respect to V. Again, we'll go back a timestamp and this time we have to find out the change of E2 with respect to V. Again, we'll go back and this time we have to find out the change of E1 with respect to V. So now, once we have the individual changes of these errors with respect to the parameter V, then all we have to do is add them up. So that will be gradient of E0 with respect to V plus gradient of E1 with respect to V, gradient of E2 with respect to V, and gradient of E3 with respect to V. And when we add all of that up, we'll get the final change in error with respect to V. Now similarly, we'll do the same thing with respect to W over here. So first we'd have to find out the individual change in errors with respect to W. So that'll be gradient of E4 with respect to W, gradient of E3 with respect to W, gradient of E2 with respect to W, and so on. And then we'll have to add all of that up, and finally we'll get gradient of E total with respect to W. And then we'll do the same thing for U over here. So that'll be gradient of E4 with respect to U, gradient of E3 with respect to U, gradient of E2 with respect to U, and so on. And again, we'll add all of that up and we'll get the gradient of E total with respect to U. So this is how we've calculated the change in error with respect to U, V, and W. So we'll use this in the stochastic gradient descent formula and we'll update the weights of U, V, and W, and then we'll get our final optimal result. So this entire procedure that we saw over here is what is known as back propagation through time. So we have one-to-one, one-to-many, many-to-one, and many-to-many. So we'll start off with the first type of RNN, which is basically one-to-one. So this is what is known as the vanilla RNN, and this is the simplest form of recurrent neural network. So this basically takes in a single input and gives out a single output. So an example of this could be, let's say we given one image or a single word and we want to classify this into a single class. So let's say I given an image of a bird and the output which I want is yes or no. That is whether this is a bird or not. Or let's say I given a value 30, an integer number, and I want to classify whether this is a positive number or a negative number. So again, yes or no. So basically what I'm trying to say is this takes in a single input and gives out a single output. So this is the simplest form of RNN. And then after that we have something known as one-to-many RNN. So in this we have a single input, but that single input gives us multiple outputs. So an example of this one could be, let's say if I given the first word of a song, then this RNN has to predict the rest of the lyrics of the song. So let's say there's a song, Hello Darkness, My Old Friend. And if I give the input, which is basically the first word, hello, then what it does is, this RNN, it starts off by predicting the second word, which would be Hello Darkness. Now again, this RNN remembers these two words, which is Hello Darkness. Now, these two words are sent as the input to the third timestamp, which is T3. And then it basically predicts the third word, which is darkness. And this again goes on, and the next word predicts as my. And then it goes on to the next timestamp again. Then it will predict the next word as old. So we just started off with one word, which was hello. And it went ahead and predicted the next three words, which were darkness, my old friend. Right? So this is how a one-to-many RNN works. And then next we have what is known as many-to-one RNN. So this many-to-one RNN basically takes in a sequence of inputs and gives out one final output. So an example of this could be sentiment analysis. So let's say I feed this RNN a sentence, Cristiano Ronaldo is the best footballer in the world. Now, what this will do is, it'll take in this entire sentence and this will tell me the final sentiment of the sentence, which is either positive, negative or neutral. So I feed this the first word, which is basically Cristiano, and this will give me the output, which is either positive, negative or neutral. And this information from the first output is sent to the node at timestamp T2. And there is also an input, which is Ronaldo. So Cristiano Ronaldo, and we also have the output, which is basically the sentiment. And again, for this timestamp, we'll get another output, which is basically the sentiment, which is either positive, negative or neutral. So for the entire sentence, Cristiano Ronaldo is the best footballer in the world, will have a sequence of outputs which are basically positive, negative or neutral. So at the final timestamp, what we'll do is we'll aggregate all of these final outputs and find out the final sentiment. So if the final sentiment is positive, then we'll predict that it's a positive sentence. And similarly, if the final sentiment is neutral, we'll predict it's a neutral sentence. And if it's negative, we'll predict that it's negative. And finally, we have what is known as a many-to-many RNN, which is actually the most frequently used RNN. So an example for this could be predicting the next word in a sentence. So let's take this sentence. I'm going to be the next president of United States of America. So this will take in the first word, which is I, and then it'll predict the second word, which is am. And this is sent to the node at timestamp 2, and this will predict the next word, which will be going. So we have three words till now, which is I am going. And this again over here is sent to the node at next timestamp, and this will predict 2. So this basically becomes I am going to, and this goes on, and we have a set of nodes for different timestamps, and this predicts the entire sentence, which is basically I am going to be the next president of United States of America. So now we'll see the issues with recurrent neural networks. So it's not that these recurrent neural networks are perfect. There are issues with these as well. So again, we'll take this same example. So we'll pass in this sentence recurrent neural to this network over here. Now we have to predict the next word with the help of this RNN. So this is pretty easy. So this RNN, it memorizes this sequence recurrent and neural, and it is easily able to predict the next word, which is network. And it is able to do so because this RNN does not need any further context. And since it does not need any further context, so it is easily able to predict the next word. But now let's take this second case over here. So now I'll pass a really long sentence to this RNN. So let's say the sentence is, I've been staying in Spain for the last 10 years. I can speak fluent dash. So now for this sentence, it's not really that easy for RNN to predict the next word. And that is because this needs the context from previous words. So this has to go back a lot in the sentence. So this RNN has to go back till over here, and it needs the context of this word Spain. And only when it realizes the context of this word Spain, it can predict the next word over here is Spanish, right? So the entire sentence is actually, I've been staying in Spain for the last 10 years. I can speak fluent Spanish. But then again, this is exactly the problem with normal RNNs. And this is known as long range dependencies. So this gap which you see between the word which you'd have to actually predict and the word from which you'd have to find out the context, that is really long. And this is known as a long range dependency. So what happens in long-term dependency is while backpropagating, the chain rule becomes really long. So let's say we are done with the forward propagation for this and we start with the backpropagation. Now over here, since the gap between this word and over here is really long, and there are a lot of timestamps between all of these words. Now, if there are a lot of timestamps, this basically creates a really long chain rule. And when there is a really long chain rule, it's not really that easy to memorize the previous words for this RNN. And this is exactly what is known as vanishing gradient descent problem. Now, if there is a really long dependency, there is actually a good probability that one of the gradients might approach zero. And this would lead to all the gradients rushing to zero exponentially fast due to multiplication. So let's say we start backpropagating from over here. And when we start backpropagating, the gradient, it slowly starts to diminish. So let's say we start backpropagating over here and the gradient somewhere over at timestamp 4 or timestamp 5, it gets to zero. And when the gradient at one timestamp, it gets to zero, all of the gradients for all of the timestamps will be zero because all we are doing is multiplication. And when we multiply zero with any other number, it is basically zero. So such states would no longer help the network to learn anything. And this is what is known as vanishing gradient problem. So this vanishing gradient problem basically arises due to long-term dependencies. So let's say if we start from over here, timestamp 1, and we go back till timestamp 7. So what happens is there is a really long-term dependency over here and the gradient starts to diminish as we traverse back. So this is where we have to use a modified version of RNNs, which are basically known as long short-term networks. So long short-term networks are special kind of RNNs which are explicitly designed to avoid the long-term dependency problem. So what you see over here, this is a standard RNN. So normally the recurrent neural networks have a form of a chain with repeating modules. So all of these are the repeating modules over here and each module is pretty much the same. So normally in standard RNNs, they have a pretty similar structure. So all of these repeating modules would have just a single tanh layer or containing just a single activation function over here, right? So this is a standard RNN where there'll be just one neural network for each of the timestamps. So as we see over here, we have three timestamps, t-1, t, and t+1, and all of these are just recurrent or all of these are just repeating. So for timestamp t-1, we have the same activation function, which is tanh. For timestamp t, we have the same activation function, which is tanh again. And this would be the same for timestamp t+1 again. Now this is the standard RNN. So this is where the difference comes with LSTMs. So again, LSTMs also have a chain-like structure, but the repeating module, which you see over here, this is actually different. So instead of having just a single neural network layer, there are 4 layers interacting in a very special way. So these are the 4 neural networks over here. So what you saw in a standard RNN was there is just one neural network. But when it comes to an LSTM, there'll be 4 neural networks. So let's actually understand the core idea behind LSTMs. So this line which you see over here, this is what is known as the cell state. So this cell state, you can consider this to be a conveyor belt, and the cell state is where all of the information is stored. Now the idea behind LSTMs is to add or remove some information to this cell state so that we avoid the long-term dependency problem. So when it comes to long-term dependency problem, there might be some cases where we don't want to remember some words. So there are some words which don't really have an impact on the next prediction. So, those are some things which you'd have to forget. And again, there are some cases where we'd have to add some new information to the RNN. So all of this can be done with the help of this cell state over here. So again, I'm reiterating it. With the help of this cell state, we can either add or remove information from the LSTM. And these gates are what help us to optionally let information through. So this gate basically comprises of a sigmoid neural net layer and a pointwise multiplication operation. So let's again go back to this image over here. So what we see is we have 3 gates over here. So this is gate number 1, this is gate number 2, and this is gate number 3. Now, since this is a sigmoid layer, this basically helps us to pass information which is in the range of 0 to 1. So a value of 0 basically means that we don't let anything through this gate, and a value of 1 means that we let everything through the gate. So this is again a range of 0 to 1, and this is how we can calculate the amount of information which has to be sent through one particular gate. So if the value is closer to 0, then very little or almost no information is sent through this gate. And if the value is closer to 1, then almost the entire information is sent through the gate. So now let's actually understand the working of these LSTMs. So let's start with our first gate over here. So this gate is known as the forget layer, and this is where the LSTM decides which information are we going to throw away from the cell state, right? So this is the forget gate layer over here. So what it does is it takes information from the input and also from the previous output over here. So the input to this forget gate would be xt into w plus ht minus 1 into w. And then again we'll pass this through the sigmoid layer over here, and this will give us what is known as ft, which is nothing but a value between 0 and 1. And this is where we decide which information are we going to remove away from the cell state. So let's take the same example of predicting the next word in the sentence. So let's say this LSTM might keep the gender of the current subject so that it can predict the current pronoun for the subject. But then again, when it encounters a new subject, you want the cell state to forget the old subject's gender and only remember the current subject's gender, right? So this is basically where we forget the information. So this is done with the help of the first gate. So now that we decide which information is to be thrown away, the second step is where we decide what new information we are going to store in the cell state over here. So this has two parts. First is the sigmoid layer, which is called as the input gate layer. So this input gate layer decides which values we'd have to update. After that, there is this tanh layer, which basically creates a vector of new candidate values that could be added to the state. And with respect to the language model, this is where we can add the information of the new subject's gender and remove the information of the old subject's gender. So we have two parts over here. So first is where we update the information. So this is basically where we take information from xt and ht minus 1 and pass it through the sigmoid layer. And after that, again, we'll take information from xt and ht minus 1 and pass it through the tanh value. So what we are doing over here is we are basically creating new set of candidate values, right? So we have it and ct over here. So ct is basically the new candidate values which we want. So we're done with the first two steps. In the first step, we decided what is the information which you want to forget. In the second step, we decided what is the new information which we're going to add into this cell state. Now let's head on to the third state. So in the third state, we basically have to update the old cell state ct minus 1 into the new cell state ct. So what we do is we multiply the old cell state ct minus 1 by ft. So this means that this is where we are forgetting the old things, or we are removing the old information. So ct minus 1 into ft. So ft is basically that information which we got from the first gate, and first gate is nothing but the forget gate layer. So when we multiply ft with ct minus 1, what we are doing is we are forgetting the old information. Now we'll add this with it into c cross t. So this term basically means what is the new information which we want to add to this layer and by how much value do we need to scale this. So the first term is where we decide how much information are we forgetting, and the second term is where we decide how much new information are we adding to the cell state, and we then just add it up and get the new cell state which is ct. So from ct minus 1 we are going to ct. So I'm again reiterating it. So this consists of two parts. So in the first part, we basically forget all of the information which is not necessary or not significant. And in the second part, we update or add the new information. So from CT minus 1, we reach till CT. And then we've reached the final part. So this is where we'll decide what part of the cell state that we're going to output. It's not necessary that the entire output is useful to us. So only a range or only a part of the information or the output would be necessary. So this equation which you see, so this is where we decide what part of the cell state we're going to output. So now after that, what we'll do is we'll put the cell state through the tanh and multiply it with the output of the sigmoid gate. And this gives us ht, which is basically our final output. So first we decide which part of the cell state we are going to output, and then we'll pass the cell state through the tanh function. This tanh function gives us a range which is between -1 to 1, and we'll multiply this with the output, which is basically our final result. So these are the 4 steps which are involved in an LSTM. So first we forget all of the insignificant information, and then the second step we add the information which is needed. Now in the third step we combine the first 2 steps, and finally in the fourth step we only output the information which is necessary from the cell state. So this is the entire working of long short-term networks. So let's say if we have 5 numbers like this, 5 consecutive numbers actually, 1, 2, 3, 4 and 5, and our task is to predict the next number, which would be 6. So this is our task, and we'll be implementing this with the help of LSTM. So we'll go ahead and import all of the required packages. So we'll import sequential from keras.models, we'll import dense and LSTM from keras.layers, and we'd have to split our data. So we'll import train test split from sklearn.model selection. And we'd also require the NumPy library and matplotlib library. So I'll go ahead and click on run, and I'll just wait till all of these packages load up. So now it's time to create my input data. So this code over here, it helps me to create 100 vectors of 5 consecutive values. So I'll store this in data, and let me have a glance at the first 5 vectors. So I'll click on run. So this is what I have over here. So this is the first vector where the consecutive numbers are 0, 1, 2, 3 and 4. And over here I have 1, 2, 3, 4 and 5. This is 2, 3, 4, 5, 6. So these are basically the first 5 vectors, and these comprise of consecutive values. Right. So this is basically my input data. Now I would also require my target data, which is basically the next number. So as I had already told you guys, what we want to do with respect to this model is we want to predict the next value for a consecutive sequence of inputs. So over here, this is our input, which is basically 1, 2, 3, 4 and 5. And we'd want to predict the next value with the help of our RNN, which will be 6. So what I'm doing is I am creating the next number for each of these arrays. So over here, it'll be 5, for this, it'll be 6, for this, it'll be 7 and so on. So I'll click on run. Right, so this is what I have. So for the first vector, the target is 5. For the second vector, the target is 6. For the third vector, the target is 7 and so on. Now, I'll go ahead and convert this data and target into NumPy arrays. So for that purpose, I'll use np.array and pass in the data object inside this, and also similarly pass in the target object inside this, and store it in data with a small d, and similarly store it in target with a small t. I'll click on run. Right. So now I have my NumPy arrays with me. Now I'll also have a glance at the shape of data and target. So this is the shape of data and this is the shape of target. Now this is basically helpful to me when I am giving these as parameters when I'm building the model. So now since I have the data, it's time to finally divide this data into training and testing set. So for that purpose, I'll be using this train test split method, and it takes in these parameters. So first is basically the data or the features. Next is the target or the labels, and I'm setting the test size to be 0.2. So this means that 80% of the records would be in the training set, and the rest 20% of the records would be in the test set. And I'll just give out a random state value of 4 so that I can get the same result when I want to run this model the next time. Right. So I'll click on run. And I have successfully divided this data into xtrain, xtest, ytrain and ytest. So xtrain over here, this basically contains all the training values for the features. Xtest over here contains all the test values for the features. Similarly, ytrain over here consists of all the train values for the target, and ytest over here consists of all the test values for the target. Right. So now we've divided the data into training and testing. Now it's time to create a model. And we are basically creating a sequential model over here. So I'll use the sequential method and I'll create an instance and store it in this model object. Right. So now it's time to add the layer. And the layer which we'll be adding over here would be LSTM. So I'll use model.lstm. So I'll say model.add and the layer which I'm adding is LSTM. So this takes in a parameter over here and this is basically the output size. So I want the output size to be equal to 1, which is basically I'm predicting a single number or a single value over here. And then we have the batch input shape. So the batch input shape basically takes in 3 values. So the first value is the number of inputs, second is the input sequence, and third is the length of the input sequence. So over here, if you don't know the number of inputs which you have, you can say it as none. And since the input sequence is 5, I said it as 5. And the length of the input sequence is 1, and I've given it as 1. And then we have another parameter over here, which is basically return sequences. So this return sequences basically means that do I want the output for each timestamp or do I just want the final output? So if I set it to be true, I'll get the output for each timestamp, and if I set it to be false, I'll just get a final result. So over here, I've set this to be false. Right. So now I have created the model. Now it's time to fine tune it. And to fine tune it, I'll use model.compile method, and it comprises of these 3 things. So first I'll set the loss which I want to minimize. So I want to minimize the mean absolute error. And then I'll set the optimization algorithm. So the optimization algorithm which I'm using is Adams. And then basically the evaluation metric which I want to use. So the evaluation metric which I'm using is accuracy. I'll click on run. Right. So now I've also compiled my model. Now let me just have a glance at the summary of this. I'll click on run now. Right. So we see that this is my LSTM model and I have my output shape over here. Now, since I've also compiled my model, it's finally time to fit the model on top of the train set. So for this, I'll use model.fit, and I'm basically fitting this model on top of X train and Y train. And initially I'll set the number of epochs to be equal to 50, which is actually less. And I want this to evaluate on top of the validation data. So validation data is basically X test and Y test. So I'm reiterating it. I'm fitting the data on top of X train and Y train, and I'm validating it on top of X test and Y test. I'll click on run. So the model fitting is done, and this is what we have, the final result over here. Now that we've fit the model, let me also go ahead and predict the values on top of the test set. So I'll use model.predict and I'll pass in X test as the parameter inside this. I'll click on run. Right. So I have predicted the values and I've stored the result in this results object. Now that is done, what I'll do is I will actually make a scatter plot which comprises of the actual values and the predicted values. So I'm representing the actual values which are present in Y test with green colored dots and the predicted results which are present in results with red dots. And I'll plot it out. Right. So these green dots which you see, these are the actual values, and these red dots which you see, these are the predicted values. So with the help of this graph, we understand that the prediction is totally wrong and our model is very bad. Now, along with this, we'll also make a plot of the loss. So plt.plot, and I'll make a loss plot. I'll click on run. Right. So you see that the loss of the model does not decrease at all, right? It stays constant. And that is why this is a very, very bad model. Now, this is because we have not normalized the data. So whenever we don't normalize the data, there might be chances of exploding gradient descent and the model turns out to be really bad. So that is why we have to make sure that our data is normalized. So I'll go ahead and do that. So I will basically divide the input data with 100. Similarly, I'll also divide the target data with 100. So what we are doing is normalizing the data. I'll click on run. Again, I'll click on run. Right, so now we have the normalized input and output data with us. Again, I'll go ahead and convert these into NumPy arrays. Again, I'll split this into training and testing set, build the model, add this, compile this. Now I'll go ahead and fit the model. I'll click on run. Right, so all of the 50 epochs are done and I'll predict it on top of the X test. Now again, I'll go ahead and plot the actual values and the predicted values. I'll click on run. Right. So this time we see that there's a bit of improvement, but then again, this is not much. So initially all the red dots were scattered over here. Now it's just that they have come up a bit up, but then again, there is no correct prediction at all. Again, let me print out this loss plot. So this time it's okayish, it is reducing, but then again the loss is not decreasing much. Now, what I'll do is I will go ahead and increase the number of epochs. So the number of epochs were 50, I'll change the number of epochs to 500. And let's see if there's a difference in the prediction or not. I'll click on run. Alright, so the model is being fit. Right, so all of the 500 epochs are done. Now I'll go ahead and predict this on top of the test set and again make a scatter plot of actual values and predicted values. So this time the prediction is much better. But then again, this is not 100% accurate. So now let me print out the loss plot again. Right, so this time the loss reduces in a better way. Now again, what I'll do is I'll increase the number of epochs again, and this time I'll set the number of epochs to be equal to 1000, and let's see what happens. I'll click on run. So now we've fit the model. I'll predict this on top of the test set, and again I'll make the scatter plot. I'll click on run. Right, so this time we see that the accuracy is very good. The predicted values and the actual values are very close. So the red dots are the predicted values and the green dots are the actual values, and we see that most of them are coinciding, right? And this is a very good result for us. So basically what we had to do was we had to normalize the data, and after that we had to increase the number of epochs, and this is how we could make correct predictions and reduce the loss. And just to be sure, let me again plot this loss. Right, so now we see that the loss is actually decreasing very well, and after that it stays constant, right? So this is the sort of loss plot we wanted. So this is how we could build an LSTM network which was able to predict the next number for a consecutive sequence of numbers.
Here's a quiz question for you guys. What is tokenization in text processing? Your options are converting text to lowercase, removing punctuation and special characters, breaking text into individual words or tokens, or translating text from one language to another. Please mention your answers in the comment section.
So it is a process of turning a string or a text paragraph into smaller chunks, and those chunks are also called tokens. Tokens can be sentences, they can be words, they can be even phrases or even symbols. When we extract smaller chunks or tokens from a huge text document, that process is called tokenization. We have some useful tokenization methods that we'll discuss here. So the first one that we'll discuss is called sentence tokenization, which we will use to extract all the sentences that are present in a text document. And then we'll move on to understand how can we extract individual words from a huge text document. And then after that, we'll use regular expressions to match patterns in our text document and only extract those words which match that regular expression. And then we have our blank line tokenizer, which will tokenize sentences even if they have spaces or blank lines in between them. It will ignore the blank lines and it will extract the whole sentence. So let's begin with our sentence tokenization. It is used to split a body of text into different sentences. To perform tokenization for sentences, we have to import the sent_tokenize function from the nltk.tokenize subpackage. After importing, we'll generate a sample text that we'll use for tokenization. I've used this text here that Google will shut down its job application tracking system Google had that was launched just 2 years ago. The company had built Hire with Diane Green, a former Alphabet board member. This is our sample text, and using this text and using the sentence tokenizer, we'll extract different sentences present in this sample. For doing that, I have initialized a variable called tokenize_text and I've set it equal to the send tokenize function. So our send tokenize function will take the argument, which is a sample text that we have generated here. So it will first of all extract all the sentences that are present in our sample, and then we have stored all those sentences in the tokenized text variable. So it will be a list of all the sentences that are present in our sample here, and then we can print the list using the print function. So when we print, we'll get all the sentences that are present in our sample text. You can see this is the first sentence that starts from here and it ends here, and the second sentence starts from here and it ends here, and the third one will start from here and end here. So we have 3 sentences present in our sample text. So now let's go to the Jupyter notebook and we'll implement the sentence tokenization on a sample text. Now let's implement. First of all, I'll import the sentence tokenizer from the NLTK tokenize package. So after importing, I have to run this line. So I'll run this line. So my send tokenizer will be imported from my nltk.tokenize package. So now after that, we'll generate a sample text. I've copied a text from a Google article. So I'll use this text and I'll extract all the sentences that are present in this text. So I'll just copy this and I'll generate a sample variable which will contain this text. So I'll paste my text here. So now we'll use this text to extract all the sentences that are present in this text. So I'll run this line to generate my sample variable. Now my sample text is generated. I will use the send tokenize to tokenize all the sentences that are present in this document. So I'll write sample because my text is stored in the sample document. This is our text document and I'll pass my text document to send tokenize function. So it will tokenize all the sentences present in the sample and I'll store the result in send tokens. So when I run this line, all of the sentences will be stored in the send tokens. So now if I want to print the first 5 sentences that are present in the send token, I'll write the line. So it will print the first 5 sentences that are present in the send tokens. So if I want to print the first 5 sentences that are present in the send tokens, so I'll use the following. So if I run this, we'll get the first 5 sentences that are present in our send tokens after the sentence tokenization. First sentence starts from here and it ends here, and this is our second sentence. The apps were removed by Google soon after, and this is our third sentence. So it starts from here and it ends here, and the fourth one is here, and this is our last sentence that we have in our send tokens list. So if I want to know how many sentences are there in my send tokens, I can just use the len function and pass my list, that is send token, and if I press Control Enter, so I'll get there are 9 sentences that are present in this sample text. After this, we'll use corpora, Gutenberg corpora from the NLTK corpus, and we'll extract the sentences present in the files that we have in Gutenberg corpus. First of all, we have to import the Gutenberg corpus from the NLTK corpus. So we'll write from nltk.corpus import Gutenberg, and after that I will import any one of the file that is present in the Gutenberg corpus. For importing a raw text file that contains all the text, so we have to use the method .ra for the Gutenberg. So I'll write Gutenberg.ra, and then inside the parenthesis we have to mention the name of the file that we want to import. We have a file name called brandstories.txt in the Gutenberg corpus. So we'll import the raw text file. So this file will contain all the raw text, and I'll store it in your sample text, and then we'll use this sample text to tokenize all the sentences using the send tokenize function. And I'll store all my sentences present in this file in tokenized text, and then I have printed sentences from the 5th, so this 6th sentence to the 14th sentence, it will be printed. These are our sentences from 6 to 14. So now let's go to the Jupyter notebook to implement this. We'll start by first of all importing the Gutenberg corpus from the NLTK corpora. For doing that, I'll write from NLTK corpus import Gutenberg. Once I press Control Enter, my Gutenberg corpus will be imported. Now I want to import a text file from the Gutenberg corpus that we'll use as a sample text for tokenization. So I'll store the text in a variable called sample, and then I'll use the Gutenberg corpus and the raw method of the Gutenberg corpus that will extract all the text that is present in a file. And inside the parentheses, I have to mention the name of the file. The file I'm importing is called Bible KJV. So this will import this raw text file, all the text that is present in this file, and the text will be stored in the sample. So once I run this line, my sample text is generated. So now if I look at the sample text, so you will see we'll have a lot of all the text that is present in our text file. So if I want to extract only sentences from this whole text file, I'll use the send tokenizer, extract all the sentences. So I'll store all the sentences in send tokens. Then I'll use the send tokenize function to extract the sentences. And inside the parenthesis, I have to mention the text from which I want to extract all my sentences. So that is our sample. So now when I press Control Enter, all the sentences that are present in this text file will be stored in send tokens. And now if I want to print first 10 sentences from this list here, so I can just write send tokens, and it will print the first 10 sentences that are present in our send token. So this is our first sentence. It starts from here and it ends here, and the second is this one. And similarly we have the first and the 10th sentence is this one. So these are the first 10 sentences that are present in this text file. So now the next function that we'll use is word tokenize, that will extract all the individual words present in the whole text. For that I would have to import the word tokenize function from tokenize sub package in the NLTK package, and then I will take a sample text from which I will extract all the words, and then I will use the word tokenize function and I'll pass my sample text, and all these words will be stored in TOK object, TOK variable. So it will be a list of all the words. And now if I want to print the first 20 words, I'll use print this statement, and the first 20 words that are present in this text will be extracted and they are present in form of a list. And similarly we can use corpus. Here we have used the genesis corpus that is also present in the NLTK corpora folder. So if you go to NLTK corpora folder, you will find a corpus named genesis which has a text file named english.kjv.txt. So we have imported first of all the genesis corpus and the word tokenize function, and we have stored all the text that is present in this file using the .ra method of genesis corpus, and I have stored all the text in sample. So our sample contains all the text, and then we have used the word tokenize function on this sample, and all the words that are present in this text file will be stored in TOK variable, and then we have printed the first 30 words. The first 30 words you can see in the beginning God created. So all these words are separated and they are stored in form of a list. So let's go to Jupyter Notebook and we'll perform it on a corpus. So we have same corpus, that is Bible KJV. So I'll use this corpus and I'll use the sample text that we have, and I'll extract all the words that are present in this sample. So now first of all I'll import the word tokenize function from the NLTK package. So after I run this line, my word tokenize function will be imported. Now I'll use the sample text and I'll extract all the words that are present in the sample text. So I'll store the words in word tokens list and I'll set it equal to, use the function word tokenize, and I'll pass my sample that I've created above. Now when I run this line, all the words that are present in the sample text will be stored in word tokens. So after that, if I want to print the first 50 words, I'll just write words tokens. Now if I run this line, first 50 words of the sample text will be extracted and stored in the form of a list. You can see we have this also as a word, as a single token, and this also as a single token. So every single, even if there is a symbol or a punctuation mark, that will also be stored as a. Now the third function that we'll use for tokenization is regular expression tokenization, which is regx tokenizer. This is the function. So in this function we actually pass a regular expression, and it will match all the words that are present in our text with that regular expression, and it will extract all those words. So for example, first of all we have to import the regx tokenizer from the NLTK tokenize. By running this line, you will import the regular expression tokenizer, and then we have a sample text here which we'll use for extraction, and then we have to define a regular expression which will be used to match every single word that is present in this text document. And according to the regular expression, if the words match the regular expression, those words will be extracted and stored in our cap word tokenizer list. First of all, we have to import the class. So this is a class regular expression tokenizer. So we have to initialize the class. So this is an object of the class. We have named the object as cap word underscore tokenizer, and in the class arguments, when we initialize the class, we will pass our regular expression. This is the regular expression that we'll use to extract all the words which begin with a capital letter. This is a group of words, so it will start with a word and it will find any word that's lies in this range. So if a word begins with any of these letters that lie in A to Z, so it will take that word, and then slash is an escape character. For W plus means any word after a capital letter. So if there is any word which starts with a capital letter and there is any other word, any other letter after it, so it will pick all those words. It will store in cap word. So now we have to use the dot tokenize method of the cap word object to tokenize these sentences, tokenize this text, and we'll write cap word tokenizer dot tokenize. Then we'll pass out sample text, and then when we run this line, all those words which match this regular expression will be extracted and will be displayed. So let's go to the Jupyter notebook and extract different words according to a regular expression. First of all, I will start with importing the regular expression tokenizer class from the NLTK tokenize. I'll write from NLTK tokenize. I've imported the regular expression tokenizer class. Now create an object of this class that we'll use for performing regular expression tokenizer. So I'll name the object as regex tokenizer, regex tokens, and then I'll initialize the class. And now I have to, inside the parentheses, I have to mention a regular expression that will be used to match all the words that are present in our text document to extract those words. So I have to write commas, inverted commas, and inside this I'll mention my regular expression. So if I want to match all the words that contain a number, or all the words even if they don't have a number, or all the numbers if I want to extract from my text document, so I'll pass a range, so it will search for all these numbers. Then even if there is a word after the number, it will also extract those tokens. So my regular expression tokenizer will extract all the numbers, and even if there is any word after the number, it will also extract those tokens. So I'll initialize this class. Now we'll use the object instance of this class to extract tokens which match this criteria from our sample that we have used above. So this is our sample, that is viable KJV sample from the Gutenberg corpus. Initialize, I'll use the object that is regex tokens, and there is a method called tokenize. So I'll use the method tokenize, and I'll pass the sample that I have generated above. So once I run this line, you will see all these numbers that are present in our text document are extracted. You can see after the number there is a comma, inverted comma, so that is also extracted. So all these numbers, there is no number which has any word after it, so all these numbers are extracted from our text document. So the next method that we are going to use is called the blank line tokenizer. Blank line tokenizer is used to preserve a sentence even if there is a blank line in the middle of it. So if we have a sentence and in between the words of that sentence there is a new line character which is /n, so that sentence will be preserved and a new line won't be created. So on the background, this function actually uses the regular expression, this regular expression, to match all the tokens. We'll start off by importing the blank line tokenizer class from the nltk.tokenize. So after importing, we'll create a sample text. This is our text where the text says that good muffins cost $388 in New York, and you can see there is a new line character in between the words, and here also there are new line characters. So once we initialize the class blank line tokenizer, and then we use the tokenize method of this class, and we'll pass our sample text. So once we do that, so our two sentences will be extracted, and you can see the first sentence starts from here and ends here. So it did not treat it as a new sentence. It preserved all the blank lines that are present in the sentence. And the second example is also a sentence where we have, this is the first sentence, so there was a very loud beep is the first sentence, and the next sentence starts from here, and there is a blank new line character in between, and here also there are new line characters. So once we tokenize this using the blank line tokenizer class, so we'll see that we have sentences, but the new line characters or the blank lines are preserved. Now we'll go to Jupyter notebook and we'll implement the blank line tokenizer. First of all, we'll start by importing the blank line tokenizer class from the nltk.tokenize. start by importing the blank line tokenizer from the NLTK tokenize package. Once my class is imported, now we can define a sample text which we'll use for blank line tokenization. So I'll write a sample here. So this is my sample. This is the words that we are using. So good muffins cost $3.88, and there is a new line character and there is a space also. So it will preserve these new line characters and spaces as well. So I'll initialize the blank line tokenizer class, and I'll use the tokenize method of this class to tokenize the blank lines and sentences. And pass my sample text to this function, and then when I run this, so after importing the blank line tokenizer class, now we'll define a sample text that we'll use for tokenization. So I'll just write sample. I've copied the text, so we'll use the same text to tokenize all the blank spaces or new line characters that are present in the text. So I'll initialize my blank line tokenizer. So I'll firstly run this line to create my sample variable. Now my sample text is created. Now I'll initialize the blank line tokenizer class, and I'll use the dot tokenize method to tokenize the text. So I'll pass my sample text into this function, and so now I'll initialize the blank line tokenizer class, and I'll use the diff tokenize method of that class to tokenize my text. So after that, now I'll initialize my blank line tokenizer class. So I've initialized the class, and then I'll use the tokenize method of this class to tokenize the sample text. So I'll pass the sample text into this method, and then when I run, so I'll get two sentences because this sentence contained a new line character and spaces as well. So it has preserved this whole sentence, two sentences, and then we have the other sentence that is thanks. That is how we use blank line tokenizer to preserve new lines or spaces present in the text. Text into sentences and regular expressions or words. Now we'll understand what is frequency distribution and how we can leverage frequency distribution. So after performing tokenization using send token, word token, and regular expressions, now we'll understand what is frequency distribution and how can we use frequency distribution to get more insights of the text. Frequency distribution is basically, it represents the word frequency in a text. So it will count all the word frequencies and it will display a list of tuples where the first element of the tuple would be the word itself and the next element of the tuple would be the number of occurrences of that word in that text. So we'll use this to gain insights from the data, and we'll see which are the most common words in our text data, and then we can use that information to extract different information from the text, and we can analyze the text further. So for doing that, first of all, we'll import the word tokenize to tokenize the words. That is the first step. And then we are using the Gutenberg corpus from the NLTK corpus as a sample text, and then we have to import the frequency distribution class that contains the functions to perform frequency distribution. So after that, we'll create a sample text which is from the Carol Alice.txt file which is present in the Gutenberg corpus. We'll import the raw text file from this corpus and we'll store it in sample, and after that we'll tokenize all the words. We'll extract all the words that are present in this corpus and we'll store the words in tokenized words. So after we have all the words that are present in this corpus, we'll use the frequency distribution class and we'll pass tokenized words as an argument. So it will count the frequency distribution of every single word and it will store that in fdist. So this is our object that we have created, fdist of this class. So this object contains the information of the word frequencies of all the words present in the text document. So after that, if you want to find which words occur the most in our text document, so we'll use most common method of the fdist object. So we'll write fdist dot most common and 20. So this will print the 20 most common words that occur in the text. So as you can see here, this comma, it occurred 2418 times in the text file, and the occurred 1516 times. So you can see that we have a lot of punctuation marks that don't mean anything. So if you want to extract important words, there is only one important word that you can see here is Alice, which is 394 times. So from here you can actually get the information that this text has something to do with Alice. And we can do the same thing by plotting the frequency distribution. We use the same object, that is fdist. We use the dot plot attribute or dot plot method of this object, and when we write 20, so it will print the 20 most, it will plot the graph for the 20 most common words that occur in the text. Here you can see that the only word that makes sense is Alice. Other words are not as useful. So to implement frequency distribution in Python, we have to import the frequency distribution class from nldk.probability. And the first step is to create a sample text or a sample document from where we can extract the frequency words and then plot their frequency distribution. Firstly, we'll create a sample, and after creating the sample, we'll tokenize all the words that are present in the sample. And after tokenizing all the words that are present in the sample, we'll create a frequency distribution using the frequency distribution class. So I have imported the word tokenize function from nldk.tokenize, and then I have imported the Gutenberg corpus from nldk.corpus, and then we have for the frequency distribution the frequency distribution class from nldk.probability. And after that, I have imported the raw file, that is carolalice.txt from the Gutenberg corpus, and I have stored the text in sample text. So after creating the sample, now we'll use the word tokenize function to tokenize, to extract all the words that are present in this sample. So for doing that, I have used the word tokenize function and I have passed my sample into it, and it will extract all the words that are present in the sample, and it will store the words in tokenized words. So after we have the list of all the tokenized words, we will pass our tokenized words to the frequency distribution class, and we will create an instance of that class that is named here as fdist. So then if we print fdist, it will show us that how many samples exist, or if we just write the fdist, then it will print us all a dictionary which will contain the keys as the words and the value for the keys as the word counts. So let's see how we can implement this in Python using the Jupyter notebook. So we'll start off by importing all the required libraries. First of all, I'll import the word tokenize function to tokenize my words from nltk.tokenize. Now I'll import the Gutenberg corpus from where I'll pick a text document, text file. After that, now we have to import our frequency distribution class, which we'll be using for creating a frequency distribution of the words. So I have to import it from nltk.probability. So I'll run all this code to import all the required libraries. Now after importing, I'll create a sample text so that I can tokenize all the words from it. For doing that, I'll store my text in sample, and I'll use the Gutenberg corpus, and I'll use the raw method to import a raw text file which contains all the text present in that file, and I'll use the Carol Alice. Once I run this line with Control Enter, so my sample, now it will be generated, and all the text that is present in the Carol Alice file will be stored in the sample variable. So now after we have all the text, now the first step is to tokenize the text, which means to extract all the words present in the text. So I'll use word tokenize for extracting all the words from this text. So I'll store my words in word tokens. I'll use the word tokenize function and I'll pass my sample into it. So once I press Control Enter, now all the words that are present in the sample will be stored in the word tokens. So now if you want to know what is the frequency distribution of every single word that is present in the sample or word tokens, now we'll use the frequency distribution class. So we'll create an object of this class, and let's call it frequency, FREQ. And then now we'll initialize the class. And this class takes one argument, that is of words, all the words that we want to count frequency for. So I'll pass my word tokens into it. Now if I press Ctrl Enter, all the words along with their frequencies will be stored in the FREQ variable or object. So now if I print FREQ, so you will see we get a dictionary. The keys of this dictionary are the individual words that are present in this text document, and the values are the number of word counts. So how many times this word is appearing in this text document, it will be printed as the value for this keys. So our frequency object is FREQ. So now we'll use this object to print the most common words that are present in our text document. We'll add the object name, then we'll use the most common method of this object. And then we can mention how many words we want. So if I want 30 most common words that occur in my document, so I'll add 30, and when I press Ctrl Enter, the 30 words that occur most in my document will be displayed. And out of all these words, you can see the only word that conveys some information to us is Alice. So if we can think of it as this document as it has something to do with Alice. And if we want to plot this frequency distribution instead of printing it, so we can use the plot method of this object. So I'll plot the 30 most common words that are present in the text document. So now you can see and that these are the words that occur in my text document. The is occurring around 1500 times and Alice word is occurring around 400 times.
Let's have a quick quiz question, guys. Your question is, what does natural language processing or NLP refer to? Your options are a method for identifying plant species in the wild, a subfield of computer science that deals with human-computer communication, a branch of linguistics focused on studying regional dialects, or a technique for extracting information and meaning from human language. Please mention your answers in the comment section.
We'll understand what are stop words and why we need to remove these words from our text document in order to gain more insights and clear insights from our text data. So stop words are basically the useless words that we have already seen in the frequency distribution that don't convey any information to us. Instead of keeping these words, we'll remove these words. So English has some stop words and these stop words are actually present in the NLTK corpus. If you go to NLTK corpus folder, you will find a corpus named stop words, and in the stop words we have different text files which contain stop words for different languages, 16 languages, and I will import the English version, English stop words. So for importing stop words, we just have to import the stop words from nltk.corpus, and then we'll store these stop words in stop_words list, and we'll use the set argument. So the set argument will arrange these words in an ascending order starting alphabetically. All the words that are present in the English stop words text file will be stored in stop words, and once we print these stop words, we'll get all these stop words, which are like words that occur most of the times in your document and they don't convey any information to us. After importing these stop words, if you want to remove these stop words from our text document, so here's a method that we have used. First of all, I imported the sendTokenize and wordTokenize functions from nltk.tokenize. Then I've created a empty list which is called filter words, and then I have imported the Carol Alice text file from the Gutenberg corpus, and I've stored all the text in sample. So now firstly we'll tokenize all the words that are present in the sample using the word tokenize. All the words will be stored in tokenize_word. If we want to remove the stop words from this tokenized words, we can use this code here. We have used a for loop, so it will iterate through every word that is present in tokenized word, and it will check if that word is in stop words or not. So if the word that is present in tokenized word is not in stop words, then it will continue and it will check whether the length of the word is greater than 3 or not. If the length is not equal greater than 3, it will not continue within the loop, and if the length is greater than 3, then it will append that word in the filtered word. So in the filtered word, we'll only have words that are not present in the stop words, and all those words which have a length greater than 3 characters. Once we write 3, so it will remove all the punctuation marks as well. This is a handy method to remove punctuation marks. So at the last, we'll get a filtered word list which will contain all the words. So after we have our filtered word list, then if we create a frequency distribution of all the words present in our filtered word using the frequency distribution class. And now we have 2733 samples. So now you can see a lot of words have been removed from this sample. And now if we print the 20 most common words, so now you can see we get a lot of information from the words because the punctuation marks and the stop words were removed. So you can see we have Alice, and we have Queen, then we have King, then we have Turtle, Mark, Hatter, Gryphon. All these words actually convey more information to us than all those words which were before. This is one step in pre-processing, that we have removed all the stop words and all the punctuation marks. And if we plot now the frequency distribution of all the words after removing the stop words, so you can see the word that occurs most of the time is Alice. So now we are pretty sure that this text has something to do with Alice. So this is how we make our machine or computers understand the text using pre-processing. So now let's go to the Jupyter notebook and we'll implement how to remove stop words from a text document. So I'll start by importing the stop words corpus from the NLTK corpus. So my stop words corpus is now imported. So now I will store all these stop words and all the English stop words in a list called stop words, stop_words. So now when I mention the name of my corpus, so I can use the words argument, so it will extract all the words directly from a corpus. So now I have to mention which corpus I want. So I want the English one, so I'll write English, and then I use this set function to arrange these words in a alphabetical order starting from A. So now if I write the set function, if I run this, now my stop words are stored in this list. Now if I print my stop words, so now you can see these are all English stop words and that are imported. You can see there is no ones other which we have until. So these words don't convey any useful information to us, so we remove them before performing any text analysis. So after importing stop words, let us import a corpus or a sample text from which we'll remove these stop words. So if I go to my NLTK corpora folder, and you'll find there is a corpus called Genesis, and in this Genesis we have different text files. So I'll import the English web text file from here. So this is one document in our corpus. There are several documents in a corpus, and once I open this, you can see we have a lot of text here. So now for importing this, first of all I have to import the Genesis corpus from the NLTK corpus. So after importing, I'll import the raw text file, that is English web, from this corpus, and I'll store it in sample variable. So this will import the raw text file, and I'll englishweb.txt. So now my sample, all the text that is present in englishweb.txt will be stored in the sample. So now next step is to tokenize all the words that are present in this sample. For doing that, I'll store the words in word tokens list, and I'll pass my sample in this. So now my word tokens, all the words that are present in the englishweb.txt will be stored in the word tokens. So now there will be stop words and punctuation marks, everything will be present in these words. Now we want to remove the stop words and single line characters as well. So we'll create a new list, that is, we'll call that filtered words, and then we can define which words we want. So we can define it in using for loop in multiple lines, and we can also define it using a single line. So I'll write the single line version here. So it will take all the words that are present in word tokens. Now it will take all the words W here for W in word tokens. So it will iterate through all the words that are present in word tokens, and it will check if the word is not in stop words. So our stop words is this list which contains all our stop words. So if the word that is present in word tokens is not present in stop words, then only it will take those words, and it will also check this condition, which is it will take only the words which have a length of more than 3, and it will store all these words in this filtered word list. So once I run this, I'll get a list filtered words with all the stop words removed and single line and punctuation marks also removed. So now if you want to print the frequency distribution of all the words, So I'll create a frequency distribution. I'll store it in FREQ, and I'll use the frequency distribution class, and it takes the words. So our words will be filtered words as an argument. So now my filtered words is created. Frequency distribution of all the words that are present in filtered words is created. So now if I want to know what are the most common words that occur in this whole text, so I'll use the object and I'll use the method called most common, and I'll print the 20 most common words. So you can see these are the 20 most common words. We have Jacob, Yahya, Joseph, Abraham, Pharaoh, Isaac. So you can clearly see it is something related to the Bible. And if you want to plot these words, so we'll just use frequency.plot. So we'll plot the 20 most common words, and here also you can see that the Jacob is occurring most number of times. Then there is Yahya, then is Joseph, and Abraham, Pharaoh. This is how you remove all the stop words. This is a one-liner, so you can remove using multiple lines, or you can use simple one-liner, and it will remove all the words which are called stop words. So after removing the stop words, now we'll move on and understand what are bigrams, trigrams, and n-grams. Bigrams are two consecutive words that occur in a text. So if we have a text where our words are in such a way that two words convey more information to us than a single word. So suppose if we have an article about Harry Potter, if we want to know without actually reading the article what it is all about, so if we just tokenize single individual words, so it might not convey the meaningful information to us. So instead, if we tokenize two words at once, so definitely the Harry Potter word will be together. So that is why we use bigrams or trigrams, that will be 3 words, and we can use multiple words 4 and 5 in order to check whether we get more insight from the text data or not. So for implementing bigrams, we'll start by importing the web text corpus in our NLTK corpora, and we'll also import the stop words. Then we have to import the bigrams function from the NLTK package, and then we'll first of all, if we import a text for the first time, we can also pre-process that text using the wlower function. So if we have Harry Potter, which occurs in the beginning, if there are caps in front of it and there are lower caps or upper caps of the same word, while creating bigrams, those two words will be treated differently. But if we have a same word with lower caps, and that word will be counted as single word. So if we have two words but they are in different caps, so that will be counted as two words. If we lower the words, then they will be counted as a one word. So that is also a pre-processing step for text analysis. So we'll store the text words from the web text corpus. The web text.raw will import the raw text file, all the text that is present in this file. And if you use the words method, so it will import all the words, individual words. But this won't be possible for every text document. It is possible only for corpus. So for other text documents, we have to use tokenization. So if we have imported all the words that are present in pirates.txt file using webtext.words, and it will lower, all the words will be in lowercase. And then if you want to remove the stop words, you can use a single line like this, or you can use the multiple lines. So you will create a empty list. First of all, we'll store all the stop words in stop_words list, and then we'll create an empty list filtered word, and then we'll use the for loop, which will iterate through every single word in our list. It will check if the word is present in the stop word or not, and it will take only the words which have length greater than 3 characters, and all those words will be appended in the filtered word list. So after creating bigrams, after creating the filtered word list, now if we want to create bigrams, we'll use the bigram function and we'll pass our filtered words list, and we'll store this in A. So here A is also a list with 2 words. So if we plot the frequency distribution, first of all we create a frequency distribution using frequency distribution class, and we'll store it in fdist, and then we'll use the most common at method to print 20 most common words that occur in the text. So you can see here we get the 20 most common words that occur in the text. We have Jack Sparrow, Elizabeth Swann, Davy Jones, Black Pearl, Flying Dutchman. This gives us all the bigrams that are present in our text. So you can clearly see it is something about the Pirates of Caribbean. Before moving to trigrams, let's go to Jupyter notebook and implement this code. So I'll start by importing the bigrams from the NLTK package. And after that, I'll import a sample text from my web text corpus from the NLTK corpus. I'll import. So now I've imported the web text corpus and the bigrams function. So now I'll take all the words that are present in the pirates document, pirates text file in our web text. So I'll create a list. I'll directly take the words instead of taking the whole text. So I'll create an empty list. Now I'll store all the words in this list. So I want to keep my words to lowercase, all the words, and it will take all the words that are present in web text.words. It will take all the words that are present in pirates.txt file in the web text corpus, and if we want to remove the stop words, we can directly write it in one line. We have already created the stop underscore words list above, so we'll use that list. So if you're running this for the first time, so you have to import the stop words and store it in a stop words underscore list, and then you can remove these words from your text document. And we'll mention another condition that take only the words which have length greater than 3 characters. So now if I run this, now all my words which are present in pirates.txt text file and which are not stop words, after removing the stop words, and all the words having length more than 3 characters will be stored in words list. So now if I create a frequency distribution of these words, so if I print, after creating the frequency distribution, if I print the most common 20 words, now you can see we have different 20 most common words, but the Jack is different, Will is different, Sparrow is different, Elizabeth is different. That is why we use bigrams and diagrams to actually gain more insights from the data. Now I'll create bigrams from these words. For doing that, I'll create a list called bigram, and my function is bigrams, and I'll pass all my words into this. So now my bigrams will be created, and now I'll create the frequency distribution for the bigrams. It is bigram, the list name is bigram. So now after creating the frequency distribution, I'll print the most common 20 words, and now you will see we have Jack Sparrow, Will Turner, Elizabeth Swan, Davy Jones, Black Pearl. So this completely changes the information that we get by just using the bigram. So after understanding what are bigrams, trigrams and n-grams, now we'll move on to stemming, and we'll understand what stemming is and why and how we use stemming in text preprocessing for text normalization. Stemming is a process for text normalization which involves the reducing words to their root or base forms. So if we have two sentences or more than two sentences which contain a word with their derivational affixes, for example, we take a sentence which has the word like, and we have another sentence which has the word likely. When we use these words for stemming, they will be trimmed down to their base forms, that is like, and in stemming we don't have any morphological analysis, so you'll find a lot of these words after stemming, they don't actually belong to the dictionary, they don't have a meaning, but still the words which are stemmed, they will have a base form, and then we can use that base form to create words by just adding the derivational affixes, that is ing or ed, the tenses without the tenses. Derivational affixes means tenses here. So to perform stemming, we have a class named Potter Stemmer in NLTK. So we'll import the class Potter Stemmer from nltk.stem, and then we'll initialize the class and we'll define where an object or an instance of that class, that is PS, and then I've imported send tokenize and word tokenize in case we want to tokenize sentences or words from a text document, and then I've defined some example words. So you can see the word is like, then likely, liking, liked, then unlike, and then when I perform stemming on these words and I print each of the words that is present in example words list, so you'll get the first 4 words like, likely, liking and liked, they have the same stem, that is like, and the word unlike has a stem unlike. This last one does not have any vocabulary, but in stemming we don't include vocabulary. If there is any word unlikingly or unliked, it would have the same stem. And we can also perform stemming on a complete sentence. So I've imported the Potter stemmer class from NLTK.stem and have initialized an object, instantiate an object PS, and then this is my example test. So driving a self-driving car might not be fun for a professional driver, but for a lazy driver, a self-driving car saves a lot of driving. When we firstly tokenize the words from this sentence, after tokenizing we'll store the words in words list, and then we'll iterate through the list, and after iterating through the list we'll print the stemmed version of each single word that is present in this list. For driving, you'll see that we have the stemmed version, that is drive, and for this driving we also have the same drive, and then for a professional we have profession, for driver we have same driver, and similarly you can see the other words, so it will be the stemmed version of those words will be printed. Let's implement this in Jupyter Notebook. So for performing stemming, first of all we'll import the Porter stemmer class from the nltk.stem subpackage. Once we have imported this, now I'll import the word tokenize, so then I can tokenize the words. Then the next step will be to find the stemmed version of those words. So I'll import from NLTK tokenize. So after that, then I'll store all the words that are present in this file. So I'll store it in words list. So I'll use the word tokenize function. Then I have to import first of all the state union corpus. Now I've imported the state union corpus. Now from the state union corpus I will import the 1961 Kennedy file. I'll import the raw text file. So for that I'll write this command state union, and I have to import the raw text file. So all the text that I want from this file, I'll write this, and it is a text file. So when I run this, all the words from this file will be stored in the words. So now if we want to print the stemmed version of all those words present in the words list, we'll first of all instantiate a Porter stemmer class object which we'll use for stemming. And the name of the object is PS. Now I have instantiated an object of this class. Now we'll use this object to print the stemmed version of the different words that are present in this words list. So I'll iterate through every word in the words list, and I'll print the stemmed version of these words. If I run this now, it will print the stemmed version of every single word that is present in the words list. So you can see the first word was president, so it has stemmed it to present. So even if it doesn't make sense, still the stemming does not include any vocabulary or morphological analysis, so it will still write present. And for Kennedy, I wrote Kennedy here, and for message it has stemmed the word message to MESSAG. And similarly for president, it has stemmed the word to president. Similarly, you can see there are a lot of words here in this file, and they will have the same words will have the same stemmed version. In lemmatization, it is a process that involves reducing words to their base forms, but this time we'll use vocabulary and morphological analysis, so that after reducing words to their base forms, they belong to a vocabulary and they have a meaning, and also different morphological analysis will also be performed. So if tenses will be changed, and you will get the base tense of every single word that we lemmatize. So it will bring the context to the words, which is not done in stemming. So to perform lemmatization using NLTK, we have a class in NLTK.stem, which is WordNet Lemmatizer. So we'll import this class first from NLTK.stem, and then we'll instantiate this class with an object lemmatizer, and then we'll use this object with the method lemmatize, and then we'll pass our text or our strings that we have or our words that we have, and every single word will be lemmatized to its base form. So you can say we have the corpora, which is plural of corpus, so it has been lemmatized to corpus. And then we have cacti, which is a plural of cactus, so it has been lemmatized to cactus. The lions has been lemmatized to lion. And then we have rocks, which is lemmatized to the base form, that is rock. And then we have geese, which is a plural of goose. So every single word has a vocabulary associated with it. And we can also mention the part of speech of that word. So if the word is an adjective, we can write A. The word is a verb, so we can write V. according to the part of speech, those words will be lemmatized. So if we lemmatize the word better, giving the argument that it is an adjective, so it will be converted to good. And if we lemmatize the word best, according to the adjective, it will be still kept as best. And for runs, it will keep run. And for if we mention the part of speech as verb, so it will also keep the same lemmatized version, that is run. So for similar words, we have the same lemmatized and stemmed versions. So now let's go to the Jupyter notebook and implement lemmatization using WordNet lemmatizer. So we'll start by importing the WordNet lemmatizer class from nltk.stem. Once I import this class, now I can use some, first of all, I'll instantiate this class, create an object of this class, so you can use that object to perform a lemmatization. So I've created an object PS. Now I'll define a words list. It can be any words, so I've copied one list. So we have cats, feet, bats and corpora. So let's see what is the lemmatized version of these words. We have to use the .lemmatize method of this object to lemmatize the words. So we get the cats. For the cats, the lemmatized version will be cat, and for feet it will be foot, and for bats it will be bat, and for corpora it will be corpus. So later on in this course, when we use machine learning algorithms to perform text classification, so we'll use the lemmatization technique to reduce words to their base forms. So when we prepare data for our machine learning algorithms, our data will be in a cleaned form. So this is a pre-processing step that we'll use later on. So after understanding lemmatization, let's move on to the part of speech tagging, which is actually used for categorizing words into their grammatical groups. So in part of speech tagging, the task is to label each word in a document, in a text document, with its grammatical group. So we'll label a word if it is a noun or a pronoun or a verb or an adjective or an adverb. So we'll use this for categorizing and understanding the syntax of different words that are present in our text document. So these are some of the tags that will be attached to our words that are present in our text. The word has a tag as CC, so it means it is a coordinating conjunction, and if it has a tag of NNP, it means it is a proper noun, singular. And then for JJ, it is adjective, and for there are a lot of other parts of speech. So for those, there will be a different tag attached to every single word in the text document. So let's see how we'll use part of speech tagging using the NLTK package. So here I have imported NLTK package, and then I have imported the word tokenize to tokenize all the words present in the text document. So this is our text document. So I have stored it in sample text. So the Google has actively been purging malware-laden apps from Play Store. And this is our text document. Now the first step is always to tokenize the words. So I'll perform the word tokenize on this sample text, and I'll store all the words from this text in tokenized text. So when I print this, you'll see that all the words that are present in this whole text document are displayed. And the next step now is the part of speech tagging. So we have a function called POS tag in NLTK. So once you import NLTK, then we can use this function. So I'll write NLTK.POS underscore tag, and then I'll pass the words that are present in the text document. So my words are stored in tokenized text. So I'll pass my words in tokenized in NLTK.part of speech tagging. So every word that is present there will have a label attached to it. So you can see the Google has been classified as a personal pronoun, and has is a verb, past form of verb, and RB is adverb, and VB is also a verb, and malware laden, so this is classified as tagged as an adjective, and apps has been tagged as noun, and from is tagged as interjection, and the is tagged as DT. So those are called determinants. So DT is determinant, and similarly we have for every single word that is present in our text, tag has been attached, and it is returned as a list of tuples. The first element of the tuple is or word, and the second is the part of speech tag. So now let's go to the Jupyter notebook and implement on this part of speech tagging on a corpus. So I'll start off by importing the POS tag function from the NLTK package. So I'll let once my function is imported, now let's go to the state of the union addresses. So we'll take the 1996 Clinton address. So we'll take this file, take this document, and we'll import all the words, tokenize all the words present in this document, and then we'll attach a part of speech tag to each word present in this document. First, let us extract all the words using word tokenization. So I have already imported the state union corpus. So I'll import the raw text file, and we have the 1996 Clinton text. So all my words will now be stored in words. So now let's print the POS tags of each single word that is present in words. So once I run this, so I have all the words along with I have a list of tuples, and the first element of the tuple is the word itself, and the next element is the POS tag associated with that word. So the president has been classified as a personal, as a proper noun, and then we have interjection before is tagged as interjunction, and we have most of the personal proper nouns, and there is a preposition you. So for every single word there will be a tag attached to it. So later on we'll use these tags to understand the syntactical structure of sentences and how we form sentences and how we make computers understand how to make sentences. So we have used the part of speech tagging to tag different parts of speech that are present in our text. So after that we'll use named entity recognition to identify different entities present in our text. So if there are any people, places, organizations, or locations that are present in our text, so we'll use the named entity recognition to identify those words. So named entity recognition is used to identify important named entities in text, such as people, places, organizations, location, even dates, so work of art. So these are different tags that our named entity recognition will assign to all the words that fall in this category. So if there is an organization, so it will be tagged with organization, and then we have location, so any particular location will be tagged with location. Then we have geopolitical entity, which is any country or a state or a province, and we have date, time, person, so any person will be tagged with the named entity as person. So to perform named entity recognition, we have to use the NE-chunk function that we'll use. So first of all, we will import the 2005 George W. Bush State of the Union address from the State Union corpus. I have imported the word tokenize and the State Union corpus, and I have imported the raw text file from that is 2005 George W. Bush address, and then I have tokenized all the words from this text file, and these are all the words that are present in this text file. So the next step in named entity recognition after tokenization is attaching a part of speech tag. Once we attach a part of speech tag using the POS tag function from the NLTK, so we'll pass our tokenized words to an POS tag function, and then it will attach a part of speech tag to every single word that is present in the tokenized text list, and that will store the result in POS words. So after that, to perform named entity recognition using NLTK, we will import the NE-chunk named entity chunk function from the NLTK, which will chunk all the named entities present in our text. So we'll first of all import, and then we'll store the named entities in NER words. So use the function NE_chunk, and we'll pass the part of speech tags. So this will be the words along with their part of speech tags, and then all those words which belong to any category of named entities, all the named entities will be assigned a category according to these rules, these categories. Once we have processed this, we'll store the result in NER words. So when I print NER words, you can see that George has been classified as a person, and address has been classified as an organization, and joint is also tagged as an organization, and we have Congress as an organization. So a lot of times you will find that wrong classification also, so it is still improving. For some words it will have the correct tags, for some words it won't have the correct text. So now let's go to the Jupyter notebook and implement named entity recognition on a corpus. So after importing the Gutenberg corpus, I'll extract all the words and then assign a part of speech tag. So I'll store it in part of speech words, and then first of all I'll tokenize all the words, and I want from the Gutenberg corpus the raw file, which is edgeworthparents.txt. So all the words from this file will be tokenized, and then I want to add a part of speech tag to every single word. So I'll wrap this whole thing in part of speech POS tag function. This function will extract all the words that are present in this file, and it will tokenize, and then it will attach a part of speech tag and will store this in POS words list. So once I run this, my part of speech tags will be associated. Now if I want to find all the named entities present in these words, so I'll import the NE-chunk function from NLTK. I'll import the NE-chunk function, which is named entity chunk. So I'll use this function to extract all the named entities present in this word, these files. So you can see if I print the length of my POS words, so there are around 22,09,120 words. So it will take a lot of time to process all these words and find named entities. So I'll take the first 2000 words and file to find all the named entities present in that. So for that I'll store my named entity words in NER words, and then I will use the NE chunk function to chunk all or to find all the named entities. So I'll pass here my POS words, the words after attaching part of speech, and if I want only the first 1000 words, so it will chunk all the first 1000 words, and then we'll print all the named words along with their named entity tags. So you can see that first 1000 words, it has attached a tag of organization to parent and organization to assistant, and then person to Maria, organization to the, and then Rosemary is also classified as geopolitical entity any place, and then we have Ireland, which is also tagged as a geopolitical entity. So these are all part of speech tags, which is a proper noun, and this is our named entity recognition NER tag, which is geopolitical entity. So after learning about different pre-processing techniques such as tokenization, lemmatization, stop words removal, part of speech tagging, and named entity recognition, now we'll move on and we'll implement all of those concepts using a more advanced package called Spacy. Spacy is a free and open source library, and it is extensively used for natural language processing. It is written in Python language, which is C extension of Python, and that is why it gives us performance like C in Python. It is fast and it provides us concise application programming interfaces to access its methods and properties. So we can perform all of the operations that we have performed with NLTK using Spacy, and you will see that how easy it is to perform such operations using Spacy. So we can perform tokenization, lemmatization, part of speech tagging, dependency parsing, named entity recognition, and some other concepts such as sentence boundary detection, similarity, and text classification. Before using Spacy, we have to install it. For installing Spacy in Anaconda, you have to go to your Anaconda folder in the start menu, and you have to open the Anaconda prompt. After opening the Anaconda prompt, you have to run the following code, and once you press enter, so you'll be asked to proceed with Y or N. So just type Y and press enter. So once your Spacy is installed, now you have to install Spacy model. So Spacy has different models in different languages. So these models contain vocabularies, pre-trained vectors, syntaxes. We can train our own models, but for these tutorials, we'll use a pre-trained model, which is the English model. So for downloading the English model, you have to run the following code in the Jupyter. You have to run the following code. For downloading the model, you have to run the following code in the Anaconda prompt. So your model will be downloaded. So after these two steps, we are ready to work with the Spacy module. So our first step is to perform tokenization with Spacy. So we'll see how to perform tokenization. So the first step would be to import the Spacy package. And once you import the Spacy package, the next step is to load the model that you want to use. So we have downloaded the model, that is N-Core Web English core model. So we'll load it using spacey.load. After loading the package, we'll store it in the NLP object. So now we'll use this object to perform different functions like tokenization, lemmatization. So firstly, we'll create using this object pre-processed variable or another object. Once we create a spacey object, then the next step is to pass the string or the text that we want to pre-process. So once you write NLP, which is this object, and then you pass your text document inside of it. Once you pass, so the spacey model will automatically pre-process this text and it will extract all the entities, and it will perform lemmatization and named entity recognition. Once we create a processed object, we'll store it in doc. Once our process object is created, the next step is we just have to see how to print different tokens, lemmas or named entities. To perform tokenization, we just have to write token.text. So the tokens are stored in .text attributor for this document. To print all the tokens that are present in our text document, we'll just use a for loop to iterate through all the tokens. So we have written for token in doc. Doc is the processed object of spacey model, and then we'll iterate through every single entity that is present in every single token that is present in our doc. For that, we have written for token in doc print token.text. So this .text is the token that we want to print. We'll see that all the word tokens that are present in our text document are printed. So the next step that we'll perform is a lemmatization with spacey. We'll create another processed object. So we'll use the NLP object that we have created using the spacey.load, and we pass our text document into it, and then we'll store it in doc. And after creating this processed object to print lemmas, we just have to iterate through the lemma.text and .lemma. So the lemmas are stored in .lemma underscore method of our document. So we'll iterate through every lemma. So we'll print the text, which is the actual word token, and we'll print along with the lemmatized version of those words. We'll iterate through using for loop. For lemma in doc, we'll print lemma.text. So this will print the token, which is Google, and the next it will print lemma.lemma underscore. So it will print the lemmatized version of those tokens. So you can see, or these are the second words are the lemmatized versions. So our locations is changed to location, and uploading is changed to upload. Images is changed to image, and here we have some scary. Deemed is changed to deem. Scariest is changed to scary. The scary is the lemmatized version, and creepy is also the lemmatized version, and include is also the lemmatized version. How easy it is to perform lemmatization with spacey? You just have to load a document and use the .lemma underscore argument to print the lemmas that are present in our document. So the next step is to perform part of speech tagging with spacey. We have already loaded the same document, which is this one. So it is stored in doc. So to print all the part of speech tags, we'll just iterate through all the tokens present in the doc. For printing the token, we use token.text, and then I have added this 3 lines here. And then for part of speech tag, we have to use .pos underscore attribute or method. So it will print the part of speech associated with that token. And if you want to know the part of speech just as a tag, so we'll write .tag underscore. So it will print the spacey version, and this is the NLTK version. So our Google is tagged as a proper noun, NNP, and maps is also a proper noun. And then we have similarly verbs, nouns, interjection, determinant, verbs, determinants. This is a preposition. This is how we perform part of speech tagging using spacey. So we have to use .pos underscore method of document, and to print the text we use the .tag underscore method. So spacey also provides us different visualizers to visualize these part of speech tags. That package that we need to visualize is called displacey. So we'll import displacey from the spacey, and this is our model that we are using, that is English model. And then we load an object of this model, and we pass a string. When we pass a string, we'll get a processed object which we have stored in doc. So to visualize this, we have to use displacey.render. So this is the function that we'll use in the Jupyter notebook. Once you write displacey.render, so we have to pass the document that we have processed, and then the style argument will tell us which style we want. We want here it is DEP, which is called dependency passing. So it will print the words, or will print this image where it will show which words depend on each other. Is our root verb here, which is a verb, and once you run this line you will get this graph here. So our is a root word, and is depends on processing, and processing depends on language, and then language depends on natural. This is also tagged as a proper noun, and this is also a proper noun, and or is a verb. So our root word is, and then we have an attribute called fun, and our subject is processing. So these are two dependent tags that depend on process, and this all of this depends on its. Next we'll see how we perform named entity recognition with spaCy. We'll load the spaCy model, and then we create a pre-processed object using the model's object. So once we pass our text document in this, we'll store the process object in doc, and then to print named entities, we have to use .ents method of our document. So for printing all the named entities, we have used the for loop to iterate through every single entity. We'll use for entin doc.ents, and we'll print entity.text, so it will print the text of that entity, and then to print the label of which tag is associated, which entity is associated with which tag or which category. For that we'll use ent.label underscore. So this text is our entity, this is the label that is associated, or the class that, or the category which it has been classified. So our Tokyo in this text has been classified as a geopolitical entity, which is country or a city, and then we have more than 38 million, so it is tagged as a cardinal, so it means cardinal is a number. And we have Japanese, so it is classified as NORP, so that is nationalities or religious or political groups. And then we have a same geopolitical entity, that is Osaka, which is also a city, and then we have 20.5 million, which is classified as a number, so a numerical entity. We can also use visualizers using the display-C method for named entity recognition. So this is the same text that we used before. So this is our text document which we have passed to the NLP object, and then it will be processed and will be stored in doc. So we'll use display-C.render. So we'll pass our document here. Yes, and now we want style to be ENT, means it will show all the named entities that are present in our text. Once you run this code, you will get this graph here. So every named entity will be separated with a color and along with its label. So now let's go to the Jupyter notebook and implement all of these concepts using space. So I'll start by installing spaCy first of all. So I have pasted this code here, conda install conda for spaCy. So once I run this code, my spaCy will start downloading. Now you have to press Y to proceed. So you enter Y and press enter. So now your spaCy libraries and other packages will be installed. It is 91.9 MB, so it will take some time to install. So once it is installed, then we'll move on to install our English core model. So once your spaCy is downloaded, now you can move on and download the English module using the following, just using this code here. Now it will download our English module. Now our spaCy and our English model both are downloaded. Now let's go to the Jupyter notebook and start working with spaCy. So we'll begin by importing first of all the spaCy package. So after importing the spaCy package, now we'll load our English model. So I'll create an object called sp and load my English model using spaCy.load, and the name of our English model is N. Now our English model is loaded. Now we'll create pre-processed object in which we'll pass our text document. I'll store it in doc, and we'll use our object sp, and inside of this we have to pass our text. So I've copied this text where Google on Friday celebrated its 21st birthday. So this is our text. So we'll start by tokenization. So we'll first of all find all the word tokens present in this text. For that, we'll iterate through all the word tokens. Word tokens are stored in .text method. So when I press enter, you'll see we'll get all the word tokens present in our text document. Now after this, we'll print all the lemmatized versions of these words present in the text document. So for that, we just have to use another for loop. So it will print the original word, and then if you want to print the lemmatized version of those words, we have to use the method lemma underscore. Once I print this, once I run this, you will see we have the original words and the lemmatized version. So we have for celebrated, it is celebrate, and for showcases, it has showcase, and for biggest, it is big companies, it is company. So these are all the lemmatized versions of the words present in our document. After lemmatization, let's implement the part of speech tagging, and we'll print the part of speech, the words along with their part of speech tags. So for that, we'll just use another for loop. So if I run this now, we'll get every single word along with the part of speech and then the tag associated with that part of speech. So our Google is a proper noun here, NNP. And similarly, for every single word present in our text document, we have a part of speech label and a part of speech tag. Now we can make using display-C, we'll make a dependency tree. So first of all, we'll import our display-C package from Spacey. So after importing display-C, we'll use the display-C.render function to print our part of speech tags as a dependency tree. Side of this function, we have to pass our document, that our processed Spacey document, that is doc, and then we have to mention what type of plot or graph we want. So we want a dependency passing using the part of speech tag. So we'll write style. For dependency passing, it is DEP. So once you run this, you will get all the words along with their part of speech category and the dependency parse tree or the parse object. It will show us which words depend on each other and which is the determinant, which is the compound noun and subject. So we can all see it through this graph. This was about our part of speech tagging. Now let's see how we can perform named entity recognition on the same text that we have mentioned above using Spacey. So you just have to use another for loop. So for named entities are stored in .ents method of our document. So this will iterate through all the entities present in our document. Print. So here you can see that among all the entities, our Spacey has recognized these, and from all the words it has recognized these entities. So our Google has been identified as an organization. Friday is a date, 21st is an ordinal, so it is a number, and Google is also an organization, and this is September 27, 1998 is a date, and Larry Page and Sergey Brin are identified as persons. Now let's use the visualizer using display-C for making a plot, making a graph that will represent all the named entities present in the document. So I've already imported this display-C package, so now we'll just use display-C.render. So in this we'll pass our processed object process document, that is DOC, and then the style will be now equal to ent, which will print all the named entities present in the document. Once I run this, you will see we'll get all the named entities along with their labels that are present in our text document.
Here's a quiz question for you guys. What is word embedding? Your options are a method of printing words on paper, a technique for converting words into numerical vectors, a way to encrypt text for security purposes, or a style of formatting text in a document. Please mention your answers in the comment section.
So syntax can be defined as a set of rules that govern or that define the grammatical structure of words and phrases that is used in order to create coherent sentences. So in simple terms, you can say that the format in which the words and phrases are arranged in a sentence is called syntax. We have different words such as nouns, pronouns, verbs, adverbs. So how these words and phrases are arranged, those rules are actually defined by the syntax. A sentence typically follows hierarchical structure and contains the following components. A sentence is formed firstly from the words, and then the individual words are combined to form phrases. So in a phrase, we cannot have both a subject and a verb. So either we'll have a verb or either we have a subject, and then we have clauses. So a sentence can have clauses and phrases both as well. So in clauses we have both a subject and a verb, and all of these components are combined to form a sentence. So we have different components or syntactic categories that we'll use to define the syntax of a sentence. We'll represent our sentence as S, and then we have the first thing in our sentence is a noun phrase. So noun phrase is represented by NP. These are some of the syntactic categories that we'll use to represent different words and phrases in our sentences. So our sentence will be denoted by S, and then we have determiners, which are words that determine something. Words like and, the, every, these are called determiners. And then we have nouns, so the name of a place, person, or a thing. And then we have, which are represented by N. And then we have verbs, any words that show an action, those will be represented by V. And then we have our prepositions. These are the words that are used to link different words and phrases in our sentence, so such as on, for, with. So these words will be represented by P. And then we have our noun phrases. So our noun phrase is a group of words or a single noun where a noun is mandatory, there should be a noun. And then we have optional, so a modifier can be an adjective or an adverb. And then we have optional objects and also optional determiners. So a noun phrase can contain a determiner, which is an optional, and it can also contain an optional modifier, which is an adjective or an adverb, but a noun phrase should and must contain a noun. And then we have verb phrases. In a verb phrase, there is a main verb, and which is preceded by a helping verb, and along with these two, we have an optional modifier, which can be an adjective or an adverb. And then we have our prepositional phrases. In a prepositional phrase, we have a preposition along with its object and an optional modifier. So now, after understanding what is the syntax and what are the different syntactic categories of a sentence, now we'll move on and understand what are syntax trees. So a syntax tree, which is also called a parse tree, is a tree that represents different syntactic categories of a sentence. This is a simple definition. If we consider the following sentence, that is, I drove a car to my college. So you can see we have tokenized it. Every word is a token. So if we want to draw a syntax tree for this sentence, which will represent what every word in this sentence, which category every word in this sentence belongs to, this will be our syntax tree for the sentence. Here you can see the S is our sentence, which is a complete sentence. Our sentence is composed of a noun verb, noun phrase, and a verb phrase. So a noun phrase here only consists of a single noun, that is I, or a pronoun, that is I. Next we have verb phrase, which consists of a verb and a noun phrase. So here our verb is drove, and our noun phrase consists of a determiner, a noun, and a prepositional phrase. So our determiner is A here, and our noun is car is a noun, and then we have a prepositional phrase which will contain a preposition and a noun phrase. So our preposition is to, and our noun phrase now consists of two elements, that is a determiner and a noun. So our determiner is my, and a noun is a college is noun. So this is how we have represented different parts of this sentence according to their syntactic categories using a parse tree or a syntax. We use concept called chunking, where we'll chunk different words and we'll understand what the sentence is talking about. So it is an NLP technique which is used to group words or tokens into phrases in order to analyze the structure and meaning of a sentence. So the grouping of the words is based on the POS tags, and we can also group different phrases from a sentence. So if you have a sentence that has different words, so these boxes represent different words, and now you know that how to tokenize, how to extract these words, individual words. So now after that we'll understand how to extract group of words that convey any meaningful information to us. So we have a noun phrase which can contain a noun, an adjective and a determiner. So adjective and a determiner are optional. So it can contain a noun or a pronoun. And then we can have verb phrases in our sentences which contain a main verb, a helping verb, or any modifier. So it can be an adverb. And we can have different noun phrases, multiple noun and verb phrases. So in noun phrase we actually have the noun and we can know what our sentence is talking about. We can chunk different phrases from a sentence. The first we'll know how to chunk noun phrases, and then we'll see how to chunk verb phrases, adjective phrases that contain an adjective, and prepositional phrases that contain a preposition or an optional object and its modifier. So we can chunk all of these phrases from a huge sentence to understand the meaning of the sentence and syntactic structure of the sentence. So to start with, we will firstly understand how to chunk noun phrases from a text. First step is we have to import the word tokenize, so that we tokenize every single word, and then after tokenizing we'll attach the part of speech tags of every word, and using those part of speech tags we'll chunk a group of words as a noun phrase from our sentence. So here I've imported the word tokenize function from nltk.tokenize, and then this is our sample text that we'll chunk our words from. We'll tokenize the words and then we'll chunk different phrases from this sentence, and then after performing the word tokenization, we have different words that are present in our text. The next step is to attach a part of speech tag to each word present in the text so that we can chunk later on. So after using the POS underscore tag function, we'll tag each and every word with its respective part of speech, and when we print, every word will be having a part of speech. The here is a determiner, and JJ which means an adjective. So our crazy is an adjective. Brown is a noun. Here it is classified as a noun, and dog is also a noun. And then we have VB, which means verbs, different tenses of verbs, and we have interjection determiner nouns. Based on these part of speech tags, now we'll see how we chunk thus noun phrases from our sentences. To perform chunking, we'll use both part of speech tags and regular expressions. So using regular expressions, we'll extract different chunks, or we'll define different patterns that suit a particular chunk. So we have defined a regular expression that will be used to chunk all the noun phrases from our sentence. Regular expression will chunk the NP, so we can write anything here. So I've written NP, which is a noun phrase, then it's colon. So after the colon we have to mention our regular expression inside these braces, and the first word that it will chunk should be a determiner. We have to put it inside these brackets, and DT is for determiner, so the is a determiner. And then we have a sign of interrogation, which means either 0 or 1. In a noun phrase, there can be either a 0 determiner, no determiner, or only one determiner in the beginning. And the next word, it can be an adjective. This means 0 or more, this asterisk. In our noun phrase, there can be either 0 or more than 0 adjective. And the third word is a noun. There can be either 0 or 1 noun. So if there is any noun, so it will be extracted. And if there is any noun and in front of it there is an adjective, so that word will be extracted. And if there is a noun and in front of it there is an adjective and a determiner, all these three words will be extracted. Based on this regular expression, when we use regular expression, we have to import the regex parser class from NLTK. So I'll write from NLTK import regex parser, or if you have imported NLTK already, so you can use along with the NLTK, and you have to pass your regular expression, which I have stored it in grammar. So when you pass your regular expression to a regex parser, we'll create an object of this class, that is chunk parser. So after creating the object of this class, we'll use the dot parse method of this object to parse our sentence. Once we parse our sentence, so in the regex parse we have to pass our POS tags. So this will be all the words along with their POS tags. So when we pass our words along with their POS tags to our chunk parser.parse, all the words will be chunked and will be stored in tree. So once we print the tree, now you can see this is our sentence, and the first noun phrase, this is NP. The noun phrase it contains a determiner the and an adjective, that is crazy, and then we have two nouns, that is brown dog. And apart from that, these are verbs. So these are not chunked because we have not chunked the verbs till now. And then we have another verb that is running, and then we have an interjection, that is through, and then after that we have another noun phrase, that is NP, denoted by NP, and it contains determiner, that is the, and a noun mud. In this noun phrase, there is no adjective, so there is only one determiner and one noun. We can represent this chunking using a tree, so that makes it visually easy to understand. So we'll draw the parse tree that we have seen before, which is also called a syntax tree. So for doing that, you just have to use this variable that is tree and the draw method of this variable. So once you run this line, there will be automatically a new window popping up that will show your syntax tree. So you can see this was a sentence: the crazy brown dog went running through the mud. And we have two noun phrases in this sentence. So the first noun phrase, it contains a determiner the, an adjective that is crazy, and two nouns that is brown and dog. And then we have another noun phrase that contains a determiner and a noun. So we have two noun phrases in this sentence, and we have successfully chunked these two noun phrases from our sentence. So now we'll chunk another set of phrases using another regular expression. So I've defined my sample text as the term 5G refers to the fifth generation of mobile technology, which promises of faster browsing, streaming, and download speeds, as well as better connectivity. The first step is to tokenize all the words present in this sentence. So for that, I've used the word tokenize function on the sample, and all those words are extracted as tokens and stored in this list. So now our next step is to attach a part of speech tag to every single word. So we'll use this part of speech tags to create chunks and extract them from our sentence. To attach part of speech tags, we'll use the POS underscore tag function, and we'll pass our tokenized words. Once we pass our tokenized words, all the words will be labeled with a part of speech tag. You can see that there is a determiner, and then we have nouns, cardinals, which is a number, and another nouns and determinants, adjectives. Now we'll use another regular expression. So we'll chunk different phrases from this sentence. So here we have defined a regular expression that will chunk these two phrases from our sentence. So we have written the name of the chunk as NP. So it will first of all check if there is a determiner or a prepositional phrase till the end of the line. So this dollar sign means end of the line. So it will check every word till the end of the line if it is a determiner or a prepositional phrase. And then we have added sign of interrogation, which means 0 or 1. So either this part can be 0 or 1. And then we are searching for an adjective. It will be asterisk means 0 or more. So 0 or more adjectives, and then one noun is mandatory, that is NN. And then it will also search for this part, which is at NNP, which is a proper noun. So it will search for NNP, and the plus sign means that it will search for one or more. So there can be minimum one NNP or one or more NNPs, that is proper nouns. So it will check chunk, determiner, possessive, adjectives, and a noun. And then we have chunk sequence of proper nouns. Once we define this grammar or this regular expression, so we'll pass this regular expression to our regex parser. So once we pass this to our regex parser class, so our object is created. So we have stored the name of the object is chunk parser. So now we'll use the dot parse method of this object to parse our text. So the text that we need to pass is our text that contains the text, the words along with their part of speech tags. Because our text are matched with this regular expression, and then all the phrases or words that match this criteria will be chunked. And then we have stored it in tree variable. So once we print the tree, I will see that the first NP, which is our chunk, has one determiner and then one noun. And after that we have another noun phrase, that is determiner, then adjective, and then a noun. And then we have another noun phrase which is only proper noun, that is mobile, according to this regular expression. And then we have another noun phrase that has only technology, which is another, according to this expression. There is only one noun in there. We don't have any adjectives or determiner and prepositional phrases. And then we have another noun phrase here and another noun phrase. This is how we'll chunk based on the POS tag values from our sentences. So now if we draw the parse tree or the syntax tree for the same sentence, for the same chunks that we have extracted here, so we'll just have to write the tree.draw attribute, so our tree.draw method. So once we run this, all the NPs which is the name of our chunk, they will be extracted from rest of the sentence. So now we'll see how to chunk verb phrases from a sentence. So I've defined a sentence sample which says he should wait before going swimming. So this is my sentence. Next two steps are to tokenize the words. and then to attach part of speech tags to every word. So I've done that in one step, that is analytica.word tokenized sample, and then I'll attach the part of speech tags to every single word, and then we have stored the word in POS text. So once we print this, we'll get all the words along with their part of speech tags, and then we have to define regular expression that we'll use for matching the words and chunking the words. Define the regular expression here, which will chunk all the verb phrases from the sentence. The first word of that verb phrase should be a personal pronoun, and this sign of interrogation means it can be either 0 or 1 in number. And then the next word is a verb, so it can be any one of these verbs. So the VB is the base form of a verb, and then we have VBD, which is the past form of a verb, and then either it can be VBZ, which is a third person as singular present form, third person is third person singular, and then we have VBG, which is the present participle form of verb. So it can be either one of these four, and the asterisk means this can be either 0 or more than 0. And then the third word can be an adverb, so RB means an adverb, and then or it can be adverb which is comparative form. So comparative form such as better, greater, taller, so it can be an adverb. And then sign of interrogation means it can be either 0 or 1. We'll chunk all these words in verb phrase from our sentence. So after defining our regular expression, now we'll use the regex parser class to create an object. So this class will take our regular expression as an argument. The object that we created is chunk parser. So after we create an object chunk parser, we'll use the dot parse method of this object to create chunks from our sentences. So we have to pass the POS text list which contains the words along with their POS tags. So we have stored it in tree. Once we get our tree variable, now we'll print tree. So once we print the tree, our first verb phrase is this one, he. So he is a personal pronoun. So this was the only one verb phrase. So this will be chunked. And then the next verb phrase that will be chunked is wait, which is the base form of verb. And then we have going, which is the present participle. So it will also be chunked. Once we draw the parse tree for the same sentence, so this is our sentence, and then only the verb phrases are chunked. So the first verb phrase is he, the next verb phrase is wait, and the third verb phrase is going, which is the present participle form. Let's go to the Jupyter Studio now and implement chunking, and we'll see how we chunk different phrases from our sentences. Chunk noun phrases from this sentence. So I've written a sentence, the dark cloud covered the sky. The first step would be to tokenize all the words and attach a part of speech tag to every single word. So I'll store that in POS list. Once I run this line, all my words will be tokenized and a part of speech tag will be attached to every single word. So if I run POS now, so you can see that every word has been attached a part of speech tag. So now based on these tags, we'll extract all the noun phrases that are present in this sentence. So for that, I'll define a regular expression. So I'll store it in regex, and then R is for mentioning that it is a regular expression. So I'll name of the regular expression, the name of the chunk that I'll keep is NP, and then we have to define our tags we want. First word can be a determinant, and there can be either 0 or 1 determinant. For that, I'll write sign of interrogation, and the next word can be adjective, that can be 0 or more. So for 0 or more, I'll write asterisk, and the third word should be a noun, and they can be 0 or more nouns. So you can write this. So after writing this, when I run this, my regular expression is created. Now I'll use the regex parser class to pass this regular expression and then extract all the noun phrases from the sentence. For that, I'll firstly define the instance of my regex parser class, and I have to pass my regular expression as an argument. So once my object is created, now I'll use this object to identify all the noun phrases from my sentence. So I'll just write dot parse method, and I'll pass my POS words list, and I'll store this in tree. Once I run this, now I'll print my tree to see how many noun phrases are there. So you can see this is our sentence, and we have the first noun phrase, the dark cloud, and then we have another noun phrase, that is the sky. Now let's print on the parse tree for this. So now let us extract different phrases from this sentence given here, that is Mary saw a cat sitting on the mat. So the first step will be to take all the part of speech tags words. So I will just use these two functions. So once I run this, now my words along with their part of speech tags will be stored in POS list. So now I can create a regular expression. This is my regular expression that I have created. So here we are chunking all of these words, all of these phrases. First we'll chunk the noun phrases. So we have a determiner 0 or 1 times, and then an adjective 0 or more times, and then a noun. So the noun can be on any form. So it is NNP or NNS. Then for any word after NN and 0 or more times, if we just write NN, only NN nouns, singular nouns will be extracted. If you write this one, so all of the nouns will be extracted. And then we have defined how to extract preposition. That is just IN for preposition. POS tag is IN. And then to extract verbs, so if you want to extract VB, VBZ, VBG, so you have to write this code, because after V the point means any word after V, and that is 0 or more times, so it will extract all the verbs. And then to extract prepositional phrases, we have used PP, that is preposition, which is IN, which is defined here, and a noun phrase which is defined here. And then to extract verb phrases, we have used VP, that will be any verb which is defined here V, and then after that there can be a noun phrase or a prepositional phrase 0 or more times, so that is optional. Once I run this code, so my regular expression will be created. Now I'll use parser to parse this regular expression. So once I run this code, now my parser is ready. Now I'll use the dot parse method of this parser to chunk all the phrases that I've defined in my regular expression. So I'll write, and then I'll pass my POS words list. I'll store it in tree so you can print it. So after that I'll print the tree. So now you can see that from our sentence, Mary, which is proper noun, has been chunked as noun phrase. Then we have verb phrase, then another noun phrase, and then verb phrase, and a prepositional phrase, and then a noun phrase. So it is better if you visualize this to see how it is chunking. Just write tree dot draw to draw the parse tree. So to exclude specific phrases from our chunks, we have a concept called chinking. So chinking is used to exclude a specific chunk from the whole chunk, and we can define chink to be a sequence of tokens that we don't want to be included in our chunk. For example, we have noun phrases, verb phrases that we have chunked. So if we don't want verb phrases or any specific verbs, specific type of verbs, then we can define how can we chink those verbs by using chinking. To implement chinking, we will first import word tokenize to tokenize all the words, and then we have defined a simple text that we'll use for chinking, and then the sample text is tokenized and a part of speech tags are assigned to each and every word that is present in the text, and we have printed it. These are all the words along with their part of speech tags. So now we'll define which words we do not want from in our chunk. For that we have defined a regular expression. So here is our regular expression. So our name of the chunk will be chunk, and first of all we'll chunk everything using the braces. The dot means any word, and 0 or more of any word. Then we want 1 or more of any word, so it means it will chunk every word that is present in the sentence. And then to perform chinking, to exclude a specific tokens or specific words from our chunk, we just have to invert the braces here. So if you just invert the braces and mention the tokens that you do not want in your chunk, those particular tokens will be chinked. So you just have to mention all the tokens that you do not want to be chunked. So I have mentioned the first token to be a verb. It can be any verb, any form of verb. It will be VB and also VBZ, VBR, VBG, because I've inserted a dot, so it means even if any word is after B, that verb will also not be chunked. And then sign of interrogation means 0 or 1. Then or, we have 4 tokens, so if any one of these tokens is found in the sentence, these will not be chunked and rest of the sentence will be chunked. And then we have a preposition and the determinant and the to word. So if there is a to word going to, so that will be a to word, and we want 1 or more of these. There will be at least one word that will not be chunked, so it will be either one of them. And then after defining the regular expression, we can use our regular expression regex parser class to parse our grammar or our regular expression, and then once we create an object of this class, we can use this object to parse our words and to find chunks from our sentence. So we'll use the object and the dot parse method of that object, and we'll pass our text that has words along with the part of speech text, and we'll store it in tree. Once we print the tree, we'll get sentence, then whatever the words that will not be chunked, and we'll get only the chunks where the words that we only want to be chunked. So the determinant which was mentioned in the chink regular expression, this word is not chunked, and our verbs you can see and our preposition are not chunked, and whatever is left after these words, those words are all chunked. So let's see a parse tree of this to understand it better. So here you can see that this was whole sentence. Only the words which do not include determinant, verbs and prepositions, they are not, only those words are chunked, and these words are not chunked. Now let's go to the Jupyter notebook and implement chinking on a sample text. So we have a sentence here. The little yellow dog barked at the cat. So we'll see how can we chink certain phrases from these words to extract only the phrases that we require. If I only want the noun phrases from this sentence, either I can define a noun phrase, but if my sentences are huge and if I know there are certain words that I don't want from the sentence, then I can directly exclude those words using chinking so that I only get the noun phrases. First of all, we'll tokenize the words from this text, and then we'll attach a part of speech tag to every single word, and I'll store it in POS. So after running this, all of my words, they are stored along with their part of speech tags. So if I only want noun phrases, so I can either define noun phrase or I can chunk certain phrases so that I'm only left with noun phrases. This is my grammar that I'm going to use, so I'll store it in regex. So we define it by R, and then I'll define the chunk that I want. First of all, we'll chunk everything using this expression. And now once we chunk everything, now if I want to exclude the verbs and the prepositions from this text, so I'll invert the braces. After inverting the braces, I'll write my regular expression that I want to chink. So I want VBD, the verb form, which is the past form of verb, and then either it will chink this one, or if it finds a preposition and one of more, so either one of these or more than one of these will be chinked from the whole sentence. So once I run this, my regular expression will be created. Now I'll parse my regular expression using the regex parser. So I'll store it in parser object, and I'll pass my regular expression in this, which is regex. So after this, I can parse my sentences and I can chunk and chink everything that I want. So I'll store the chunks and chunks in the tree, and I'll use the parser object along with the parse method, and I'll pass my tokens which already have a part of speech tag to them. So I'll just write POS. So now if I print my tree, so you'll see that VBD, which is the past form of verb, and preposition have been chinked. They are not included in the chunk, and rest of the words are included in the chunk, which are actually the noun phrases. So let's draw the tree. So here's the tree that we got. So we have chinked these two words from the whole sentence. So first of all, we chunked all of the words, and then we chinked these two tokens, and we are only left with the noun phrases. So a context-free grammar is used to describe the syntax of a natural language by defining things recursively, and a language that is described by a context-free grammar is defined as all the possible derivations within the rules that are defined by a context-free grammar. So a language can contain a lot of strings, and all those strings are found by the rules that are described by a context-free grammar, and each possible derivation or each possible string that a language has at least one corresponding syntax tree. So if there is any string that is formed by a language that uses a context-free grammar, has a corresponding syntax tree. So if you cannot parse a string into a syntax tree, we cannot say that that string belongs to that natural language or the language that is defined by a context-free grammar. The string is not valid in that language if you cannot parse it into a tree. So now let's understand context-free grammar. Context-free grammar basically consists of 4 tuples or 4 elements, and the first is our set of non-terminal symbols. Those can be your noun phrases or verb phrases or determiners, nouns, verbs, adverbs, etc. And then we have a start symbol, which is the starting string or the sentence from where we begin. So that is denoted by S, which is also a non-terminal symbol. And then we have a set of terminal symbols, which are the actual words that we get after replacing all the non-terminal symbols. At the end, we'll get a string which consists of all the terminal symbols. Then we have a set of production rules that are used to define things recursively. Here you can see that our sentence S, it has two parts, that is a noun phrase and a verb phrase. And a noun phrase then recursively is defined as a determiner and a noun. And a verb phrase is defined as a verb and an adverb. So we'll keep replacing the things that are on the right hand side until we reach a point where we have all the non-terminal symbols. That will be our final string that we'll generate using a context-free grammar. We'll understand it by implementing on Jupyter Notebook. Let's see how it is implemented using NLTK. There is a class called CFG in NLTK that is used to define context-free grammars. So in that class we have a method called fromString. So in that method we can write all the production rules, and we can mention all the terminal and non-terminal symbols. So here you can see that I have written, first I have imported the NLTK package, and then I have defined a grammar which I have named as grammar1. The function that I'm using is cfg.fromString, that is from NLTK package, and inside that function, within the curly braces, we have within the inverted commas we have to mention our production rules. And you can see our first production rule is that a sentence, it has two components, that is a noun phrase and a verb phrase. And then we'll define a verb phrase which can be either a verb, a noun phrase, or a verb, noun phrase, or a prepositional phrase in that order. And then we'll define a prepositional phrase. It can be a preposition and a noun phrase. So these are all our non-terminal symbols. And then V, whatever is on the left hand side, is our non-terminal symbol, and all the words that are present here, these are the terminal symbols. So in order to form a sentence, we have to recursively replace the non-terminal symbols until we reach a point where we only have terminal symbols. So that will be a valid string in that language. So this is a language that is defined by our context-free grammar. The set of all the strings that is present that can be generated from this context-free grammar, that will compose of a language. So here we have a sentence: Bob saw a man with a telescope in the park. So we'll see if this sentence is a valid sentence according to this context-free grammar or not. To do that, we'll parse the sentence using the context-free grammar. So first of all, we'll tokenize all the words present in this sentence, and then we'll parse our grammar. This is our grammar which is stored in grammar1. So we'll parse our grammar using the recursive descent parser, which will parse our grammar. So this is another function that we'll use to parse the grammars. And then after creating the object of this class, that is recursive descent parser, we'll pass all the word tokens that we have generated. So if we are able to generate a parse tree for this sentence using this grammar, because we have created our object on using this grammar, so if we are able to parse this sentence using this grammar, this sentence will be a valid sentence of the language that is defined by this grammar. So here you can see I'll iteratively pass through every single word that is present in our token word, and we'll see what our context-free grammar parses this sentence. So you can see it starts from here, then we have a noun phrase called Bob, and then we have a verb phrase that contains a verb and a noun phrase. A verb is saw, and noun phrase also contains a determinant and a noun and a prepositional phrase. Let's look at this structure in a tree form so that we can understand it better. So we'll just write tree.draw from this tree, and then you can see that our whole sentence is parsed using different phrases by this context-free grammar. So we can easily say that this sentence is a part of the language which is defined by this context-free grammar. So we have our sentence here. So we have a noun phrase called Bob, and then we have a verb phrase. So the verb phrase is broken down into three parts, that is verb, noun phrase, and prepositional phrase. So these are all the production rules that were defined by our language. So if you look at here, so we have verb phrase. Either that verb phrase can be a verb and a noun phrase, or it can be a verb, noun phrase, and a prepositional phrase. So here we have a verb, noun phrase, and a prepositional phrase. and then verb is saw, and then in noun phrase we have a determiner, a noun, and a prepositional phrase. And here in this prepositional phrase we have a preposition and a noun phrase. So here all the words, they belong to one of the categories. We can draw a parse tree for this string. We can say that this string belongs to the language that is generated by or that is defined by this context free grammar. We can also print the production rules of the grammar using the print function. If we just write the print and the grammar that you have defined, you will see that our grammar has 25 production rules, and it starts from here, which is the start symbol, which is a sentence. Sentence will be broken down into noun phrase and verb phrase, and verb phrase will be broken down into verb and noun phrase, and then verb phrase will also be can also be equal to this verb phrase, noun phrase, and a prepositional phrase. These are our terminal symbols, and whatever is on the left hand side, all are our non-terminal symbols. And then after defining a grammar, we can use that grammar to generate sentences. So for doing that, we have to import the generate function from nltk.parse.generate. So once we import the generate function, and this is our context free grammar class that we have to import from nltk package, then after importing this, we'll iterate through every sentence that is generated by this grammar. So we'll write for sent in generate. So this function will generate all the sentences, and will iterate through every single sentence that is generated by this grammar. So we'll write inside the generate function the grammar that we have defined, grammar 1. Here is our grammar 1, and then we'll write n equals 10, so it will print the 10 sentences. Otherwise, if you don't write n equals 10, so it will go on and print all the sentences. And then we have used print function, so we'll join all the words basically that our grammar will generate. This is the space that is between the words, and it will join all the words, and it will print each sentence line by line. You can see the first sentence is John saw John, John saw Mary, John saw Bob, and John saw a cat, John saw a man, John saw a cat. So all these words are actually the strings that are contained in that language. You can see there are some words, John saw and man, which doesn't make any sense, which are grammatically not correct. So in context free grammars, the reason that they are called context free is because the placement of these words, placement of the non-terminal symbols are not according to a context. So it is according to the production rules. So even if the production rules are not generating a sentence that has a meaningful grammatical meaning or a meaningful grammatical sequence, then also it will print, because it is a context free language. It is not a context sensitive language. So now let's go to the Jupyter notebook, and we'll generate a context free grammar, and then we'll generate some sentences using that context free grammar. So after importing CFG, now we'll define a grammar that we'll use to generate and parse sentences. So I'll write the name of the grammar as grammar, and then we have to use the function from string, which will generate a grammar from the strings that will pass in the parenthesis. This is our grammar that we have defined. These are the production rules. On the left hand side, you can see these are our non-terminal symbols. Start symbol is S, which is the sentence or the string from where we begin, and then our string contains a noun phrase and a verb phrase, and then we define what a verb phrase is. So using another production rule, a verb phrase can either be a verb and a noun phrase, or it can be a verb, a noun phrase, and a prepositional phrase. Then we'll define another production rule about prepositional phrase. So it can be a preposition followed by a noun phrase, and then we have defined a verb which is either ate, saw, or walked. So these three words are called the terminal symbols. So all the words that you see on the right hand side, they are terminal words, terminal symbols, and on the left hand side we have all the non-terminal symbols, and these are our production rules. And S is our start symbol. So these are the four tuples that define a context free grammar. Once I run this, now our context free grammar is generated. So after that, we'll take a sentence and we'll see if we can draw a parse tree, or we can parse that sentence using this grammar or not. And if we are able to do so, we'll say that that sentence falls in the language that is generated by this grammar. So let us write a sentence. I'll store it in sent, and let us write a sentence that John saw Mary with a cat in the park. So we'll parse this sentence using this grammar, and if we are able to parse this sentence and draw a parse tree for the same, then we can say that this sentence is a part of language that is generated by this grammar. So for doing that, we'll import the recursive descent parser that is used to parse a context-free grammar from the NLTK. So once we have imported the recursive descent parser, now we'll create an object of this class that we'll use to parse the sentences. So the argument is the grammar that we have defined so that it will parse the grammar, and then we can use the object to parse sentences. So now after parsing the grammar, we'll generate sentences using this parser. So we'll firstly check if the sentence that we have mentioned, John saw Mary with a cat in the park, is actually a valid sentence in this grammar or not. We'll set the name as tree for our iterator. Once I run this code, you can see that first we have tokenized the sentences here. So all the words will be given to the parse, and this parse is a method of the parser which we have declared here, this parser object, and it will parse this sentence. And if it is able to parse the whole sentence, then you can say this sentence is a valid sentence according to this grammar. So now you can see that our sentence has a noun phrase that is John, and we have a verb phrase which contains a verb, a noun phrase, and a prepositional phrase. So we'll visualize it using a tree so that it is clear. We'll just write tree.draw. Now what are the production rules that our grammar is using? We'll just write print and the name of the grammar. So you can see we have 25 production rules, and the start state is S, and these are the production rules, so they orient. On the left hand side we have all the non-terminals, and on the right hand side wherever there are words, those words are the terminal symbols. So now let's generate some sentences using this grammar. So for that I'll have to import generate function from nltk.parse. So once we import the generate function, now we'll generate some sentences using the grammar above. So I'll write for sent, and I have to pass my grammar, that is grammar, and we'll print 10 sentences. So I'll write n equals 10, and then I'll print. If I write without the spaces, so it will print without any spaces. So I'll use spaces to print sentences with spaces in between the words. So I'll add join and then sent. So now you can see we have first 10 sentences that our grammar has generated. So John ate John, John ate Mary, and John ate a dog, John. So most of these sentences they don't make sense because this is a context-free grammar and the words are placed according to the production rules, and where there is no context or there is no particular order in which the words should be placed. So some of the sentences will make sense and some of the sentences won't.
Here's a quiz question for you guys. What is the primary goal of text classification in natural language processing? Your options are converting text into speech, predicting the sentiment of a text, summarizing a lengthy document, or translating text from one language to another. Please mention your answers in the comment section.
So if you talk about bag of words, so bag of words is a method for extracting features from a text document, and then those features are used to train different machine learning algorithms. So if we talk about text classification using machine learning or deep learning, most of the machine learning and deep learning techniques, they require a numerical input, not a textual input, because they work on mathematical equations. So the input is always a numeric input, but if we want to classify text, so our input, which is text, is present in a textual form. So that problem is actually solved using different techniques which we use to represent text in form of numbers that we can use to train our different machine learning models. One of such techniques is called bag of words model. So in bag of words model, we represent text data in a format that is suitable for machine learning, and then we do this by creating vocabulary of all the unique words. So if we have different text documents, so we'll create a list or a vocabulary which will contain all the unique words that are present in that text document or in the text corpus, and then we'll use that vocabulary to build word count vectors. Once we build word count vectors which will represent a text document or a sentence in form of word counts, word frequencies, then we can use those as an input to our machine learning models. These are some of the steps that are involved in building a bag of words model. First of all, we have our text documents which contains textual data, and then the next step is pre-processing. So in pre-processing, we'll remove stop words or punctuation marks and other irregularities from our text data, and using all the techniques that we have already learned and will also learn in this module and in the next module as well. So after pre-processing, our next step is tokenization. So we'll tokenize all the words present in our text documents. And after tokenization, the third step is building a vocabulary. So it will contain all the unique words present in our text documents. And then after creating a vocabulary, we'll create word count vectors or feature vectors. We call them as an input to our machine learning algorithm. So a bag of words model is used in a lot of fields such as natural language processing, in order to understand and interpret human spoken languages, and then to extract information from our text documents, we also can use bag of words model. And the third one is document classification. So in order to classify documents into different categories, we can also use the bag of words model. So to implement bag of words model in Python, we require some of the libraries. The first library is the NLTK, which we have been using till now. We'll import NLTK, and then we'll import NumPy to create arrays that we'll use later. And then the word tokenize function is to tokenize all the words, and then I will import it and the stop words from NLTK corpus. We can remove the stop words in the pre-processing step. So after loading all these libraries, I will define 3 functions. These 3 functions will perform the bag of words model from the scratch in Python. So we have inbuilt functions that we can also use to perform bag of words model, but first we'll learn about how this concept is actually approached. We have defined a function that will return us a clean text, the tokenized text in a clean format. The name of the function is extract words, and this function takes a sentence as an argument, and it will first of all tokenize all the words present in the sentence, and then it will clean all the words. By cleaning, I mean it will lowercase all the words, and then it will remove all the stop words using this one liner. And after removing, it will return us a list of all the words lowercased and stop words removed. The next step is to build our vocabulary. We'll iterate through every single sentence present in our corpus, and then we'll take all the words. And after taking all the words, we'll only keep unique words. So if a word is occurring 10 times, we'll only keep it once. For that, we have defined a function called tokenize sentences. The argument of this function is sentences. So it will take multiple sentences, which is also called a corpus. We have defined an empty list called words. So we'll iterate through every single sentence present in our sentences, multiple sentences or in corpus, and then we'll call our extract words function, this function. So it will extract all the words by removing the stop words and by lowercasing all the words, and it will store all those words in W, and then we'll add or we'll extend this W to our words list. So when we use extend, the single elements of every element of this list will be added as an element to this words list. So after this loop is over, our words list will contain all the words that are present in our whole corpus. And in the last part, we have used the set function, which will remove the duplicates, and it will only keep distinct elements from our words list. And then we have converted this object to a list using the list function, and then I use a sorted function, so it will sort it alphabetically from A to Z, and will again store it to words. This function will return us the words list, which is actually the vocabulary which contains the unique words present in all of the text documents in our corpus. That was 2 steps. The first step was pre-processing, where we tokenize the words and remove the stop words. Next step is building a vocabulary, and now the third step is to build a bag of words model, that is create word count vectors. We have defined a function called bag of words, which will take 2 arguments. Our first argument is the sentence, which will be used or for which we'll create a word count vector, and the next argument is words, which means vocabulary. The first task it will perform is to extract words. So it will call the function which is extract words, and it will extract all the words present in this sentence by firstly lowercasing the words and then removing the stop words, and it will store all those words in sentence words. And the next function or the next code we have written here is the np.zeros. This will create numpy array of zeros, and the length of the array will be equal to the length of the words, which is our vocabulary. For each word count vector, the length will be equal because the length is equal to the word count vector. When we use the length equal to words, so it will be equal to the length of the vocabulary, and it will create array. So if we say that our vocabulary contains 50 words, the length of this array will be 50. In this array there will be 50 zeros because it is a np dot zeros. It will create an array of zeros and we'll store that array in bag. Now we have our words in sentence words and an array which is stored in bag. Now we'll iterate through every word in this sentence words list and we'll check if that word is occurring in our vocabulary and how many times it is occurring. We'll use two loops here. So firstly we'll iterate through every single word that is present in our sentence words, and after that we'll use another loop to check whether the word we are iterating or we are at this point of time is actually present in the vocabulary or not. If it is not present in the vocabulary, this bag will be 0, and if it is present, we have set that for I, so this will be for each individual word starting from index 0 to the last word in these words, and then the word which is present in enumerate words. So when we use the enumerate function, we'll add a counter to our words list. This words is actually our vocabulary. It will start with 0 and it will go to the last word in our vocabulary. It will check whether the word in the vocabulary is equal to the word present in this list or not. And if it is true, then it will increase the count of that particular word from 0 to 1 by adding 1. So if this word occurs 10 times in this sentence words, the value of that particular word in this array will be 10. I will return that bag array as a numpy array bag. So once we use the enumerate object, this object will also be an enumerate. So to convert it back to an array, we'll use np.array and we'll pass our bag object to this function, and then it will return us a numpy array of word count frequencies. So after that, let's see an example to understand it better. So we have a corpus which contains 5 sentences. This one sentence is also called a document. There are 5 documents in this corpus. Based on this corpus, we'll generate vocabulary. For generating a vocabulary, we have defined a function tokenize underscore sentences, which takes sentences. Sentences mean corpus. There are multiple sentences, which is corpus. So we'll pass our corpus into it, and then we'll store it as vocabulary. So once we print vocabulary, we have this list which contains all the unique words present in our corpus. Then and all the stop words are removed. Now these words will be used to create word count vectors for each sentence that is present in our corpus. Now here it is, the way that we use to create word count vectors for each sentence. So here is a vocabulary that our function has made. These are all the unique words present in our text corpus, and then we use the bag of words function, which will return a numpy array of word count vectors. So if we want to calculate the word count vector for this sentence, Max and Rob took the bus, we'll pass it to our bag of words function, which takes 2 arguments, that is sentence and a vocabulary. This is our vocabulary that we have used. We have stored it in vocabulary variable. Once we pass our sentence and a vocabulary, this bag of words function will return an array of the word count vectors. This is a word count vector for this particular sentence. So we can see that the word arrived. This is how we check. We look at the vocabulary and then we find each word if it occurs in our text or not. We'll check first of all the arrived. So if arrived appears in this text, then we'll increase the count by 1. If it doesn't appear in this text, then we'll keep it as 0 and then we'll move to the next element. Arrived doesn't appear, so we'll keep it 0. Then we'll check the bus. So bus appears once here, so we'll keep it 1. Then similarly for early, I, John and late, and then we see that only Max will appear. So this is 8th word. Here you can see the 8th element is 1, and similarly we'll check for all the elements. So if these words are present in the sentence, so for that particular index the value will be increased by 1. Here you can see in the next sentence we have arrived. We'll check by seeing the first word, that is arrived. So arrived appears once here, so we'll keep it 1. And then we'll check for bus. So bus appears twice here, once here and once here, so we'll keep it 2. The good thing about the word count vectors is that no matter how short or long your sentences are, but the word count vectors will have the same length, because the length of a word count vector is equal to the vocabulary that we have built. Now let's go to the Jupyter notebook to implement bag of words from scratch using Python, and we'll implement it on corpus and we'll create word count vectors for. So we'll start by importing all the required libraries. Import NLTK first. Then we'll import a numpy because we need numpy arrays. Import numpy. as NP. This is a common alias used for NumPy. Now we'll import our stop words from our NLTK corpus, so we can remove our stop words. After that, I'll create a stop words list which will contain all the unique stop words. Use set function which will only take the distinct unique words from our stop words. We only want the English stop words. So I'll set store my stop words in stop underscore words list. Now we'll create our first function which will return us the clean text by first of all tokenizing and then removing all the stop words. The name of the function I've set is extract words, which will take a single sentence as an argument and then it will return us the clean text. So I'll write clean text list. I'll define it in one line. First of all, we'll lower the words. We'll tokenize the word. It will lower all the words after tokenizing. And now we'll remove all the stop words. It will return a list of all the words present in a sentence by removing first of all stop words and then lowering, making all the words to lowercase, and then it will return us the list. This function will return us the clean text list. Now let us define another second function which will create a vocabulary for us. I'll let the name of the function as vocab. This function will take a whole corpus as an argument, which will be a list of sentences or a list of documents. CSA. First step will be to extract all the words that are present in our corpus. Let's create a list that will first of all contain or an empty list which will contain all the unique words. So let's first create an empty list. Iterate through all the sentences present in our corpus and we'll call the function extract words, so it will only return the list of words which are cleaned, and once we have the list of words which are cleaned, we'll use the dot extend method of our list vocabulary to add that list of words as single words to our vocabulary list. Now after this loop is finished, we'll have all the words that are present in clean text in all the sentences. Now we have to find all the unique words. For that, we'll use the set function. So first of all, we'll find all the unique words from the above vocabulary that we have generated, and then we'll create a list out of it, so it will be converted to a list. And then we want to sort the elements alphabetically, so we'll use the sorted function. At the last, our function will return us the vocabulary. In this function, first of all, we will declare an empty list which will contain all the unique words from or all the text documents, and then it will call this function which will return the clean text for each document in corpus, and then we'll add that element or add those words to our vocabulary list, and then we use the set function to find the distinct elements and list to convert it into a list, and then sort it to sort the elements alphabetically, and then finally we return the list using this function. After creating vocabulary, our third function will be to create a bag of words model, or to use this vocabulary to create word count vectors for each sentence or each document present in our corpus. Let's define bag of words function. So I'll write it at BOW, and this function takes two arguments. The first one will be a sentence for which we want to create a word vector. Second argument will be the vocabulary which it will use to create the vector. Here, first of all, we'll take each sentence and tokenize it and find all the words present in the sentence, or find out the clean words present in the sentence using this function. Let's call it words. So it will be, we'll call the function extract words, and we'll pass our sentence into it. So it will return us a list of all the clean words. Stop words will be removed and all the words will be in lowercase. Now we'll create an array of numpy zeros that we'll use to create word count vectors for each text document in our corpus. Let's create a numpy array of zeros. So we'll store it in bag. So we'll create an np, and it will be equal to, the length of this array will be equal to the length of our vocabulary. After creating an numpy array of zeros, now we'll use for loop for each sentence to make a word count vector using this numpy array of zeros. We'll iterate through every word and that is present in our words list. This is a words list which contains all the words, and then we'll iterate through every single word that is present in this list. Then we'll use another for loop to check whether the word is in vocabulary or not. This enumerate function will add a counter to our vocabulary, which we'll use to iterate through every single element in the vocabulary, and we'll check whether that element is equal to the word present in our list or not. We'll check if the word in vocabulary is equal to the word in our words list, and if it is equal, then we'll increase the 0 corresponding to that word in this numpy array by 1. For that particular word, we'll increase the numpy array of zeros by 1, and in the last we'll return the numpy array. So we have to convert this to an array of our bags list. So after this, it will when we use the enumerate function to it will create an enumerate object. Then we have to convert that enumerate object to our numpy array. So this function will return, this input for this function is our sentence and our vocabulary, and it will return word count vector for that particular sentence using this vocabulary. Now we have declared these three functions. Now let's use one corpus to use these functions. I'll store my corpus in corpus. So I have copied these 4 sentences. So in actual we'll have 4 documents. So this first document can contain thousands of sentences, and similarly for the other documents. We can pass these sentences in a corpus as a list, and then we can use these functions to create word count vectors for each sentence that is present in our list for each document. Now let's create this corpus, and after that we'll create a vocabulary for this particular corpus. So I'll store the vocabulary in vocabulary, and our function that creates vocabulary is this vocab function. I'll write vocab, and then I'll pass this corpus, and it will use this corpus to create and to return a vocabulary. Once we run this line, now let's print the vocabulary. So you can see these are the words which are treated as our vocabulary, which we'll use to create word count vectors for each sentence. So you can see there is both football, games, John, likes, Mary, movies, and others. So you can see that this is one like, this is another likes. So later on, when we perform text classification, we'll also use stemming and lemmatization. We'll reduce these words to a single word, that is like, that we only have one word because they mean the same thing. Now after creating a vocabulary, now we'll use this vocabulary to create a word count vector for each of these sentences. Our word count vector function is BOW, which will take a sentence and vocabulary and return a word count vector. So let's use this function. So I'll call this function and then I'll pass the sentence. So let's create word count vector for this sentence. And then the second document will be our vocabulary, which is stored in vocabulary. Once I run this, so I'll get word count vector for this particular sentence. So we have in our vocabulary both does not occur in this, so it will be 0. There is football. Football, you can see it occurs 2 times. The word count value will be 2. Word frequency is 2. And games occurs 1 time. The word frequency is 1. And similarly for others, this array represents the word frequency according to our vocabulary. We can print this for each sentence that is present in our text documents. And once we have these arrays, then we can use these arrays as an input to our machine learning models for text classification. Bag of words model. Python scikit-learn library provides lots of inbuilt functions for implementing machine learning models and for text pre-processing or data pre-processing, and also to calculate different metrics about our model. It includes our bag of words functions as well. We have a class known as count vectorizer, which we'll use to implement bag of words model. It works on terms frequency, which is also called as the word count frequency. It will count the occurrences of words or tokens. It will make a sparse matrix. So it will make a matrix of zeros, and with the words which occur with the word counts of every single word that occurs in our document or in our corpus. We'll use the count vectorizer class to implement bag of words model, and we'll import this class from the feature extraction method or feature extraction method of scikit-learn library, and then we'll initialize this class and we'll train the object of this class to create word count vectors or term frequencies of all the documents present in our corpus. Instead of making different functions that we did earlier, We'll not make functions now, we'll just use the count vector as a class, and we just have to pass our corpus into it, and it will automatically create a vocabulary and create word count vectors for us. So to implement bag of words using count vector as a, first of all we'll import numpy as np, and then we'll import our count vectorizer class, which will create word count vectors. So it will import it from feature extraction methods, feature extraction.text, and then we have imported pandas, so you can visualize the results as a data frame. And then I've declared a corpus. This time we have to declare it as a numpy array so that you can feed it to our count vectorizer. We have corpus which contains 5 text documents, which is John saw the train was late, Max and Rob took the bus, I looked for Max and Rob at the bus station, and the 5th sentence. These are the 5 sentences. Then we'll use our count vectorizer class to instantiate first of all an object. Once we create an object of this class, then we can use this object to pass our corpus, and it will create the vocabulary and everything. So it will represent directly the word count vectors for each text or each sentence or each document present in our corpus. So once we instantiate an object of count vector as a class, now after instantiating, we'll use the fit underscore transform method. So it will first of all fit our data to our object, then it will transform our data in word count vectors. So we'll store it in bag of words variable. Once we have a bag of words variable, so it will be a sparse matrix, which means a matrix of zeros. So we'll convert it into an array. Once we convert into array using the toArray method, so you can see we have our array. So this array contains a word count vectors, or which we also called count vectorizers, for each sentence that is present in our text. First vector, the first element of this array is word count vector for the first sentence, that is John saw the train. So this time we don't have to manually conclude to a vocabulary or manually define a function which will print a vocabulary for us when you find a vocabulary. So it will be automatically done by the count vector as a class. So it's just you have to use the fit transform method, and we'll pass our text data. So once we pass our text data or a feature matrix which will contain the word count vectors for every text, document or sentence present in our corpus. So now if we want to get the feature names, which is also the vocabulary, so here this is our vocabulary which is stored in feature names. This will be to get feature names, we just have to use this object and the get feature names method of this object. Once we write this and we store the feature names in feature names, when we print it, this is our vocabulary which are called features in count vector as a class. These are the features that our count vector as a class uses to make these word count vectors. Now if you want to represent every sentence with a word count vector as a data frame, so we'll just use pandas data frame. So pd.data frame, then we'll write the bag of words to array, this array which contains all the word count vectors for each sentence, and then the columns are the feature names. This is our vocabulary, and according to this vocabulary, which are columns, each sentence is represented. So this is our first sentence, this is the second, third, fourth and fifth sentence. This is the word count vector for the first sentence, this is for the second sentence, this is for third, fourth and fifth sentence. So this is printed as a data frame. Now let's go to the Jupyter notebook and implement bag of words model using count vector as a class. We will start by importing the count vectorizer class from sklearn.featureextraction.text. From sklearn, after this I'll import both numpy and pandas. After importing these three libraries, now let us define corpus that we'll use for creating count vectors. I'll take this corpus from here. Now we have a corpus. So our next step is to create a count vectorizer object. So we'll store it in count vectorizer, count underscore vectorizer. Once we create this object, now we have to use the fit transform method of this object on our corpus, so we get our word count vectors or our count vectors. I'll store my count vectors in bag of words. We have to use the object that we have created, that is count vectorizer, and inside you have to use the fit transform method of this object, and then we have to pass our corpus. So word count vectors will be created and stored in back of words. Now after we have to print our word count vectors as an array. Once we print this, you can see we have 4 sentences in our corpus. So for each sentence it has printed a word count vector. Now let's look at the vocabulary, or which is called feature names in count vectorizer. Let's extract the feature names from our count vectorizer object. We have to use the get feature names method of this object. Now we'll have our feature names. Now let's print our feature names. If I print my feature names, so this is a vocabulary which we call in backwards model. Here we call it feature names. So you can see we have and, both, but, does, football, games, like, likes, marry. There are more feature names. So if you compare it to our vocabulary, you can see the and is not there. So because and is a stop words, and we have not removed any stop words here. In order to remove the stop words, we can use the count vector as a class, and it has an argument called stop words. So we'll set it equal to the stop words list that we have created here. I'll set it equal to the stop words, so it will remove the stop words. Once we remove the stop words, now you can see our array has changed a little bit. If I print my feature name and both, which are both stop words, are removed. Now this is our vocabulary, which is called feature names, and according to these feature names, we have the word count vectors of each text or each sentence that is present in our corpus. Now let's print our array of word count vectors as a data frame. We'll use pandas data frame. Here we have to pass our array that we want to view as a data frame, and then the columns of our data frame will be our feature names. So if I print this now, you can see these are our feature names, and these are the word count vectors for each sentence that is present in our text corpus. So this is our corpus, and these are the 4 sentences. This is the word count vector for the first sentence, word count vector for the second and third and fourth. This represents the word count of each word that is present in the vocabulary. So football occurs 2 times in this and third sentence, and games occur 1 time in third sentence. So here in count vectorizer, we have used the word count vector, so we'll represent each sentence with all the words as their word counts. This is the word count representation of our text.
Hello everyone. Intellipaat offers executive postgraduate certification in data science and artificial intelligence in collaboration with iHub IIT Roorkee. Through this particular course, you'll get to learn multiple tools like Python, PySpark, SciPy, NumPy, Pandas, Matplotlib, TensorFlow, Git, etc. You are going to learn multiple skills like data science, natural language processing, deep learning, fundamentals of generative AI, prompt engineering, and application-based generative AI, as well as recent trends like agentic AI. This course is designed to get you ready for the AI world. So do check out link available in the description. Also, through this course, we have already helped thousands of learners take positive step in their career. You can check out their testimonials on our Achievers channel.